Hi, my name is Prateek Naran, and in this tutorial we will be quickly revisiting many fundamental concepts associated with data structures like arrays, dynamic arrays, linked list, stack, queue, hash map, priority queue, and much more. Not just that, we will be also exploring Java's collection framework to use these data structures in solving problems and building real software. We will do many hands-on examples that will solidify your understanding of these concepts. But before we get started, make sure to check out free masterclasses on Scalar's event page to learn from the best industry-leading experts. The link is in the description below. Also, make sure you hit the subscribe button if you haven't already. Alright, so let's begin with the tutorial. Let us start by revisiting the concept of a data structure. A data structure is a meaningful way of arranging and storing data inside the memory of the computer, that is your RAM. Okay, we are not talking about your physical memory, we are talking about your volatile memory in which your algorithm will execute and it will do some certain operations like insertion, deletion, searching, and removal of data. We have different data structures and they are optimized for different kind of operations that we can do and different kind of orderings we can do on that data, right? So some of the data structures you might have heard about: arrays, stacks, queues, hash tables, trees, and graphs. Every data structure has its own properties, own way of ordering data, own way of implementing these operations. We'll try to understand how these data structures are different and how we can use them in Java as well. Broadly speaking, they are divided into two categories. We have linear data structures, we have non-linear data structures. There is one more category, I would say. We have associative data structures in which we store data in the form of key value pairs. For example, your hash maps. We will talk about hash maps later in this course. Those linear data structures, they can be of fixed size, like a fixed size array, or they can be dynamic. That means they can grow and shrink in size. For example, your array list, your linked list, your stack, your queue. In nonlinear data structures, we might have data structures which have a hierarchical structure. For example, your trees. Also have data structures which have network-like data structure. For example, this is a very high-level overview of how data structures are classified. But let us start by revisiting the importance of data structures in our real life. So suppose you go to a grocery store and you find everything is disorganized. Then it would become very difficult for you to search for a given item. But if your items are organized across racks and categories, you will easily find a particular item that you're looking for, right? So keeping data organized makes certain operations like your searching faster, right? Similarly, if you go to tickets and if there is no queue, then it would be very unfair for the people to wait randomly, right? But if people are organized on the basis of their priority, the person who is coming first and he is getting the queue ticket first, then it is called as FIFO ordering, right? Similarly, in data, we might require FIFO ordering. So queue is a data structure that provides us with this kind of a ordering, right? And let us look at one more example. Sometimes I go to a restaurant, I say, okay, I want to order a burger. Right? Then I quickly get an answer that the burger cost is ₹100. What is happening? For every item, there is a value attached to it, right? So for every key, there is a value, right? So the data might be stored in the form of key value pairs. And this is where some other data structures like hash maps come into the picture, right? Another example could be that if I'm on my system and I'm locating certain files, right? I know that, okay, in this folder, I have kept this kind of a data. In this folder, I have kept my PDFs. In this folder, in this drive, I've kept my pictures, right? So what is your file system? The file system is a tree-like structure. You start with your My Computer, you go to your drive, then you go to certain folders, and you find the files that you're looking for, right? You do not organize this data in the form of hierarchy, and if so, I'll search the whole computer, it would be very inefficient for you and you will spend a lot of time searching for a given file, right? So the file system is also an example of a tree-like data structure. So that means we use data structures a lot in our daily life in building software applications. So in real world also, the meaningful structuring of items helps businesses operate efficiently. We saw the example of grocery store. So similarly, data structures allow us to execute certain operations like insertion, deletion, searching, updates on the data very efficiently, and that this data is stored inside the memory of the computer. But depending on the problem that we are trying to solve, we select a suitable data structure that fulfills our requirements. This is the goal of this video. In this lecture, we are going to understand how, according to different requirements, what data structure we will use, and we will look at its implementation using Java collections framework, right? Now you might ask, okay, that's data structure. What is an algorithm then? Algorithm is the main logic. It is the step-by-step, unambiguous set of instructions for solving a problem, right? We can define algorithms for real life scenarios like making a pack of noodles. You might say, okay, take a pan, put 2 cups of water inside it, boil something. That list of instructions is an algorithm to make a pack of noodles. Or maybe something complex, like if we want to play a Ludo game, or if I want to make an algorithm that suggests the best photo out of a set of photos, we can devise an algorithm for that as well. So in real world, from every deterministic action, for example, your washing machine, a self-driving car, all the actions your machines are taking, that can also be expressed using an algorithm, right? In the software world, all the apps that you're using, photo editing app, scrolling Instagram, browsing Netflix, uh, in a cargo hub, sorting of shipments, detecting collisions in games, transferring money through UPI, ordering food. There is an algorithm behind every action that we perform. So that is why it is very important for us to learn data structures and algorithms, right? And when we combine data structures along with the algorithms, we build products that can solve real life problems. That is an importance of data structures and algorithms. I will start with arrays. Let us start with the array, which is the simplest and the most widely used data structure. So I am hoping most of you must have worked with an array. What is an array? Array is a linear collection of elements of the same type. So this is true for Java. Other languages like Python, they also support heterogeneous arrays. That means you can put different types of data, for example, integer, string, float, inside one array. Arrays are used to store multiple values in a single variable. So let's say this is a container which is linear. That means it will occupy linear block of memory. For example, if this address is 104 and this bucket takes 4 bytes, then the next address will be 108. Next address will be 112, right? So it is a linear block of memory, right? And this whole block of memory has a single name, right? And each element, if I want to access, it can be accessed using an index. The indexing starts with 0. So I can say, okay, I want to put something at array of 0, then I will say array of 0, it is 4. If I want to overwrite it, I will say, okay, array of 3, it's going to be 20. So I can just overwrite this data and it will keep 20 here, right? Each array location is accessed using an index. The indexing starts from 0. That is what we have just seen. So you have the array name followed by the index. This is how you access the ith location inside an array, right? Now let us look at some examples of an arrays. For example, if I want to create an array of strings in which I'm calling the variable as bill payments, so I have defined 3 strings: electricity, mobile, and credit card, right? And I have an array of numbers. I have defined 4 numbers here. I have int followed by square brackets followed by name of the array. This is a very simple way of creating an array. But you can also create an array of fixed size where you have not given your data, right? In the previous scenario, we have not defined the size. Size will depend upon how many items we have initialized in this list, right? So you can directly initialize, or you can first create a fixed size block. You can say, okay, I want an array that is able to hold 5 integers. We'll use the new keyword followed by the data type and followed by the size. So what happens? It creates an array. So if I talk about Java, the variable ARR, it most likely it goes into your stack memory, and the actual array that we have, this is created in the heap memory, right? ARR we call as a object reference. ARR is holding the address of this array. ARR is going to hold 104. ARR is in the stack, whereas this actual object, it is in the heap memory. Now we are updating the data at the ith index. We are actually storing 10, 20, 30, 40 and 50 here. This is how you create an array. And all the array objects, they have a length property added to it. So if you say, okay, this is a cars array and I want to say cars dot length, this will give me, okay, how many objects are stored in this array, or what is the size of this array. This will give me 4, right? The size of this array. And using the length property, I can also iterate over the arrays, right? So I can say, okay, let me go over every index from 0 till cars dot length. That means I'm iterating from 0, 1, 2, 3. The length is 4, so I'm iterating over these indices. And I'll say, okay, let me print every car. I will print the ith object, right? That is one way of iterating. Using the length property, you can get the size. Other ways, you can use a for each loop, or also called as enhanced for loop. You can say, okay, for every string value that is there inside my cars array, I want to go over that value and I want to print it. That is another way of iterating over the complete array object. Then let's talk about the advantages of arrays. They are very simple and they are very easy to use. The insertion is really fast at the end of the array, because if you keep a variable that, okay, these positions are filled, I want to put something here, you can simply say array of I equal to value. So that value will get stored here. So you can insert at the end of the array very fast, and array element can be accessed in a constant time. So if you want to get this element, you can simply say, okay, give me the jth element. So you can access any random element, any random index in just order one time. That is an advantage of an array. But they also have certain disadvantages. The thing is, arrays have fixed size. So once you create an array, okay, new int of some size 10, cannot say I will make it 15 or I will make it 20. They have a fixed size. They cannot grow in memory once they are allocated. Insertion in the middle requires shifting of the elements. If you have inserted something, let's say 1, 2, 4, 6, 8, and you say, okay, I want to insert 3. What you will have to do, you will have to shift these elements to the right. Then you can insert 3 in the middle. So it's going to take order of n time for doing the insertion, right? And second thing is, since array requires a linear memory block, such blocks might not be available if the array size is big. Suppose this is your heap memory, and suppose certain portions of the heap memory, they are already used up, right? And suppose you want to create a very big array, which might go like this. Now it is possible that such a linear block of memory is not available, but this amount of memory is available in the heap in chunks, right? So you might say, okay, some memory is available here, some memory is available here, some memory is available here. That is where linked list might perform better, because linked list does not need big linear chunk of the memory, whereas array requires a big linear chunk of the memory, right? So for big arrays, it could be a disadvantage that such a linear block could not be present in the memory. Now, arrays are used a lot in the real world. For example, this is a UI from a shopping website where I have to display these components, right? The type of bill payments. I can say, okay, each bill payment is a string. So I have a fixed size array of bill payments in which I have defined all the categories, right? Now you might say, okay, this looks very simple. In actual world, it might be a bit more complicated. Yes, it can be. What may happen is that each item is not just a string, but it is a something more complex. Let me call this as a payment category. What I can do, I can define a class called as payment category, which hold three things. Maybe the category ID, which is not displayed, the category name, and the image of the category, right? The URL of the image of the category. So I can hold all these things inside a class, and then I can create an array of the following class. I can say, okay, I'm creating an array where each item is of the type payment category, right? So I'm creating an array of objects of the type payment category, right? I have initialized this array that is going to contain 14 items, and I need to create these objects as well. I need to say, okay, the bill payments of 0, it is going to hold new payment category, and using the constructor I've initialized these values. Okay, the payment category is 1, the name is electricity, and some URL. So instead of creating an array of primitive data types such as integer or float, we can also create an array of complex data types such as payment categories in this example, right? Secondly, there are two-dimensional arrays as well, which are also used a lot, especially in games and puzzles, right? So here is an example of tic-tac-toe, where we might need a board, right? Or here is an example of Sudoku game where we might need a two-dimensional array to represent the state of the game, right? So it's a 9x9 array. So I've created this array, right? And I can also create a list of players. It's going to be a 1D array, but the data type is now a player, right? Each player might have a name, it might have a score, might have certain methods associated with it, right? It's an array of pairs, right? That is also how arrays can be used. Another use case could be that array can also be part of a data member of a class. For example, you have an enemy object. The enemy has certain bullets inside it, like certain number of bullets the enemy can fire. I can create an array of bullets where each bullet is of the type bullet, and I have created it when the enemy is created. For example, I want this enemy to have exactly six bullets when this enemy is created. I can do something like this. Okay, and when you're firing the bullet, maybe a particular bullet might get deactivated. Something like this can also be possible, where your array is a data member of a particular class. This can also happen, right? Another example could be your images, right? So when you deal with images, each image is made up of a matrix of pixels, okay, of the size rows into columns. So you might have heard about an HD image. So that is 1920 by 1080. That simply means that we have these many pixels in this image, and each pixel is actually made up of three numbers: a component of red, component of green, and a component of blue. So that means each pixel itself is an array of three numbers, right? If I look at an image, the image is actually a three-dimensional array of rows, comma, columns into three, right? Where each pixel is actually going to store three numbers, right? When we do with work with images in Python, we often see the arrays are three-dimensional. Okay, another example, that when you're building software components, for example, a tool like Photoshop, right? You will say, okay, there is this grid where every item is a tool. So I can say, okay, toolbox, this is new tool, and in every index I'm creating a new tool, right? Marquee tool is a type of a tool, move tool is a type of a tool, right? I can also do something like this. They are used a lot in building real life software, and that is the importance of arrays, right? Now we'll look at some code demo to work with arrays. Now we are going to look at some code of an arrays, especially how do we perform an operation like sorting on arrays, which comes very handy in solving lot of problems. Okay, so I have an array of numbers, and I want to use a method called as sort, right? So in java.util package, there is a class called arrays, right? This class contains methods that will work on a array that we have created, right? Arrays.sort is one such method. We want to use this method to sort our numbers array. Let's see if I go and run this code. So I just need to call this function f1. So my array is created, the array will get sorted, and we are going to output this array, right? Another such method is arrays.toString. I can convert this array into a string like representation that I can print directly. So let us just go and run this main method. So now you see the data that you're getting is in a sorted order. Let us look at one more example. Let's say I have an array of strings and I want to sort these strings. Again, what I can do, I can use arrays.sort method, which is again an inbuilt method inside java.util. And I just need to pass the array object to this method. It's going to sort these objects, and let us call our function f2 and let us run this code. Now what do I see? I see output apple, banana, grape, lemon, and orange, right? Now how two strings are compared? Let us talk a little bit about comparisons as well. Now comparing numbers is easy. I can compare as 5 less than 13. The answer is yes, right? But if I have a string called as, let's say, s1, that is abc, and I have string s2, let's say I call it as abe, right? Now are they equal or are they not equal? How do we compare? By default, inside the string class, there is a method called as compare to. If I say s1 dot compare to, you see there is a suggestion coming out, and I say, okay, let me compare it with the string s2, and let me show you the output of what this comparison function is going to return. Right? Now why I'm teaching you is, this is very important because we also want to write custom comparisons for our objects. I'm getting an output that is minus. Basically, how sorting function works is, internally calls the compare to method. When you use arrays dot sort, and you give um, some array of objects to sort, right? So what it does, it calls the compare to method of that object. So string, basically it is calling the compare to method of this object. So I'm saying s1, which is abc. I want to compare it with another string abe. Now this compare to method, it's going to produce three types of outputs. One is a negative output, one is 0, and another is positive. So negative output simply means that my first number is smaller. First object is smaller. That means it will come first in the list. Positive number means my second object is smaller. That means it will come first in the list. And 0 means the two objects, they are actually equal. If I get a negative output, which I'm getting in this case, that means ABC is smaller than ABE. Let us also see how this -2 is actually coming, right? So when you compare ABC with ABE, right? So you compare A with A, they are equal. So you move to the next position. You go with B and B, they are equal. You move to the next position. Now you compare C and D, right? Now suppose C has some ASCII value, right? So maybe this was 97, 98, 99, right? And this is 97, 98, 99, 100, 101, right? The ASCII value of E could be 101. So when you take this difference, right, I think A is actually 90, not 97. Whatever the ASCII value is, right, you will take the difference. If you subtract C from E, you will get a difference of -. That basically tells the sorting function that I will place ABC first and then I will place ABE, the sorted order. The compare to function is responsible for defining the sorting order. When I'm sorting these fruits, you see apple, banana, grape, lemon, and orange. They are coming in their dictionary order, right? Because a string knows a compare to function is present inside it, right? Then I say, okay, I want to reverse this order, right? What you can do is, one simple way of doing it is that you supply a custom comparator called as collections.reverse order. That is exactly going to reverse the default output. Okay, by default you're getting this output. If you specify this, it's going to reverse the default output. If I run this code now, you will say I will get orange first, followed by lemon, grape, banana, and apple. That is one thing that you can use to uh, convert your ascending array into a descending. That is one way of doing it. So now you might ask, then why we are studying this compare to method, or where do we need it? Let us try to understand that as well. This was very simple. This was an array of integers or an array of strings, right? Now you might say that I have a custom object. I have, let's say, a class called as employee, where my employee has a name, age, and salary, right? And I want to create an array of employees. I have an array of employees, array of custom objects, and I want to sort them. If you sort them, right, and if you do not tell Java that, okay, I do not know how do I compare two employees, most likely you're going to get an error, right? Now arrays.sort can also accept employees, but given that you define a method called as compare to inside the employee class. Okay. In the string class, it is an inbuilt method, but in the employee class, which we have written, we have to define how do I compare two employees. For example, I have an employee E1. I want to call the compare to method and supply it some another employee E2, right? So when you say, okay, I'm sorting a list of employees, right? This is an array of employees. So it will say, okay, I'm going to compare this employee with some other employee. So I will say employee I dot compare to some other employee, that is employee J, right? So the sort function is internally going to call this method called compare to, right? But this method is not there. What we have to do, we have to define this method inside our employee. I have my employee class, and here I'm going to define my compare to method. How it will get called? It will get called internally. So employee I getting compared to with some other employee J, right? Now it is up to you. How do you compare two employees, right? Some other employee J, right? EMP. Now look at this. How do I write this method? So basically what I'm doing, I'm saying if the two employees have the same age, I will compare them according to their salary. I'm saying salary 1 minus salary 2. So if the first employee salary is 100 and second employee salary is, let's say, 60, 100 minus 60, it's going to produce a positive number. That means the second employee will come first. The person with the lesser salary will come first. Or if the age is not equal, I'm saying age minus employee dot age. So this is the age of the first employee and this is the age of the second employee. For example, if the first employee is 50 years old, the second employee is 40 years old. 50 minus 40, it's also going to produce a positive number. That means the second employee, it is smaller in age, right? So what this sort function is going to do, what this compare function is going to do, it's simply going to compare the two employees based upon their age. If their ages are equal, it's going to compare according to their salary. People with the less age and less salary, they are given priority. They will come first in the output. So let us run this code and see what do we really get, right? Okay, one more thing is that we have to, so whenever you're creating this class, we have to tell that it implements the comparable interface, right? Why? Because the sort function expects that you will implement a compare to method. This compare to method is coming from the comparable interface, right? We'll discuss the concept of interface very shortly, but you should know that you have to say this class implements the comparable interface for the employee, in which we have an abstract method compare to, and we have defined this method in the current employee class, right? The body must be given here. So what is happening now? Let me show you the output. Let's run this one. We are sorting an array of objects, right? So I'm saying let me print employees. So now I'm getting 6025. This is salary and age. I'm getting 12,025. That means higher salary, same age, right? Then I'm getting 8,045. According to my logic, the first preference is on age. Employees are sorted first on their age, 25, 25, 45 and 56. Then they are sorted on their salary if the age is same. So Jamin and Aryan, they have the same age. So the person with less salary, it's going to come first. So you can make any logic, like depending upon the situation, and this compare to method will tell the sort function how do I actually sort. So I'm hoping that this is clear. So one way is use the default sort function, but it does not work for the custom objects, right? Then what you can do, you can write the compare to method. And now there is one more scenario in which you might not want to go this way. You might want to go with the comparator way, right? Let me discuss that as well. So let us discuss one more way of sorting using comparator. Now I'm going to tell you why it could be important. Now suppose you have maybe a list of strings, okay? Let's say ABC, or let's say some fruits, apple, mango, guava and orange. And you want to say, okay, I want to sort my fruits. I want to say, okay, arrays dot sort. I want to sort fruits, but I want to sort fruits maybe according to the dictionary order. I want to use the default comparison, or maybe I want to sort fruits according to their length. I'm not writing the proper code, but what I'm trying to tell you is that if I want to sort fruits according to their length, I will have to go inside the string class, and inside the string class I will have to change the compare to method. Do you think changing the compare to method inside the string class, which is implemented in the Java library, will be a good thing? Answer is no. We cannot go and make changes in the library, right? That is one reason we will not use the default compare to method, or we need some other way to do the sorting so that we have the flexibility, right? Another reason could be that I might have a if else like this. If the condition is this, I want to sort according to some criteria. If there is some other condition, then I have to use some other criteria for sorting, right? I might have something like this. Then also I will have to say that, okay, go with the first way if your if condition is true, go with the second way if your second condition is true. Something of this sort. What I'm going to tell you is that in such scenarios where either you have conditional sorting or you will have to use your, you cannot go and change the library compare to method for that particular class. There is third way of doing the sorting, so that way is called as comparator. I'll show you an example of using a comparator, right? In this case I am creating an array list of integers. So array list we will study very shortly. It's just like a array, but it's dynamic in size. It can grow and shrink. So it is part of collections framework we will study. So the demo that I'm going to do here is also applicable for arrays.sort method. What we have done is we have created a dynamic array in which I have added few numbers. What I want to do is, instead of sorting these numbers directly, right? I know 10 is less than 22. That's okay. But what I want to do, I want to sort these numbers based upon their sum of their digits. You might say, okay, how do I override such a comparison? In such scenario, there is this third way that I'm going to teach you. It is called as sorting using comparator, right? What we can do, we still need to call the sort method. If it is an array object, you will use arrays.sort. But if it is an array list, which is part of your collections framework, you will use collections.sort. In this sort method, you need to give your array list object, that is a that we have given, right? And now you have to say that, okay, I'm creating a new comparator object. It's an anonymous object. We are not giving it any. And in this object, we have to override the compare method, right? So I'll just write this part again once. You will see if you're using IntelliJ, it will come using the autocomplete feature. I create a new comparator object. And in this, it automatically creates a method called as public int compare. Note that it is not compared to. This method, it's going to accept two objects that you want to compare, and you want to tell how do I compare these two objects. Okay, so if there are simple strings, so integer o1, integer o2, let's say first object a is 10, b is 20, right? If you simply return a minus b, that will simply compare these strings based upon their values. That means, okay, 10 minus 20, sorry, o1 minus o2, first object minus second object, I can do that. That will say, okay, 10 minus 20, it's a negative number. That means 10 will come first. But if I do it other way, if I say I will negate this entire comparison, that means I'm doing o2 minus o1. That means this list will be sorted in the descending order. But suppose if I want to do based upon the sum of their digits. Okay, for example, this is 10. The sum is 1 plus 0, that is 1. 2 plus 2, that is 4. 4 plus 1, 5. 4 plus 0, that is 4. 35. 3 plus 5, 8. 5 plus 1, that is 6. I want to sort according to this. What I can do, I can convert an integer into its sum, right? What I have done, I've written a function called as getSum. Given an integer x, I want to get the sum, right? So this is very easy. You know how to find the sum of an integer. When I'm making a comparison, what I will do, I'll say, okay, I'll get the sum of first integer object. I'll say get sum of a, and I will subtract get sum of a is my object o1 and b is my object o2. If I do this, what's going to happen? So numbers whose sum is lesser, right? So I'll just comment this code out. I'll show you the output. Let us run this code once, right? This comparator is telling the sort function that now you have to compare the objects using the following criteria. Okay, so I've printed it twice. Now if you look carefully, 1 plus 0 is 1, this is 4, this is 4, this is 5, this is 6, and this is 8. Now you look carefully at these numbers, they are sorted according to their sum. That is something that you can do, right? You can do the same thing with strings as well. You can do the same thing with employee as well. You do not want to implement the compare to method inside the employee class. You can use a comparator. Or you want that on the top of it, I need another comparison based upon certain condition, right? If employees are near their performance period, I want to compare according to their salaries, not according to their age, right? So you can have that. Comparator gives you another option to do the sorting, right? You might say, okay, this looks little tricky. Is there a shorter, easier way to do it? The answer is yes. So what we can do, we can use something called as a lambda function as well. I'll just tell you in a very short way what is a lambda function. It's a one line function. It's an anonymous function. So in Java, what you have to do, you have to write the inputs that you need to compare in these round brackets. For example, if I'm comparing two objects A and B, right? And with an arrow, you have to write the output of the comparison. Now, if you want to compare A and B in this case, what is the output? I'm saying, okay, get sum of A minus get sum of B. That is what we are doing in the compare function as well. That thing you put it here, and this becomes a lambda function, and it will do the trick for you, right? So you can just say that, okay, I don't want to write the compare method. I just want to use this value, that is the output, and use these numbers that are my inputs. Given these two inputs, I want to return this output from the comparison. This will also work. And if I show you, if I comment this code out, this lambda function will also do the same sorting thing that we want to do. Let us sort them and let's see what do we get. We are still getting the same output. That is another way of doing the sort. So hopefully now you have understood the three different ways of doing sort, and that's all for sorting. And we'll start with the collections framework next. Let's talk about Java collections framework now. So Java collections framework is a framework in Java that provides us with set of classes, interfaces to manipulate, organize, and perform operations on data without writing your own data structures from scratch. It provides you with library implementation of data structures and their associated methods that can do anything that you will ever need to do, right? That means we will be using inbuilt data structures because they come very handy when you're solving problems or you're building real life software. These data structures are also highly optimized, and they will of course save a lot of development time. So you don't need to write your own hash table, you don't need to write your own linked list, right? So this is what is a standard practice. We will, most of the times we would be using the library implement. Just to summarize once again, what do we have? We have set of interfaces. We'll see. We have implementation classes, the classes that actually implement those interfaces. And we have also algorithms. Okay, so I showed you the examples of arrays.sort method, collections.sort method. Similarly, we have methods for searching like binary search available in the Java collections. So you can just go and look at what all those methods are. But for now, what I will be doing a quick demo of interface versus a class so that you can really understand how these interfaces and classes are being organized inside the Java collections, right? So let us jump into a small code demo to understand the concept of interface versus a class. In this example, what I have done, I have defined an interface called as a payment method. Okay? So what is an interface? An interface specifies what a class must do and not how. That means we do not have the implementation of the pay method. We do not know how to make the payment, but we are saying there must be something called as a pay if it is a payment method. Any payment method that we have must implement a pay method inside it. So it is a blueprint for the class. Interface methods are abstract by default, so they don't have any code inside. Now suppose I'm going to create payment method called as debit card. So debit card is a class which implements payment method. That means now debit card must define a pay method. So for now, I'm just saying that debit card pay method prints paying via debit card. Similarly, I have one more class called credit card, which also implements the payment method. I have one more uh, class called UPI, which also implements the payment method. All these classes, they have the pay method and they're implementing the payment method. There are different ways of creating the payment method. Execution of each payment method would be different. Okay, a credit card might have a different mechanism. A UPI might have a different mechanism of making the payment. Debit card will have a different mechanism of making the payment. Why we are doing this? Let us try to understand. Now, suppose we have a method called as make payment, and this method can accept any payment method, right? I'm not hard coding here. I'm not saying that I will only accept debit card, DC. I will not accept debit card. I can accept any payment method. One thing is we need a general structure. We need a general data type that can hold all payment methods. Okay. And here I'm going to call pm.pay. So now why this method will work. So let me show you how do you create objects of it. So I can say, okay, debit card DC, this is equal to new debit card. And I say, okay, I'm creating a debit card. Then I can call dc.pay. So this will work. I'm creating a debit card object. dc.pay will actually work, right? So I'm not calling this method as of now. But what I can do is I can call the make payment method and I can pass it the debit card object. Why? Because debit card object implements the payment method interface. A better way to do it is, suppose you have like some code here, you say dc.pay. Suppose your debit card is not working or the debit card service is down or there is some issue and you want to change it to the credit card. Okay, you want to say, okay, no, I want to try credit card. Now if you do this is going to give you a problem because a debit card data type cannot hold a credit card, right? But what we can do is we can use a more general data type, that is payment method. Payment method is PM. I can say, okay, on the left side I'll have a payment method which is implemented by a credit card, right? So payment method is a more general data type. So this is a good design practice as well. So this data type, we will keep it more generic. And this is a specific class that provides implementation of methods defined in this class. This is a specific class. Now this could be credit card, this could be debit card, this could be UPI, right? And I can pass this object PM to any method, make payment, right? Now it does not care whether I'm going to call the pay method of debit card, credit card, UPI. Whatever is the object passed, it will call the pay method of that object. So that means with minimum change in code, we can achieve this general behavior, right? So any payment method object will work inside the make payment method. If I go and run this code, I will show you what's going to happen. It will say, okay, I'm going to make a payment using a credit card, paying via credit card. But if I say, okay, no, I will make it UPI. So without changing your make payment method, you have just changed this object. It will pay via UPI, right? I'm going to run this code now. Paying via UPI. That means this object reference can hold any object, like any object which implements the payment method interface. That is a quick revision about interfaces and classes in Java, and collections framework heavily uses this concept of interfaces and classes a lot. So let us look at how this is implemented in the collection framework as well. There are so many components inside collection framework. There are interfaces, there are classes, there are child interfaces, there are child classes, and the hierarchy is a bit complex. So what I've done is I've drawn a simplified diagram so that you can understand how these components are related. On the top, we have something called as a collection interface. Okay, so collection is a interface inside collections framework. There are three more interfaces which are child interfaces of the collection interface. So they are list, set, and queue. They all extend the collection interface. Okay, queue extends collection, set extends collection, and list also extends collection. That means some methods are there in collection and list adds some additional methods which are specific to the list. Set adds more methods which are specific to the set. Queue adds more methods which are specific for the queue-like behavior. Right? And then there are implementation classes which actually implement a list. So array list implements a list. The other way, the array list is going to implement a list. A linked list is also going to implement a list. Stack is also going to implement a list. Vector is also going to implement a list. So a vector is a concurrent data structure. That means if you need to work, you need to share this data structure across multiple threads, then vector is the synchronized data structure. Okay, so we are not going to do concurrent data structures in this tutorial, so I will leave vector at the moment. Similarly, hash set implements the methods of the set. Linked list implements, linked hash set implements methods of the set, and tree set also implements methods of the set. Right? Now, what is the difference? The way these methods internally work, that is different. Okay, a tree set might use something like a self-balancing binary search tree, whereas hash set might use the concept of a hash table to store the data, right? So the implementation of methods is different, and their time complexities, they are also different. Right? So for queue, we have three implementations. We have array deck, which is a doubly-ended queue. We have a linked list, which is like your which serves as your FIFO linked list, and there is a priority queue, which again internally uses a heap-like data structure to give priority to the elements which should come first, right? So we have interfaces and we have classes that implement those interfaces. The ones that are in the orange, they are the classes. The ones which are in yellow, they are the interfaces, right? So I hope you understood this simple hierarchy. Now you might be wondering, where is hash map? Hash map is not a part of collection interface. It is not a subtype of a collection interface. It has been kept separately and it behaves differently from the rest of the collection types. So that means the map will be treated differently. So map is an interface that we will look, and hash map, tree map, and linked hash map, they are the implementations for the map interface, right? We will use one of these implementations if you want to build a something like a map which can store key value pairs. So we'll understand the differences between these implementations as we go through this tutorial, right? So let me tell you little more about collection interface. The collection interface, it's a general interface. It represents a group of objects which are known as elements, right? So it's simply grouping different objects, and it is used to pass around collections of objects where maximum generality is required. Okay, you just want a group of objects, you don't want to use specific priority queue method or specific queue method, or you don't want to use specific hash map method, right? So you just want some general methods that I should be able to add into the collection, I should be able to remove from the collection, I should be able to delete from the collection, right? For example, you have a collection of string. Now this collection, again, it might be implemented using a linked list, it might be implemented using a set, it might be implemented using a array list. We don't know, right? So we have to provide one way implement or represent this group of strings, right? So let me show you a code demo here. So I have collection of string s1. Now this interface, collection is an interface, so I need a class to implement it. So I'll say, okay, this collection will be stored using a array list. So I'm adding something into the array list, right? I'm saying s1.add hello, s1.add world, right? Now you might ask, where is this add method defined? So I will tell you, the collection interface contains method that performs basic operation. Okay, so such as size. Every data structure, you need to get its size. Every data structure should know whether it is empty or not. Every data structure should know whether a particular object is present inside it or not. Every data structure should support that I want to add some element, I want to remove some element, I need a iterator, right? It also contains methods that operate on entire collections, such as add all. Given another collection, can I add all the elements of this collection into the current collection? Yes, I can, right? Remove all, retain all, clear, right? These are general methods that are defined in the collection interface. That means all the implementation classes will have to define these methods. Let me show you something here. So let us say I create one more collection. and this collection is implemented using a hash set. Now in this hash set, I am adding few strings A, B, C, and D, right? Now this add function is going to behave differently from this add function, because this add function is implemented by the array list, but this add function is implemented by the hash set. So if I print S1 and S2, I would be able to see, okay, there are two group of elements. Okay, if I just run this code, I'll say, okay, I have collection S1 and I have a collection S2. Now suppose I want to add all elements of S1 into S2. Can we do that? Of course I can do that, because the collection interface gives me methods like add all. So S1 dot add, I can give any collection here. I can give list, I can give array list, I can give queue, right? I can say, okay, in my hash set, I want to add all elements of array list, that is S1. So I can pass another collection into my add all method. The method is add all, right? So it's a general method. Any collection can be passed to, right? This is what it means, right? Method is add all, that's correct. So let's go and run this code. Now if I see ABCD, it's here. I will also see hello world is also there. So you can see all elements of S1, they got added into S2, right? All these general methods, they are defined in the collection interface. Okay, I hope you're understanding it. So that is at the top, right? Now why we are learning this? Because we want to use these data structures to solve problems efficiently. It is so powerful that we can do a lot of things. For example, we can create a list in which we can keep adding to. We just saw an example of array list. We can search items very quickly inside a hash map. We can sort a list of students by using a comparator, right? We have just seen comparators. We can also find topmost ordered items using a priority queue. We can filter out duplicate elements using a hash set. We can build a rate limiting algorithm using a queue, right? We can do a lot of stuff using the collection framework, and that is why we are learning it. Now next we will dive into specific classes, and the first class that we will start is array list. So let us talk about array list. So array list is like a dynamic array for storing elements. It's an array but with no size limit. That means if an array gets full, it will grow in size and it can accommodate more elements till you have memory available inside your heap, right? So array list class, it's a dynamic array. It maintains the relative insertion order. So if you add element, it will always get added at the end. So that means you'll get the same order as insertion. We can add or remove elements. Even we can search for elements, and it implements linear search. That means it will take linear time to search it. So in Java, it implements the list interface. So we saw that list is a interface and array list is a implementation of the list interface. All the methods that are available in the list interface are implemented by array list. Now, how it is going to work internally? So I'll give you a quick idea. So internally, it uses a fixed size array only, right? So it starts with some fixed size array. So in Java, the default size is 10. So by default, it will create a new array of size 10. And as soon as the array gets full, it will double the size of the original. Now that doubling cannot happen in the same place. Suppose this array was full, right? What it will do, it will create a new linear array. Suppose this size was 10. It will create a new array of size 20, and it will copy all these elements into the new array. And then you will have some extra buckets for new elements. Once this gets full, it will again delete the previous array. It will create a new array of double the size, copy elements here, and delete this array as well. This is how it happens. Copy the elements from the old array in the new array and delete the old. This is how this array actually works. That means the doubling of the array list is an expensive operation, and we should reduce the frequency of this doubling. How do we do that? If you know you're going to store 1000 elements, create an array list of initial size 1000. If you by chance exceed 1000, the doubling will happen, the array size will become 2000, right? So it's a good idea to start with some initial size that is equal to your requirements. In Java, this doubling procedure is little different. It says, okay, I'll maintain something called as a load factor. This load factor is, I think, around 0.7. That means if 70% of your array is full, the doubling will get triggered. So we will not wait till filling of 100% of the array. If 70% of the array gets full, the doubling function, it's triggered. Okay, so after adding the seventh element, if the initial size was 10, a new array is created with a capacity of 20. So there are two things. When you talk about size of the array list, it tells you how many elements are currently stored in the array list. So if you use the size method, it's not the capacity. Capacity is generally more than the size, right? So capacity is how much space has been allocated internally, whereas size is the number of elements that we have stored in the array list, right? So what are the features? It is dynamic in size. It can grow and shrink in size. Secondly, it is ordered. It preserves the order of elements. Third, it is index based. Just like an array, you have indices. Array list also have indices. If you want to access a particular element, okay, I want to get this ith element, you do not write array of I. Instead, you write array list dot get I. Give me the ith element. So get is a method that you will use to access any ith element. So this also works in order one time, right? Indexing is zero based. So another property you need to know is it is object based. Array list can only store object data types. That means it cannot be used with primitive data types. So you cannot create an array list of int, float, etc. Then you might be wondering, how do we create an array list of integers? For that, you have to use wrapper classes. In Java, the wrapper class for int is called as integer. So you will always create an array list of the data type integer, not as int. And secondly, it is not synchronized. That means it's not a concurrent data structure. If concurrency is important for your application, you have to use vector, which is the synchronized version of array list, right? So array list operations are not thread safe, and multiple threads should not operate on the same array list. So this is a basic data structures tutorial. If you want to learn about advanced concepts, we will cover it in some other video, right? So what are the operations? We can get any element using the get function. We can add any element using the add function. We can also add more elements using the add all function. So I give you a list, I want to add it, I can use add all, right? I can give some element x that can be added. Insertion and deletion, in the middle it's going to take order of n time. So if you insert something in the middle, right, you want to say, okay, I want to add something in between, it will require shifting of remaining elements. That means that will take order of n time. Searching takes order n time. So by default, if you use the contains method, it's going to do linear search, right? But if you know the array list is sorted, then you can use your own binary search method or the binary search provided by the library function. You can use that as well. That searching will take log n time if your array list is already sorted, right? Now let us look at basic syntax, how we can create an array list. Array list, this is, you have to define what kind of objects you want to store here, right? And then you say, okay, I want to create a new array list object, right? So this is how we do it. For example, you can create an array list of strings, and you say it's a new array list. You can create an array list of integer, right? I told you it does not work with primitive data type. So you have to use the wrapper classes, okay? So in general, I would make this left data type to be of the list type, because array list is a type of a list, right? And as a good design principle, it is preferred that we make this data type more general as possible. So we can say, okay, the list, we are creating an object of the type list. The implementation is given by new array list. This is a more recommended thing to do, right, than doing array list, right? This you will learn in the design principles, right? So we'll create an object of the type list, which is implemented using the array list class, right? So this is what we will do, right? So we can also use the constructor to give an initial capacity, right? So you can pass a number here that will tell me, okay, I want an array list whose initial size is 50, it is not going to be 10. So by default, the initial capacity of the array list would be 50. That means until this array list is not full, or it's not 70% full, the doubling will not execute. If you know that you're going to work with 10,000 elements, create an array list of size 10,000 or 11,000, so that your doubling does not happen again and again, because it's a expensive operation. We can also initialize array list using another list. Okay, so you can give another list. For example, here we have a list of strings which is storing foo and bar, and I'm going to initialize an array list with another list. That is also possible. So we have seen three ways: the default constructor, a constructor with the initial capacity, and a constructor that accepts another list collection to initialize this array list, right? Now, one more cool thing about array list is we can also store objects of various types in this array list. Why? So if you want to create an array list which can store objects of multiple different data types, then don't parameterize the instance. So if you see here, I've not specified any specific data type here. That means this array list can store different object data types. So I can add an integer, right? So I'm saying array list dot add integer dot value of 1. Now you might ask why I cannot do this array list dot add 1, because it is of the type int, right? So I need to typecast this into integer data type. Integer dot value of is a method that creates an integer object out of this one, right? String dot value of scalar. So this is optional. We can simply say array list dot add scalar. So it's going to add a string object inside my array list, right? If I show you in the demo, I have created an array list here. I say okay, array list dot add integer dot value of 1. This is going to add an integer, and then array list dot add scalar. So I'm storing an integer object and a string object inside the same array list, right? So this is also possible, right? So you see the output here, right? Let us talk about some more methods of array list. So predefined methods include a lot of methods. So there are methods for adding objects. So if I simply call the add method, it will add at the end of the list. There is a add method which also accepts an index and an object. It will insert into a specific index of the list, right? There is a add all method. It will add another list in another collection into this list, right? So we can also add another collection at a particular index in this list. So let us look at the add methods first. So I can say I want to create an array list. So list of it's integers. I call it as list, and this is equal to new array list. So you can see we have imported the list interface and we have imported the array list class. Now inside this list, I need to add some numbers. I can say add 1, add 2, add 4. So let me show you. And if I print this list, I see I get 1 to 4. I have added these numbers. Okay. Now what I can do, I can add at a particular index as well. I can say, okay, I want to add at a certain index. So either I give a integer or I give a int followed by an integer. I can say, okay, add at index 2. The element is 15. If I do it, it will do insertion in the middle of the list. That is also possible. So you can see I get 15, which is now present at index 2. So by default, it is like the first parameter is the index, the second parameter is the value that I'm going to insert, right? That is the add function. I can create another list as well. I can say, okay, I need another list 2, and I can say list 2 dot add 15, and I can, or let's say this is 25. I can also add all elements of list 1 in list 2. So I can say list 2 dot add list. So I can pass another collection here. So add all. So I need to call the add all method, and this will also work, and I can print list 2 as well. You can see I'm having 25 here followed by all elements of list 1. That is how do we use the add method. Next we will look at the remove method. So now remove method is, it's actually a overloaded method. If you look at we can pass an object, we can also pass an index. Now this becomes tricky, especially if we are working with integers, right? If I say, okay, I want to remove something, I want to say list 2 dot remove 1. What does it mean? Am I removing the index or am I removing the value 1, right? So let me just say list dot remove 1. So if I talk about first list and I want to remove 1 from it, so let me show you. It will actually remove the index, because when you're passing 1 simply like this, it's going to assume it is of the data type int, right? So if you look here, right? So when I pass int data type, it removes the index at the following index it will remove. So that means it will remove the element 2 from list 1. But if I want to remove the value that is 1, what will I have to do? I have to convert that into an integer object, right? So I have to say list dot remove integer dot value of 1. That means remove 1 as a object. So if I remove both, let's say, so that means 1 and 2 both will get removed. Let me show you the output. I'll print system sout list. Show me what you're going to remove, right? So now you can see the output that both 1 and 2 they got removed and we got 15 and 4. Similarly, you have a remove all method which will accept another collection. It will remove all elements from that collection, from the given collection. Clear will remove all elements from the list. Contains will tell me whether a particular element is present or not. So I can check that, okay, if list contains 15, do something, right? So contains is your linear search. So sout, yes, 15 is present, something like this. So you can use the contains method with almost every collection. Let me run this and you can see that we are getting 15 is present. Okay, so there are more methods. There is a get method. So if you want to read a particular index, you want to say, okay, show me what is present at the 0th index. You can say sout, or you can, maybe you want to iterate over the entire array list. You can say for int I equal to 0, I less than list dot size or list 2 dot size I plus plus. I want to get the elements at each index. You can say sout list 2 dot get I. This will give you the elements at given ith index. So get function is used to access the ith element. So let me run this and you can see we are able to iterate over all the elements in this list. So just like get, there is another method that is called set. So if you want to update a particular index, you want to say, okay, I want to make this 0th element as 50. So you can say, okay, list 2 dot set 0th element, make it 50. This will work and now your 0th element will be 50. You need to give the index and the object that you need to store here. This is the set function. There are more methods. I won't be able to cover all the methods, but we have covered like most of the important methods. There is a method called toArray. If you want to get an array from an array list, you can use this. And there is a method called as size, which we have just seen. There is also a method called trim to size. That means if we want to reduce the current size, right? Like if we want to reduce the capacity to the current size, we can use this method trim to size, right? These are some of the important methods associated with array list. There is also index of, returns the index of the first occurrence of the specified element in the array list, or -1 if it does not contain the element. So contains is going to give you boolean, present or not. Index of is going to give you at what index it is present or not, right? Now we'll look at some more ways to iterate on the array list. Let's do a quick demo. So we have seen for loop. We can also use a for each loop. So I can say for every integer x in my list 2, I want to access it and I want to print it. So I can say, okay, sout list 2 dot get I. That is my another way of iterating and printing. So sorry, I will not do this. I'll say, okay, let me print this number x. Let me run this code. There is one more way that I can also iterate on the list using an iterator, right? So you can see we are getting all the elements, that is 1, 2, 15, 4, and 50 is also there, right? So we are starting from 50 here and we are getting all these elements. Okay, so iterator is one more way to traverse on a Java collection. All Java collections, they support iterators. So what you can do, you can create an iterator object by calling list.iterator. This iterator has a method called as hasNext, which tells me whether I can access the next element in the collection or not. Right? If your collection has finished, your hasNext will give you, okay, there is no other element, right? So I can say while it.hasNext, if there is an element present, I can access it. So I can say, okay, sout it.next. This will give me the next element in the collection. This is another way using which I can iterate on given collection, right? So iterator is coming from the java.util package only, right? So this will also print all the elements present in this array list. Let us quickly run the code and see. We are getting the same output using iterator as well. So I iterated on list 1, so which is 15 and 4. Again, I iterated using iterator, which is 15 comma 4. That is what I am getting by iterating on my list. That's all for array list. I hope you understood the methods of array list and how it works. Now let us jump into linked list. So linked list is also a linear data structure in which elements are represented as objects and stored in non-continuous memory. For example, if this is your heap memory and you have some data, maybe 1 is stored here, 2 is stored here, 3 is stored here, 4 is stored here. They might form a chain-like structure, and where each object is referring to is holding the address of the next object in the chain. This is called as a single linked list, where each object knows the address of the next node, but it does not know anything about the previous node. So if you arrive at 3, you can only go to 4. If you arrive at 4, you can only go in the forward direction. Let us talk about linked list little more. So we don't have to specify the size of the linked list. It's a dynamic data structure. As you add more data, more objects get created in the memory and they become part of the chain. And size is changing automatically as the data is added or removed. So you don't need any fixed size array to initialize it, right? Now let's talk about the implementation. As I just talked about, each node in a linked list, it's going to hold data. It is also going to hold the address of the next node. And if it is a doubly linked list, it is also going to hold the address of the previous node. The nodes are not stored in a continuous memory location. They are linked to each other with the help of next and previous pointers. Okay, so this is something we'll go into the detail when we talk about when we do a tutorial on linked list. But for now, we just want to see how to use the inbuilt linked list class and understand its advantages and when to use it, right? So in Java, the default implementation provides us with a doubly linked list. So a doubly linked list, each node stores 3 things: the object or the data, the next node's address, and the previous node's address. So at 2, you know where is the next node located and where is the previous node located. At 3, you know where is the next node located and where is the previous node located. So you know all the 3 things at each node inside a linked list. That is what a doubly linked list is, right? And creating a doubly linked list is fairly simple. So you just need to use the linked list class provided by the java.util package and the data type, what kind of data you want to store in this linked list, and it will create a linked list for you, right? Now let's talk about the features of the linked list. The biggest feature is we can use the non-continuous memory. So if you don't have a linear block available, we can still create a big chain by utilizing the non-continuous blocks of the memory. It is a dynamic data structure. There is no need to pre-allocate the memory, and hence it results in efficient utilization of the memory as well, right? And insertion and deletion at the ends of the linked list are performed in constant time. Now this is a very big advantage. So if you have an array and you want to insert something at the beginning, you would see that I will have to shift the entire array, then I can insert a 0 here, right? But in case of a linked list, this time, which is order n in an array, inserting at the beginning, it's going to be very fast. Suppose you have 1 2 3 4 5, you already know this node, okay, and you say I want to insert a 0 here. So you create a new node and you say okay, head should point here and 0 should point here. This can be done in order 1 time. Similarly, the last node is referred by a tail pointer. If you want to create something at tail, you can simply add 6 here and your tail will move here, right? So if it is a doubly linked list, insertion and deletion both at the both ends can be just done in order 1 time. This is a very, very big advantage of linked list, and concatenation of 2 linked lists is much more efficient in terms of space and time. So if you want to merge 2 array lists, you will have to copy all the data, right? But if you want to merge 2 lists, let's say I have another list 7 8 and 9, in that case merging is also very easy. You just need to connect this node with this one, which is again going to take order 1 time. Concatenation is also very fast in case of a linked list, right? So let's talk about the differences between the operations, right? So random access. Now that means if I want to get any ith element, this is very fast in array, right? So I know I can get I can do array.getI. this works in order 1. But if you want to get some ith element inside a linked list, there is no direct way. You have to iterate it. It's in the worst case, it will be order of n. Insertion and deletion at the beginning. In case of linked list, as I told you, it's order 1. In an array, it's going to be order n because you have to do the shifting. Insertion and deletion at the end. So if it is a doubly linked list, and we are maintaining the tail pointer, we can do it in order 1 time as well. And in array, it is also order 1. So this can be made order 1, right? It depends upon the implement. Insertion and deletion from the random location. So of course, this deleting something from the middle, both in array and a linked list, will take order of n time. Right? So I hope you understood the basics of a linked list. Now let's look at the implementation. So I have this code in which we said, okay, we are creating a list which is using a new array list object. So instead of now using array list, I can simply replace it with linked list. And since both array list and linked list implement the list interface, so all the methods that we saw with this list, they will also work with linked list as well, right? So I need to import this class. Let me just type linked list, and this will get imported. So import java.util.link. So this is also there. If I run this code as it is, the same array list code, it will work. All the methods that we used on array list will also work on linked list as well. Right? Now, apart from it, there are some additional methods as well, which are provided by linked list. For example, adding something at the beginning of the list. So that method is not there in array list. We can use that method. For example, I can say list dot add first. I can say, okay, in the beginning, you add an element that is 0. You might be saying, okay, we are getting an error here. Add first, there is nothing like this. Now, why we are getting this error? Because add first is not a method inside the list interface. Okay, so what happens is your list says that, okay, you must implement an add method, whereas your linked list class, which implements your list interface, right? It says, okay, I will implement the add method. I will also implement the add first method. That means you cannot call add first method on a list kind of a variable, right? It is of the type list. What I need to do, I need to say, okay, the object that I'm now creating is exactly a linked list. Okay, if I make it linked list, you can see add first will work because you can easily add in the beginning of a linked list. I can say, okay, maybe add -20 here and show me this list. So I'm running the code and you can see -20 is there. It's added in the beginning of the list. So we have more methods. Let's look at some more methods. All right. So just to save time, I'll quickly go through all of these methods. So there is an add method, which we saw on the list. This is also there. Add all is also there. Add all we have seen, right? Now add first, I just showed you the demo. It adds the desired element in the beginning of the list. Similarly, there is a add last method. It will add at the end of the list. So it will work same as your add method. There is a clear method, which is fine. There is a clone method, creates a shallow copy. There is a contains method, element present or not. Right? Then popular methods are get. I want to get particular element, works in a linear time. Get first, get the first element. Get last, get the last element. Index of, you can use, right? Now, there is also a method called as offer, right? This method is used to add at a specified element at the tail of the list. Now you might be asking, what is the difference between add versus offer? So let us discuss this as well. For that, you need to go to the Java linked list class, right? So I'm Java linked list, the Oracle docs, right? So if I look here, what is happening? The linked list class, it actually implements not just your list interface, it also implements your deck interface, it also implements your queue interface. That means all the methods of the queue, all the methods of deck, they should be available as a part of linked list. So what is deck? A deck is a doubly ended link. It's a doubly ended queue. So that means you can do push and pop. That means you can add from the rear end, remove from the rear end, and you can also do push and pop. That means you can add from the front side and also remove from the front side of the queue. That means insertion and deletion can happen at the both ends of the queue. Now, in order to implement this deck interface or the queue interface, let us look at what all methods are there in the deck interface. Inside the deck interface, you see there are methods. You want to insert something at the beginning, there is a add first method that should be implemented by that class. If you want to remove something, the remove first should be there. You want to get something, get first should be there, right? Similarly, for the last element, add last, remove last, and get last should be there. Now there are two versions of the same method. One is add first, one is offer first, right? What is the difference between add first and offer first? So the difference is written here. So what they're saying is that both methods are provided to insert, remove, and examine the element. Each of these methods exist in two forms. One throws an exception if the operation fails. The other returns a special value. Basically, your offer method, it returns like true or false or null if your operation fails, right? Whereas add first will throw an exception. So it again depends upon your use case, how you want to use this method. If you're working in an environment where your capacity of the data structure is restricted and you are trying to insert something and your data structure is already full, so what do you want? Should it return false, that I cannot execute this operation, or should it throw an exception? If you want to throw an exception, go with the add first method. If you want to handle it using a value like true, false, or null, you will have to go with the offer first method. So because linked list implements the queue and the deck interface, which needs these methods, hence you will see there are many methods which are doing the almost same work, right? Between add and offer, there is a difference of the return type. Should you, not the return type, but how do you handle the failure case, right? So you are going to return something like true, false, or should I throw an exception, right? So that is offer, and we have offer first, we have offer last, right? Then there is a method peek. So peek means to look. I want to look at the element. So if you simply call peek, it will show you the first element of the linked list, the head of the linked list. Peek first fetches the head of the linked list. So peek and peek first, they are same. Peek last, show me the last element, right? Then there is a method poll. Poll means I want to fetch the first element of the linked list. It will return the first element and remove it, right? Poll first is also same. Removes the first element, or it's going to return null if the list is empty. Then there is poll last. It will remove and give you the last element of the linked list, or it will give you null if the linked list is empty, right? There is a method called pop as well. Linked list can also be used as a stack. So in stack, we generally call removing the last element as pop, right? And push is also there. If you want to push something in the stack, I can say, okay, I'm pushing something. So it will push something into the linked list. If I say pop, it will remove the last inserted element from the linked list. Similarly, the remove method is there, right? Remove first is there, remove last is there, set is there. You want to update a particular element, and toString is there. That means if I want to print a linked list, it will call the toString method, and each element is separated by a comma and it is enclosed in square bracket. Whenever we are printing this, whenever we are using system.out.print list, what is happening internally, it is using the toString method of the list object to give us list which looks like this. Okay, this is coming from the toString method. So I hope you really got an idea on what all methods you can use on a linked list. So many methods are there. So mainly you need to remember that you can work on both ends. You can work on the front side, you can work on the rear end, and you can also insert in the middle, search in the middle. But insertion and deletion at the ends, it is fast. In the middle, it's difficult. Random access, it's difficult. It's going to take order of n time compared to an array. So that's all. I'll see you in the next data structure. Let's talk about stack. Stack is a very simple and easy to use data structure. So just like arrays and linked list, it is also a linear data structure that is used for storing data, and it looks very much like a real life stack, such as a stack of books, a stack of plates, and let's see. So it's kind of an ordered list in which insertion and deletion are done only at one end. For example, if you have items coming in 1, 2, 3, and you push them items into a stack, so 1 will go, then on the top of it 2 will go, and 3 will go. And if you start popping items, 3 will come first, then 2 will come, and then 1 will come. So it's also called as last in first out data structure. The element which is inserted at the last is the first one to get removed. For example, if you keep a stack of books, you put a C++ book, then you put a Java book, and then you put a Python book. Python book is the one that you can pick first, followed by Java book, followed by C++ book. Last in first out property stack has. So internally, if you want to see how it is implemented, you can use a fixed size array. You can also use a dynamic array. You can also use a linked list to implement a stack. And how it is different from arrays, arrays allows random access. You can get any ith element, but in case of stack of books, you can only access the topmost element. So in a way, there is a limited access possible, and only topmost element is directly available in case of a stack. Stacks are generally dynamic in nature. That means we don't have a fixed size, and size can be increased or decreased depending upon the push and the pop operations that we are doing, right? So the container that you are using can be a fixed size array as well, but in general it would be dynamic, such as a dynamic array or a linked list. So the operations on stack, they are very simple. You can push an element into the stack, you can pop something from the stack, and you can peek. Peek means you can look at the topmost element. Let us look at a code demo to understand these operations well. So in Java, we have a stack class, which also implements your list interface. But on the top of it, stack has its own methods as well. So let's look at a demo, right? So I have created a stack object, stack of string called books, and in this I can push something. So I can say books dot push, right? Now you see there is a add method as well. The add method is coming from the list interface, or I can simply call push method, which is specifically implemented by the stack class. So I can say, okay, let me push C++, let me push Java, and let me push Python. Let me just create 3 books and push it. That's okay, Python. Now, if I print the stack, I can say, okay, show me what elements do we have. I call it as books. Let's run the code. And suppose if I want to see the topmost element, the topmost element will be what? It should be Python, right? If I want to look at the topmost element, so I can simply call peek, right? So I can say, okay, sout books.peek, that will give me Python. And if I want to remove it, I can call the pop method. I can say books.pop, that is going to remove the topmost element. And now if I do peek, I will see Java next. Sout books dot. And apart from these methods, we can run a loop, like we can say, okay, while the stack is not empty, I want to books dot is empty. While this is not empty, I want to keep on popping elements. I want to remove them, so I can say sout books dot peek, and I want to pop everything, books dot. This is one way to iterate on the stack. You have to remove all the elements, and yeah. So I hope you are able to understand this example. So we are able to remove all elements. We first removed Python, then we removed Java, and then we removed plus plus as well. That's all about stack. Very simple data structure, right? And hopefully you will be able to use it. Let us talk about queue. A queue again is a very simple data structure. It's just like a real life queue. The sequence of object waiting to be served in the sequential order starting from the beginning of the queue. So in general, queue maintains a FIFO kind of ordering, but we also have something called as a priority queue, which is little different. For example, a FIFO queue would mean a queue of cars at a toll booth. Cars are coming in to get their ticket, or people are standing in a line to buy their tickets. What happens in general, people enter from the rear end of the queue and they leave from the front side of the queue once they get the ticket. So adding something into the queue, it's called as NQ. Removing something from the queue is called as DQ. Someone has been removed from the queue. So insertion, as I discussed, it happens at the rear end of the queue, whereas deletion happens at the front end of the queue. Last in, last out. The person who is entering in the last is the last one to come out, or you can say it's a FIFO, first in, first out. The person who is coming first is the first one to come out, right? The front of the queue is returned using a peek operation. So if you want to say, okay, I want to see who is at the front, the most libraries, they have a peek method. Like in Java, we have a peek method to see what element is at the front of the queue, right? And similarly, there are methods like offer to add something at the end of the queue. And if you want to remove something from the front side, it's called as poll, right? We'll look at three methods: offer, adding something at the rear end; polling, removing something from the front side; and peeking means looking what is at the front. Okay, so peek only gives you the element, whereas poll removes an element from the queue, right? So these are three methods that we will discuss. If you want to implement a queue at your own end, you can use a fixed size array, also known as a circular array, to implement the queue. You can also use a dynamic array, or also you can use a linked list. So there are limitations of queue data structures. A queue is not readily be searchable. You cannot go inside the queue and search. So you might have to maintain another queue to store the dequeued elements. Okay, so you have to empty the entire queue if you want to search for something. And traversal, of course, we cannot traverse. That is the same thing. You have to again remove all the elements to do the traversal, and in this process, queue becomes empty. So these are limitations of the queue. So operations, you want to add something. So the equivalent Java method, it is called as offer. I want to add something into the queue. Want to remove something, the Java method, it is called as poll. And if you want to look who is standing at the front, the method is called as peek. Let us look at the queue methods in our code demo. And if I talk about what are the methods there in Java, right? So if I told you that queue is an interface in Java, right? So this interface is implemented by three different classes. One is called array_deck, which stands for doubly-ended queue. We can use linked list, which we will be using to implement our FIFO queue. And there is also something called as priority queue, which we will also study very soon, right? We'll go with the linked list wala implementation, right? The methods that I told you, they are insert, remove, and examine. Examine is like peek, right? Now, again, I told you there are two versions that Java provides. One set of methods that throws exception. So if you use, okay, I want to add something into the queue, there is a add method. Or if you want to do the same functionality, you can also use the offer method. Offer method returns a special value whether your operation was successful or not. Add method might throw an exception if your add operation fails because of some reason. Okay. Similarly, remove throws an exception if your operation fails. Poll will not throw an exception. Element, you're looking for an element maybe at the empty queue, right? It can throw an exception. Peek will not throw an. This is how these methods are designed. So I will be going with these methods, okay, in the implementation. Let me jump into the code and let's quickly create a queue, right? Well, it's okay. I want to create a queue of integers. I call it as queue, and I say, okay, the queue implementation. So queue is an interface. The implementation is provided by the linked list. So we'll be using linked list for this queue, right? So we also need to import it. Now, how do I do it? I can say queue.add some numbers. Let's say 1, 2, 3, and 4. Let me just copy this. Now, if I say, okay, I want to see who is at the front of the queue, or let's just print the entire queue. Let's run this code, and simultaneously, let's see who is at the front of the queue. So I can say sout queue.peek, show me who is standing at the front. I will see 1 is standing at the front. So 1 came first, right? Now, if I remove this, I say, okay, I want to remove 1. I can say queue.poll, and then I can say show me the entire queue and also show me the front element. I can say queue dot. Just like stack, you can also use a while loop to empty all the elements of the queue. So after removing 1, the queue is 2, 3, 4. And if I look at the front element is now. So you can put a loop like this while your queue is not empty. You can keep on removing the elements from the queue. That is all about queue. I hope you really understood how to use queue in Java. So next in line is the deck data structure. So it stands for doubly ended queue and it's pronounced as deck. So it is again a linear data structure that allows insertion and deletion at the both ends. Okay, so you can do insert here. You can say, okay, I can expand in this side, or I can also expand in this side. Maybe I insert 5, maybe I insert 12, or I can remove from both ends of the queue. It's a queue that supports insertion and deletion at both ends. So basically, internally, we can use a linked list to implement it. And Java also provides a special class called as arrayDeck, which implements the deck, right? So if I look at the hierarchy, so we start with the collection interface. We have seen the queue interface extends the collection interface. It adds some more methods into the collection. Then there is also a deck interface, which I've not shown earlier in the diagram. And the array deck is a implementation of the deck interface, right? Array deck is implementing the class that implements the deck interface, which is extending the queue interface. Okay. So this is what it's a good to know thing, not mandatory, right? Array deck and linked list are commonly used deck implementation. If it is a doubly linked list, you can see it is very easy to expand something on both the ends, right? So you can simply add something here as well and your tail will move, right? You can add something here as well, your head will move, right? So it's pretty easy to use linked list, but ArrayDeck internal implementation is little more complicated. So I'll discuss few more points about ArrayDeck. It is an implementation of the deck interface that uses a resizable array to store its element. And deck is a subtype of queue interface that we have just discussed. Best thing about ArrayDeck class is it provides constant time performance for inserting and removing elements from both the ends of the queue. Now this is very tricky, right? In an array, we cannot do constant time insertion and deletion at both the ends. We can do only at one end, right? But in array deck, it uses internally some complicated mechanism so that we can remove and insert from both the ends of the queue. And these operations can be done in order one time from both the ends, right? This is a very powerful feature of array deck that we must know, right? Talking about the operations, right? If you want to add something at the beginning, you can say add first. Okay. Or you can use a method called as offer first. These are two methods which are doing the same work. There is a minute difference. If due to, let's say, capacity limitation, you don't have memory or you're restricting the size of the queue and you're trying to add some element, then add first will throw an exception. Just like other add methods we have discussed. The offer method will return false, that okay, I could not return this element. I could not add this element. Similarly, we have remove first and poll first methods. So remove will throw an exception. Poll will return true or false. Get first will throw an exception. Peek will tell me whether the element, like if I could not get that element, it will throw an exception. Peek will tell me null. I could not remove that element. That might happen, right? There is add first, there is add last, offer last, remove last, poll last, get last, peek last. Now, if you ask me what methods I would be using offer first, poll first, peek first. So if you want to do operations at this end, you want to add something, use offer first. If you want to remove something from the front, use poll first. And if you want to look at what is this element, you can use peek first, right? Same operations. If you want to do at this end, what you will do, you will say offer last. I want to add something here. I want to remove something from here. I will say poll last. And I want to see something. What is this last element? So I can say peek. Show me the last element. This deck. So that is about the operations of deck. Now let us look at a code demo for deck. So let us create a array deck object. You can say array deck of, let's say, integer deck equals to array deck. And in this deck I can add elements. I can say offer. So there is a offer method as well. Offer first is there, offer last is there. Seconds, okay, let me show you offer first. Let's say 12 deck dot offer first, let's say 15 deck dot offer last, let's say 20 deck dot offer, let's say 30. Let me show you what order the elements have been inserted. S out, I will say deck, and let's run this code. I'm getting 15, 12, 20 and 30. So first I had 12 offer first. I said in the beginning I want to add something. 15 gets added here. Then I say offer last 20. So 20 gets added here. Then I said offer 30. Offer is actually behaving like offer last. Offer and offer last, they are doing the same work. This is how your deck is getting created. Similarly, if you want to remove something, you can call the poll method. So you can say s out deck dot poll last. Give me the last element. S out deck dot poll first. Give me the first element. And if you want to see now what is the new first element, you can just call peak. So you can say s out deck dot peak first. Show me the new first element, and s out show me the new last element. Peak last. Let us run the code and see. So this is our deck. Now I say give me the last element, so it removes 30, it's gone. Give me the first element, it removes 15, it is gone. Show me the first element is 12. Show me the last element, the last element. That is how easy it is to work with deck, and I hope you understood the concept. Let us talk about priority queue. Priority queue is a special type of queue in which each element is associated with a priority value. For example, if people are standing in a queue and you might want to give priority to the senior citizens, maybe age is a criteria in which people will get their tickets. Okay, senior people will get their ticket first, young people will get their tickets later. So basically elements that we are going to serve in the queue, they will be served according to a certain priority. Higher priority elements are going to be removed, and it is up to you how do you define the priority. Okay, maybe a big number has a more priority, or maybe a lower number has a more priority. We can have a max priority queue, we have a min priority queue. We can insert, like people can join the queue, right? But maybe this is 16 years, this is 20 years, and this is maybe 4 years, right? Now if I say okay, I want to remove someone, I'll remove the person with the maximum. I'll remove person 20, right? So this will get removed. So people can join the queue, but when I'm going to remove people, the people with the higher priority will get served first, right? So the underlying data structure for a priority queue, it's a heap. We can have a main heap or a max heap. I will not be able to dive into the details of heap at this point. We'll be looking at how do we use the Java priority. So the operations that are supported, we can insert something. Inserting in a queue, it's called as a offer. Right? I can offer some data inside a queue. I can look at, if I want to see who is standing at the front of the queue, that is called as peak. And if I want to perform deletion, I want to remove someone, right, from the queue, that is called as poll. Right? We'll be looking at these methods, right? And insertion and deletion, they are login methods looking who is at the front, the order one method, right? So let us do a quick code demo as well. So we have seen how to work with the queue. This is the code for a queue. A priority queue also is a class that implements the queue interface. Okay, so right now it was a FIFO queue. Now I'm going to change it to a priority queue, right? So rest everything will change. So if you want to add method will also work, but if you want to use the offer method, I can use the offer method as well. I can say q.offer some numbers 10. Will change the data. Like I have 10 0 8 maybe 7 and let's say 9, right? Now if I say okay, I want to print the entire queue, let's see what output do we really get. Okay, so I'm getting this output 0 7 8 10 and 9. Now I want to look at what is the first element. I'm in this case the lowest element, it's getting priority, right? So you see 0 is coming at the front of the queue. Rest of the queue is not actually sorted. Only the uh, priority element, it comes to the front of the queue, right? So 0 is there. If I say, okay, I want to look at this element, so this element is 0, and I want to remove this element, so it removes 0. And now what is the next lowest element in the queue? That is 7. So 7 comes to the front of queue. If I make it 17, then the next lowest would be 8, right? So let me run it once again. Now I have 0, 9, 8, 17, and 10. The lowest element, it is at the front, right? Then if I remove 0, the next lowest is actually 8. So that comes to the front. So if I remove that element, or if I look at what is that element, I get that element 8. Using the peak operation, you can see the element. Using the pole operation, you can remove the priority element. Now you might ask, if I want to reverse the order, okay? So in that case, you can pass one more comparator. So I can say, okay, comparator dot reverse order. This is exactly going to reverse the comparison. A min priority queue becomes a max priority queue. In this case, the highest element, it's going to get a priority, right? So now you look at 17 is standing at the front. If we remove 17, 10 is standing at the front, and there is no specific order for rest of the elements. That is unpredictable. We are only worried about the element at the front should be either the min element or the max element. This is about priority queue in Java. Let us talk about a set interface now. So what is a set? Mathematically, it is a collection of elements that cannot contain duplicate elements. Okay. So set in Java, it models the mathematical set abstraction. Now the set interface that we have seen, it contains only the methods inherited from the collection. So that means there are no additional methods inside the set interface. All the methods are inherited from the collection, but it adds the restriction that the duplicate elements are prohibited. Everything, all the methods which are there in collection, right? The same methods are there in set, except the condition that duplicate elements cannot be present. There are three classes in Java that provide the implementation of set. There is hash set, there is link set, linked hash set, and there is tree set. So let us try to understand the differences between the three implements. So as I discussed, there is hash set, tree set, and linked hash set. So hash set stores the elements inside a hash table. It is the best performing implementation. However, it makes no guarantees regarding the order of iteration. You say, okay, I inserted 10, 20, 15, 18 inside the set. And if you start iterating over the elements, you are not guaranteed to get any order. You might get 20, 18, 10, and 15. So the elements will come out in any random order, right? So it does not ensure any kind of ordering on the hash set. The internal data structure is a hash table, and there is a linked hash set. So it is implemented again as a hash table, and along with the hash table, we maintain a linked list. So that means these elements are going inside the hash table, but also we uh, like chain them together so that we are able to maintain the order of insertion. So it has implemented a hash table with a linked list running through it. So it combines the features of hash table and a linked list and orders its elements based upon the order in which they were inserted. So basically, it maintains the insertion order. Okay, so it's going to give you the features of the hash set along with the ordering that is maintained. There is one more thing that is called tree set. It stores the elements in a red black tree. So red black tree is a self-balancing binary search tree, which is a height balanced tree, and it orders its elements based upon their values, and it is subsequently slower than the hash set. Basically, whenever we talk about BST, right, and it is a height balanced BST, so if you have to do an insertion searching inside in such a tree where the tree height is log n, so it's going to take all the methods like inserting data, finding data, they are going to take order of log n time inside a tree set. Whereas on hash set and linked hash set, the time complexity is going to be order 1 on average, right? So basically, the advantage of tree set is that it keeps your data sorted. Linked hash set keeps the same order as input. Hash set, it is the fastest and it is the, but it does not give us any guarantees on the order. So these are three different implementations of set in Java. Let us look at the code demo for hash set. Okay, if I want to create a set, let's say set of integers. s, this is equal to new hash set, right? Now I want to do something on this. Let us import as well, right? Java.util.set, import has been done. Let us add few numbers into it. Let's say set dot add s dot add some numbers. Let's say 10, s dot add 20, s dot add 18, and s dot add, let's say, 15, right? And s dot add 40. I've added few numbers, so let me display s out the set. Let us run this code and see what do we get. So I'm getting 18, 20, 40, 10, and 15. You see, the order is random. There is no fixed order. 18, 20, 40, 10, 15. It's kind of a random order, right? If I want to add, like if I add a duplicate element once again, so if I say okay, add 10 once again, and if I run this code, you will see this, it will not store the duplicate elements. Only 110 is stored. Even if I added once again, the duplicates get filtered out. So no duplicates are allowed in the set, right? Suppose I want to remove an element, so I can say s dot remove 40, right? This will remove 40 from the set, and what is not there, right? And suppose if I want to check if a particular element is present or not, so if I can say s dot contains some number 20, so you can say yes, it is present. Or I can simply say just do s out whether 20 is present or not. So s out s dot contains, so it will give me true or false whether this element is present or not. So I will get a true here, right? So 20 is present. These are the three fundamental methods: add, remove, and contains. And if you remember, these are the methods, they were part of collection interface as well. We can use these methods on uh, any data structure that we have seen so far, right? And all of them, they inherit from the collection interface. There are few more methods which we have with the collection interface. Is empty, we can check size, how many elements are there in the set. Clear, remove all elements from the set. And we'll also see how do we use set with custom objects. So let me first show you the size method, how many elements are there in this set. So currently we have 4 elements, so this method will tell me, okay, there are 4 methods, there are 4 elements inside it. Now we have worked with a set of integers. Now sometimes we might have to work with a set of a complex class, maybe a set of books, set of students, a set of payment IDs, or set of debit cards, right? Anything can come here. So data type can be anything. So let us see how do we implement set with a custom data type and what will change. Okay, before we discuss the custom set, there is one more thing. So we just discussed that okay, we can use a hash set class in Java, but we can also use linked hash set, and we can also use tree set. So I'll comment this out and I'll show you 2 more examples. Instead of creating a hash set, I can create linked hash set in Java. And if I use this, you will see I will be able to maintain the same order as insertion in this set. If I remove 40, I will get 10, 20, 18, and 15. So this follows the order of insertion, right? And if I use something like a tree set, that is slower because it uses self-balancing binary search trees. Doing add and remove, it's going to take log n time on a tree set, but it's going to maintain elements in a sorted order. So let's see that as well. Now the elements are sorted in the set because we are using a tree set. So I hope you are able to understand the differences between hash set, link set, and tree set. Now we will move into a set with a custom class, set of custom objects. Let's see that. Now let us discuss how do we use set with a custom class. Now suppose you want to create a set of books. What I have done, I have defined a book class in which book has 3 properties: ISBN, name, and price as the attributes of a book. What I'm doing, I want to create a set in which every item is of the type book. Now let us insert few books into this hash set. I can say books.add. Let's say I want to create a new book. Each book should have a name, a ISBN, which is a unique code, and let's say the price of the book. And let me say, okay, I'm going to add few more books. And here I make the name as, let's say, Java. ISBN is 2. And let's say I change the price, right? Now, if I, let's say, go and run this code, let us see how many books we will have. So s out books dot size, and let's say s out books. I also want to see what are the books that the set is storing. So I'm storing 3 books, and you can see C++ book is getting stored twice, right? And Java book is coming once. Now, why is this happening? Why it is not able to filter out that these 2 books are really same? The reason is we are creating this object using new, right? So for the set to know whether these 2 objects are same or no, there is no way, right? So we are creating a new object. Set will treat that these are 2 different objects created at 2 different memory locations. Maybe this is 1056, this is 2080. So for set, these 2 books are different because they are 2 different objects in the memory, right? We need a way to tell this set that, okay, you should consider these 2 objects as same. In order to do that, one thing we need to do is we need to define, internally it is using the concept of hashing, right? So it's going to compute the hash code for an object. You have to tell me, how do I compute the hash code? So for that, I need to override a method which is called as hash code. What I'm going to do, I'm going to overwrite a method called as hash code. In this case, if I want to compute the hash code of a book, maybe I want to say, okay, compute it only on the basis of ISBN. ISBN is a unique number, right? So let me do it once again now. Let's see if something changes or not. So again, it is not changing. So when I'm hashing the books, although the books are getting hashed on the basis of ISBN, still the set does not know whether the 2 books are equal or not. So what happened? We uh, computed the hash code for this book, inserted it into the set. This book went into the set. We again computed a hash code for this book, it also went into the set. 2 objects, they can have the same hash code, that is okay. And the thing is, I need a way to tell the set, consider these 2 objects are equal. So maybe I want to say that so I need to provide a method that is called as equals method. Okay, so let's see how do we write this method. So there is a pretty standard template to do it. So whether 2 objects are equal or not. So whenever you are inserting a new object, let's say you're inserting this object into your hash set, it's going to compare that whether such a object is present or not. So why, at what location it's going to compare? It's going to compute the hash code, and it's going to check whether we have something at that location or not. So suppose C++ was there, some other book Python was there. Suppose they two had the same hash code. So it's going to compare whether these 2 are equal or not, whether these 2 are equal or not. So this concept will be a little more clear if you understand the technique of separate chaining, right? Different objects, they can have a same hash code if they have the same ISBN, or the hash function is producing the same value for 2 different numbers as well. It can happen, right? But what we need to do is we need to tell that, okay, the 2 objects are equal if their ISBN is same, right? So what I will do is, what I have done here is, I'm saying that, okay, I'm giving you an object. So I say, okay, book B1, compare this object equal to B2. These 2 objects are equal in like 2-3 scenarios. I'll discuss what are those scenarios. Suppose I create a book B1 which is equal to new book, and I say, okay, B2 is a book which is equal to B1. So in this case, what is happening? I have just one book object. Both B1 and B2, they are pointing to same, right? If I make any change in B1, it will also affect in B2. So what I'm doing, that if this is equal to O, that means if the current object and the other objects, they are referring to the same memory, that means they are equal, right? If O is null, if one of the object is null, they cannot be equal. Or if the 2 objects, they belong to the different class. So suppose if I compare a book with a student, they can never be equal. I am returning false. Otherwise, any given object, I typecast this into book clause, and then I compare that is the ISBN of my book is equal to the ISBN of other book. If this is the case, consider the 2 book objects to be equal. If I add this equals method, my hash set will come to know that, okay, these 2 books, they have the same ISBN. I will not insert them again. Even if I now look, I have only 2 books, okay, and C++ is stored only once. Now even if I change the name of this book, I say, okay, this is C++ version 2 and the price has been increased to 120. Will hash set store this book? The answer is no, because it is only going to compare on the basis of ISBN. If ISBN is same, I will not again store this book, right? But if you want, okay, the two books are equal, if their name is same, if their price is same, if their ISBN is same, then in the equals method, you can have two more conditions along with the ISBN, that I should match all the three parameters for the comparison. The equals method is important, so you need to override this method to tell the set in what scenario you should consider two objects as equal. So I hope you're getting it, and that's all for this implement. Let us talk about the final data structure, that is a map. A map contains values on the basis of key. That means it contains information in the form of key value pairs, just like a restaurant menu. Whenever you go to a restaurant, you say, okay, I want to have a burger, and you immediately get to know the burger is 50. I want to have a pizza, the pizza is 200. I want to have a Coke, the Coke is, let's say, 70. There is a key, there is a value associated. A map contains unique keys. That means I cannot have a burger twice in my menu. Okay, a map is useful if you have to search, update, or delete elements on the basis of key. So we do not ask, okay, what item is after burger or what item is coming before pizza. The ordering is not that important to us. What is important, that given a key, what is the value associated with that item? And I want to, okay, Coke is out of stock, so I want to delete this key value pair. Or something new has come up, I want to insert that key value pair. Right? For operations like these, map is a very good, useful, powerful data structure, and most of these operations, they run in order 1 on average. So search is order 1 on average, update is order 1 on average, delete is order 1 on average. So very powerful data structure. Now let us talk a bit more about map. Java platform contains three general purpose implementations. One is your hash map, another is your tree map, another is your linked hash map. So the behavior and the performance is same as the way hash set, tree set, and link set work, right? So hash map internally uses a hash table. It's the technique called separate chaining that is used to implement a hash map. So to understand hash map, we'll do a separate video where we'll dive into the internals of a hash map. Tree map is like a self-balancing binary search tree, and linked hash map is your hash table, and it also maintains a linked list of the elements in which like it chains the elements through the linked list as well, in the order in which they were inserted. So it's more complex than a hash map. Map does not allow duplicate keys. Just like a hash set, we cannot have duplicate elements, but we can have duplicate values. For example, burger can cost 50, noodles can also cost 50. The value can be duplicated, but the key must be different, right? Hash map and linked hash map, they allow null keys and values, but tree map does not allow null key or a value, right? Tree map, you cannot store a null key. A map cannot be traversed, so you cannot directly iterate on the map, so you need to convert it into set using key set or entry. This we will look into the code demo. Talking a bit more about the hierarchy in Java, there is a map interface, okay, and hash map is an implementation for the map interface, right? There is a linked hash map which builds on the top of your hash map class, right? Hash map is a class, linked hash map is also a class. Tree map is a class that implements your sorted map interface. Sorted map interface is again an child interface of map, right? It kind of extends that map. Here ordering is important, right? You get the keys in a sorted order. Here you get keys in the order in which they were inserted. And hash map, it is the fastest. Here you don't get any ordering on the keys. This is the difference between the implementation. Also, the operations are order 1 here on average. The operations on tree map, they are order of log n on average. Why? Because it is using a self-balancing binary search tree. Okay. So here I have implemented a map object by using the hash map class, right? So I've created a map called as menu, and I'm going to add certain items in. So I can say menu dot add. It say the item is dosa and the price is 200. Menu dot add. Let's say the item is burger. The price is 50. We are getting a error here. So the method is called as put. Hash map, we don't have the add method because it does not inherit the collection interface. Okay, I told you map is separate from map interface is not it's not a child interface for of collections interface. Okay, so it has method called put. It does not have a method called add. I can put key value pairs like this. I can say menu dot put noodles and maybe some price, and here I can say s out, show me the menu. Let's see if we get something here. So let's see what do we get if I run this code. In the meanwhile, I will write down some more methods. I can see I can see the list of key value pairs that are stored inside this map. I can also remove something. I can say menu dot remove. I give burger. I just need to give the key. The burger will get removed from the map. I can also search that if my menu contains some item like dosa, I can say contains key. This is the method, and I can check whether it is present. So you can say yes, out, s out dosa found. So you can do this as well. But after removing burger, we have two items, noodles and dosa in our map. Right? So dosa is there. So dosa found, it gets printed. Now let us also talk about how we can iterate on the map. There are multiple ways, right? So what we can do is, okay, I just written the 3 ways to iterate so that we can save some time. So the way one is, I can create an object of the type map.entry, and this object is iterating over uh, all. So menu.entry set is a method that gives me the list of key value pairs where each key value pair is considered as an entry, right? I'm saying, okay, give me all the entries, and given any entry, I want to get the key and I want to get the value. So that is one way. So you are printing the first entry, the second entry, and then the third entry. That is one way. Another way is if you want to just get the keys of the map, you can say, okay, menu.keyset. So it will give me all the keys like dosa, burger, noodles, and you are iterating over these keys. Those keys are strings. Then you can say, okay, I want to iterate over the values that are 250, 70. I just want to iterate over these values. So you can call the method called menu.values, and it will give you a set of values, and you can iterate over this set using a for each loop, and for every value you can print it. I'll just run this code and show you the output. You can see I'm able to iterate over the keys, I'm able to iterate over the values, and I'm also able to iterate over key value pairs, right? So this is coming from this loop, right? And apart from it, there are some more functions which can come handy. So you can, I would suggest, can try those methods. Is empty, whether the map is empty or not. Size, how many elements we have. Clear out everything in the map, right? This is clear method is helpful if you are working with multiple test cases. Every time you have to load new items and discard the previous items from the hash maps. Instead of destroying the object and creating a new object, it's better to clear out everything from the previous map. So then there is get or default. If the key is found, you want to return some value. You want to return the value, or if the key is not present, you want to return some default value. This is something you can use. So for example, I can say menu dot get let's say pizza. So pizza I have not inserted. If the pizza is not there, I can say the default value is, let's say, 0. That means in this case I will get an answer that is 0. Right? S out this value, right? What I'm getting 0. That means pizza is not present. The default value, if the item is not present, I think the default value for that item is 0. I can also say I want to put pizza if it is not there. So menu dot put if absent. I can say, okay, it will first check if the item is not there. If pizza is not there, put pizza inside the map and put the value of pizza as 200. If I go and run this now, it will first insert pizza because it's not there. So it's basically using the put method with a condition. And now if I inquire about, give me the price of pizza, now the pizza is present because we have added it, and I'm getting the pizza price as. That's all for map, right? And now what you can do is you can also have a custom class here. You can also have something more complex here. For example, list of integers, list of books. Key can be of any type, value can be of any type. But if you're using a custom key, again, you will have to overwrite your hash code method and the equals method. This we did in the case of hash set as well. One more thing we can do is if you want to replace this with a linked hash map, you can do that. Everything will remain same, and your ordering will also be maintained. And you can also replace it with a tree map if you want. Everything will remain same except the internal structure will be now, it will be using a self-balancing BST, right? So you can also do a tree map kind of a stuff here. We need to import it. Tree map is the code will work fine, except now the elements will be sorted according to their keys, right? Let us begin by revisiting the concept of an array. Array is a very simple data structure that represents a linear collection of elements of the same type, right? So the concept of array is therein across all languages. In Python, it is called as list. In C++ and Java, it is called as an array, right? And most of the time, it is of the same type. But in Python, the arrays can also store elements of the different type. So arrays are used to store multiple values inside a single variable. I say, okay, this is a container. The name of the container is just one variable, but it is going to hold multiple values, right? Instead of declaring separate variables for each value, we just create one variable. Now this helps us because suppose you want to store 100 integers, you will not create 100 variables. Instead, you will create one array, and in this array, you will have multiple buckets. Each bucket is referenced by an index. Okay, if you want to store something at this position, indexing always starts from 0, right? We will say, okay, array of 0, I want to store the number 4. At this position, if I want to store something or I want to update something, I will say, okay, array of 1 should store 5 or it should be 15. So I can update the value anytime I want, right? So this is the syntax, right? So the variable name is array, and how do I create it? So if I want to create an array of integer, I will say int followed by square brackets followed by arr followed by, here we will see there are a few different ways. One is we can use new keyword to allocate some memory, or we can directly give the values which we want to initialize the array with, right? Let us jump directly into the code and see various ways to create an array and work with them. So first of all, I'll say, okay, I want to create an array. So this time I'm just initializing it with some random numbers. I'm not using the new syntax. You will do that as well. This creates an array. If you do s out arr, let us understand what happens behind the scenes in the memory if you do this, right? So let me go and run this code. I will see some kind of address. In Java, it is called as object reference. So I see this number. Now, what is happening if you dive little bit into what is happening in the memory, right? When your program is executing, your RAM memory is divided into two parts. One is your stack memory and one is your heap memory. Both of these memories have their different properties. Any function that you're calling, it goes into stack and it creates a stack frame out of it, right? And when you're creating this something like this, you say, okay, uh, I'm doing int x this that is equal to 20. When you create a primitive variable like this, x is a bucket, it is created here and it is storing 20. But when you create an object, Java array is an object, right? The actual object, it is created in the heap. So your 14689, it is created in the heap, and the address of this object, whatever is this address, 264, right? So 264 is stored in a variable which is there in the stack, and this is storing 264. That means the variable in the stack frame is pointing to the array object. So we call this arr as a, this is a object reference. This arr is not the array itself, it is referring to the array, right? So this is how it is created behind the memory, right? Now when you're going to print arr, it's not going to print the contents of the array. Instead, it is going to print um, what is stored in array, right? If you want, okay, I want to print the contents of this array, right? So what I will do, I will say, okay, I need a way to iterate on this array and convert everything and print everything, right? There is an inbuilt function that we can use. So there is a different class, okay, it's there is a class called as arrays, and it is part of java.util. So arrays class has certain helper methods to work with these kinds of arrays. In these methods, we have to pass the array object and get our work done. So one such method is toString. I will give you some kind of array, and I want you to convert this into a string like representation that can be printed using system.out.println. So let me give this array, and now if I show you what is the output, let's see. Now I'm getting this array. So I'm hoping that you're able to understand why this is working, right? What could be the logic behind this to string? It is doing nothing but it is doing a traversal on the array using a for loop, and it is adding everything into a string. So it says, okay, I'll start the string with the square brackets, then I will add the zeroth element, then I will append the first element, and so on. Something like this it is doing. But what is happening? It is simply iterating over the array. So if I talk about how much time it will of course take order of n time to iterate over all the elements of the array. Okay, so let us look at one more method in this array. So let me create one more array. Let me call it as some array. Let me call it as array2. This is equal to new int. I'm saying, okay, let me create an array. This time I'm not going to define you the give you the data, but I'm simply giving you size of the array. That okay, I want an array that should be able to hold 10 numbers. One thing you can do is you can manually initialize every index. You can say array of 0 should be 8, or let's say I want to fill 5 in every position, right? One way is you put a loop and update every index, right? Or you read input, that we will see very soon. But there is one more method if you want to initialize an array with a particular number. So that method is called as arrays dot fill. Look at this. There is a fill method, and you can say, okay, I want to fill this array with a number that is 12. So you need to pass the array object, that is array2, and maybe the value that you want to fill. Maybe I want to fill with the number 13. Now, if I show you the output, I can say s out uh, array2, but I have to first convert it into a string so that I can print it. Arrays dot to string, that is array2. Let me print the second array. Can you guess what the output would be? The first element would be 8, which I have overwritten. Okay, so this is updating the 0th element, and rest all the elements will be 13. This is what we are getting right. The fill method is going to fill this array with 13 at each position, and so on. And first 0th index I am updating as 8. So I get 8 followed by all 13s. That is another method present in arrays class. Okay. Arrays dot toString, arrays dot fill. One more method that is coming into my mind. It is very popular. We need it often. This method is called as arrays dot sort. That is also present in this arrays class. So I can say, okay, let me sort this array. I want to put all these numbers into ascending order. So I say 1, 14, 81. So I just randomize the numbers so that after sorting, I can see they're actually in the sorted order. Right? If I run this code now, you will see this array, it's going to be in the sorted order. We see the array is getting sorted. So internally, it uses something like a quick sort kind of an algorithm, and the running time complexity of the sort method, it is order of n log n. Okay, so this is something that you should. Okay, so let us look at one more fundamental thing in arrays, that is traversal. So there are two ways to traverse the array. One is that I can find out the length of the array, and then I can go over every index. If I talk about this array, I know there are 5 elements, so the indices are 0, 1, 2, 3, 4. So array object has a property called as length. So if I say, okay, I want to see the length of an array, so s out array length, I can say this is given by length attribute of the array object. I can say array dot length. This will give me, okay, this particular array has 5 elements. So, and if I have to iterate, I can say, okay, for I equal to 0, the index starting from 0, I less than array dot length, I plus plus, and what I will do, I will say s out array of I. This is going to print the ith element of the array, and we are doing it for all indices less than 5. We do not go till 5, but we go till less than 5 because the indices start from 0 and they go till n minus 1. This is n. The last index will be n minus. The other way is you can also use enhanced for loop, also known as for each loop. Right? So you can say, okay, for every integer x that is present in this array, I want to print that x. In this case, x is not your um index, but x is the value that is contained in this array. If it is like 1, 6, 9, 14, and 81. So in the first iteration, x will take the value 1. The next iteration, it will take the value 6. Then it will take the value 9. Then it will take 14. And then it will take 81. If I simply print the value of x, it will again give me the contents of. These are two ways to iterate on the array. Right? So if you want to iterate on some part of the array, better go with the for loop. If you know that, okay, I want to iterate over all the values, then the for each loop is a more simpler syntax. Okay, but the first loop is more powerful because you can start at any point, start at any index, and you can stop at any index. So let's run this code and see that we are able to iterate on this. Okay, so we can see we are able to iterate 1, 6, 9, 14, and 81. This is coming from the for loop, and 1, 6, 9, 14, and 81. This is coming from the for each loop that we have written. Okay, let us look at another way of building an array. Many problems will require you to reading n numbers and storing them and working with them. So for example, a very simple use case is we have to read n numbers and we want to print them in reverse. So without storing them, we cannot print them in reverse. That means we will need an array to do it. How do we read n numbers? So it's very simple. First of all, we need a scanner, Java. So scanner object is used to read something from the command. Okay, I can say, okay, first tell me how many numbers are there. The method is called as next. Once you know n, you can say, okay, I'm going to create an array. How do we create an array? Let's say I want an integer array, and I can say this is new. Here I define uh, what is the size of this array. This will create an array of size n. Now I want to read this array. So again, it is pretty simple. I will read the 0th index, first index, second index up to n minus 1th index. It's okay, I less than n, I plus plus. And in every iteration, I can, so array of I is going to hold an value that will read from the user. I can say scanner.next. Scanner.nextInt will pick one number from the command, put it in the ith bucket. And once I am done, I want to print them in reverse. Printing is easy. So how do we print it? I can say, okay, I can start from the last index, that is n minus. I can go till the first index, that is 0, I minus. So I just need to reverse the loop that I'm using to iterate over the array, and I can simply iterate in the reverse direction. So system.out.println array of I. Let us go and run this code and see. Suppose I want to read 5 numbers and print them. So let's say the numbers are 10, 20, 30, 40. So you can see I'm able to print 50, 40, 30, 20, 10. So what happened? I created an array of size n. Then I stored numbers. I said, okay, go over index 0 and read one number from the command line. So it read 10. It stored it here. Then I becomes 1. It is reading one number again, scanner.nextInt. The next integer in the line, it is reading, it is storing it, and so on. So 30, 40, 50. Then what I did, I iterated from the last index, which is n minus 1, till 0. In this direction, I iterated and I printed array of I. This will print my array in the reverse order. The next thing I want to talk about arrays is array of objects. Okay, we have seen how do we create an array of primitive data types like integer. Similarly, you can make a array of float, array of boolean, right? Primitive data types you can work with. But what is an object? So complex data types like strings. String is an object. Okay, you can also have a user defined class and you want to store objects of that class in your array. Let us see how that actually happens at the memory level and also at the syntax level, right? So suppose I have a book class. I'll just delete this method. In this book class, I have defined three attributes of the book. One is ISBN, which is your unique book code, a name, and a price. And I also have a constructor to create a book object, right? If I want to simply create one book object, how I will do it? I will say, okay, I want a book B. This is equal to new book. In this new book, I want to pass the name of the book and ISBN and a price. I say, okay, these are the three values that I'm going to initialize this book with. This just creates one book object. But what we really want, we want to create an array of books. How do we do it? We say, okay, book followed by square brackets. That is the data type of the array. Then you have to give a variable name. I say, okay, the name of the array is called as books. Let's keep it intuitive. And followed by new book. Suppose I want to store 3 books in an array, right? This is going to be 3. Now, what it's going to do, right? So as I discussed, in an integer array, your memory is going to get divided into 2 parts. One is your start memory, which your main is getting called, and we have a variable called as books, which is going to refer to an array that is capable of holding 3. Now this position is books of 0, this is books of 1, and this is books of. Now how do I put a book here? One option is that, okay, I have created a book object B already. So B is a book. So B is also created here. B is pointing to a book that is a C++ book. C++ book has some address, let's say 104. B is storing this value 104. Now I want to put this book inside this array. I cannot like physically, I cannot say, okay, this object will go inside this box in the heap. No, this is now not how it happens. The way to do it is, you will have to say that books of 0, it is going to hold B. Books of 0 is going to hold B. That simply means that whatever is the value stored in B, it is also stored in here. So this value is 10. That, what does it mean? So it simply means that books of 0 is referring to the C++ object, C++ book object that is present in the heap. This is how it is getting stored. In case of array of integers, it is different. In case of array of integers, you say, okay, array of 0, this is equal to 5. The number is directly stored here, right? But when you say books of 0, this is equal to B, books of 0 is holding the address of this book object. You might say, okay, this might be the reason, because we have created a B reference variable and then we are copying that value. Even if you do something like this, you say, okay, books of 1 should be equal to new book, and let's say this is a Java book with code 2 and price is, let's say, 200, and let's say books of 2 is a new book, which is, let's say, a Python book, and code is, let's say, 3, price is, let's say, 150. Something like this, let's say we have. Now, books of 0, books of 1, books of 2. What is happening when you're doing this statement? So this is even doing the same work, just that this new book object is getting directly stored inside books of 1. So that simply means whenever you use new book, it creates a book object in the heap memory, right? It's not going to create inside the array. So Java book is created somewhere in the heap. Maybe this location is 216, and this address is getting copied here. So this is going to be 216. That means books of 1 is going to refer to this Java object. And when I say books of 2, this is equal to new book. So again, a new book object will be created in the heap. Let's say this is Python, and it has some address, let's say 780. So 780 will get copied here. Now you want to say, okay, I want to really verify this is how it is stored. Let me show you by doing an S out, right? If I say S out books, what I'm going to get? I'm going to get the address of the whole array. Maybe this books array is created at a location that is 200. I'm going to get this 200. But now you might say, okay, no, I don't want to print this. I want to print this entire array. If I say s out arrays dot to string, basically I want to traverse on this books array and I want to print it. Let me show you this output. What output and do we really get? Okay, let me run this one. Now you see what we are getting here is the address, is the value that is stored in this books variable. And what we are getting here, these are the 3 addresses stored in this array, which are referring to the 3 books that we have. This is C++, Java and Python. 3 objects, their addresses are stored in the books array, and this is what we are getting, right? Now you might say, I want to print the content. I actually want to print the object. I don't want to print an address. How do I do that, right? The reason is Java does not know how do we print this book. Okay, how do we actually go to a location and print that object? So in order to do this, there is a method called as toString that is present in inbuilt classes. Okay, for example, when you print strings, string has a toString, or if you print like some object, right? So many objects have their own toString method. What we have to do, uh, we have to go inside the book class, which is this, and we have to say, okay, I want a toString method, right? Public string toString. So this method should return a string. It is automatically giving me a recommendation that there is a default template in which I will concatenate these three properties of the book, which looks good to me. So I will just click OK, and it will create a method for me, right? So when I want to say, okay, I want to convert this book into a string, internally it is going to call the toString method of book, right? Which method I will tell you, right? Let us go to array of objects. When are you saying arrays.toString, it is going to iterate on each book, and it is going to convert that book object into the string like representation if the toString method is overwritten, right? We have overwritten that method, so what we will get, we will get the contents of the book. Let's run this code now once again and see what do we get now. Now you can see I'm getting a book, that is the C++ book, then the Java book, and then the Python book. You might ask, okay, can we do something more on this object? The answer is yes. Maybe you want to sort this array of books, right? So do you think arrays.sort will work? Want to sort this array of books? Will it work? I might get an error. Okay, I'm really getting an error here. Why? Because the sort function does not know how do I compare two book objects. Okay, so how do I do it? There are three ways that I have discussed in my previous video, in which I have discussed Java collections. One is using compare to method, one is using comparator, and one is using lambda function. I'll give you a quick uh, way to do it, which is using the lambda function in this video. What I need to do, I need to define one line function in which I will say, okay, how do I compare two book objects? The two inputs, let's say book B1 and B2. So they can be any two books. The sorting algorithm is going to pass book objects to this function, followed by an arrow, followed by I should return a number which is negative, 0 or positive. Right? So if I return a number that is negative, it simply means that my first book is smaller, right? Okay, and if I return a number that is positive, that means my first book is bigger, right? I need some way to convert these two books into the numeric values. For example, I want to sort these books according to their price. Let's say I'm comparing C++ and Java. If I return 100 minus 150, what does it return? It returns a negative number. That means the C++ book is smaller than the Python book, something like that. Let me show you. If I say I want to compare two book objects B1 and B2, and in return I will say that compare on the basis of their price. So I will return a number B1 dot price minus B2 dot price. This is a shortcut way of writing a comparator, right? Using a lambda function. So I'm comparing two books. If the first book price is, let's say, 50 and second book price is 100, this expression will return a negative number. That means the first book is smaller and hence it will be placed first in the list, right? Let me go and run this and we will see what happens. So I'm getting now the C++ book followed by, okay, I forgot to print this after sorting, right? Before sorting it is C++, Java and Python. Let us see what happens after doing the sorting, right? I'm getting C++, the least price, then I'm getting the Python book, which is 150 price, and then I'm getting the Java book, which is having a price of 200. Okay, so I hope you are really understanding how we are doing the comparison, and we can uh, tell the sort function, this is the parameter on which I want to do the sorting, right? If you want to write more complex comparisons like multiple if else conditions, then you have to go with the comparator way of uh, comparing the two books. Okay, So that is how you work with array of objects, and I hope these concepts are clear. Let us move on to the next concept, that is how do we pass arrays to functions and what happens internally in the memory. So let us discuss these concepts. For example, let's say I have a variable called as money, which is, let's say I have 100 rupees, and let's say I have a function called as double money, right? So I say, okay, I will get some money and I want to double it. So I can say, okay, money equals to twice of money, and that's it. Now I call this method, I call the method called as double money, and I give it money, right? And now I can say, okay, let me, so let me call it as public void. I'm not going to return anything. Public static void double money. I've just I have a single variable, right? So basically what I'm trying to tell you is I have this money variable. I pass it to a method called as double money, which people might think that it's going to double it. But let's see what do we really get. If I print money here, what do you think? What output you can expect here? Let me go and run this code. The output will be still 100. The money is not going to change. I'm still getting 100. So let us understand what is happening behind the scenes. So this main function created in your stack memory. This is your stack memory. And there is a variable called as money. And when you make a function call, another function is called, that is your double money. And in this function, you have another variable called as money. It exists in a different scope, in a different part of the memory. This money was 100. So when you call this function, this money is getting copied here, right? Copy, right? Passed by value. The value that is here, it is getting passed here. We are passing this value 100, and here you say money equal to twice of money. You say, okay, I'll make it double. I will make it 200. Now this function call is over. It does not return anything. This stack frame is destroyed, and you are back here. Now when you print this money, what you are going to get? You are going to get just 100. Now let us repeat this experiment in a case. Instead of having one variable, let's have a array object. So I say, okay, I have uh, multiple friends and they have some money, right? So I say friends money. It's a integer array, and let's say a friend has 100, 200, and 300, and I create one more function called double money, which is going to accept a money array or friends money, right? Whatever you want to call it as. In this case, I iterate over this array for int I equal to 0, I less than money dot length I plus plus, and I say money of I should be twice of uh, money of, and again I do not do anything, right? I do not return anything. Now I again call this function, I call double money, and I give friends money, which is an array, right? Now what do you think? Will my array get doubled? Will my money in this array, will it get doubled? The answer is yes, it will. So let us see how and why it's going to happen. So if I print friends money, and if I show you the output now, okay, I have to use the method arrays dot toString so that I can actually print the contents of the array. So code java.util. Now this money is actually getting 200, 400. You might think it is not doubling for the primitive data type, but it is doubling for the array. Primitive behind the scenes, what is happening, we have already seen. Now let us see what is happening when you are passing an array. So you have your stack memory. Okay, I told you the array is created in the heap memory. Your 100, 200, and 300, they are created here, right? And they have some address. Let's say the address is uh, 556. This is the location at which the array is created. When you called your main function, it got created in the stack. Your variable friends money, it is also created here. What is this variable holding? It is holding the address of the array. So it is holding 556. Now, when you call this function double money, you're passing the variable, the object reference friends money to it. Okay. So we are calling this function double money. and it has a variable called as money, in which what is the value that is getting copied. It is not the array that is getting copied, it is the value inside this function variable friends money, it is getting copied, right? So in Java everything is passed by value. Okay, but in case of array, what is the value that is getting passed? It is not the array object, it is the address that is getting passed. You have 556 getting copied here, right? When you say, okay, money I equal to twice of money. So this money is also referring to the same array. When you access the ith location using this address, you eventually end up here. You say, okay, money of I should be twice of money. You make it double, make it 400, you make it 600. Now this function is over. This is this call is gone. This link is also gone. And when you come back again here and you try to access the friends money array, the actual array has been changed, right? Okay, so although it appears like pass by reference, but the concept is still called as pass by value in Java. Okay, but for the objects that are stored in the heap, okay, so objects in the heap, when you pass them to a function, their address is being passed. Okay, that is something that you should know. And now I hope you're able to understand what happens when you pass an array to a function. You change the array, the actual array will get changed. Okay, if you want to create a copy of the array, you have to use some methods like clone or what, right? So that is how arrays are passed to a function. Now let us move on to two-dimensional arrays. Okay, so many real-life problems, for example, games and puzzles like tic-tac-toe, they might require you to store data in the form of a 2D matrix. Now, if you want to store data in the form of a 2D matrix, you need a two-dimensional array, right? You can also have a three-dimensional, four-dimensional, n-dimensional array, right? So how do we create such an array? I'll show you few ways to create these kind of arrays. So first, I need to define the data type, and in this case it's a 2D array, so I will have to use these square brackets two times. I'll tell you the reason why, and then one way is I can directly give the data, right? Now if you look at this array, it has 3 rows and 4 columns, so it is like 1 2 3 and 400. This is like one object. Then I have 4 5 6 and 100. This is like another object. And then I have 7 8 9 and 100. 7 8 9 and 100. This is like another object. Now, how they are stored internally in the memory, let us discuss. For Java, a 2D array is nothing but it's a 1D array in which each each row or uh, each row is like one object, right? So can I say it's a 1D array of objects where each object itself is a one dimension. So in the memory, there is no 2D array created. Internally, it's going to use a 1D array where I can say the zeroth row, this element is my array of 0. Array of 0 itself is an array. Right? That is what I'm trying to tell here. Array of 0 is of the type int square brackets. That means array of 0 represents 1D array. Array of 0 is going to hold the address of another 1D array. Let's say this address is something, that address will be present here. If I say array of 1, that is also going to hold the address of another array, and array of 2, it's also going to hold the address of another. This is array of 1, and this is exactly how it is stored, right? And where is your ARR? ARR is here. This variable, it is in the stack memory, and these arrays, these 4 arrays, they are in the. Okay, so this, I'm saying this is an object. A 2D array is nothing but it's a 1D array of objects, 1D array of objects where each object is also an array. This treat it like this way, right? So treat it like this is one book, this is another book, this is another book, right? Each row is one object. Now you might say, okay, prove me this is how it is stored. So let us go and do a s out. Let me show you. I can say arrays dot toString. I want to print this array. I give ARR, right? And again I will import java dot util dot. If I make this import and I call this method arrays dot toString, now what I'm hoping to get, will I get the contents of the array or will I get these addresses? Let us see what do we really get. I need to run this. look at this. I'm getting three addresses. What are these three addresses? These are the three addresses of these three row objects that we have created. This is 264. This is stored here. This is 30C. So this is the address 30C, and this is 1970. 11970. This is the address of another. Then you might ask, okay, if I want to print a 2D array using a two string method, can I do that? Or should I iterate over this array? I will tell you, you can do both. Okay, so you can use an inbuilt method to print this entire array. You can also iterate over this array. Let us first look at an inbuilt method. If you have a structure like this, right, so you just don't need to iterate over these values, but instead you need to say, okay, I also need to iterate the objects they are referring to, right? So basically, it's kind of a recursive structure, right? So this is referring to some object. This might also be referring to some other object, right? So I want to go deep inside this structure and iterate over all the values, right? In order to do an iteration like this, what I have to do, I have to use a method called as arrays dot deep to string. I iterate deeply inside these structures and then print this array. If I call this method, right, arrays dot deep to string, what will happen? It will go inside those arrays, those rows as well, and it will print them, right? If I go and run this code, you can see this is the output that I'm getting, right? I hope you're able to understand the difference. Okay, now how this 2D array is stored, just a quick recap. This array, this ARR is a 1D array which is holding three rows in it. So three rows, each row is a 1D array object containing four numbers. So now let us do one more thing. Let us write a method called as print that is going to iterate on this 2D array, right? So sometimes we have to manually use a for loop to iterate over a 2D array. Let's see how we can do it. So public void, public static void, let's say traverse. Input is a 2D array, so I'll create a reference variable ARR. How do I iterate? If I simply say s out ARR dot length, can you guess what is this length going to be? What is the length of this array? This array is holding three items. This length is giving me the number of rows I have. If you want to figure out how many rows I have in this array, these are the number of rows. How many columns I have in this? That is nothing but the number of elements in each array is the number of columns. So I can say if it is a fixed size array, rows cross columns, rows will be nothing but the number of rows will be nothing but array dot length. How many columns I will have? That is nothing but array of 0 dot length. The number of elements in the first array. If this is same across like all the arrays, the number of columns I know, right? So how do I iterate? Iteration is pretty easy. I can say I equal to 0, I less than the number of rows, I plus plus, and then I can say okay, for j equal to 0, j less than the number of columns, j plus plus, s out array of ij. So let's see what does it really mean. So if I have an array like this, let's say 1 2 3 4 5 6 7 8 9. This is one object, another object, this is another object. Array of 0, right? I iterate over rows. I is 0, so array of 0 is fixed. If I go over 0 1 2, these are the row numbers. For each row number I say okay, iterate over the columns. Array of I gives me this, then using this j gives me the column. So array of 0 0 gives me 1, array of 0 1 gives me 2, array of 0 2 gives me this number. So j is going along this direction, I is changing across rows, right? So what I'm going over each ith object, and then I'm using a j to traverse the elements of that particular row. This is how we generally do the traversal, right? You can also do it other way around. So I'm iterating across the rows. You can also iterate across the columns by changing the order of these. Okay. If I show you the output, I'll say okay, I'm going to print them in the same line. And after my row is finished, I'm going to give a new line. So I can say s out print ln. So now if I call this method that is going to be traverse, and I give this array, I will see an output which looks like a 2D array. Right? Let us go and run this code, and you can see it. So I'm able to iterate over all the rows, and for each row, I'm able to iterate over all the columns of that particular row or all the numbers in that particular. So I hope traversal is clear to you. Now, some of you might ask that, okay, can we do some kind of sorting on this 2D array? Maybe I want to compare each row with some other row. Okay, so I want to do sorting across the rows. I want to sort rows. And you might have a different criteria. You might say, okay, I want to sort on the basis of first element, or I might want to consider the sum of all elements, right? So how do I do that? So it's very easy. So consider each row as one object, and I want to compare this with other objects, right? What I can do, I can use arrays.sort method. It will assume that I'm going to give you a 1D array. That's okay. So it's going to, and this is actually a 1D array. Okay. So although the syntax is 2D array, but Java considers this as one element of the array. This has another element of the array, and this has another element of. Suppose if I want to sort according to their sum, right? What I have to do? I'll say, okay, fine. I will give you two objects. What are the data types of these two objects? These two objects are arrays. I have int square brackets object 1, int square brackets object 2, and in return I want to get their sum. So I can say, okay, I can create some method called as get sum, int public static int get sum. Given a 1D array, I want to find the sum of that array. I give some array, I want to find the sum of that. I want to sort these rows according to their sum. So basically, the row which has a higher sum should come at the end of this array. How do I do it? First, let's write a helper function to get the sum. So for now, I can say int sum equals to 0 for int value inside this array. I can say sum equal to sum plus val, and I can return this. Finding the sum is pretty easy. Now, here in my lambda expression, I can say, okay, I'm going to compare on the basis of sum of these arrays. So array 1, which is my object 1, minus get sum of array 2, which is my object 2. That's it. And if I do this, and now I want to show you the output, I can again print this array after doing the sorting, and let us see what do we really get. Now, if you look carefully, I'm getting this array first, which has the least sum. This array has a higher sum, and this array has even the highest sum. Why? Because I have a very big element 400. You can verify. So what I have done, I have written a lambda function that is comparing two rows. Any like internally, it will call some logic to compare two rows. Okay, so it is comparing two rows according to their sum. If you want to compare on the basis of first element or the last element, that can also be done. So if I do this once again here, I can say, okay, uh, o1 dot get last element. How do I get it? I can say, okay, o1 dot length minus 1, that is giving me the last element, and o2 of o2 dot length. I'm saying, okay, let us compare on the basis of last element. In that case, this array will come first, then this array will come, and then this array will come. If I go and run the code once again, let's see what do we really get. Okay, so I'm getting 10, 100, and 400. That is how powerful these lambda functions are. They can also work with 2D arrays, but now you're not going to compare. You're going to treat each row as one object. Okay, that is something that you must learn. So we have seen how do we work with a 2D array, but we have not seen how do we take input a 2D array of size n cross m and read it from the user. Okay, let us do that as well. First of all, I'll create a scanner so that we can read numbers from the user. So scanner sc, this is equal to new scanner, and let's read how many rows we want to create. Number of rows is scanner dot next int, and number of columns is also going to be scanner dot. So I'm going to create a 2D array of size n cross m. So how do I do it? Pretty simple. So I define variable arr is of the type int square bracket. This is equal to new int, and here I define the number of rows, which is n, and the number of columns, which is m. Once I do this, Java will create an array in which I have, let's say, n equal to 3 and m is 4. It's going to link these like that. Internally, this is how they will get created. Now, what I want to do, I want to read numbers and put them here. I want to say, okay, 1, 2, 3 is the first row, 5, 6, 7, 8 is the another row. How do I do it? I have to go to the zeroth index. Then I have to iterate over uh, from j equal to 0 till j equal to 3. 0, 1, 2, 3. Then I have to go to this index, read this array. I have to go to this index, read this array. Let's see how we can do it. I can say for int I equal to 0, I less than n, I plus plus. Then for each row, I need to read the elements j equal to 0, j less than m, j plus plus, and array of I comma j. So in the ith row, the jth cell, I want to read a number. Scanner dot extend. Fine. This is it. It's once this is done, I have read all the elements. Now what I need to do, I need to print. So I can say okay, s out arrays dot uh, deep to string, and I will give it. I need to import java dot util dot. So let us run this code and see are we able to read an array from the user or not. Let's say I want to have 3 rows and 4 columns. I need to give data. Let's say I'll give 12 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so yes, I'm able to create an array with 3 rows and 4 columns, and you can see first row, second row, and the third row. So this is how exactly we did a two-dimensional array, and this is how the memory representation of 2D array looks like. This is my variable arr. Okay, so let's move on to jagged array next. So we have seen how do we work with a 2D array, but we have not seen how do we take input a 2D array of size n cross m and read it from the user. Okay, let us do that as well. First of all, I'll create a scanner so that we can read numbers from the user. So scanner sc, this is equal to new scanner, and let's read how many rows we want to create. Number of rows is scanner dot next int, and number of columns is also going to be scanner dot. So I'm going to create a 2D array of size n cross m. So how do I do it? Pretty simple. So I define variable arr is of the type int square bracket. This is equal to new int, and here I define the number of rows, which is n, and the number of columns, which is m. Once I do this, Java will create an array in which I have, let's say, n equal to 3 and m is 4. It's going to link these like that. Internally, this is how they will get created. Now, what I want to do, I want to read numbers and put them here. I want to say, okay, 1, 2, 3 is the first row, 5, 6, 7, 8 is the another row. How do I do it? I have to go to the zeroth index. Then I have to iterate over uh, from j equal to 0 till j equal to 3. 0, 1, 2, 3. Then I have to go to this index, read this array. I have to go to this index, read this array. Let's see how we can do it. I can say for int I equal to 0, I less than n, I plus plus. Then for each row, I need to read the elements j equal to 0, j less than m, j plus plus, and array of I comma j. So in the ith row, the jth cell, I want to read a number. Scanner dot extend. Fine. This is it. It's once this is done, I have read all the elements. Now what I need to do, I need to print. So I can say okay, s out arrays dot uh, deep to string, and I will give it. I need to import java.util. So let us run this code and see are we able to read an array from the user or not. Let's say I want to have 3 rows and 4 columns. I need to give data. Let's say I'll give 12 elements. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so yes, I'm able to create an array with 3 rows and 4 columns, and you can see first row, second row, and the third row. So this is how exactly we read a two-dimensional array, and this is how the memory representation of 2D array looks like. This is my variable ARR. Okay, so let's move on to jagged array next. Let us discuss what is a jagged array, right? A jagged array is an array with variable number of columns. Variable number of columns in. Now, how this is possible? Let's see. Let's see an example. Let's say I have 3 columns in one row. In another row, I have let's say 4 columns, and in another row, I have just 2 columns. Can we create such an array? The answer is yes. Why? Because when you create a 2D array in Java, each bucket is referring to a array object. Now, each array object is independent of the previous object that we have created. What I'm saying is, we are creating 3 different objects for 3 different rows, and each object can have its different length. For example, this length is 2, this length is 4, and this length is 3. Right? Let's see how we can create an array like this. Java. It's again a 2D array which looks like this: 1, 2, 3, 4, 5, 6, 7, 8, and 9. In this case, we don't have fixed number of columns in each row. Number of columns are variable in each row. How do I do it? So let's see. I'll start by creating a scanner equal to new scanners dot in. Now I'm just going to read the number of rows from the user. I say scanner dot next. Once I know the number of rows, I can initialize my array. I can say int square bracket arr. This is equal to new int, and here I just define the number of rows. It's okay. I need r number of rows. How many columns are there? I will tell you later. What does this code do? It creates an arr that points to an array that will hold these array objects, but they will be created later. It's only going to create an array with r number of buckets inside. Okay, these will be created later. This part we will do next, right? Now what I need to do, I need to iterate over each bucket. I equal to 0, I less than r, I plus plus. Now I'm going to ask, okay, tell me how many columns you are going to have in this row, right? So I will ask the user. I can accept columns in current row. How many columns? I'll ask the user to tell me number of columns in the current row. You can also output here s out columns in current row. You tell me how many columns will have in the current row, and then you can say s out data in the current row. Maybe if I say I have 3 columns, then I will run a loop 3 times to read those numbers. So I'll say okay, for int I equal or int j equal to 0, j less than um, columns in the current row j plus plus. Now the thing is, where should I store this data? This array object is not yet created. First, I have to create an array object here in which I should be able to store data. How do I do it? I said fine, this array of I. Array of I is this bucket. It should point to a new 1D array in which I can hold these many numbers that is equal to columns in the current. This line of code will actually create this array, and suppose this address is now 702, so this is stored here 7, and this link is established. Now I can read data and I can store it, and this thing we will repeat for every row. I'm iterating over these buckets now, and I'm going to say okay, read the next number and store it here. So I can say array of I comma j, this is equal to scanner dot. That's it. And in the next iteration, we move on to the next row and we do the same work in. We ask how many columns you have in the next row. It says, okay, I have 4 columns. So I create an array of size 4 and I link it here using this line. And then I again read it. Okay, I read these. Let me show you by running this code that we can actually create a jagged array. Sout arrays dot uh, deep to string, and I can give array here. And again, I have to import java.util. So let's go and run this. Okay, I want to create an array with 3 rows. Now I have to tell me how many columns in the current row. I say okay, 4 columns, and then I have to tell me what are the 4 numbers in that. So let's say 1, 2, 3, 4. Then in the next row, how many columns? Maybe just 3 columns, and the numbers are 7, 8, 9. Then in the next row, let's say 2 columns. The numbers are, let's say, 10 and 20. What do I see? I see a jagged array. 4 columns, 3 columns, and 2 columns. This is how we can create a array in which every row has variable number of elements, and this is called as a jagged array. Now we are going to look at dynamic arrays. So far the arrays we have created, they had a fixed size. Once you create an array of size n, you cannot add more than n elements into it. That is where dynamic arrays come into picture. For example, you are building a to-do list where you can keep on adding tasks every day, and you might be removing some old tasks as well. So you do not know how many elements you would be storing in your list. So you need something like a dynamic array in that case. Right? So in Java, dynamic array is provided by the library as a part of Java collections framework. The class is called as ArrayList. We will also see how this class internally works. But before that, we will look at a demo of using ArrayList. Okay, an ArrayList is a dynamic array for storing elements. It's like an array but with no size limit. It also maintains the insertion order. That means keep on adding elements and they will get added at the end of this array. Right. So if I say okay, I want to add 6, I want to add 7, I want to add 12, they will keep on adding in this at the end of the array. We can add elements, we can also remove elements, and it implements the list interface in Java. So we can use all the methods of the list interface here. So list interface is part of collections framework, and I've done a detailed video on collections framework. Link you can find in the description also. You can watch that video if you want to learn about more about the collections framework and various data structures present inside the Java collections framework. Now, how this array list is implemented. Let us talk about how this array is actually dynamic. How does it grow and shrink? One way of implementing the array list is start with some fixed size array. So I guess in Java, this fixed size array is having a default size of 10. So whenever you say, okay, I want to create an array list, it will give you space for 10 elements. But as soon as this gets full, right, you say, okay, I have used all the elements, right? What it will do? It will double itself. Now you cannot double in the same memory because this memory might be occupied by some other data structure or some other part of the program. What it does, it looks for new memory in the heap where it creates an array of the double size, and it's going to copy the old data into the new array. Let's say this data was 1, 2, 3, 4 up to 10. So it's going to copy all this data in the new array, and then the remaining elements, the remaining 10 boxes are available for putting some new data, right? Once this gets full, again you have to do the same thing again. Double the old array by creating a new array, copy the data from the old array, and you have to delete the old array. So in Java, the deletion is done by the garbage collector. For example, if this is my old array and I say old ARR equal to null, what does it mean? No one is referring to this array. This object becomes eligible for garbage collection, right? Okay, so in other languages like C++, you have to use the delete keyword, but in Java, the garbage collector takes care of objects that no one is referring to. So first, let us first look at the demo, right? So to be precise, in Java, so Java maintains something called as a load factor. Right? Load factor is what percentage of your array is currently filled, right? So if I say, okay, if my load factor goes more than 0.7, that means if I have space for 10 elements and I put 8 elements in this array, right? That means it is the time to double the array, right? So right now I was doing it full capacity, but you can also do it early. If your 70% of the array is full, right? So that is your current size upon your capacity. If this percentage exceeds zero point 0.7, so Java triggers this function that doubles this array. So it creates a new array, copies the data here, and you have more space available for storing um, new elements. Okay. So ideally, if you know that, okay, I'm building a application in which I will require space for around 1,000 elements. So it is better to initialize your array list with the initial capacity of 1,000 so that your doubling does not happen again and again. And if you, okay, I need maybe 1100 elements, so take a safer limit, okay? And you took, okay, I created an array with 1,000 elements. That is fine. It will double one time. So from 1,000, it will become 2,000, right? In 2,000, you can easily store 1100 elements. Basically, you should have a rough idea of the range, how many elements you would be needed, and accordingly, you can initialize a array list so that your repeated doubling operation can be minimized. And doubling is an expensive operation. Why? Because it copies all your data into the new array, which is going to take linear time, right? That is how the internals of the array list work, right? So let us also talk about features. Array list is a dynamic data structure, and it can grow dynamically. It can also shrink as we remove elements from the list. So again, there is certain criteria. Okay, when 20% of the list is occupied, I might shrink it to the half, something like this. We can have a condition on shrinking as well, just like we have a condition on growing. Second thing is it is ordered. It preserves the order in which the elements were added to the list. It is index based, so thus it's an array internally, right? So it also has indexing. So if you want to get this element, we will say, okay, array dot get 0. It provides us with a get method, and I need to tell, okay, this is the index I need to um, access, right? And okay, and array list can also store uh, it can only store object data types. That means it cannot store primitive data types like int. If you want to create an array list of ints, you will have to use the corresponding wrapper classes. Okay, so you need to have some idea about wrapper classes. I can create an array list of integer, where integer is the wrapper class for int data type, right? It cannot be used for primitive data types. We require a wrapper class in that. And another thing is it is not synchronized. So you need a concurrent data structure. Then there is a something called as vector, which is a synchronized implementation of array list. Okay, so this concept is pretty advanced. If you're working with multiple threads and stuff, then you might be using vector. So let us look at a demo of using array list. Before we jump into the code, let us talk a little bit about the kind of operations we can do on an array list. So one common operation that we do is we want to access any ith element. So it is called as random access. That is done using the get function. So I can get any random element in order of one time, which is pretty obvious because internally it is accessing the array. Okay, then I can add elements. I can add elements at the end of the array list, which will take order of one time. But you can also add elements in the middle of array list, which will require shifting of elements. Okay, inserting elements in the middle, it's going to take order of n time. Similarly, deleting something from the middle is also going to take order of n time because the remaining elements will have to get shifted. Searching in general, it takes order of n time because it's going to use a linear search, right? But if you have a sorted array list, you can use your own binary search method, or you can use collections.binary search method to search in order of log n, in order of log n time if your array list is sorted. Okay, so how do we create an array list? It's a predefined class in Java collections. I can say, okay, array list of a following type, followed by name of the variable, followed by new array list. This will create an array list with the default size. Default size in Java, it is 10, right? For example, an array list of strings can be created like this, and it does not work with primitive data types. Okay, so I told you that you have to use wrapper classes. So you will have to say array list of integer. If you say array list of int, it will not work. So you will have to say array list of integer, right? This is equal to new array list. That is how you will create a array list object in Java. Next thing is you can also give some default size. So basically the array list class has three constructors. In one constructor you don't give anything, so it uses a default size of 10. In another constructor it accepts you give me the default size and I will create an array list of that capacity. So I'm saying 50, that means it is able to hold 50 objects in this array list, and once you reach 50 capacity it will double itself, right? And there is a third constructor as well in which you can initialize an array list from some other list or from some other collection as well, right? That can also be done. For example, in this case, we have a list of strings and we are initializing the array list using this list. That is the third constructor call that is being done, right? So one more point to note about array list is it allows us to store heterogeneous elements as well. For example, I can add an integer into it. I can also add a string object into it, right? We can store objects with various types in an array list instance also. In this case, when you are creating this array list object, you don't need to parameterize the instance. Don't need to define what kind of data it is going to hold. It will hold all types of objects in it, right? So you can put a string, you can put a book, you can put a dog, anything will work in the same array list. So that is about uh, how do we create an array list. Now I will show you a quick demo as well. So I did this demo in Java collections video that I have already done. So I have shown you that you can create an array list. So the first four lines, if I show you, we are creating an array list in which we have not defined the data type. Then we are pushing an integer. Then we are adding a string, and then we are going to print it. Let me just run this code and let me show you the output. I need to run this. Yeah. So if you see here, I'm getting an array list in which one item is an integer object, the other item is a string object. So we can definitely do this. So I'll comment it out. Then I can say, okay, create an array list, because array list implements an interface. So I can say this left hand side data type can be more generic. It can have list as the data type. That is perfectly fine because an array list is an implementation of a list. So I can call the add method to add something at the end. I'm saying add 1, add 2, add 4. Then I can also use this add method by specifying the index. So the add method is overloaded. There are two add methods, one which adds at the end and one which adds at a particular index. I'm saying, okay, at the second index, you should add 15. So it becomes like this 1, 2, 4. Then at the second index, which is 0, 1, 2, I want to add 15 here. It will become 1, 2, 15, and 4. This is the output that we get. Right? Then I've created another list in which I have added 25. And then I'm using a method called as add all. Add all is used if you want to add all items present in one list into another list. Add all will iterate over all items in list 1 and it will add them into list 2. So you will see 25 followed by all items that are present in list 1 are now present in list 2. So just like add, we have a remove method. Remove method is also, there are two remove methods. The one remove method which accepts an integer. So if I show you something like this, list.remove. So you can see one remove method accepts the index and second remove method accepts the object. So if you have to give the object of the type integer, you have to typecast into the integer data type. So I can say, okay, integer dot value of 1. It will mean that I want to remove 1 from this list. But if I simply pass 1, it would mean that I want to remove the element at index 1, right? That is how the remove method works, right? And if you want to search something, then there is a contains method. It will tell you, okay, whether the following integer or following object is present inside this list or not. That is your searching method. Now there is one more method that is called as set. So that means I want to update something. So if I want to say, okay, I want to update the zeroth index, and this is the object that I want to store at the zeroth index. If I do this, you will see at the 0th index, instead of 25, now the new element that I have stored, it's going to be 50. And apart from it, we can iterate over the list. So list dot size gives me how many elements are there, right? Not the capacity, but how many elements are currently present. That will give me, and I can use the get function to get the ith element from this list. That is one way of iterating over an array list. You can also use a for each loop if you want to iterate over the entire list. And third way is you can also create an iterator object, and while iterator dot has next. So has next tells me whether the next element is present in the list or not. While it has elements, keep on iterating and you access the next element using the next method. So that is another way of iterating over the array list. So you can use these methods, and you can work with array list while solving a lot of problems. Okay. So that is about array list. And if needed, you can also refer the Java Oracle docs to go in more details of these methods. Now let us come to the final part of this tutorial. So far you have worked with arrays, you have worked with array list, and now I want to show you if you want to build your own dynamic array class. Okay, just for your better understanding of array list. Suppose you are asked to implement an array list at your own, how you would do it. What we want to do, we want to implement a class called as dynamic array. What thing we learned? First thing is it internally uses an array. That means one data member of this class would be an array. And this array would have some size also. We will say, okay, it has some default capacity, right? This capacity can be provided by the user, or it can have some default value as well. So we will look at that, right? And then if you start putting elements, start adding in elements in this array, you also need to maintain how much array is full. So maybe current size, maybe the current size is 3, right? So 0, 1, 2. If a next element comes, can I insert it at the current size index? Can I insert it at the third index? Yes. I will insert it at the third index. Let's say the element is 4, and I will increment the current size, right? So it is clear that I need one data member that is array, one data member that is current size, one data member that is capacity, and maybe one constant where in which is going to store how much should be my default capacity, right? So that I can call it as default. So by default, the capacity of this array should be. So let us create these data members. I've created an array, right? I've created a capacity. I've created current size, and I've created a default for which the value is 10. Now, user says, okay, I want to create a new dynamic array object. How you're going to initialize these variables, okay? So suppose I do not give you any default capacity. I will need a constructor, right? And in the constructor, what I will do, I will initialize my array equal to the default size, okay, a default of size 10. I will say, okay, the capacity variable is also equal to default, right? Why I need this capacity? Because capacity can keep on changing. If 10 size 10 gets full, I will make it 20. If 20 gets full, I will make it 40. So the capacity will keep on doubling, and current size, that is going to be 0, right? Because I have not added anything. But suppose if the user says, okay, no, I'm going to give you the default size of the array, then how do I do it? In the constructor, I will accept, okay, you tell me the capacity. I will initialize my capacity equal to that capacity, and I will create an array of that capacity, right? And current size is still 0. Okay, so that is how the constructor is getting created. The third constructor, in which I get another list and then I create this array, I'm not creating that. I'm writing a simplified version of an array list, right? Now suppose I want to add something into my array list. So how should I do it? Very simple. I will define a method called as add, and I will I'm just printing the capacity as of now, but I will remove this statement so that we can see while running the code. Right? So I can say array of current size, this is equal to data. Basically in the beginning, my current size, it is 0, and I get some data. Let's say data is 5. So I said fine, array of 0, this should be equal to 5, and I say current size plus plus. So my current size becomes 1. So that means next time I will do an insertion here. Again, I get a data that is 6. What I do, I put it here, and I increment the current size to 2. So the next time my insertion will go here. Now suppose I keep on adding elements, and after some time my current size becomes equal to the capacity. Okay, so my capacity was 10 and my current size is also 10. That means I have already inserted 10 elements. So if something like this happens, that okay, my current size it's going to be equal to the capacity. What should I do? I need to double my array. So how I am doing it? Let us try to understand that. So let's say I have an array of size of capacity 4. Okay, I insert one element, current size becomes 1. Insert one more element, current size becomes 2. I insert one more element, current size becomes 3. I insert one more element, my current size becomes 4. Current size is equal to capacity. If this happens, and this is my ARR, what do? I create a variable called as old array. I say okay, old array pointing to this ARR, the old array. Then I say ARR, which is the data member of the class. It should refer to a new array which has a double capacity. It should have double capacity. So that is what I do here. Then I iterate over the old array. I iterate over these elements. And I say array of I, this is equal to old array of I. So I copy all these elements here. Okay, fine. I do it. What should I do? I say old array, this is equal to null. So I break this connection. That means no one is pointing to this array now. The garbage collector will delete it. Here, the garbage collector will get invoked. And of course, for the new array, we have updated the array property, but we have not updated the capacity property. The capacity was still 4, but now the capacity should be 8. I'm saying capacity equal to twice of capacity. So what do? I first check if my array is full, I double it, and then I can insert data into it. I say array of current size is still 4. So 0, 1, 2, 3, 4. At the fourth index, I can put the new data. Maybe the data is 50. I put it. That is how I implement the doubling operation inside my array. Now, suppose I want to remove something. So removing is easy, right? I'm not removing from an empty array. So that check you have to uh, either you do not either you put some conditions here or you throw an exception, right? I'm simply saying okay, I want to remove an element. I'm simply removing the last element. So this is my current size. I said okay, I'll reduce the current size, and it means okay, I am going one step back. Current size minus minus. So I'm removing one element from the array, right? So the element will stay here, but next time you add something, it will get overwritten. Okay, and if you have to iterate, you will only iterate on this range. Doing current size minus minus will remove the last element as well. Now there are some more methods we can implement. For example, if I want to um, get the ith element, that is pretty easy. You simply return array of I. If I want to get the capacity, how many elements my array list can hold, I can say return the current capacity. I cannot use access this directly because it is a private variable. So I have created a getter to return it. Then if I want to get how many elements I currently have, I say okay, there is a function called size that I've implemented. It is going to return the current size. Now you can create more methods. You can create a method called contains, in which you will implement linear search and you will tell whether that element is present or not. Okay, you can implement a method called as index of, in which you will return the index of the element where it is present. So instead of returning a boolean, you can return an integer index as well, right? You can also overload the remove method, where you will get a integer value. So either you remove the element at that index or you remove that value, right? So you can do something like that as well, right? So the internal implementation is bit more I would say it's more robust, it is more powerful. But this implementation we did so that you get an idea how the doubling operation in an array list is actually working. Okay, how things are happening behind the scenes. Now let us test our class by creating a dynamic array object. Okay, my class that I have defined, it is called as dynamic array. I can say dynamic array da, this is equal to dynamic array, and I want to use some methods inside it. Now let me say default size is 5 instead of 10. So default capacity is 5. Da dot add 1. Let me just add 5 elements. Let me say 1, 2, 3, 4, 5. Now at this point, I want to see what is the size of the array and what is the capacity of the array. Let us see. S out da dot size and S out da dot capacity. Both should be 5 at this moment, but as soon as I insert the sixth element, the size should be 6 and the capacity should be okay, so both are 5 at this moment. Let me insert one more element. Let me say da dot add 6. And now if I add this element, you will see the doubling operation will get triggered, right? That means the capacity should be now 10, the size should be 6. Yes, that is happening, right? So your array of size 5, it got full, and as soon you add sixth element, it doubled itself. That doubling thing is happening, right? You can see here. Now I can also say, okay, I want to add 7. I want to remove the last element, and then I want to add 8. That means I added 7, I removed one element, I added 8. So 7 will get overwritten by 8. And if I want to iterate on this array and see, right, what all elements are there. So I can say for int I equal to 0, I less than n. What is n? The number of basically da dot size, the number of elements present, I plus plus, and I can say s out. I want to get the ith element. So I can say da dot get ith element. I want to show them in a straight line. I'll do s out here and like this. So you can see like 1, 2, 3, 4, 5, 6, 7, 8. Now you can also implement a method called as toString, which will simply iterate over the array and join all these numbers inside a string. So you can use the toString method also to print your dynamic array, right? So instead of traversing, you can give this as a method inside the dynamic array class as well. So let us begin with linked list. So what is a linked list? A linked list is a linear data structure in which the elements are represented as objects and they are stored in non-continuous memory locations. Okay, so one thing that you need to note about linked list is it's a dynamic data structure, right? So unlike an array where you need to tell, okay, I want an array of size n, you don't need to specify the size of the linked list. Every time you get a data, you create an object, you put the data inside it, and you put it in the form of a chain or in the form of a linked list, right? So why the name linked list? Because we have a lot of nodes. Okay, each node is an object in a heap, and these nodes are connected with each other, right? How they are connected? So each node is created at some memory. Let's say this address is 205. So the previous node knows that the next node is present at this address, right? So 2 will know the next node is present at some address. So that is also going to store there, right? So each node is going to store two things. One is your data and one is the address of next node, right? So if you know the address of next node, you can easily traverse the data structure, and you can also put things in an ordered way, right? So every time you get a new data, we can insert at the beginning, we can insert at the end, we can also insert in the middle, right? So it's up to you how you want to maintain the ordering inside the linked list, right? One thing to note is it's a dynamic data structure, and the nodes in which the data is getting stored, they are stored in non-contiguous memory locations, unlike an array, right? So that is what linked list looks like, right? Now in linked list, we do not specify the size, as I have already discussed with you, and it is a dynamic data structure. It automatically changes size when an element is added or removed. So we'll go into the internals of how addition and deletions are performed on a linked list in this tutorial. So while doing the implementation, I will show you that, okay, if there is a node, how do I connect the next node? How do I add something in the beginning? How do I add something in the middle? How do I delete something, right? So the fundamental operations that we will be learning would be addition, okay, removal, right, and getting a node, right? So I want to get a particular node. How do I get that node, right? So given an index, I can iterate to that index, right? One thing that is bad about linked list is if you suppose want to get the middle node, right? In array, you can say, okay, give me the ith element. So this property is called as random access. So linked list is a bad data structure if you need to access ith element. Why? Because you cannot directly get this element. You have to traverse till I positions to get this element, right? So it's bad at getting nodes. It's bad at random access, but it is good at certain things that we will see. All right. So that being said, let us jump into the implementation of linked list. So now let us dive into the implementation of linked list. So far what we have learned is that linked list is a chain of nodes in which every node is connected to the next node. Okay. So if there is a node 1, it must be connected to the second node, let's say node 2, right? So the way to do it is that in every node, we also store the reference of the next node. Okay. So for example, if this node is created at some memory location, let's say 206, then this node must store what is the reference of this node, where it is created, right? And for the first node, what we need to do, for example, if this node is created at some location 115, then we need to store this location 115 in a special variable. Okay, we generally call this special variable as head, right? Okay, and second node will store the reference to the third node and so on, right? So third node, maybe it might be at 480, so I might be storing 480 here, right? Now the first step in the implementation is that how do we implement this structure? Okay, this object that we see here. So we are calling this object as a node object, right? So what I will do, I will say, okay, I will define a node class, and this is capable of holding two things. One is my data and one is my reference, right? So each of these boxes is a node, right? So each node is going to hold a data. Now a data can be of a different type as well. So just for the sake of simplicity, I'm treating it to be a integer, but it can be an image, it could be a book, it could be any object, right? And second thing I have is a reference to the next node, right? So how do we store a reference to the next node, right? So I say, okay, this will be of the type node, and let's call this variable as next, right? We have data and we have next. So if you're confused, I will explain you what is this concept. So let us first start with the code. Let us create this structure and let us try to understand that, okay, inside the node class, you can have an object reference which is holding the address of the next node, right? So let us go into IntelliJ, and I have created a package called linked list data structure, and here I'm going to create a Java class called as let's say node.java, right? Now it automatically creates a class for me, but it does not have data members. So how do I add data members? I can say, okay, I want data, and I also want something called as next. So that will be of the type node, right? Now this does not mean that there will be an object inside an object. No, this is only a way, this node, right? It's only a way to hold the address of the next node, right? So this is of the type object reference. I will tell you, right? And let me do one more thing. Let me add a constructor here as well. So you will see why we need a constructor. Let's do one thing. Let's create main, right? Let's create linked list demo, another class in which I'm going to test my functionality. In this class, I will create my main method where I'm going to test my functionality, right? So let us create a node object. Guys, okay, node A, this is equal to new node. Right now, this does not hold any data, right? So A is not going to contain any data. By default, the value of integer is 0, right? And next would be null, right? So what I can do, I can say, okay, A dot data equals to 5, A dot next equals to null. And if I say, okay, S out A dot data, what I'm going to get, let us see, right? So I'm getting this value as 5, which is absolutely correct, right? Now why this is happening, let's see, right? So what it did, writing this code, it created a node, right? And what is A is referring to this node. So A is a address, right? A is a object reference. So A is another bucket which is holding the address of this node. So this node has two things. One is my data and one is my null. So this is your data and this is your next. And this node has been created at some memory location in the heap, right? This is my heap memory, right? So this address might be, let's say, 508, right? What is A holding? A is holding 508. This is what is exactly happening behind the scenes. So in this case, This A is also an object reference, right? And it is referring to an object. Inside that object, I have one more reference. Okay, how do I access this value? I access this value by a dot next. So this is what is happening when you are creating this node, right? So it is giving you, it's wrapping up two data members inside one bucket. Inside node, you have an integer value and a reference to the next node, right? If I say, okay, there is one more node, right? Let's say node b equals to new node, right? And I say, okay, a dot next should refer to b. So if I print out what is a dot next, so a dot next is nothing but it is the address of the b node that we have created, or the value that is getting stored inside b, right? Now if you see, this is the reference of the next node, right? So let me show you through a memory diagram. So a is referring to a node, okay? So a is 5, b is some other node. So let me do it like this. So a is a variable that is holding this address, let's say 108, this value is 5, and b is 30c, right? So b is some other node, b is another variable that is holding this value 30c, right? And this is the address of next node. I don't have any data and null value here, so it will be the default value of integer and next, right? So that will be 0 and null, right? So I have 0 and I have null, right? Now b is referring to this. So when I say a dot next equal to b, so inside a dot next, which is this field, I'm copying whatever is present in b. So I'm copying 30c. So it means in a way this b got connected with a, right? Now even if I lose this variable b, this chain is still connected, right? So this is how we are going to work with nodes, and we will write one more class that does all this manipulation of nodes, okay? So we'll call that as a linked list class, right? So I hope this node concept is clear. What is a, what is new node? The new node is getting created in heap. In this case, this is a reference variable here, and this variable is created inside stack at this point, right? So what I will do, I'll remove all this code and I will do one more thing. So instead of like every time doing a dot data equal to something, a dot next equal to something, I will define a constructor inside this class. So I call it as node. It will accept some integer, let's say data. It will accept some value of next, but in general we will not know that value of next, okay? So whenever you're creating a new node, you know the data. You say, okay, I want to create a new node with data 7. Now what will be connected in the next node, we do not know at the moment, right? So what we can do, we can leave this variable initialized with the default value, right? So I can say this dot data equals to data. So I'm initializing this variable with the data that I'm getting, right? So since the two variable names are same, writing this here is important so that compiler knows that we are talking about this data member as an attribute, right? And next, what about next? So you can say next is null, or you can say this dot next is null. Both are fine, both will work, right? So this is the constructor for the node class, right? Now if you want to create a node a, now you will say, okay, node a equals to new node. You just give the data as 5 and you say node b equal to new node, you say data is 6 and a dot next equal to b. So this creates a very simple linked list in which we have two nodes, okay? So if I say s out a dot data and show me what is the data in the next of a. So how do I do it? A dot next gives me the address of b dot data. So I'll say 5 followed by 6, right? So I will see this. So I see 5 followed by 6. So what we did, we simply created a linked list in which we have just two nodes. This is a, this is b, right? Okay, and a dot next is storing b. So a dot next is storing, right? Now you might say, okay, this looks very easy, but if I have to add 10 nodes, 20 nodes, 100 nodes, 1000 nodes, will we create so many variables and attach them manually? The answer is of course no. We will write an algorithm that does insertion in the linked list, deletion in the linked list, and it helps me to get the nodes in the middle of the linked list, or at the end of the linked list, or at the beginning of the linked list, right? So to do all these operations, what we will be doing, we will be writing our own linked list class. So what I will do, I'll create a new Java class and I will call it as linked list.java, in which all these operations involving these nodes will be done, right? So let's see the implementation of linked list. So let us see the implementation of linked list. Now suppose you want a data structure that is like in the form of a chain, right? And you want to build certain methods. You want to say, okay, I want to do addition in this linked list. That means I should be able to add more nodes inside it. I should be able to remove nodes from this linked list, and I should be able to get the nodes from this linked list. That means I want to read nodes from the linked list, right? Now the add operation, it can happen at 3 places, right? So maybe if there is a linked list like this, you can say, okay, I want to add something in the beginning of the linked list. So I can say, okay, add at the first position. Or you might say, okay, I want to add something after the last node, right? So you might say, okay, I want to add at the last node. Or I might want to say that I want to insert something in the middle. So I might be doing something in the middle or at a given location, okay, at a given position inside this linked list, right? Similarly, remove can happen at the beginning. So I will say remove first would be an operation, remove last would be an operation, and remove at a particular position can be an operation. Similarly, get means, okay, I want to read something, I want to get the first element, I want to get the last element, or I want to get the middle element, right? So I will say I want to get first element, last element, and element at a given position, right? So what we will be doing, we will be implementing these operations, right? Now in order to implement these operations, right, what is important? Let us start by understanding how my add operation will work, right? So whenever you want to add something, so one thing you need to know is what is the starting point of the linked list, right? So suppose you want to add something in the beginning, you must know the starting point, or you want to add something at the end, right? Now one way is if you're adding something at the end, right? That means if you're creating a node here, you must access this node and update the next variable of this node, right? You would say, okay, in the ending of this node, I will attach this node. So one way is you always iterate till this point, starting from the head. And this will actually take order of n time. If you iterate from here to here, it will take order of n time. So I don't want to do that. So what I will do, I will say, okay, every linked list will at least know what is my head and what is my tail. So I will keep another reference that always point to the last node of the linked list. Whenever you will add a new node at the ending of the linked list, I'll say, okay, I'll modify the tail node, I will attach the node, and I will update my tail variable to go here, right? So let us see how these operations are implemented. So what I'm trying to tell you is that if you're implementing a class called linked list, this linked list will have data members, okay, something that the linked list should know, okay, and some operations that the linked list will does, right? So here are the operations, they will be part of the methods, right? And we will have some data members or attributes. So what are the data members? What are the things that the linked list must know? One is head, what is my starting address, one is the tail, what is my ending address. So again, keeping this is optional, but I want to optimize certain operations. For example, add at last should not be an order n operation, it should be an order 1 operation. So I need to keep the tail variable as well, right? And maybe some optional information like size, how many nodes I have in the linked list. Okay, so maybe I want to implement a method like get size, how many items are already inserted in this linked list. So this is a useful operation. We want to check, okay, if the size is 0, that means linked list is empty, right? Otherwise you can check if the head is null, that also means linked list is empty, right? So we will also implement this operation like get size, and maybe we'll implement an operation like display. I want to show the entire linked list, okay? Or you can implement a method like toString, iterate on this linked list and convert it into a string. So that is just like a display method. I want to show the entire linked list to the user, right? So let us start by implementing these operations one by one. So this is my linked list class. So first of all, what I will do, I will add some data members and I will add a constructor to it. Else, okay, I want to create a head. So node head, right? Again, head is a object reference, hence it has the data type called as node, right? Then I will have node tail And one thing I can do is I can make them private. So private node head and private node tail. I don't want people outside the linked list class to know where is the head node, where is the tail node. So I will not expose this data outside the linked list class, right? And I can also say private int size. I'm not making it public because I don't want this size to be changed by someone outside. The size should change automatically when something is inserted or something is removed from the linked list. So it should be a private variable only changed by the linked list class, right? Next thing I want to do is I need to initialize a constructor. Okay, whenever user says, okay, give me a new linked list, what should I do? So that linked list will have 0 nodes inside it. So I need to initialize these 3 data members as well. Else, okay, linked list, there is a constructor here. And what I want to do, I want to say head and tail, they will be null and the size would be 0. Okay, so this is my constructor. Now what is the first thing I will do? Else, okay, I want to do an insertion. So I'll write 3 methods. One to add something at the beginning, something at the end, and something at a given position in the linked list. Else, okay, public method, and the method is of the type void add, and let me call it as add first, and public void add last, and public void add at a particular position. So add. So in all the 3 methods, I should know what is the data that I need to add. And in the third method, I should also know at what index I need to add, right? Now take a pause and think how you will implement these methods. Okay, if you're given a linked list and you want to add something at the beginning of the linked list, how you would add in. Okay, so what will be the code behind this method? Take a pause and think about it. Okay, so let us discuss the first method, add first. Now suppose you have a linked list, right? Let's say this is A, this is B, this is C. This is already there and head is referring to this node. I want to say, okay, I want to add another node D, which is at the beginning of the linked list, right? So how I will do it? So first thing is I need to create this node. So how do I create a node object? Very easy. I simply say, let me create a node called as N. This is equal to new node, and the data of this node is same as this data that I've given. So this creates a new node and N is referring to this node, right? N is an object reference, a local reference created inside this function, which is referring to this particular node. What should I do? How do I connect this? So I would say, okay, n.next should refer to the head. So if head is already there, n.next should connect to head. So it makes this connection, right? One thing I need to do is I need to say, okay, this head, it should move here, right? This head should not refer to A, instead this head should refer to now D. So I can say head is equal to N. So this will work really well. And one more thing I will do is size plus plus. Every insertion will increment the size of the linked list, right? So this will work really well if the linked list is already there, right? But suppose you are creating the linked list for the first time and you call the add first method. So head and tail both were null, right? And you said, okay, I want to create a new node. So you created a new node called D, and n.next is equal to head. So head was null, so D's next is also null, which is fine, right? And then you say head is equal to N. This head refers to this node, which is also fine, right? But the thing is, the tail is not getting updated, right? Whenever the first node is inserted, right? Let's say the first node is A, both head and tail should refer to this node, right? So what I can do, I need to add a separate condition that if the size was 0 before adding this node, in that case my tail will also get updated. So tail should also point to head, or tail should also refer to N, right? Now this is a special case when you have 0 nodes. In that case you also need to update the tail, right? So this is my add first method. Now let us test the functionality of add first method. So what I will do, I will go in linked list demo. Else, okay, I want to create a linked list. L, this is equal to new linked list. And now in this, I can say, okay, L dot add first, and I will give some data, let's say 10, and say L dot add first I will add 20, and then L dot add first, I will add 30, right? So I want to see this linked list. So I will call the display method, which I have not implemented. So we will implement the display method as well, right? So let us go back into the linked list class and let us add one more method, public void display, right? So how do I display the linked list? Now it's going to be pretty easy. Suppose the linked list is 30 followed by 20 followed by 10, right? And head is referring to this node. Okay, tail is referring to this node. This is 10, right? So tail is referring to this node. So what I need to do, I need to start iterating from head till the end. So I'll say, okay, I'll take a temp variable, I will print it, and I will take temp here. I'll print it, I will take temp here. I'll print it, I will take temp here, right? So what is happening? So once my temp reaches null, I will stop. What I can do, I can say node temp, this is equal to null. So temp is again a reference, it's not a node, right? So sorry, it's equal to head. It starts from head, and while this temp is not equal to null, what do? I print the node. So I say sout temp dot data and take this temp to the next node. Temp equals to temp dot temp goes to the next node. This while loop will help me to iterate on the entire linked list, right? So temp starts from head, temp is referring to this node, I print out 30, temp equal to temp dot next. So temp dot next means this value. So this value means this node. So temp goes here. Again, temp dot next means this value, which is this node. Temp goes here. Again, this is not null. This node is not null. So I say temp dot next, which is this value, which is null. So temp actually becomes null and my loop stops, right? Now the display method is there and we can run this code. Okay, so I see 30, 20 and 10, which is okay. That means my linked list is getting created. But to show you in a linear fashion, what I can do, I can put an arrow here and I can put a new line here, right? This will make the representation look little better, right? I'm getting 30, 20, 10. Now if you look carefully, I added 10 in the beginning, so 10 got added. That means my head and tail both were here, right? Then I added 20, in which 20 got added here and my head moved here, right? Then 30 got added, a new node was created, it got connected here, and then my head moved here, right? This is how the linked list is going to look like, 30, 20 and 10. So I hope you're able to understand the add first method, right? Now on the similar lines, what we will do, we will implement the method called as add last. Now take a pause and think how you will implement the add last method. All right, let us see, right? Now suppose you already have a linked list A, B, C, right? And I want to add a new node D, which is at the end of the list. So this is my head and this is my tail, right? So how do I add a new node here? So first of all, I need to create this new node. So how do I do it? I can say, okay, fine, node n, this is equal to new node, and I give the data to this node that I'm getting, right? Now how do I connect this tail node with the new node? So that connection is pretty easy. What I need to do, I need to update this value and give it the reference of this node, which is stored in n, right? So I need to say that fine tail dot next, this is equal to the new node that we have created, right? So this makes the connection, and I also need to say, okay, this tail should be here because this node is now the new tail, right? So I can say tail equal to tail dot next, or you can say tail equal to n. Both are fine, right? Now this tail has also moved, and one more thing we will do is we will say size plus plus. Now this will work fine when the linked list is already there, right? But think of a case when your linked list is not created. That means both head and tail, they were null, and you inserted the first node by calling the add last function. You say, okay, I don't have a linked list. That means if the size is 0 and you are adding the first node in the linked list, then how should the update should happen, right? So you still created this new node n, right? With the data d, n is referring to this node. So in this case, both head and tail should get updated. They should point to this node, right? So what I can do, I can say, okay, head and tail, they will refer to n, right? They will also store the address that is stored in n, right? Now you might ask, okay, what happens to this n? So n is a local variable. It will get destroyed after this function call is over. But head and tail, they are the data members of the class. They will exist till you have the linked list object in your memory, right? So they are not going to get destroyed, right? So n is a local variable. It will be over, right? And anything that is allocated using new will not get destroyed. Why? Because if someone is referring to this memory, that memory will not be garbage collected, right? So head and tail, they are referring to this node. N is a local variable. It will get destroyed, right? So this way, add last will work. So now let us test our functionality, right? So I say, okay, L dot add last. Maybe this is 40 this time. And again, I say, okay, L dot add last. This is 50, right? Now, if you look carefully, I'm adding the first node by calling add last function. First 40 was added, add first 10. So 10 was added, then 20 was added, then 30 was added. Now again, I'm calling the add first method on a linked list which is already built. So 50 should get added, right? So if I say L dot display, right, it will give me this linked list. Let us see the output. So we are getting this linked list 30, 20, 10, 40, 50. That means this is working really fine, right? Okay, let us go back here and let us implement one more method. That is, okay, give me the size, right? How many nodes we have. So that's going to be easy. Public int get size, and what we are going to do, we are going to return the size of the linked list, right? Now we are doing it this way because if you make this size public, anyone can change it, right? So I'm only giving the getter to access the size. I'm not giving any method to set the size of the linked list. Okay, so that size should be updated only through the add and the remove methods. So this is also fine. So I can say L dot get size, and I want to display how many nodes I have in this linked list. This is again a order one operation, right? So I can say, okay, there are 5 nodes. Now let us talk a little bit about the complexity. So your constructor is doing order one work. Add first, it is also doing order one work. No loops involved. Here also we are doing order one work. Get size, we are doing order one work. Display, we are iterating over all the n nodes. We are doing order of n work, right? Now the next method is add, right? So take a pause and think how you will implement add method, and if you want to insert something in the middle of a linked list at a particular index. Okay, so let us see it next. So we are discussing how do we implement the add method. Okay, so we are given, okay, this is the data that you need to add, and you have a particular index at which you want to do this insertion, right? Now suppose my data is 4 and my index is 3. That means, okay, 0th index, first index, second index. Here I want to add, like at the 3rd index, the new node should come, right? Or you can say, okay, after 3 nodes, I want to insert the 4th node. So this is my 4th node that I want to insert somewhere here, right? So how I will do it, right? So one way is, okay, I will create a new node, n is referring to this node 4, right? But how do I connect 3 with 4 and 4 with 5, right? So this is going to be easy. How? You can say, okay, let me create this new node n. So node n, this is equal to new node with my data 4, right? Now one way is, okay, I can say I need to reach this node, right? How do I reach this node, right? That means if I start from this node, right, and I want to reach the 3rd node, right? After 3 nodes I have to insert. That means I have to reach the 3rd node. So if I take one jump here, I reach 2. If I take one more jump here, I will reach this node, right? That means in order to reach 3, I need to take 2 jumps, right? Okay, so if my index is some p, right, I need to take p minus 1 jumps, right? For a particular position p, I need to take p minus 1 jumps. This we will do it using a loop, right? Let's say I've reached this node and I'm holding this address in a variable called temp, right? Now how I will do it, right? So I can say, okay, temp's next should point to 4. If I do this, temp dot next should refer to n, what loss I will have? I will lose the address of 5. I don't want to do that, right? How should I do it? I will say that before doing this operation, let me say that 4 should store the address of 5. Can I do that? Of course, yes. So how do I do that? I can say n dot next, that is the next of 4, should refer to 5. So what is the address of 5? It is nothing but it is the next of temp. So it is temp dot next, right? Once it is done, can I update the address, the next of 3? Of course, yes. I can say, okay, 3 is next now should point to 4, and this link will automatically get broken. So I can say 3 is my temp dot next should be equal to n, right? So in just these 3 steps, I will be able to insert a node in the middle, right? Now we might have a special case where we might need to insert a node in the beginning or at the end, or we are getting an index which is out of bounds. So let us see how we will handle those cases. So first of all, I'm going to check if this index is out of bounds, right? So if my index is less than 0 or my index is greater than the size of the linked list, that means I cannot insert this node, right? So in this case, what we can do is either we simply return, right? But that's not a good idea. We should tell the user that you are doing something wrong, right? So one way to do it is we can throw a new exception and we can say, okay, index out of bounds, right? That you're using the incorrect index. And here I have to say, okay, this method throws a exception, right? So I can throw an exception in this case and an error will come in the main when this program is executed, right? And now if my index is 0, that becomes a special case. That means, okay, I'm trying to add something at the beginning. So that I have already handled. We can just call the add first method with data, right? So I can say you call the add first and you give the data. That's it. Else if your index is equal to size, that means if the linked list has 3 nodes and you want to insert something at index 3, that means you're inserting something here, right? Which is again at the ending of the linked list. In that case, you can call the method add last and you can give the data, right? So in the else block, we have to write the exact logic that we are talking about, right? So let's see how we will do it. Suppose your linked list is like this, 1, 2, 3, right? And I have 5, 6, 7, right? So I'm telling you that, okay, after 3 nodes, you have to insert a data that is 4, right? So how do I do it? First, I need to reach the 3rd node, right? So I need to take a temp and reach this node. So temp will start from head. So I can say node temp, this is equal to head. How many jumps I have to take? I have to take index minus 1 jumps. So I can say, okay, for int jump equal to 1, jump less than equal to index, right? Jump plus plus, right? Or if it is sounding confusing to you, you can say less than equal to index minus 1, right? These many jumps, as I told you, we have to take, right? Now in each jump, what we should do, temp will take a step. So temp will go to the next node, temp equal to temp dot next. Now I'm in a good position to do some insertion here, right? What I will do, I'll say, okay, let me create a new node n whose data is 4. So I can say node n, this is equal to new node with the given data, and n dot next should refer to temp dot next, as we have just discussed here as well, right? So 4 should get connected with 5. That is the first step. Then I need to connect 3 with 4, right? So how do I do it? So 3 is my temp dot next should point to 4. So 4 is n. That's it. And size plus plus. Size we will update here. So here we are not doing size plus plus because add first and add last will automatically increment the size, right? That's it. So that is my insertion in the middle. Now let us run this code in main and see if it works really well or not, right? Now I can say, okay, this was my original linked list. L dot add at index. Let's say I want to add at some index 0. Let's say the data is 0, right? L dot add at index. I want to add something at the last index. So L dot get size. Okay, now I'm getting not add last, but I can say add at. So index will be, let's say, the last index. So data is, let's say, 100. L dot get size. Now again, here I'm getting this because I'm not written throws exception. So main can also throw an exception because it is calling a method that throws exception. So main can also throw exception, right? So we have to write this here, right? And let's add something in the middle as well. So L dot display, and I also, okay, L dot add at index 4, sorry, data is 4 at some index, let's say 3, right? Something like this. And again, let me say L dot display. So this will test our all the 3 cases, and we should be seeing that they should work fine, right? So in the first case, I added 0 in the beginning, fine. I added 100 at the end, fine, working fine. Then in this linked list, I said, okay, at index 3, I should insert 4. So 0, 30, 20. This is the third index. So before 10, I will insert a 4. So 0, 30, 20. I'm getting a 4 here. Then 10, 40, 50, and 100. That means in the middle, it is also working fine. And I display this list, right? And finally, I have 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. That means that size update is also working fine in all the 3 cases, right? So that completes part 1. That means we are able to add nodes in the linked list in all the 3 cases. We have seen add first, we have seen add last, and we have seen add in the middle, right? Next, we will move on to get, and after that we will move on to remove, right? So take a pause and think how you can implement these methods: get first, get last, and get an element at a particular position. It's your time to code, and I'll just show you the add at method, right? So pause this video here and try to implement these 3 methods. Let us implement the get method, right? So I need to write a method called public int get first. That means I want to get the first element of the linked list. But what if the size of the linked list is 0? I do not have any such element. So I will have a special case. If size is 0, I can throw a new exception that the linked list is empty, right? So linked list is empty. That is the error that I'm trying to show to the user, right? And here I have to tell that, okay, this method also can also throw exception, right? So throws exception. But if the size is not 0, the linked list is there, then it is pretty easy. We just need to return the data present in the head node, right? So head is referring to this node, access the data and return it. So return head dot data. That's it. Size will not change, and this is what you will do. So similar to this, you can also write get last. So again, if the linked list is having size 0, then there is no last element. You will throw an exception, and in that case, the last data will be at the tail node, right? You can say return tail dot data. That's it. Now if you want to get something in the middle, that is going to take one more step, because you will have to loop through it, right? Okay, so add at, we did not discuss. It's going to take order and time, because your the worst case you might have to loop till the second last or the last node, right? So get last we have done. Now this will be get at a particular index. If I give you an index and I want to get an element at that index, how it will work out? Take a pause and think how you will do it. So this is also easy, right? Now user is giving you an index. Now it is possible that this index is also out of bounds, like we saw here, right? Like in the case of addition, it is also possible that this index is out of bounds. So if index is less than 0 or it is greater than size, I can throw an exception index out of bounds. Then if this is not the case, right? So if this is not the case, if the user is really giving you a valid index, right? Else if it is possible you're talking about index 0, If that is the case, you can say return get first. This can happen. Else if index is equal to size, you can say return size or size minus 1. It will be size minus 1 because the last element will have an index size minus 1. You can say return get last, right? Otherwise, what you need to do, you need to iterate on the linked list, right? So that iteration part is easy. What we will do, we'll have, let's say, A, B, C, D, and so on, right? This is index 0, 1, 2, 3, 4, right? So I want to get something at the second index. What I need to do, I need to take one jump, one more jump, two jumps to reach this particular index, right? So that means take the number of jumps equal to that index. So I can say, okay, fine, node temp that is equal to head, and for int jump equal to 1, jump less than equal to index, jump plus plus. What do? I take my temp to the next node, temp equal to temp dot next. Once I reach this node, I need to return the data of that node. So return temp dot data. That's it. So I take my temp here and I return this data, right? This will give me the data at a given position. So that is my get at a particular index. Now let us test this code. So I want to say, okay, fine. In this linked list that we have, I want to get the 0th element, s out l dot get first, s out l dot get last, and s out l dot get at index 4. Let's go and run this code. The first element is 0, last element is 100, the fourth element is 10. Let us verify. So 0th index, first index, second index, third index, fourth index. So fourth index is really 10. That means my output is correct. That is how we build the get at methods in the linked list. So far we have seen the add method and the get methods. Okay, all the three versions. So getting first, adding first, they all take order one time, but doing some work at a particular position, they take order of n time, right? So other methods are all one. Now we have the remove method. We want to remove first, remove last, and remove at a particular position. So let us see how we will write these methods. Okay, so what I will do, I'll create remove methods, public int. So remove, I will also get the data that has been removed from that particular index. So return type would be int. So remove first. You might think it should be very simple. Whatever is at the head, I will return that, right? So I want to remove this. Let's say 10 is there, 20 and 30, and this is my head. How do I remove this node? So one way is, okay, you can store the output, that is going to be head dot data, and then you can say, okay, this head will move to the next node. So head will go here, right? So head is going to be at head dot next, right? So doing this, will it remove this node? The answer is yes. So in heap, this node is a node that no one is referring to. What will happen? It becomes eligible for garbage collection. So garbage collector will come and it's going to sweep away this memory. So that means now your linked list will be only this, right? But there are few special cases, right? So I can say the output will be returned. That's okay. You also need to reduce the size. This dot size minus minus. This is something we need to do, right? But what is a special case? If the linked list is empty, can you remove the first element? The answer is no. So we have to check if the size is 0. What we will do, we'll throw an exception, right? We'll say throw new exception that linked list is empty, right? Fine. And we need to tell that this method throws exception. Now what about if the size is 1, right? So head will get updated, fine. But if you have just one node and both head and tail, they were pointing to this node, will it form a special case? Of course, yes, right? So if this node is getting removed, what will happen to head and tail? They will be reset to null, right? If your original size was 1, how do you remove it? You will set your head and tail equal to null. Size will become 0, right? Okay. And else, sorry, yeah, so one thing we can do is this code we can move here. Output is equal to head dot data, okay, and we'll of course return output. This code we can move in else case, right? That means if there are like at least two nodes, in that case tail will not be affected, right? So what about this case, else case? If there is 10, there is 20, and there is 30. So this is my head, this is my tail. Even if my remove this node, head comes here, right? So head goes to the next place, size gets reduced, so tail is not affected, right? But if I have just one node and I remove that node, in that case head and tail both will be affected, so they are reset to null and the size becomes 0. So that is how the remove first method should work. Now let us test this method. Let me create a new linked list. Let's say I add at the first position, let's say 10, then I add 20, 30, 40. 20, 30, 40. And I can say L dot display. Then I can say L dot remove first and L dot display, right? So I'm getting 40, 30, 20, 10, fine. And if I remove the first element 40, my linked list is 30, 20, 10, which is fine. Okay, if I have just one element in the linked list, and let me see if it works well. So I have one element, I remove that one element, so my linked list is empty, fine. That also works well, right? And I can say s out L dot size. I want to see if my size is getting updated properly. Yes, the size is 0 and I don't see any output here. That is how I will implement remove first method. Now on the similar lines, can you implement the remove last method? Okay, just need to think what will change, what will happen to head and tail, how much time it will take. So this method, it's going to take order one time, right? Remove first, but you have to think how much time remove last will take. Okay, so let's see remove last. Okay, so first case is, okay, if your linked list is empty, you cannot throw anything, you cannot remove anything. So if your size is 0, you will throw a new exception. Okay, then similar to this one, your output in this case will be what? Your output will be now tail dot data. You know the last node is tail and that data is your output, right? So if your size is 1, what you will do? You will reset your head and tail to null and you will say size is 0. If this is only one node, both head and tail are referring to this node, you want to get this data, you store this data in a variable called output, that is tail dot data. Original size was 1. If this is removed, head and tail, they are reset to null and size becomes 0, which is correct, right? Otherwise, if you really want to remove something, right, so you will have to check that if your index is in the bounds, or is it 0, or is it the last index. Sorry, you don't need to check here because we are talking about remove last, right? So you just need to remove the last node, right? So what I will do, I'll say, okay, else we have the other case, we know what node to remove if there are more nodes, right? There is one tricky thing here, that if it is a single linked list, right, and this is your tail node, you're saying I want to remove this node, right? That means tail should be updated, tail should come here, the new tail should come here, right, after removing this node. So I've stored this d in a variable called output, so output is tail dot data, so output is d, right? But how do I bring it back? There is no way to do it, right? Even if you maintain, okay, I'll maintain previous of tail for every node. Suppose this was the previous, but when you remove C, how you will get the previous? So the answer is, we don't have any order one way of coming to the previous node. We have to iterate from the beginning to reach this node, right? So that I can update my tail variable, right? So this is going to take time, right? Or the other option is you maintain a doubly linked list in which every node is also connected back, right? If you do that, your remove last will work in order one time. But for now, we have a singly linked list. That means we have only the next address, right? Singly linked list. In that case, we have only one option: start from the head node and try to reach the second last node. So how do I do it? So I take a variable called temp, which starts from head. I can say while temp dot next is not equal to tail, right? So what is the stopping condition? So when I reach this node temp dot next, this is equal to tail, right? So this is the tail node, right? Suppose this is my C, this is my temp, and this is my tail node, this is my D, right? So I'm saying while temp dot next is not equal to tail, right? Until this condition is not met, I will take my temp to the next and next node. So temp starts from here, it goes here, it stops here, right? Because C's next is equal to tail, so temp will stop at C. So I can say temp equals to temp dot next. My temp stops at the second last node, right? Now why this is important? Because I want to update the tail thing, right? Now at this point I want to disconnect D. So this D I don't want. So what should I do? I would say temp dot next is equal to null. So if I reset this variable to null, what will happen? This object becomes eligible for garbage collection because no one is referring to this object, right? So garbage collector will come and sweep away the memory of D because there are no object references which are holding the address of this node. So this D will get deleted from the memory and C's next is updated correctly, right? But what about the data that we wanted to return? That is still copied in a variable called as output, right? So once this is done, what should I do? So temps next is now null. This tail should be updated. So this tail should come here. So this tail will become equal to temp and the size will also get reduced, right? So here we have reset the size. So here it will be one lesser, size minus minus. That's it. And I will return the output in both the scenarios, right? So return output. In this case also I'll return the output. In this case I will also return the output. That is how remove last will work. And if I now show you L dot remove last, and maybe if you want to output, that's okay. We just want to see the linked list. So I can say L dot display. What do I get? Okay, let me add some numbers, only then we can see. 20, 30, 40. So right now I'm getting an exception because it's an empty linked list. So 10, 20, 30, 40 L dot display, and then I called the remove last method. So this was the linked list. I removed the last element. This is what I am getting, and the size is 3, right? Which is fine. That means the remove last is working as expected, right? Now the next thing we would like to do is, any guesses? Of course, it's going to be remove at a particular index. So we want to write one more method, public int remove at a given index. So again, before I write the code, take a pause and think how you will implement this method. Given a particular index, I want to remove something from that index. So let us start implementing a remove at, right? So first thing is, if the size is 0, that means you cannot remove anything. So you will throw a new exception. So throw new exception, and you will say, okay, linked list is empty. You cannot remove it. Or you can check that if the index that you're getting is out of bounds. So if index is less than 0 or your index is greater than size, you cannot remove, or equal to size. Even at size we don't have anything. The last index is size -1. So if this is the case, I have to throw new exception, right? So I'll throw a new exception and we'll tell that this method can throw an exception. Alright, so the error is fixed. Now what to do? I still want to remove it. So if my index is 0, that means I want to remove something from the head that we have already implemented. So whatever is returned by the remove first, we will return that. Else if index is equal to the last, which is size -1, we will return whatever is removed by remove last method. And now is the time we will see the actual working of this method, right? How do I remove something from the middle of the linked list? So let's say I have a linked list like this, A, B, C, D, E, F, right? And I say, okay, I want to remove something from index 2, right? 0, 1, 2. I want to remove this element. So if I want to remove this element, that means B should get connected with D, right? And this link from B to C, it should get broken, and C should be garbage collected, right? If this happens, C will be deleted from the memory, right? So how we are going to achieve this, right? So first of all, we need to reach this node, that is B, right? So if my index is 2, I need to reach one node behind that index. So how do we reach that node? Again, fairly easy. I can say I will start with temp, that is equal to head. And if index is 2, that means I need to iterate one less than that index. For int jump equal to 1, jump less than index, jump plus plus. So if it is 2, I'll just take less than 2 jumps, that is I'll take one jump. I will come here, and at this node I will start doing certain operations, right? So first of all, let me take temp to that particular node, right? Now I'm standing at this node. So what I want to do, I want to return this node, right? I want to return the data of this node. I will copy it in a variable called output. Output is nothing but temp.next.data. That is what my output is, right? And I want to return that output. Or let's say this is my node, which is okay. Either way we can do it, right? Node called output. So this node is my output node. And what I want temp to connect with next of this node. So I want B to connect with D. So how we can do it? So temp.next, either you write it should be equal to temp.next, which is my output dot next. So that is my D. Or you can say output.next. So again, I'm connecting B with D, right? Now no one is pointing to C. It will get garbage collected, right? Okay. And if this node is garbage collected, this link is automatically broken. So what I need to do, I need to say size minus minus, and I need to return output dot data. Output dot data. This output is a local variable, right? It is there only in this function. Once I return output dot data, there is this function call is over. Output will be out of scope. It will get destroyed, and hence no one is referring to C. This memory will also be cleared off. That's it. That's what you need to do, right? So that is going to remove something from the middle of the linked list, right? Now I can test my code. So I can say l dot remove at index, let's say 1. So given this linked list, let's say remove at index 2, which is okay. Show me what will happen if you remove something from index 2. So this is my linked list, and if I say okay, remove index 2, 0, 1, 2, 20 is gone, I get 40, 30 and 10. That means the code is working absolutely fine. So this is how we can remove something from the middle of linked list. So far we have seen the implementation of single linked list, right? So in which we said every node is going to store the address of the next node, right? But what happens in real scenarios, you might need sometimes a double linked list. So what is a double linked list? So just like you were storing the next, you will also store the address of the previous node. That means each node is now holding three things: a data, a next reference, and a previous reference. So 2 will hold the address of 3, 2 will also hold the address of 1, right? Now the advantage of double linked list is that you can traverse in both directions, right? For example, we were doing removal at tail, in which I said, okay, I want to remove this node and I want this tail to come back. So if it is a single linked list, I have to iterate from the front to reach this node, which is going to take order of n time, right? But if I do it the same operation, deletion at end, for a double linked list, I can just come back to the previous node, okay? Because 4 knows the address of 3, so I can update my tail pointer very easily, right? So it comes at the cost of extra memory, but it can save some time. For example, if you want to delete something at the end, it can then be done in order one time. Insert at end can be done in order one time. Insert at head can be done in order one time. Remove at head can also be done in order one time. So at both ends, you can do insertion and deletion in order one time, right? So each object stores data and memory location of next as well as the previous object, right? So this is something you can implement, right? Now there won't be a lot of change. For example, if you're making a method to insert something in the middle, let's say I want to insert 5 here. What are the variables that you will have to update, right? So you will have to update that 2's next should point to 5. Okay, but if you do this first, what will happen? You will lose the address of 3. So what I will do is, okay, let me create this new node 5, and let's say this is my temp. Here I want to insert it. So 5's next will point to 2's next. So 5 gets connected with 3, right? I can also say 5's previous can point to temp. So 5 also connected with 2, right? Now I just need to change these variables. So I can say t's next will point to n. So 2 points to 3, right? And I also need to say 3's previous, right? Or we can do it other way, right? We can first say that this node, which is the next of 2, so t dot next, right, dot previous, 3's previous should point to n. So this link will get like this. This link is gone. Now what you can do, you can remove 2's next and make it point to n. So you can say this will get connected here. So you can say t dot next, this is equal to n, right? So again, you just need to think logically, and you need to execute these instructions in a particular order so that your updates are correct. You're not making any changes which are inconsistent, right? So again, all the operations get remove, add. You can try creating those operations on a doubly linked list as an exercise, right? So let's talk about what happens in Java, right? So if you want to use this class inside your collections framework, then this class is already implemented. So there is a class called as linked lists. So it's part of java.util package as a part of collections framework. By default, this class internally uses a doubly linked list, right? So if you're using this class directly in solving problems, you're getting a doubly linked list by default, right? So if you want to learn more about this, I have covered collections in my DSA tutorial on the channel. You can watch that and learn how do we use the inbuilt doubly linked list or inbuilt linked list class. You can definitely learn about the methods of that as well, right? So let us quickly revisit the features of linked list, right? So it provides us an ability to use the non-continuous memory locations, right? So if you have like different chunks of memory available in different parts of the heap, and you cannot create a big array, but what you can do is you can use some memory here, some memory here, some memory here, and you can just connect those chunks, right? Non-continuous memory parts can be utilized efficiently using a linked list. Second advantage is it's a dynamic data structure. There is no need to allocate pre-memory, and again this results in efficient utilization of memory. For example, if an array you say, okay, I need 1000 elements, but only suppose 100 get used up, then what is happening? All this memory is it's a waste of memory. It's not efficient utilization of memory. So linked list, you create memory on demand, and hence you only use that much memory that is required, right? Okay, and if you are using a doubly linked list, insertion and deletion at the ends of the linked list, they are performed in constant time. So if you compare it with an array, and if you have to do some insertion or deletion in the beginning, right, you will know that it's going to take order of n time, because I have to do shifting. If I insert something or if I delete something, again I have to shift all the elements, right? And joining two linked lists is much more efficient in terms of space and time. So if there is one linked list and there is another linked list, right? So think, if you have to join two arrays, you have to copy all the elements from one array into another array. But if you have to join two linked lists, you just need to connect the tail of one with the head of other linked list, and that is going to be again an order one operation. So it saves both your space and time, right? So that is all about linked list. So a quick revision on the operations. Random access, if it is a linked list, it's a bad thing, right? Because it's going to take order of n time. In an array, getting the ith element will take order one time. Insertion and deletion at the beginning, order one time. In an array, it's going to take order n time, as I just discussed. Insertion and deletion at the end, right? So this, if it is a doubly linked list, it can be done in order one time, right? In an array also it can be done in order one time. Insertion and deletion from a random location. So if you're doing somewhere in the middle, both are going to take order and time, right? So in an array, this part is bad, insertion and deletion at the beginning, random access is good. In a linked list, this insertion deletion part is good, but random access is bad. So you can see each data structure has its own pros and cons. So depending upon the problem, you have to decide whether you will go with a linked list or an array. Let us talk about stacks today. So just like arrays and linked list, stack is a linear data structure that is used for storing data, right? And it looks very much like a real life stack, such as stack of books, stack of plates, and so on, right? So you might have guessed the kind of behavior this stack will show. So what happens is you can insert something. If you want to put a book, that book must be inserted from the top, right? You cannot insert books directly in the middle, right? You cannot insert a book at the bottom of the stack, right? Basically, any book, let's say C++ book, it goes on the top. Then a Python book, it goes on the top of the stack, right? So this is how it's going to be. And if you want to remove some book, you will have to remove the topmost book first. Then you can remove the next topmost book. Then you can remove the next topmost book, right? Basically, it's a data structure in which insertion and deletion, they are done only at the one end, where end is called as the top of the stack, right? So if you're pushing something, this blue goes, then this blue goes, and then this yellow goes. Okay, the item which is inserted at the last, right? Last item, it is at the top of the stack, right? Now, if you want to remove something, this 3 will come out, then this 2 will come out, then this 1 will come out. So the last item is the first one to come out. So hence this behavior is also called as last in first out, right? So when you do execute these operations on your computer, undo, redo, you do, right? So when you do Control Z, so the last operation has been reversed. When you do again undo, the previous operation gets reversed, right? So stack is a useful data structure if you want to implement recursion. If you want to build something like an undo redo stack, you can do that, right? And problems where this last in first out behavior is important, stack can be used there, right? Now, talking about implementations of stack, we will discuss 3 implementations. We will discuss one using fixed size array, we will see dynamic array, right, or an array list, and we'll also see using a linked list, right? So we'll go into the implementation details very soon, but before that, let us also talk about features of the stack, right? So stacks are different from arrays in a way that in arrays random access is possible. That means you can pick any ith element, but in this case, stack only limited access is possible. That means only the element which is at the top is directly available to us, right? And stacks are generally dynamic in nature. In general, we can have a fixed size stack as well, but generally we can push and pop elements, so the size of the stack can keep on changing, right? So generally we do not say it's going to have any fixed size, right? If you use an array list or a linked list, you will be able to implement a dynamic stack, right? So 3 fundamental operations that we will have with every stack. We'll say, okay, we want to push something at the top of the stack. We want to remove something, again, that happens at the top of the stack. And we want to peek, that means we want to get the element at the top. We are looking for the element, so we call it as peek, sometimes also called as a top, right? We want to seek the topmost element. That is about stack. And now let us jump into the implementation of stack. Let us talk about implementation of stack. So we will be discussing 2 implementations. One is stack that uses a fixed size array, and the second implementation would be a dynamic stack, right, which can use a array list or a linked list. Okay, so we'll discuss a fixed size array implementation and another implementation using dynamic array, which is called as array list, or we can also use linked list, right? So one of those data structures we can use to give the behavior of a stack, right? If you're using a fixed size array, right, so you have to think of a container which is getting filled and getting empty only from one end, right? That means if I say, okay, every insertion will go from here, right? So 1 2 3 4 5. If I want to insert 6, I will insert something from this end. If I want to remove something, I will also remove something from this end, right? So I can say, okay, I'll push something into the stack. So that means I'll push 6. And if I pop something, that pop will also remove 6, right? And there is one more method that we would like to implement, that okay, I want to see what element is at the top of the stack. So if you remove 6, right, and we call this method as peak, right? So if I want to see what element is at the top of the stack, so that element would be your 5, right? These are the three most important operations that we need to implement on a stack, right? Now clearly we can use a fixed size array to do it, right? So internally we'll say okay, there is an array which is having fixed size, and we can add elements from this end into the array, and we can also remove elements from this end of the array. So let us see how we can implement a stack class in our code. So let us start implementing the stack using a fixed size array, right? Now if you look at this fixed size array, what are the three things you will need in this class? One is the name of the array or the container in which you are going to hold data. Another is the top variable that is going to move as you insert and delete elements. And another thing we need to know is what is the maximum capacity of the stack, right? What I will do, I will define these three attributes as data members of the class. So first thing I will have is a private array, which we call it as data. Next thing I will have as top, and another thing I will have as a constant. The default capacity can be treated as a constant. So public static final int, I can say default capacity, right? And this is equal to 10, right? Now I need to define a constructor. So I can say okay, stack using an array, there is a constructor, and I'm not getting any default capacity, so that means my array size will be 10 in this case. So I can initialize my data array, so I can say this is equal to new int, how many integers, the default capacity, right? And what is the initial position of the top? So top is the index at which I'm going to store the element, at which I'm stored the last element. So in the beginning, I can say my top is at -1. Why? Because I have not stored anything. When you insert something, you can say okay, 3 is there and top will come here. So top will move after you can do the insertion. So I can initialize my top variable as -1. So I can have another constructor in which I'm getting some capacity as user input. So I can say fine, I'm getting some capacity. So in this case, I can say okay, the array that I'm creating, it has this particular capacity, right? Or you can also put a check that if your capacity is less than 1, right? That means is it negative or 0? In that case, we can throw an exception. So I can say throw new exception, invalid stack capacity, right? So something like this we can do, and here we can say okay, this function can throw an exception, throws exception. So this is how we will create the constructor for the stack class, right? And we are using a fixed size array. Now we have to define three functions. Okay, we have to define a push function. Okay, I want to push something into this stack, so I'm going to get data, right? Now we have to check whether my stack is full or not. Only I can push, right? So how do I check? Right? So let me do one more thing. Let me also write a function that will give me the size of the stack, right? So I'll say public int get size, right? The methods would be made public. So I want to see what is the current size of the stack, right? So can I say the current size is nothing but the value of top plus 1. So in the beginning, top is -1, and if you have not inserted anything, this output will be 0. So -1 plus 1, it will be 0. When you inserted, let's say something, so top will be at index 0. What is the size of the stack? The size of the stack is 1, right? So when you're going to push, how do you check whether the stack is full or not, right? So what you can do, just think about it. Okay, so what we can do is we can check that whatever is the current size of the stack, is it equal to the array capacity, right? So I can say if I can call the get size function, which is basically giving me top plus 1, is it equal to the capacity of the stack, right? So how do I know? So I can say that capacity is nothing but array length, right? So array has a property called as length. So if these two are equal, that means my array is already full. Okay, so we are getting an error here, data.length, because of this reason. Data is a variable here, and data is also an array here, right? I need to make it something different. I need to say this is some item that I'm pushing into the stack, and now this data means the arrays, right? If they are equal, so in that case I cannot push anything more. So I can say throw new exception, and the exception name is stack is full, right? So that is some message we can display, and we can tell this method also throws exception. All right, but if this is not the case, so what I will do, I will increment my top. Also, okay, fine, increment the top variable, and at the new position of top you are going to store that item, right? That's it. If the stack is not full, right? Function can be made as void, public void push, so we don't return anything, right? Now what is happening, that your top was here, I said push 3, so my top comes here and I put the item. I say push 4, my top comes here and I put the item. Again I push 5, top comes here, and so on, right? So eventually if your top plus 1 is this value, that means if my stack is full, okay, so get size is how many elements I've currently stored, let's say 6 7, and the capacity of the array is also 5. So if it is there, so I can say stack is full, right? So that is how we can perform the push operation on the stack, right? Now let us talk about how do we remove something from the stack, right? Now I can say I will have public int pop. Okay, I want to remove the topmost item. So again here, what you can do, you can make a check that if my stack is empty, right, then I have to throw an exception. I cannot pop from an empty stack. So if get size tells me, okay, this size is 0, there is no data in the stack, so you can say throw new exception, stack is empty, right? And here we can say this method throws exception, right? Okay, if this is not the case, I can easily remove something from the stack. I will store my answer. So answer that I want to return, it will be data of top, right? Now what I can do, I can reduce top minus minus, and I can return the answer that I have. So let's see what we are really doing. So we are saying, okay, 1 2 3 4, this is my top, right? I want to remove this, so I can simply say, okay, this top will come here, and I will copy this 4 in a variable called answer, and I will return it, right? Now you might say, okay, if I print the stack, I might see 4. That's not going to be true, because we will only print up to 1 2 3, right, up to top, right? So this data, if you want, you can make it 0, or you can keep it as it is, right? So just to make it little more clear, I can say answer of top, I'm making it 0, so that sorry, data of top, I'm going to make it 0, so that it looks good when you try to look at the entire array, right? So so in general, you are not going to look at the whole array, but only the array till the top, but that's okay. So this is an optional step if you would like to do, right? Because data can be 0 also, right? So again, this is an optional thing if you want to. That is how you will remove something from the stack, right? Now we have the method to look at the topmost element, right? So sometimes this method is called as top, sometimes it is called as peak, right? If you want to look at the peak method, it's pretty easy. You just need to do the similar thing, right? So I'll say, okay, if the array is empty, then you can throw a new exception that stack is empty, otherwise you get the data but you don't remove it. So that's it. You can simply return data of top. Okay, the topmost element you can return directly. So that is your peak method, right? Let us add some more methods if you want to print the stack. So I will print everything up to top, right? Public void display. So I can say for int I equal to top, I greater than equal to 0, I minus minus. So I will iterate on the items in the reverse order. So if it is like 1, 2, 3, 4, I will first say, okay, I'm going to print from top to the bottom, right? Like this. So what I will do, I'll say, okay, s out data of I. That's it, right? So that is my display method, and I can give a new line here. Okay. So any other methods if we would like to write? So maybe we want to write a method called as is empty or is full. So we can write those method as well. So I will write is empty method whether the stack is empty or not. So I can say public int public boolean is empty. So this is helpful when you want to continuously remove elements from the stack until the stack is not empty. So this method can be used, right? Now I can return if my get size is equal to 0. So this expression will evaluate to true or false. So I think this looks good. Next, we will test the functionality of this stack that we have created. Now let us write one more class so that we can test the functionality of this stack class. So I'll call it as stack demo.java, right? So in this stack demo, we will create a stack object. So main method is there. I can just this should be stack using an array, right? Stack using an array. I call it as stack. This is equal to new stack using an array, right? So I've created the stack object, or just call it as s. Let us push some numbers into it. So I can say s dot push 1, s dot push 2, s dot push 3. So we have to push method can throw an exception. So I can say main can also throw an exception, right? So s dot push 3, 4, 5, whatever it is, right? And then we can try to extract items from the stack. So 4, 5, 6. So I've added 6 items. Now I can say, okay, s dot display show me the stack, right? Let us run this and see what do we get, right? And at the same time, I will do one more thing. I will pop items from the stack until the stack is not empty. So while the stack is not empty, what I will do, I'll say, okay, give me the topmost element. So I can say s dot peak, print the topmost element. So s out topmost element and remove it. So I can say s dot pop, right? A pop function you can also use because it also gives you the element and remove it, right? But here we are not reading the value from the pop, we are just reading the value from the peak function. So when we are printing it, you see 6 is at the top, then 5, then 4, then 3, then 2, and then 1, right? If I do not call the display method, instead I use this while loop, what is the first element that will get removed? That will be 6, last in first out, then 5, then 4, then 3, then 2, and then 1. Let us go and run this code, and we will get a same output by removing all elements from the stack as well, right? So you can see that means our class is working perfectly fine. By default, the capacity is 10. So if I say the capacity is 5 and I try to insert 6 elements, then this code is going to throw an exception that the stack is already full and I cannot push any more elements into the stack. The next implementation of stack we will see using a dynamic array and a linked list. Let us talk about dynamic stack. Now there are two options to implement it. One is you can use an array, or one is you can use a linked list. So when I say array, we can use a dynamic array, right? So suppose you are implementing the stack using an array, and at some point your array got full. Okay, your current size is equal to capacity, right? So what you can do is, using the same logic as array list, inside your push method, what you will do, you will say fine, I will create a new array of double the capacity. If this is C, I will create an array of 2x of my capacity, and I will copy the elements here, right? So that is how my push method will get changed, right? And pop will remain same. I am not going to shrink anything, so pop will remain same. Even the top method will remain same. No changes, right? Nothing changes here. Only in the push method we are going to change. So array will not overflow. Instead, it will get doubled, right? And again, this copying is a expensive operation, right? So we should make sure that this is not happening too frequently, right? So that is why initial capacity is important, right? So that is using an array list, right? Now, if you want to discuss it in the code, so you can say, okay, I have a class called stack. So either you can keep a array list object here, right? Because we have already implemented array list. It can be your implementation. It can be library based implementation as well. Whenever you get a call for push some item I, you can simply say, okay, a dot add the item I. So add function, we know it adds at the end of the array list. The code becomes even simpler, right? Or if you don't want to use the inbuilt class, right? What you can do, you can take the manual array like we did in the previous example and write the doubling logic inside the push method. So I'm hopeful that you will be able to do that part, right? Another option is you can use a linked list also, right? Now suppose we are building a stack, I got 1. So I insert that node into the linked list. So my head is updated, tail is also updated, right? Now suppose you got 2. Now the question is, where should I insert 2? Should it go at head or should it go at tail, right? One option is, okay, if I put it at tail, insert at tail, if I do it, this tail will go here, right? Okay, and suppose I got 3, then you can again insert it at tail. This tail will go here and 3 is also inserted, right? Now the question is, if I want to remove something, if I want to pop out 3, right? How do I move this tail back, right? I cannot move it back in order one time, right? I have to traverse from the beginning. This is going to be time taking. So push is going to be order 1, but my pop is going to be order of n, which is not acceptable here, right? So hence I need a better implementation using a linked list. So let us do one more try. Suppose I got 1 and both head and tail, they got updated, right? Now if I want to insert 2 will go here. I will create a new node, okay, and I will connect this node with the head. So basically I'm inserting at the head only. This head will move here, fine, right? Because that we have seen how to insert at head. Then I insert 3, I create a new node connected with the previous head, and I update this head, right? This head can come here, right? Now if I want to remove something, I can say, okay, I want to remove the topmost node. I want to pop this node, right? How do I remove it? This is now pretty easy. How? We can say, okay, fine, let me move the head from here to here, and this node now becomes eligible for garbage collection, right? That means popping is very easy. Even looking at the topmost element is very easy. So the element at the head is the element at the top. So again, if I want to remove this thing, my head will go here and the node 2, it will become garbage collected. So using linked list also, building a stack is very easy. If you want to insert something or you want to push something, you can say, okay, I will call the add front method of the linked list, right? Or insert front, whatever it is. And if I want to pop something, I will say remove from the front. Okay, I think add first. We called it as add first. Right? I need to add at the first position and I need to remove at the first position, right? And peek is nothing but it is the get first. I want to get the first element of the linked list, right? That is how it's going to work, right? So regarding the implementation, I think it's now pretty easy, given that we have implemented array list, we have implemented linked list. What you can do, you can also put that code inside your dynamic stack class as well, right? Now 3 options. Either you write entire code, that is option number 1. You define the node, you write how do we insert at front. Second option is you can use the linked list class that we have created, or the array list class we have created. So you can use your library version. Okay, if you don't want to do that, you can also use the collections array list or the collections linked list, right? Any code you can use to build your own version of dynamic stack, right? And the behavior wise, it will have same functionality, except that it will not get full unless your system memory is not full, right? So that's all for dynamic stack. Hope you understood the functionality of dynamic stack. Okay, I'll show you one more implementation of implementing dynamic stack using the stack using array class. So this class we have just written. So what I'm doing, I have created one child class called dynamic stack, and it is extending the stack using array class that we have just written. So inside this class, I have only updated the push method. So basically I have overwritten this method, right? And I have provided two constructors so that I can build the dynamic stack object, right? So the first constructor does not accept any capacity, so I call the constructor. So this is basically calling this method with the default capacity. So I say, okay, go and create a stack with the default capacity, right? And if I get a capacity from user, then also I call the constructor of the parent class. So super is for calling the parent class, and I give the capacity. Okay, you go and call the constructor that is here, right? So this constructor is getting called, right? And I pass in the capacity. So either I pass in the default capacity that is 10, or I give the user defined capacity, right? So I give that. So this calls the parent constructor and initializes that array, right, of that particular size, right? The pop method, I told you it's not going to change. The peek method, it's not going to change. In the push method, if my array is full, right? So if get size is equal to data.length, right? And what I will do, I create a new array of twice the size. I copy all the elements into the new array. Okay. And I say, okay, this dot data should now point to this array, right? What happens? So data was pointing to the old array, right? Now data is pointing to the new array. So this reference is gone. That means this array will be garbage collected, right? So this is ARR. ARR is a local variable. It will be destroyed, but data is a class member, so it will not get destroyed. So using the this keyword is optional. It is for more clarity that we are talking about the data member array, not any local variable, right? So that is what we are doing here. And then after we expanded the array, we call the push method of the parent class. In the parent class, now if your array has already expanded, you will never get this condition. So this condition will never be met. Which condition? That data.length is equal. So exception will not be thrown. And what will happen? Top plus plus and data of top equal to item. So this code will actually execute if condition will not be true. So before calling the push method of parent function, I simply expand the array in case of a dynamic array. This is what I really do, and it will work. So what you need to do, you need to replace this stack with the dynamic stack. You can try it out and it will work, right? So that is another way of using inheritance and creating a dynamic stack object for you. One small change I wanted to discuss was I did a change that I made these data members which were earlier private. I made them as protected now, right? Why? Because I want to use these data members in the child class as well, right? So that is the only change I have done in the class called stack using an array. So let us start by understanding the fundamentals of a queue. What is a queue? A queue is just like a real life queue. So in most general terms, a queue represents a sequence of objects waiting to be served in a sequential order. Okay. So one thing you need to remember is queue is also a linear data structure. Like other linear data structures you have seen so far, arrays, array lists, stacks, linked list. Queue is also a linear data structure that stores the data in the sequential order, starting from the beginning of the queue, right? For example, if you go to a bank, right? So the person who enters the queue first, it is at the front of the queue. Second person is behind it. Third person is behind the second person, and so on, right? So in general, queue has two ends. One is called as front, from where the people will be served, right? And one is the rear end, from where people will join the queue, right? basically insertion of data will happen from this side and removal of data will happen from the front side, right? People at the front, once they are served, they will get removed from the queue, right? Now this queue can also be seen as queue of cars at a toll booth, right? People standing in a line to buy tickets, right? And in the world of computer science, we use queues a lot, right? For example, many people are uploading videos on YouTube, and YouTube has maintained a queue so that people who have uploaded videos first, their videos will be processed, right? We might maintain a queue of videos on the server waiting to be processed, right? Similarly, on in software applications, for example, an application has to perform several tasks. It might maintain a queue of the task that it needs to perform so that our work gets done, right? So queue is again a very important, very interesting data structure, right? So now let us talk a little bit more about the operations. So as I discussed, one fundamental operation on the queue is insertion, right? I want to insert something into the queue, right? So the kind of queue that we are discussing current now, it is called as FIFO queue, first in first out queue. Why? Because the person who joins the queue first is the first one to get served, right? So in a FIFO queue, insertion happens at the rear end of the queue. So this is your, let's say, rear end, right? Whereas deletion happens at the front end of the queue. So this is your front side, right? So anything, you cannot say, okay, I want to remove something from the middle of the queue. That is not possible. Only the data which is at the front of the queue will be removed, right? There is one more operation. So we have seen insertion, we have seen deletion, right? We will discuss how these operations are implemented using other data structures, right? There is one more operation that is called peek. So I want to look what is the uh, front element, okay, who is standing at the front. We call that operation as peek. So just in case of stack, if you remember, the peek operation returns the top element of the stack. In a queue, peek operation should return the front element of the queue, right? The person who is standing at the front of the queue. So that is what peek operation will do, right? So as a next step, we will look at the implementation of a FIFO queue, right? So there are three common ways to implement a queue. We can use a fixed size array, right? And we'll see how this array will behave as a circular array when we are going to implement it. Okay, so in this case, queue will have a limited capacity because the array size is fixed. Suppose n is 6. So I cannot have more than 6 elements in this queue at any given point, right? Second is I can use a dynamic array. So I can write my own logic for creating a dynamic array. For example, if my queue gets full, I will say fine, I will double the array. I will create a new array of double the capacity of the given size, right? Now, if again the queue gets full, I'll again do the same thing, right? So this is called as implementation using a dynamic array. The other option is if you do not want to write the functionality of doubling, it is already implemented inside your ArrayList class. You can also implement queue using a ArrayList, right? Third is we can build a queue using linked list as well, right? You know, linked list is a dynamic data structure. So we will look at how a linked list can be used to implement a queue as well, right? So let us start with the first implementation, that is implementing a queue using fixed size array. Now let us talk about how we can implement operations on a queue using a fixed size array. So the three operations that we need to build are enqueue, dequeue, and peek. So enqueue means I want to insert something into the queue. Dequeue means I want to remove the element at the front, and peek means I want to get the element at the front. These are the three things that we will have in a FIFO queue, first in first out, right? Now let's see how we can use a fixed size array to create these operations on the queue, right? So in the beginning, I should know if something is coming at what index I will insert it into the queue, and at what index I will remove it from the queue, right? So what I will do, I'll say, okay, let us take a variable called front, and it is here, right? We can also take another variable rear, but again that is optional if we are maintaining the size of the queue. In the beginning, size is 0, front is also at 0. That means nothing is inserted in the queue yet, right? Now someone says, okay, person 1 is going to join the queue and I will insert it, right? What I will do, I will insert it at the rear end. Okay, so how do I compute the rear end? Let's see. The rear end can be said as front plus size. I will tell you why, right? So what is front? Front is 0. So what is size? Size is 0. So 0 plus 0 is 0. So I can insert person 1 here in the queue, right? And I will increment the size. The size will become 1, right? Size is going to become 1, right? So I'm not going to change the front. Look carefully. I'm not going to change the front, right? Now it was 0 plus 0. That's fine, right? Now I can say again, I want to insert person 2. Okay, I want to insert person 2. At what index I will insert? I will insert it at the rear end, right? So what will be the rear what will be the rear value now? It will be f plus size. So f is 0, fine. Size is 1. It is going to be 1. So I can insert person 2 at this index. Very good, right? Now let's say one more person wants to join the queue. So I want to insert person 3, right? Size is already 2, right? I've inserted 2 elements. But what index I will insert? I will insert it at the rear index. What will be the rear index? 0 plus 2, that is going to be 2. That means person 3 will be inserted here, and this is the new rear. Okay, so front is not changing, rear is changing in this case. Again, I want to insert person 4. Let's insert person 4. So size is already 3 now, right? Size is already 3. So what will be the new index? 0 plus 3, it's going to be 3. I can insert person 4 at this index, and my rear is already here, right? Now suppose I've done a lot of insertions. I want to remove something, right? So I have inserted till person 4 also, and I want to see how my front is going to change, right? Now suppose I want to remove something. I want to perform DQ, right? So that means I got a query to remove the front element. The front element will get removed, right? Now how do I remove it? If I move this f one step forward, right, and I will have to reduce the size. Right now the size was 4 because 4 elements are there in the queue, right? My size becomes 4. From 4 it becomes 3, and I say okay, f should move one step ahead. So I'll say okay, I'll take this front one step ahead. That means this p1 is it's kind of a removed, it's not there, right? So the area between front and rear, it is the content of the queue, right? Now suppose I want to insert something more, right? So what I will do, I'll again do front, which is at 1, okay, plus size, which is at 3. So look carefully. So 1 plus 3, I get an index 4. That means the next insertion will happen at this index. Can I insert something? Of course I can insert something because queue is not yet full. I insert something at this index, right? Now suppose I want to do one more insertion. Again, what is the value of size now? Size is still 4. Size is 4, right? So what will be the value of rear? So it will be front, which is 1, plus rear, which is at which is plus size, which is 4, right? It is going to get 5. Now is this 5 a valid index? Is this 5 a valid index? The answer is no, right? Now I will get a problem that if it will give me index out of bounds exception, but queue is not yet full. Queue is not yet full. So how should I handle this case, right? The way to handle this case is by treating this array as a circular array, right? If you exceed 4, you should come back to this index. You should kind of rotate, and you should come back here, right? Now how do I achieve this? I have to say take a mod with 5. Every time you hit a 5, you go back to 0. Again, you start filling the queue from this index. Now suppose I got this p5 I have already got. I want to insert p6, right? This p6 will get inserted here, right? What I'm saying is the rear will not be updated using this formula. The rear will be updated by using front plus size mod of the capacity of the queue. The capacity is 5, right? So I have to take a mod with capacity. So that means if you hit the capacity, if the rear index hits its capacity, it will be again shifted back to 0, provided your queue is not full. You have to check that, okay, if my size is 5 and I have only 4 elements, right, then I can add more. The size is 5 and I have already added if the capacity is 5 and the size is also 5, in that case I will throw that the queue is full. I cannot insert anything more, right? So I will insert it here, right? Now my front is still at P2, right? Front is still at P2, but my rear is here, right? Now someone says, okay, I want to remove something, or let's say I want to insert something, right? Now what is the size? The size is 5. Can I insert something more? The answer is no, right? So what you will check, that if your size is equal to the maximum capacity that we have allocated, I cannot insert anything into the queue. So I have to throw some kind of error that queue is full, right? Now again, let's say I want to insert, perform the remove operation, right? So how I will do it? I'll say fine, I'll move this front from here to here. I will reduce down the size from 5 to 4, and this makes that P2 is not there, right? So P2 is not there. I'll either make it 0 or I'll just keep it like this, right? Now I can insert something, right? I want to insert something. So what is my front? Front is at 2. What is my rear? Sorry, what is my size? The size is 5. So 2 plus 5 mod 5, it gives me 2. Oh, sorry. The size is actually 4. The size is 4. So 2 plus 4, that is 6. Mod 5, it gives me 1. 2 plus 4 mod 5, it's 1. That means the rear should come here, and the next insertion will happen at this index. So if P7 comes, that person 7 will be stored at this place. Again, if you want to remove something, you will remove from the front. So the front is P3. So you will read the elements in this order, right? The elements will be removed in this order, right? One thing you have to notice, when you're moving your front, right? So your front will also go like this. It will go to P3, P4, P5, and again it should come here, P6, P7, right? Basically what I'm trying to say is that when you're doing this operation, that front will move like F equal to F plus 1, right? Here also we should do mod with the capacity, so that my both front and rear move in a circular fashion inside the array, right? At any given point, right? I have to check if the queue is full, I cannot insert something. If the queue is empty, I cannot remove something, right? So we have to handle two cases, that if size equal to maximum capacity, I cannot insert, and if the size is 0, I cannot remove, right? So these will become our special cases in the code, right? I cannot remove. So I hope you understood the logic for the fixed size queue, and now we will jump into the implementation. Let us start implementing queue using a fixed size array. I will be using Java, but you can use any language of your choice for the implementation. So let's begin. The first thing I will need to do is I need to create a class queue, and I need to define few data members. So as we have discussed earlier, that if we are using a fixed size array, we will need a object reference to store this array, right? So you can call it anything. I am just going to call it as ARR, right? So let's create this variable data member. So I'll say private, it's an integer array, and I need to define what is the maximum capacity of this queue, right? So that I will define using a constant, because I'm taking a fixed size array. I'll say okay, fine, this constant will be a public static final int called as default capacity, and this is equal to 10, right? One thing I need to notice, that if someone is inserting data into this queue, what is the current size of the queue? So I'll take another private variable to denote the size of the queue, right? And now in order to perform operations like insertion and deletion, I must know the front of the queue. So I'll create another variable that is private int, and I call it as front, right? These are the four data members that we will need. So one is your capacity, let's say that is 10. Then there is your front, which is initially at 0, and there is size, which will be also at 0, right? Now we need to initialize these data members. So that part we will do in the constructor for the queue, right? So I'll say fine, let's create a constructor, and in this constructor I'm going to create a queue, right? So maybe I'm going to get some capacity as input, right? If nothing is given, I will use the default capacity. So I'll create actually two constructors. One is the parameterized accepting capacity, and other one does not accept any capacity from the user. So in this case, we will use the default capacity. So one thing we can do is from this constructor, we can directly call this, and we can say, okay, fine, you can call this constructor and give default capacity as a parameter to it, right? So that will help me to avoid creating an array here, and that part I can do directly here, right? Let's see how we can do it. Now if my capacity is less than 1, if someone gives a wrong argument, maybe a negative capacity, in that case my code should throw an exception. So I can say throw new exception that invalid capacity you are giving it to me, right? And also we need to define that this throws an exception, right? All right, now let's do the actual work. The actual work is that we need to initialize this array, right? So I need to say that fine, this array that I have, right? So again, I'm using this, which is optional here, but it's a good thing to do because you are clearly referring to the data member of the class. So this dot array should be a new array of capacity, right? Now this capacity can come as an argument from the user directly, or if the user does not give, then this constructor will be called and this capacity will come from here, right? That will be your 10, right? And here also we need to say that this method can also throw an exception. So this is how we have initialized our array. Now we need to initialize the size and the front variables. Initializing them is pretty easy. So I can say this dot size, it is 0, and this dot front, that is also 0, right? So I hope this is clear. So we have created a new queue of given capacity. It can be fixed size, it can be given by the user as well, right? So we have a capacity, right? Let's say capacity in this case is 1 2 3 4 5 6. So capacity is 6, front is 0, array is referring here, and the current size of the queue is also 0. So the queue has been initialized correctly. Now the next operation that we need to build on this queue is enqueue. I want to push something into it. So I can say public void enqueue, and I'm going to get some data or value to add into this queue. Now since it is a fixed size queue and it is possible that queue is already full, so how do I check if the queue is full? I can simply say that fine, if the current size, if this dot size, that is my data member, it is equal to the capacity of the queue. So what is the capacity? This dot array dot length, right? Length of the given array. Then I can say throw new exception that my queue is, and here I can say that this method also throws a exception. But if the queue is not full, so we can insert it, right? So if the queue is not full, we can say, okay, fine, we will push something at a rear index. So we will need to compute that rear index. Let's see how we can compute that. So I can say the rear index, according to the formula, is the front index plus the size, and then we have to take the mod with the capacity. So that capacity is nothing but this dot array dot length. That is the capacity. Now in this case, rear will be 0 plus 0 mod with 6. In that case, it will be 0. So I will insert something here, and then again size will also increment. So we will put the data. So we'll say this dot array at the rear index. I want to put the value. I'm storing 1, and I need to update the size. I need to say the size is now 1. So next time the rear would be 0 plus 1 mod 6. Next time the insertion will happen here. So maybe I push 2. So I'll do the insertion at this index. So in order to achieve that, I have to say this dot size plus plus. So I need to increment the size as well. So that's how the enqueue operation will work, right? And finally, you insert here, you insert here, you insert here, you insert here. Now if you try to insert, the queue is full. You have to remove something. So maybe this gets removed. So your F will come here, right? Now let us look at the remove method as well. So in that case, we can call the method as public. Now either you can make it as void or you can make it as int. So you also want to return what has been extracted from the queue, right? So in that case, you can make the return type as int. Now this method can also throw an exception. If your size is 0, that means queue is empty. You cannot remove anything from this queue. If this dot size is 0, what you should do, you will say, okay, throw new exception that queue is empty. But if this is not the case, I can say throws new exception here. Sorry, throws exception. But if this is not the case, what we discussed, what we will do, right? So we'll store maybe this data 1. We'll store this 1 here. We can say, okay, our output, the answer that we want to return is present at this dot array of front, right? Or this dot front, whatever, right? So you can definitely return this answer, but you have to update your front and you have to update your size as well, right? So I can say fine, this dot front will move this dot front equal to this dot front plus 1 mod capacity. So capacity is this dot array dot length, right? And the size will reduce this dot size minus 1. If you remember from the diagram, this is what we discussed earlier also, that this is how my front will change in case of removal, right? Okay, and this is how I will compute rear, right, in the case of insertion, right? We have already discussed how it's going to work. So I'm changing the front and I'm changing the size as well. So this is my dequeue method, right? Now let us write some more methods that would be helpful. So one method would be peek. If I want to look at the front element, I can say fine public int peek. Now if again the queue is empty, I cannot look at the front element. So if this dot size is 0, I can say fine throw new exception, the queue is empty. Queue is empty. That means I cannot remove anything from this queue. Otherwise, okay, let's just fix the error. Otherwise, I can say return the front element, this dot array of the index, which is this dot front. Okay, that is my peek method, return the front element. So the complexity of this method would be order 1. Here also, dequeue method, it will be also order 1. The insert method, that is also going to be order 1. The constructors are also order 1. Apart from it, we can make 2-3 more methods. One is to check if the queue is empty or not. That can be a boolean method. I can say public boolean is empty or just empty, right? So I can return true if this dot size is equal to 0. I can make a method called public boolean full. So I can return if this dot size equals this dot array dot length. Okay, that will tell me if the queue is full. What else? I can also make a method to get the size, public int size. So I can return this dot size from this method. Anything else that you think would be helpful? Maybe just a method to print the entire queue, right? So maybe I want to display the entire queue, right? So in Java, this method is called as toString, which is present in the default class. So I need a way to look at all the elements of the queue, right? So right now I'm not going to iterate from front to rear. I will just display the array. So it's more of a method for debugging, not for doing anything else. Okay, I'm just going to print my array, or we can say we can print. So one simple way you can do it: sout arrays dot toString, and you can say this dot arr, right? But now instead of doing this, you can also say that fine, I would print elements from rear to front. Suppose this diagram is your queue. So maybe I want to print the elements from rear to front, right? Or front to rear. So how I can do it, right? Now suppose if my front is at 2, right? So I want to print, let's say 1, 2, 3, 4, 5, 6. So I want to print all the elements from front to rear of the queue. I want to display all these elements. So my output should be 1, 2, 3, 4, 5, 6. So how I can do it? Very easy. I know this index, I can compute this, I can compute this, I can compute this. So this is f plus 0, this is f plus 1, this is f plus 2, this is f plus 3, this is f plus 4, right? And of course you have to take the mod so that you can rotate in this circular fashion. So very easy. I can say for int I equal to 0, I less than this dot size, okay, and I can say okay, the current element, the current index will be nothing but this dot front plus I, take a mod with this dot capacity, that is array dot length. Now I can say s out that element, so this dot array of index followed by a comma and s out. This looks good to go. This will print all the elements from front to rear. Now let us test our functionality in the queue test file. So we have created a queue test. So here what we need to do, we need to create a queue, right? So we'll say psvm, that is the main method. Now we can create a queue object, queue equal to new queue. Let's say the capacity is 5. Now I want to add certain elements to it, right? Throws exception, right? We have to tell that main can also throw an exception here. Now capacity is 5. So what do? I say okay, fine. Let's push q.nq1. Let's say 2, 3, 4, 5. Then I remove something. Let's say q.dq, q.dq, and then I can say 7 and 8, and then I can say q.display, right? Now let's see how this queue should look like. Let's go and run the code. So I inserted 1, 2, 3, 4, 5. So queue was full. Then I removed something, right? So I removed this, I removed this. My front is here, and then I enqueued 7 and 8. So 7 and 8, they will come here, right? So if I now print my queue, it should be like this: 3, 4, 5 and 7, 8. Yes, that is what I am getting, right? That means my queue is behaving in a correct manner. The front element would be this, next front 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 would be this. So I hope you understood the implementation of queue using a fixed size array. Next we will jump into the dynamic array implementation of the queue. So let us now discuss the implementation of a dynamic queue, right? Now there are two ways. One, you can use a linked list, or you can use a dynamic array as well, right? So in this implementation, I'm going to show you how we can use a dynamic array functionality, and we are going to extend the implementation of the queue class by adding this functionality, okay? So queue we have already written. What I'm going to do, I'm going to create a class called dynamic queue, which will be the child class of the parent class. So dynamic queue extends the queue class, right? Now one thing to notice, that this dynamic queue, it's going to behave in a similar way. The operations nq, dq, peak, they will remain same. The only thing is the logic in the insertion operation, that is nq operation, it's going to change, right? So first of all, let us start by creating the constructors for this class. So I can say public dynamic queue. So again, there can be two types of constructors, one without the capacity and one with the capacity, right? So public dynamic queue, where I'm going to accept some capacity, right? Now in this case, in the first constructor, what I'm going to do, I'm going to simply call the second constructor with default capacity. So I can say this and call it with the default capacity. Basically what is happening, if I want to create a dynamic queue object in which I'm not getting any capacity, so I make a call here. If I get a call here, again what I can do, I already know how to create an array of given capacity. That I'm doing in the parent class, right? So Q is my parent class, dynamic Q is my child class. So if I want to create a fixed size array in both, so if I get a call here to create a dynamic queue, I can redirect the call to the parent constructor. So I can say super, and I can pass in the given capacity that I am getting, right? Basically, I'm calling the constructor of the parent class, right? Now, this is a spelling mistake, dynamic queue. Now, the parent class constructor, if we look carefully here, right? So basically what is happening, the call is going to come here to this constructor. So we are already initializing the array correctly, size is set to 0, front is set to 0, and we are also throwing a exception. We can also say that our dynamic queue can also throw an exception. This can also throw an exception. Now the errors are resolved, right? So constructor part is done. Now there won't be any change in other methods except enqueue. Let us see. So if I want to enqueue something, let's say public void enqueue. So I'm going to override the method that I have written for insertion. You can see we are overriding this method, right? Now there are two things we have to do. We have to expand the array, right? And then we have to put the element if the queue is full. Okay, put the element, right? Expand if queue is full, and then we have to put the element, right? Now this functionality we were not doing in the previous implementation. Now we have to do this functionality, right? Now assume that your queue looks like this. So suppose queue is like this, 1 2 3 4 5 6, right? And suppose my front is here. That means if I want to read data, I will read the data in this manner, right? So my capacity was 6, size is also 6. That means my queue is full, right? And I want to create a new queue, a new array basically, with double the capacity, right? Let's just say that this is going to be 2x, twice of the original capacity. Now if I want to copy this data, can I copy it directly? Can I say I'll copy 5 6 1 2 3 4? Will that be correct? The answer is no. Why? Because if I want to do a next insertion, right? So at what index the next insertion happens? It happens at front plus size, right? So in this case, front is at 2, fine. Size is 6. The next insertion will happen at the 8th index. That means I will start filling from this index. But is it correct? The answer is no, right? Because what happens at these places we don't know, right? So the correct way of doing the copy is you create a queue of double the capacity, right? You iterate over this part. Let me change the color. You iterate over this part in a circular way, and you copy the elements here, right? So you copy 1 2 3 4, then you copy 5 6. This is my front. This is my front. Now if I want to do an insertion, so my rear would be front plus size. Front is 0, fine. Size is 6. I'll start copying from the 6th index. 0 1 2 3 4 5 6. That is correct. So if I want to push something, that insertion should happen at these places, right? So let's see how we can do this, right? So let's say this is my original array. This is my temp array in which I'm going to perform a copy. So I will say if what, how do I check the size? If this dot size is equal to this dot array dot length, right? Now one thing you will notice that these members were earlier private. So I've just made them protected now, right? I've made them protected so that I can use them in the child class, right? So coming back here, so I can access the data members of the parent class because they are now protected, right? So what I have to do, I have to create a new array of double size, right? So let's say there is a new array called temp that is equal to new int of size twice of this dot array dot length. So this is created. Now I have to copy the data. So I can say for int I equal to 0, I less than this dot array dot length. That is the size, right? Or you can say this dot size. Both of them, they are equal, I plus plus. Right? I'm going to run a loop these many times, right? Okay, so I'm going to iterate over these positions. 7, 8 will come later, right? I need to copy these values, right? So I can set temp of I at the ith index in the temp. What should I copy? So at this index, what should I copy? I should copy the element from the front. So this is f plus 0. Then at the next index, I should copy this LU. This is f plus 1. Then this is f plus 2, f plus 3, f plus 4, f plus 5, and so on, right? So I can say this is going to be equal to this dot array of, let's find the old index. So this is going to be this dot original front plus the original size with the original capacity mod, right? So the elements at the at this particular index, right? Mod this dot array dot length. This is what I need to do, right? Sorry, this dot front plus this dot plus I. Sorry, that's a mistake. So f plus 0, f plus 1, f plus 2, f plus 3, right? So basically the ith element. Okay, so the element at, let's say, temp of 3 will be equal to array of f, which was, let's say, 0, 1, 2 plus I is 3 mod 6. So it will be array of 5. So fifth index 0, 1, 2, 3, 4, 5. So that element is 4. That's correct. So at the third position, I'm putting the value that is 4, right? Array of 5. This is what I need to do, right? So just like we did in the display method in the queue, that is the same logic we are using here, right? Now once this is done, temp array has been created, right? So I've erased all of it. I'll just do it once again. It was like 1, 2, 3, 4, 5, 6, right? This is my front. Now I've copied this data like this. 1, 2, 3, 4, 5, 6. So I have to reset the front here, right? This should be the new front. Okay. And this was my array. This was my temp, right? One thing I need to change is that this ARR should refer to this memory. This connection should get broken. So I can say this dot ARR. This will be now referring to temp object. And now doing this, no one is referring to this memory. So garbage collector will clean up this memory, right? And this dot front will be set to 0, right? But have I really done insertion as of now? The answer is no. We have still not done the insertion part, right? So how do I insert? I can say fine, at this position, which is rear is my f plus size mod capacity. I will do array of rear equal to the value that I'm inserting, and I will do size plus plus, right? Now this code I'm already doing in the enqueue method of the parent class. So I can just call that method super.enqueue and I can give value, right? Now this method will get to know that the array has been changed because ARR is now referring to this memory, right? And it will try to push something into this method, right? Something into the new array because we have changed ARR, which is now referring to the new array, right? So I can say this method can also throw an exception, throws exception. This error should get resolved. Let us look at the enqueue method of the parent class. So here what is happening? This is what we are doing, right? Now this condition is handled in the child class. If queue is full, double it. When you come back into the parent method, this condition will not be true. So what code will execute? This code will execute, right? That is how we have implemented dynamic queue using a dynamic array, right? Now let us test our functionality. Let us go back into queue_test.java, right? So earlier I was creating a queue of fixed size. So if I try to let's say push 6 elements in a queue of size 5, I will get a exception, right? I'm using the fixed size queue. Let's see. So I'm getting an exception that queue is full, right? Now if I replace this queue object with the dynamic queue object, let me show you. If I do this, I should be able to hold it, right? Yes, I'm able to hold it. I do not get any exception because queue is getting expanded, right? And even I can put more elements. I can say fine, let me put 9, 10, 11, 12, right? And so on. So let's see what output do we really get. So I'm getting everything from 3 to 12, which is correct, right? So you inserted 1, 2, 3, 4, 5, 6. Then you removed 1, 2, the elements at the front. Then you inserted 7, 8, 9, 10, 11, 12. Okay. Irrespective of the initial capacity, which was 5, you are able to hold more elements because your array is getting expanded during the insertion process, right? So in this case, you will never get a queue is full exception unless you run out of your heap memory or something like that, right? So that is dynamic queue using a dynamic array, right? So next we will discuss dynamic queue using a linked list. So far we have seen two implementation, fixed size array implementation and dynamic array implementation we have seen, right? You can also use a array list object if you want, right? Now third kind of implementation will involve a linked list, because linked list is also a linear data structure, right? Now you might ask how we can use a linked list. It's pretty simple and very intuitive as well. Now suppose you are inserting something. So 1 is at the beginning, then you insert 2, then you insert 3, then you insert 4, right? Now if I ask you, this is, let's say, head and this is tail, right? If I ask you where is the front element, right? So I want to get the front element, so that is 1. If I want to remove this element, can you remove it? Of course yes. You can say, okay, I will move this head here, and that means this element will be removed. If I want to read the front element, again that element is present at the head of the linked list. If I want to insert something, it should go at the rear end. So where is the rear end? The rear end is at the tail, right? So you can easily insert something here and your tail will come here, right? So your head and tail data members will behave as front and rear for the linked list. So this will be your front, this will be your rear. You can always insert at the rear end, which is insertion at tail, and it will be a order 1 operation. And you can always remove from the front end, which is again going to be a order 1 operation, right? So very simple implementation, and we have already covered linked list. So I will not write the code using linked list. Once again, you can either use the same class object. So in your queue class, you can say fine, I'm going to create a linked list object, linked list L, and whenever you want to enqueue, you add it to the linked list, and whenever you want to remove, you remove the first element of the linked list. Okay, so those methods can be implemented, or you can implement all those methods from scratch as well, right? So that is about implementation using a linked list. Now before we wind up this tutorial, I want to talk a little bit about the Java queue that is part of collections framework, right? So the Java queue supports 3 types of operations. So one is your insert, remove, and examine, right? So examine is like getting the front element, right? Now there are 2 variants of the methods that are provided. So in one variant, the methods throws an exception, like the variant that we have coded. Those methods throw an exception. So if you want to add something, the method is called as add instead of enqueue, right? So you will say, okay, I will create a queue object and I will call the library method add, right? If I want to remove the front element, the method is called as remove instead of dequeue. And if you want to get the front element, it is called as element, right? If the queue is empty, it will throw an exception, right? And the second set of methods, they are also same, but instead of throwing an exception, they will return a special value, maybe a boolean value, whether the operation was successful or not, right? So add and offer, they are equivalent methods. Remove and poll, they are equivalent methods. Element and peek, they are equivalent methods. Okay, so I've discussed about queue interface in my Java collections tutorial on the channel, right? So what we talked about is that in Java, queue is actually an interface, okay? And there are 3 implementations. There are 3 classes that implement this queue. So your linked list class, it implements your FIFO queue that we have just seen, that we can build a queue using a linked list. Okay. And there is a class called as array_deck. So array_deck is a class that implements another kind of queue in which you can insert and remove from both ends, right? So it is called as a doubly ended queue. So in this case, the behavior would be different. You can add at first position, you can add at last position, you can remove at first position, you can also remove at last position. So it is a doubly ended queue. It's called as deck, right? It's not DQ, it's called as deck, right? It's a different type of queue. And third type of queue, it's called as a priority queue, which we will of course discuss. It is based upon the concept of heap data structure. In this case, the elements don't maintain a FIFO ordering, but they maintain a priority ordering. So again, it's a big topic. We will discuss it separately. But if you want to see the code demo, how these different queues are, how these classes are different in behavior, check out my video on data structures, and in which I have discussed the complete collections framework as well as different implementations of queue as a part of that video. Let us start the topic by understanding what is tree data structure. So in computer science, a tree represents a hierarchical structure with a set of connected nodes, right? So for example, if you look at this diagram, this actually represents a tree, and this node, it is the starting of the tree. It is called as the root node, right? We will discuss where it can be useful. So in this structure, each node in the tree can be connected to many children. So this is a non-linear data structure. The first non-linear data structure that we are covering is a tree. So far we have talked about array, we have talked about linked list. All of those data structures were linear data structures because they were following a sequence. Here there is no sequence, here there is a hierarchy, right? So each node can be connected to many children. So 2 is connected with 7 and 5. It is connected with 2 children. So 7 and 5, they are children of 2, but must be connected to exactly one parent. So each node must have one parent. I cannot say 7 will have 2 parents. No, 7 will have only one parent, that is 2. 5 has only one parent, that is 2. 2 has only one parent, that is 7. 10 has only one parent, that is also 7, right? So except for the root node, which has no parent. So root node has no parent. Rest all the nodes, they have one parent, right? Now because of this property, there will be an interesting observation. Suppose you are creating a tree in which you are going to have n nodes. Okay, for example, I have 3 nodes here. So how many edges you will have? So except for the root node, for every node that you will have, that you will add, there will be an edge. So there will be of course n minus 1 edges in the tree, right? So in any tree that you are going to create, irrespective of is it a binary tree or not, each node that you add will add an edge in the tree except the root node. Okay, so root node does not add any edge in the tree except the root node. If there are n nodes in the tree, there would be n minus 1 edges. Okay, because root node has no parent, rest all the nodes that you add, they must be connected to a parent through an edge, right? So this is an interesting observation you can note. So in every tree there will be n nodes and there would be n minus 1 edges in the tree, right? So that is tree data structure. Now let us talk about where this data structure can be used, how it can be helpful in computer science. Okay, basically trees are used to represent or manipulate hierarchical data in applications such as file systems or directory structure, right? So all of you have worked with a file system. So what happens in a file system? You say, okay, I have my PC. In this, I have certain drives, C drive, D drive, E drive, and then inside this, I have folders, F1, F2, F3, F4, and here also I have folders. Then I have subfolders, right? Maybe I have photos here. Maybe I have some documents here, right? Now we often do operations like that. Okay, I want to move these photos from here to here, right? So what is going to happen? You're not going to copy this data. You're going to say, okay, I'll cut and paste. So if you simply want to move this photos from here to here, what do you need to do? You do not need to copy this information to some other part of the disk. You only need to change the reference, right? That okay, earlier this reference was stored by F4. Now this reference is stored by F2. Basically the links, right? The links to the folders and subfolders, they can be easily changed if the data structure is implemented using a tree, right? This is something we will discuss, right? The file system is a good example of a tree data structure, right? Multiple inheritance trees in programming. So this is used when you're using object-oriented programming concepts and you have a class C which is going to inherit from a class A. It is also going to inherit some methods from class B, right? So this is not exactly a tree, I would say, because this node, this is inheriting from two different classes. So irrespective of that fact, basically the trees are internally used by the compilers to see what methods would be part of the class that you have implemented using inheritance. Okay, then again in natural language processing, basically whenever you have a sentence, for example, I am going for a party, right? Now this sentence can be broken down into certain components. Maybe you have a verb, maybe you have a subject, maybe you have a predicate, or you have even for language parsers. Okay, so what are your parsers? Whenever you write code, it goes through a language parser so that compiler can figure out if there is any error in the code, it is having the correct syntax or not. So they again form a parse tree of that code, right? So again, it's an interesting concept that you will learn in compilers, right? So again, they are used a lot in understanding of the language. Okay, then in HTML there is a DOM tree. So whenever you open up a website, right, you see there is a HTML code, right? Inside HTML code there are a lot of tags. There is head, there is body, right? Inside body there is a paragraph, there is a div, there is an image, right? So if you look carefully, this whole document forms a DOM tree. So inside DOM tree you have head, you have body, right? Then you have certain elements, you have div, you have paragraph, here you might have image, you might have some text, right? What is happening? You want to say, okay, I want to click this particular button, and on clicking this button, this div will change its color, right? So how do you fetch elements from this huge web page? So there are methods like document.getElementById, document.getElementBy tag name. So what it is doing, it is traversing this DOM tree. It is a tree of objects. Okay, it is a tree of objects in your web browser. Again, it's behind the scenes. So it is doing some kind of search operation on this tree, and it is trying to manipulate this tree, right? For example, you scroll your web page and a new item is added from the bottom. So maybe it is adding something in the list, right? So your tree is getting modified, right? Then of course there are trees which are used in search operations like binary search tree. There are trees which are used to implement data structure like map, self-balancing trees. Okay, so they are used to perform faster searches and keeping data ordered. We will talk about BSTs in the coming class. In machine learning, there is a concept called as hierarchical clustering. So it is a part of a clustering technique, okay, where I want to group together similar items. So it comes under a part of unsupervised learning. So there also the tree data structure is used, right? So we see a lot of applications are there, and that becomes very important for us to understand the tree data structure. So in this video, we'll be talking more about binary trees in general, because that they are the most common ones that are widely used. Okay, so let us start with binary trees. So let us start by understanding what is a binary tree. So as I discussed, it is the most commonly used tree structure in which you can have at max 2 children. Okay, so it constrains the number of children for each parent to at most 2. That means a node can have 0 children. For example, in this case, the nodes D, E, F, G, they don't have any children. They are also called as leaf nodes. The nodes which don't have any children, they are called as leaf nodes. Node can also have one child, right? Or it can have 2 children, right? It cannot have more than 2 children. For example, if I draw a few structures, you have to tell me whether it is a binary tree or not. Is it a binary tree? The answer is yes. Each node has 0 child, 1 child, or 2 children, right? Okay, is this a binary tree? The answer is yes. So this node, the node C, it has 1 child. A and B, they have 2 children, and D, E, F, they don't have any children. Hence, in this case, we have 3 leaf nodes. So this is again an example of a binary tree, right? Now, what we are going to learn in this tutorial, we are going to learn about different operations. How do we create a binary tree? How does the node structure look like? How do we perform search or update operation on a binary tree? How do we display a binary tree? And there are 4 popular ways to do it: pre-order traversal, in-order traversal, post-order traversal, level order traversal. Okay, so we are going to look at all these things one by one, and we'll be starting with creation of tree first. Let's begin with that. Let us talk about creating the tree. So first of all, we need to understand the structure of the node that is going to create the tree, right? So in this tree, if you look carefully, there are so many nodes, and this box represents one particular node. Okay, that is the root node, right? So I have the root node. Now what is this root node going to contain, or any node going to contain? It is going to store 3 things. One is your data, one is the address of the left node, one is the address of the right node. Okay, in Java we also call it as the reference, right? Now suppose this object B, it is created at some memory address, let's say 250, right? This is the location of B in the heap where it is created. So A's left is going to store 250. Let's say this is created at some location 380. So A's right is going to store 380, right? A itself is created at some location, let's say 400. The root is going to store 400. Okay, so root is not a node, root is just a reference to the root node. Okay, so root variable is holding the address of the root node, right? Now B is left is referring to D, so D is created at some location, let's say 560. So here we will have 560. Now D is left and right, they are null, they don't refer to anyone because D is a leaf node, right? So D is a leaf node, E is a leaf node, F is also a leaf node, so they are left and right, they are null. Now B is a node with a single child, right? Because it does not have any right child, hence this value is also null. And here I will store the address of E, here I will store the address of F, right? So I hope you are understanding the structure of the node. So I need to implement a class called node, in which I will have 3 things. One is my integer data. Data can take any type. Just to keep it simple, I'm taking it as an integer. One will be my node left, a reference of the next left node, and node right, a reference to the right node. If the left and right node does not exist, then I will set this value to null, right? Now let us see in the code how can I implement this node class. So let us go to IntelliJ. Now I am going to implement the tree data structure. I have a class called binary tree. I have a class called binary tree test. Both are empty classes as of now. In order to build binary tree class, I need to define that what is node, right? So node will have 3 things. One is my data, one is my left, and one is my right. Apart from it, I also need to give a constructor here, that whenever a new node is constructed, what data it should take. Else, okay, data I will know, but at the time of construction of new node, I do not know what node will go into the left, what node will go into the right. So I will simply say that my data, this is equal to D, and left and right, they will be set to null by default. So whenever you're creating a new node, you do not know the left and right nodes. So these will be set later, right? Now comes the binary tree class. Now suppose we want to create a tree like this, okay, or let me take up another example in which I have numeric data. So I can say, okay, let me create a tree like this, 1 connected with 2, and then it is connected with 3, right? Let's say very simple tree, 3 nodes. Now how you will read this tree? The first thing is, how do I read this tree, right? So the first input I will get is the root node. Okay, user will enter 1. I will say fine, input is 1, let me read this. Create a node called a root node, and root node is going to point to this node, right? And in the left of this, I will again read from the user, right? The user says okay, fine, the next node is 2. So I'll say fine, I'll create a node called 2. I will attach it in the left of 1 like this. Okay. And now what is the next node I will read, right? Now it can happen that I have something in the left of 2, or I have something in the right of 2, or I have something in the right of 1, right? So I do not know. The way we are going to do it is we are going to read now what is there in the left of 2. Okay, so if the left of 2 is null, right? I will input -1. So -1 in the input will denote that there is nothing here. So I will simply set this value to be null. Right? What is right of 2? I'm again going to say it is -1. So I will set this value to null, right? Now this option is gone. I've read it. This option is gone. Now I can only read this. So I'll come back here. I'll say fine. This 2 is done. Now try to read what is there in the right of 1, right? So I'll say okay. The next input is 3. I will create a new node and I will attach it, of course, here. But before that, I will read what is in the left of 3, right? So attach part will happen a little later, right? I'll read what is in the left of 3. So this value would be -1, -1. What is there in the right of 3? Again, I say -1. Now this node is constructed, or in a way I can say this subtree has been constructed. So once it is constructed, I will return it back to the parent. So the parent is 1. It will get connected here, right? So this will become more clear once I write the code. So idea is I will of course do it for a bigger tree as well. This is little tricky, right? So what the idea is, we are going to build a tree recursively. We are going to build recursively, right? Now how we are going to build a tree recursively? Many tree operations, they are recursive in nature, right? So also, okay, fine, I will build the root node. That is 1. Then I will build the complete left subtree. In the above example, the left subtree has only one node, so it looks easy, right? I will build the complete right subtree, right? Okay, I will build the complete left subtree and I will attach it here. That is part 1. I will build the complete right subtree and then I will attach it in the right of 1, right? So we will do it for a bigger tree as well. So let us jump into the code first and try to see how this can be written. Of course, I will do a dry run and explain you how you can build a more complicated tree like this with the same code. Okay, so let us go into the binary tree class. One thing is for sure, that every tree must know what is the root node. What is the root node? So this is something that will be the property of the tree. Every tree must know what is the root node. Just like in a linked list, every linked list knows what is the head of the linked list, what is the tail of the linked list. So in case of tree, you must know that what is the root node, right? So one thing is there, I am going to read this tree. So user will input will come through the user, right? So let us see the tree construction part. So in this binary tree class, what I'm going to do, I'm going to first define the data members of the tree. So I have only one data member, that is the root of the tree, right? Now this root should be initialized. Where it should be initialized? Of course, when the tree is created. So when the tree is created, it is created when the constructor is called. So I need to define a constructor called binary tree, right? Now in this constructor, what I need to do, I need to take input from the user. So in order to take input, I will need a scanner object. I will say scanner SC, this is equal to new scanner system.in. So scanner object is used in Java to read inputs. So I have imported the scanner, right? Now the building of the tree is recursive in nature. So I will create a helper function to do it. So I can say find node, let's say create tree, and to this create tree method, I'm going to supply the scanner object so that this method will actually read from the user. Okay, so I will say fine, the root should be initialized by calling the create tree method. So create tree is a helper method getting called in the constructor that will read the tree from the command line, right? Now I'm going to pass the scanner object here so that I can use it to read data from the user, right? I don't want to create this object again and again inside this method. Okay, so I'm creating it once and that object is being circulated across all the recursive function calls that are going to happen, right? Now suppose I read something, right? I can say okay, data that I'm going to read is scanner dot next int. So I'm going to read something. All right. Now I have read something from the user. Let's say this data is 1, right? What I want to do, okay, this data can also be -1, right? I'm asking, okay, tell me what is the next data. So I will actually have a two types of case. One will be my base case. If my data is -1, then what should I return? Right? I will return a null. That means, okay, I don't want to attach any node here. That subtree is just null. So I will return null. But if it is not -1, if it is something else, basically I'm talking about the recursive case. For example, if my input is 1, what I will do, I will create a new node. I'll say fine, I will call node root. This is equal to new node, and I give it the value data, right? So if root is confusing to you, just call it as n, right? I create a node called n, which is initialized with this data. So suppose my input is 1, right? So I say, okay, n is a new node. Now what should I do? I need to read the left subtree. Basically, I need to create a left subtree here and attach it here, right? So what I can say, that in the left of n dot left should refer to a new tree, which is equal to create tree. Again, scanner will get passed. What should n dot right point to? N dot right should also refer to a new tree called create, that is returned by the create tree method. And again, the scanner is going to get passed. And then I can return n. What I'm saying, that n dot right should also point to a new tree. So left subtree, right subtree, right? This is the recursive way of constructing the tree. Now you might ask, okay, how does this method will actually work? I will show you it will actually work. Let's see how it's going to work, right? So let us take an example of a more complicated tree, or let's first start with a simple tree, right? Let's say I have a tree like this, 1, 2, 3, right? Now for this tree, what is my input going to look like? So input will be 1, then it will be 2, then it will be left and right of 2, which is -1, -1, then it will be 3, and left and right of 3, which will be -1, -1. So given this input, I actually want to create this kind of a structure. Let's see how it's going to happen, right? So I said fine, root is equal to create tree. I call this method create tree. It reads something from the user. So one integer it's going to read. So it's going to read 1. So data is not -1. Fine, I come here. Node n, this is equal to new node. So basically I have a stack call in which n is going to say n is a new node where the data is 1. Fine. Now n dot left, it makes a new call. N dot left, right? So I said fine. In the left of 1, I want to create tree. So again, create tree is called. If you come again in this function, you read something from the user. So you read 2. Fine. You said fine, I create a new node n. Okay, a new node n is created. So earlier n was here, now the new n is here, right? It's a local variable. It is created in every stack call, right? It is here. This is equal to new node where the data is 2. Fine. Now n dot left, this is equal to create tree, right? So again I make a function call, create tree, go and do something, right? So I've made a call for here, right? Now if I go and read what is the next number, it is -1. So I return null. Basically what happens, so 2's left made a call and it got a value that is null. So 2's left starts pointing to null. Now what is the next call that is going to happen? We are in this stack and I make a call that 2's right, this is equal to create tree. So I make another call here and this value is also null, right? Once these two calls are over, this one and this one, I return n. So I return this n back, where I return it to the place from where it was called. So who called it? 1 called it. 1 gets to know that my left should refer to this node. So by returning this n, this answer goes back to the previous function, and once left is now connected with. Now what is the next call we are going to make? So once left is now created, so this call is over. Once left is now created, right? Now 1 says, okay, fine, my left is created, I'm pointing to 2. I will make a call to update my right. So n dot right, this is equal to create tree, right? So this was already read. Again, a new function call is made. You read the next number, that is 3. You create a new node from line number 29. You said the new node is 3. N dot left, this is equal to create tree. So 3 is left, makes a call to create tree, which again reads the data, that is -1. So you return a null. So 3 is left, says okay, make a call. That call says I will return null. Now 3 is right, says make a call to create tree. It goes and reads the number, that is -1. Again, it returns a null, right? And then you return n. So now n is this, right? So it returns 3 back. When you return 3 back, what happens? Who called 3? So one's right made a call to create this tree. So one's right is now going to store the address of 3. So it gets connected here. From here, if you return n, where does it go? It goes back to the constructor because this made a call to create tree. Finally, root is referring to the address of 1, right? Okay, I'll hide myself so that you can see. The root is referring to this one, right? So this is how it is happening, right? So this is a small example demonstrating how this small tree is constructed using this code, right? Now I will run this code on a bigger example as well. Now some of you might not be convinced that whether this code will work for a bigger tree or not. So let us rerun this code on a bigger example. Okay, so this is the method create tree that again I am explaining with a big example. So let's say I have a tree which should be built like this. Let's say I have 1, I have 2, I have 3, I have 4, I have 5, and maybe I have 6. Now what input should I give? So first of all, I will give the root node. Okay, so input will be 1. Then I will go left. Input will be 2. Then again I will go left. The input will be 4. Then I will go left of 4, which is -1. I will go right of 4, which is also -1. Okay, then I will come back because 4 is done. I will come back. I will go in the right of 2. So right of 2 is again -1. Then I will go back. 2's left is done, 2's right is done, right? So I'll go in the right of 1. So right of 1 is 3. Then I will go in the left of 3, which is 5. I will go in the left of 5, which is -1. Right of 5, which is also -1. Then I will go back. I will go in the right of 3, which is 6. Then left of 6, right of 6. -1, -1, right? So the goal is, given this input, I want to create this tree structure in the output. From this input, I want to create this tree structure, right? Now let us see how we are going to do it. So again, I'm going to read some data. So I will read the first number, that is 1. I will say fine, data is equal to scanner.nextInt. It's not -1. So I create a new node n, right? So fine, let's create a new node n that is having data 1. Let me draw the stack as well side by side. So n is referring here, right? Now so if you want to learn what is the function that is currently executing, so that is at the top of the stack. So n is created. Now you make a call, n.left equal to create tree. So you are making a call to create something in the left of 1, right? So 1 makes a call for the left part. So again, you go call this function, you read data. So data is the next number, that is 2. Fine. You again create a new node. Now this function is paused. This function is paused here. You said fine, I'm going to create a new node and that node is 2. That node is 2. Right node is not connected. It's not connected with 1. Right? And again, you say I want to connect something in the left of 2. What will be that something? Again, you make a function called to create tree. So again, this is paused and it is expecting to build its left tree. So you again call the function create tree, you read the data. So now you're going to read 4. So you read 4. You read 4. Now 4 says, okay, I'm a new node and I will create something in my left. A force left makes a call to create tree. The force left again makes a call to create tree. And in this case, you read data. The data comes out to be -1. And if the data is -1, you return null. The force left gets to know that my value is null. Right? So a null is returned from this function, which is attached with left of 4. And then you hit this line for the first time in this function call, right? N.write this is equal to create tree. Now you say, okay, I will again call create tree. I will read this number. This number is again -1. It returns a null in the right also. 4's left and right, they are null. That means the subtree of 4 has been created. This subtree is finished. I will return n. So this is null and I will return n. So n is this. Now where this return value will go? It will go back to the place from where it was called. So who called it? 2's left called it. So 2's left is now connected with 4 and this function call is over, right? So 2's left is connected with 4, right? Now this is the point where this connection has been established, right? So 2 made a call to 4. 4 said, okay, I will build myself. I will build my left and right, which are null. And now I will return myself, right? So 2's left is over. Now what will happen? 2 will make a call on the right subtree. So 2 makes a call here, n.write this is equal to create tree. Now what do I read next? Again it is -1. So I return a null. I return a null from here. So 2's right is null. So 2's right is null. It's not referring to anything, right? So this value is null. Now 2's left is done, 2's right is done. I say return n. So return n means what is the function that is at the top? At the top I have this function. So I'm going to return this subtree, this whole subtree back to 1. So basically 1 will get to know that my left points to this n and hence the left subtree of 1 has been built. Now I will build the right subtree, right? Okay. So 1 will say, okay, fine, my left subtree has been built. This is over from the call stack. So once 1 is now connected with 2 and 4, right? This tree. 1 will say, okay, now it is my turn to call the right. So once left is done, it will execute this line. N.write this is equal to create tree. Now you again make a call. Next number you read is 3. So you create a new node called n. This is the new node. So 3 is created. And then you again make a call to the left. So you read a number, 5 is created. This is new node. Then you again make a call to the left, -1. So 5's left is null. Again you make a call on the right. So 5's left is null. Again you read -1. So 5's right is also null. Then you return n. So you return 5. So 5 gets attached in the left of 3. So 5 is returned. It gets attached in the left of 3. So 5 goes here. Right? Then again, what's going to happen? You'll say, okay, I want to build something on the right of 3. So 3's left is done. 3's right's done. So I'll again make a call. It will read 6. A new node will be created 6. Okay. And again, you say, okay, I will read the left, which is -1. I'll read the right, which is also -1. And then I will return n. When you return n, this 6 is returned back to the right of 3. So this 6 is being attached here. Right? And then you say, okay, I'm going to return n. So when you return n, you return this 3 back to 1. So once right is going to point to this subtree 3, 5 and this subtree is attached with 1. So finally when you are here, this call is over, right? So you will return n. So n will be this node and it is returned back here, root equal to create tree. This becomes the root of the tree. So root is a data member of the class and hence root of the tree gets updated. I hope you are now convinced that how this structure can be made so easily with this recursive function. Okay, with this recursive function. Okay, now this way of building the tree, it is called as pre-order, right? Pre-order means first we are building the root node, then we are building the left subtree, and then we are building the right subtree. Then we are building the right subtree, right? So right now we have built the tree using a pre-order recursive build tree function, right? Or create tree function, right? Next we will look at how we can print this tree in a similar way. Now let us talk about tree traversals. Okay, so tree traversal is a way to iterate over all the nodes of the tree, right? Now this traversal can be helpful if you want to perform operations like counting the number of nodes, searching for a given node, updating a given node, right? So in order to do all these operations, we must know how to traverse a given tree, right? So a tree has been built, a tree has been created. We want a way to go to each and every node of the tree, right? So as I discussed, if you want to do a tree traversal, there are two broad techniques, right? So tree traversal, right? So one is your recursive technique, that okay, you start with the root node, then you iterate recursively on the left tree and the right tree, right? There is a recursive way of doing it. There is a iterative way of doing it, right? So we will discuss all these ways now, right? So in recursive way, again, there are it depends upon the ordering. Okay, the way is same. We basically recursively iterate on the left and right subtrees, but based upon ordering, there are three different ways. One is called as pre-order traversal, one is called as in-order traversal, and one is called as post-order traversal. We will be looking at all of them. In iterative, there is only one way, that is called as level order traversal, right? So all of these traversals, they are going to travel all the nodes, but the order in which you will see the output, it will be different. So let us start with the pre-order traversal, given this as the tree, right? 1 2 3 4 5 6. So I will just redraw this tree. 1 2 3 4 5. Now what does this pre-order traversal says? That fine, what I will do, I will travel the root node, then I will recursively traverse the left subtree. Okay, this will be a recursive call, and I will recursively travel the right subtree, again a recursive call. Okay, it is very similar to the build function. What we are doing in the build function also, if you look carefully, we are first building the root node, and then we are recursively building the left tree, and then we are recursively building the right tree, right? So if you see in this case, the output will be very similar to the order in which you have built the tree. So if you start traversing, you will say fine, I will start with the root node, I will print 1, I will go to the left subtree. So this whole is my left subtree. So I will print the root node, that is 2, and then I will go to the left subtree. So left of 2 is 4. So I will print 4 and I will go to the left. Now left is null. So I come back. I will go to the right. Right is null. I come back. Now 4 is done. This whole tree has been printed. So I come back to 2. So I will go to the right of 2. Again it is null. I'll come back. So this whole tree has been printed. I go back. Now left of 1 has been printed. So I go to the right of 1. So I come to 3. I will print 3. I will go left. Now I'll print 5. I will go left. I'll print right of 5. Again null. So 5 is done. So this whole tree has been printed. I'll go back. So at 3 I'll say okay, let's go right. I'll print 6. I'll go left. I'll go right. Nothing happens. This whole tree has been printed. I come back. Now 3 has been printed. So root has been done. Left of 3 has been done. Right of 3 has been done. I'll return. So this whole tree has been printed. I come back. And at 1 I see 1 has been printed already, because before printing left and right I print 1. This output is called as pre-order output, in which before printing left and right nodes I print the root node, right? So 1 2 4 3 5 6. This will be the pre-order output for this tree, right? Now let us see this thing in our code as well. let's write a pre-order print method. Let's write a method called void display, and this is going to be the method that will display the tree, right? So inside this logic can be changed. I can display a tree in a pre-order way or in a level order way or any other way, right? So I'll again create one more helper method. So I will say void pre-order. So void pre-order print. Now this is a recursive function, so I have to tell at what node I'm currently at. So I will start with the some node, that is root node. Okay. So what I will do, I'll say fine. I will have a base case. What will be my base case? What is the smallest tree I can get? That the tree is null, the root is null. In that case, I don't need to print anything. I will simply return. Otherwise, what I will do, I'll print the root data and I will go on the left and the right tree. So I'll say fine sout root dot data, go and print the left subtree recursively. So pre-order print root dot left, then pre-order print root dot right. That's it. And in the display method, I can call pre-order print with the root of the. Now let's do one thing. Let us test our binary tree, because we have the create method, we have the print method. Now I can create a binary tree and try to print it. So I can say fine, I want to create a binary tree object. This is equal to new binary tree. I have defined the class. Now as soon as this constructor is called, your tree will start getting built because we call the create tree method here, right? Now I can call t.display, right? Now think of any tree that you want to make. We will give it as an input here. Sorry, I should run this file. Now this is waiting for the input, right? So let me draw a tree. Let's say tree is 1, 2, 3, 4, 5, 6, right? Now how this tree will be given as input? So you will input 1, then 2, then 4, then left of 4 minus 1, right of 4 minus 1, right of 2 minus 1, then 3, then you will input 5, left of 5, right of 5, right of 6, right of 3, that is 6, left of 6, and right of 6. Okay, the same input that I have shown you in the example also, this input is given, and now I'm saying that let me print this tree. What I'm getting, I'm printing 1, I go here, then I go to 2, fine, then I go to 4, fine, then I go to 3, I come back, I go here, yes, then I go here 5, then I go here 6. Absolutely correct, right? So if you look at, this was a pre-order build, right? And this is actually a pre-order print. So if you see, the output will be exactly same. 1, 1, 2, 2, 4, 4. Minus 1 I'm not printing. Skip, skip, skip. Then 3, 5, 3, 5. Absolutely correct. Minus 1 I'm not printing. 6, 6, right? That means my both functions are working fine. Tree is getting built correctly and tree is also getting printed correctly as well, right? Now I will show you two more variations of this print method, that is called in order print and post order print. So now let us discuss the next type of recursive printing that we call as in order print. Okay, so I hope pre-order is clear. Now we are moving to in order. So nothing is going to change, the order of printing is going to change. Okay, so earlier it was root, left subtree and right subtree. Now what we are going to do, in order means root will be printed in between. So before you print the root, you will print the left subtree. Okay, and after you print the root, you will print the right subtree. That is what the in order printing would mean. Right? Now let us dry run this logic on our code and see what do we get, right, in order. So what I want to do, so I will start from the root node. I want to print this root node, but before that I will have to print the left subtree, right? Now at the left subtree, again, if I am at 2, I have to print the left subtree. So that means I will have to print 4. So 4 will be the first output that I will get. Now I will print the root. So what is the root? The root is 2. All right. Then I will print the right subtree. So right subtree of 2 is null, right? Then I can go back to 1. So for 1, I have seen the left subtree is already printed. Then I can print the root. So I will print 1 and then I will print the right subtree. Now I am at 3, right? Before I print 3, I will have to print the left subtree. So only one node, I will print 5. Then I can print the root node, that is 3. Then I can print the right subtree, that is 6, right? This will be the output we can expect by traversing this tree in a in order fashion. So let us jump into the code and see what we will change, right? Just like the pre-order print method, what I will do, I will create one more method called as in order print. So in this case, the root will be printed in the middle, and this call will be now in order print root dot left, and this will be now in order print root dot right. Okay, now in the display method, instead of calling pre-order print, maybe let's just call in order print this time. I want to display the tree using in order print. I will pass the root of the tree as a parameter here, right? So let us give the input for this tree and see what output we get. We are getting 421,536. Is it the expected output? 421,536. The answer is yes, right? Now you might be interested in doing a call stack analysis of this, right? So let us see how we can do the call stack analysis as well, right? So in the beginning, what is happening? Let me also copy paste the code. This is the code, right? Let us do the call stack analysis. This is the method that we are calling, right? So the call stack is empty, so we called in order print where the root node is 1. So I say root is 1, but I'm not going to print it. So root is not null. I will just call on the left. So I make a call here, right? So that means root is now 2. I'm at this node, but I'm not going to print it. Again, I make a call on the left. That means root is 4. Okay, I'm not going to print it because root is not null. Again, I make a call on the left. When you make a call on the left of 4, you actually come here. This is null. So if this is null, you return. Okay, so you return. Then you make a call. Then you print the root data. So that means you print 4. This is the top of the stack, and this is the root that we are talking about. So you will print 4. Then what's going to happen? You will say, okay, I'll go right. So right is null. Again, you make a call to null and you return. So you come back. So again, you are here. Now for 4, you have done all the 3 things. Left is done, root is done, right is done. So you return. So from here, you go back, and this is gone from the stack, right? Now what is the new top, right? How do we come back to 2? This is how we come back to the 2. So the new top is this. Now this is the root node that is currently we are talking about. Have I printed the left? Yes. Have I printed root dot data? No. I will print it now. Have I printed the right? No. So I make a call on the right of 2, that is null, and I again return. Then this is done. So I come back. Now what is the top node? The top node is 1. So have I printed left? Yes. Have I printed root dot data? No. I will print 1 and I will make a call on the right. So I make a call on this tree, right? So again, you do a similar process. You come at 3, right? So root is 3. Then you make a call on the left. That is root is 5. So 5's left is null. So you print 5. 5's right is null. You come back. So 5 is done. Then you go back. The new top is now 3, right? It was 5. Now it is 3. So 3 says, okay, my left is done. I will print myself and then I will go right. So root will be 6. So you come here, right? So you went here, then you came here. 6. Now root is 6. Left and right, they are null. So 6 will get printed. Right is null, right? And then 6 will be popped off, right? Then, so for 3, right is also done. So this call is over, right? And you come back at 1. So for one, left is done, root is done, right is done. So this call is also over, right? Finally, the call stack will be empty, and this is the output that you will get, right? So I hope you have understood the in order traversal. Now make a bigger tree and try to generate the output for that particular tree, right? And next I will discuss post order traversal. Let us talk about post order print. So as the name suggests, post means the word after, okay? In this case, what we do, we print root in the last. So first we print the left subtree, then we print the right subtree recursively, of course, and after then we print the root, right? So if this is the tree, once again, what I will do, I start with 1, but I have to first go in the left subtree, then I have to go in the right subtree and then print 1, right? So at 2, I again have to print left subtree. That means I will print 4, right? Then I will print the right subtree. So right of true is null. Then I will print 2. So I will print 2. Right? Then at 1, I have to print left, which is done. I have to print right subtree and then I will print root. So at 3, I will say, okay, print left subtree, which is 5. Then print the right subtree, which is 6. Then print the root, that is 3. Now for 1, left subtree is done, right subtree is done. Then I can print the root, that is 1, right? So this is what the post order output would look like, right? You might be asking, why do we need so many traversals? Okay, for example, what happens in certain problems is, in certain problems you are expecting that you are expecting output from the left and right subtree. For example, given a tree, I want to calculate the height of the tree, right? For example, I want to calculate what is the height of this tree, right? So in order to calculate height, what you will need? You will need to know that what is the height of the left subtree. Let's say this height is 3. What is the height of the right subtree? This height is 2. Then can you say recursively at this root node, the height is nothing but it is the maximum of left and right. Okay, maximum of the answer that you're getting from left, comma right, and one more than that. So can I say the height will be 4? What is this? This is the answer from the left subtree. What is this? This is the answer from right subtree. So what I'm trying to claim is, in order to build the answer at the root node, you need the answers for the left subtree and right subtree, and hence in problems like these, you would of course need a post order traversal, right? So that is the idea. When you need answer from the child subtrees to calculate the answer at the root node, you will definitely need post order traversal there, right? So now let us write the code and then we will do the dry run of that code, right? So writing code is very easy. So I'm in this class. So if root is null, I will return, right? Then what I will do, I'll go on the left, post order root dot left. Then I can say post order print root dot right, and then I will print the root node. So s out root dot data, right? Now let us go and call post order print in our display method, right? So I can just pass the root here. So t dot display, it's calling the post order print method. Now for the same input, let's copy this input and we will see what output do we really get. Now we have given the input. I'm getting 425631. Is it the same output as we have got? 425631, absolutely yes. Now let us do a quick call stack analysis of this method as well. So I'll copy the code, I'll put it here, and let us do a quick call stack analysis. Let's say this is my call stack. In the beginning, I give 1 as my root node. The root is 1. Then I say, okay, make a call on the left. So my root is 2. I make a call here. Now code is paused. Right call will happen later. Again, at 2, I make a call on the left. I come here. Root is 4. A 4 makes a call on the left. So left is null. I return. Then 4 makes a call on the right. Right is null. Again, I make a call and return. Now I can say print root dot data. I will print root dot data. This is the top of my stack. I will print 4, right? Then if 4 is gone from the stack, what is the new top? The new top is 2, right? That means I am in this function. I am at 2. So I'm printed the left. I make a call on the right. So 2 says, okay, go and print the right. Right subtree is null. I return. Then what happens? Left and right, they are done. I will print root dot data. That means I will print 2. Right? Now 2 is also gone. We are done. So 1 is at the top of the stack. Now at 1, I said, okay, go left, which is already done. Left is done. Go right. I come here. Right? So now 1 makes a call to 3. Right? Now 3 says, okay, go left. So 3 makes a call to 5. R5 goes here. And R5 says, okay, go left, which is null, go right, which is null, and hence you print 5. So you will get 5 as the next output. Right? Now once 5 is gone, you're back again at 3. 3 says, okay, my left is done. This is done. I will go right. So I go to root node, that is 6. Right? The root becomes 6 in this call. So this is the top. 6 says go left, null, go right, null, and hence you will print 6. Right? And then 6 is also gone from the call stack. Then what happens? You are at 3. 3 says, okay, my left is done, right is done. I will print root dot data. So I will print 3. I will get print 3. So 3 is also gone from the stack. And now top is at 1. So for 1, left is done, right is done, and hence you will print the root dot data, that is 1. Right? So this is the output of the post order print. I hope you have understood post order traversal. Next, we are going to discuss the level order traversal. Okay, let us jump into the iterative traversal, which is also known as level order traversal. Okay, so that means we won't be using recursion. We would be using some kind of iteration to iterate on the tree. Okay, some kind of loop. Right? So let us take this example of tree once again. And idea is, instead of going in a depth first manner, okay, so in all the traversals that we have done so far, what is happening? We are starting from the root node, we are going here, then we are going here. So all these traversals, they are depth first traversals. That means you first go deeper into the tree, and then that's how you iterate. Okay, so your pre-order, post order, and in order, they are depth first traversal, right? But now the traversal that we are going to do now, it will be a breadth first traversal. That means if I have a tree like this, I will be going across the breadth of each level. This level, this level, this level, right? That means I can expect an output that is 1, 2, 3, and 4, 5, 6, right? So level order traversal. So this is my level 1, then I am printing level 2, and then I am printing level 3. Okay, what is a level? All the nodes which are at same distance from root node. So level 1, all the nodes are only one node. It is at distance 0 from the root node, or let's say level 0. Level 1, all the nodes are distance 1 from the root node, and this is my level 2. All the nodes are at distance 2 from the root node. Okay, so this is also known as breadth first traversal, right? Breadth first traversal, right? Now let us see how we can achieve this kind of a traversal, right? So let's draw this tree once again. Now if you look carefully, if you start doing any traversal, that is a recursive traversal, right? So from 1 you come to 2, right? And at 2 you do not have a direct way of going to 3, right? So that means with recursion, it will be very difficult for us from 2 to go directly to 3, right? And if we go to 3, we don't know a way to come to 4, right? So we cannot go back and forth, right? So how this is achieved? This is achieved by using a concept of a queue data structure. Okay, so what we will do, we will create a queue. The queue, you know, it is a P4 data structure, first in, first out. So in the beginning, I will push this node in the queue. Fine, right? And then I will say, okay, like queue dot push root. Now I will pop one node from the queue. So I will pop this node and I will push the children of this node into the queue. So I will print it. Output will be 1. This is popped. And what are the children of 1? Children of 1 are 2 and 3, right? Now, how do I know the children? Because I'm not going to store an integer value here. I'm going to store the reference of this node, right? So I'm going to say, okay, this root is, the address of this node is stored here. So if you know the address, you also know the child values, right? So you know the children are root dot left, root dot right. I will push the reference of 2 and 3 in the queue, right? Next, I will again pop one node. I'll say, okay, let's remove 2. Let us print it and let us push the children of 2 in the queue. So 2 has only one child. So 4 will be pushed into the queue, right? Again, repeat this process. Pop one node. So now you're going to see that, okay, 1 is done, 2 is done. The next node is coming is 3, right? So I will pop it. I will print it. And I will push the children of this 3, okay, into the queue. So I will push 5, 6. So you look carefully. When the second level or the first level is popped, the next level is already in the queue, right? The next level is already in the queue. Let's say I have some more nodes. Let's say I have 7, 8, and 9, right? So let us just extend this example a little bit. Now I will pop 4. I will print 4. This will be removed. 4 does not have any children, so nothing will be pushed. Next, I will pop 5. I will print 5. And I will push the children of 5 into the queue. So I will push 7 and 8 into the queue, right? Next, I will pop 6. I will print 6. And I will push the children of 6 into the queue. So 9 will get into the queue. Next, I will pop 7. I will print 7. And no children, so nothing will happen. Next, I will pop 8, print 8, no children, nothing will happen. I will pop 9, print 9, and the queue is empty, right? So no children, so queue is now empty. This will be my output of level order traversal, right? I hope you are convinced that this is the correct output for this tree, right? Now let us look at this implementation in our code as well. Let us discuss the implementation of level order print. So I'm going to create a method called as void level order print. And first of all, I will need a queue object, right? And I also need to pass the root here. So I'll say, okay, fine. I'll need a queue of node called queue. This is equal to new linked list. So in Java, queue is an interface and linked list is a class that implements the methods of the queue, right? We need to import this from the util package. Okay, so linked list is imported, queue interface is also imported. So to start with, you can say, okay, queue dot offer, that is your add operation, right? And I can offer root inside the queue. That means I can add queue, right? Now I said you will do some work while the queue is not empty. So while the queue is not empty, what you will do? You will pop out something. You will say, okay, give me the node which is at the front of the queue. So node f, this is equal to queue dot poll, right? So this removes the first node. Like we have seen in the diagram, we are always removing the node at the front of the queue, right? So this is going to remove it and return it, right? Now I can print the data of this node. So I can say sout f dot data. And now I can check if the left and the right child, if they are not null, I can push them into the queue. If f dot left is not null, I will say q dot push q dot offer f dot left. And if the right child is not null, or if the right child is not null, I can say q dot offer f dot right. So in this way, queue is getting filled using these if conditions, and it is getting empty from the front using this whole operation, right? That's all. That is the code. And now I can just run this code in the display method, or Here I can say t dot level order print. Okay, root. So it's better to call it internally, because root, I don't want to access it outside. So okay, I'll just call it from the display method because we are testing the functionality. So I can say level order print. So here I can just call t dot display. So now my tree will be displayed in a level order fashion. Let's see what output do we get. So for the given tree, I'm getting 1, 2, 3, 4, 5, 6, which is correct. And if you look carefully here, for this tree, I'm getting 1, 2, 3, 4, 5, 6. Yeah, this is the tree actually. So I'm getting the correct output, which is this. So I hope you understand the level order traversal and how it is achieved using the queue data structure. The code is very simple, and you can also do a dry run of this code at your own. Let us start discussing binary search tree data structure. So right now we have learned about binary trees, which we said it is a tree in which every node can have at max 2 children. A binary search tree is a special kind of binary tree which is optimized for the search operation. Okay, so that is why the name called binary search tree. In short, we also call it as BST. So BST is a special kind of binary tree with the following properties. The first property is the value of all the nodes in the left subtree of a given node should be less than the value of given node. For example, if this is the root node and it has certain value, for example, this value is 8, then all the nodes which are in the left subtree, they must be less than 8. Okay, and all the nodes which are in the right, they must be greater than 8. So this is the BST property, right? Now how this makes searching easy, for example, you are searching for 5, you don't need to have to traverse the entire tree. You will have to say, okay, I will go into the left subtree, right? Now this property that we are talking about, that nodes in the left subtree would be smaller, nodes in the right subtree would be greater, it is not just applicable for the root node, but it is applicable for all the nodes of the tree. Okay, so we will see an example. How do we construct such a tree where every node follows the BST property? So this we call as the BST property, right? Or the BST properties. So this is what makes this tree very special and efficient as well, right? Now suppose we are given this data and we want to create a binary search tree from it, right? Now how we will create it, let us discuss. So first of all, we are getting 8, right? So 8 will be the root node because my tree is currently null. So 8 becomes the root node, right? Now next element that I'm getting is 3, right? Now 3, I know it is less than 8, so it will go in the left subtree of 8. So 3 will go here. Next I'm getting 10. So 10, I know it is greater than 8, so it will go into the right of it. It will get connected here, right? Now I want to insert 1. So again, I do not know where it will go. So I will start from the root node. So 1 is less than 8, I will go left. 1 is less than 3, so I will again go left. So I will insert 1 here. Then I get 6. 6 is less than 8, I go here. Now 6, if you compare with respect to 3, it is greater, so it will go here. 6 gets inserted here. Then we have 14. So 14 is greater than 8, I go here. It is greater than 10, so I go here. So 14 will get inserted here. Then I have 4. 4 is less than 8, I go here. It is greater than 3, I go here. But it is now less than 6. So I have to travel the branches accordingly. So that means 4 will get inserted here. Then I have 13. So 13 is greater than 8, go here. 13 is greater than 10, go here. 13 is less than 14, so you will go here. And finally I have 7, right? So 7, if I start with respect to root node, less than 8, go here, greater than 3, go here, greater than 6, go here. 7 will get inserted here, right? Now this is how the binary search tree is constructed. Okay, so we have discussed how do we create a binary search tree. So we have to insert all the nodes one by one, right? Now, how much time it will take to insert one node, right? So it will depend upon what is the height of the tree. Now, suppose if this tree height is h and I want to insert a node. So in the worst case, I have to travel one branch. For example, if I want to insert, let's say 20, right? Or let's say I want to insert 12, right? So what I have to do, I have to start with 8, go here. It is greater than 10, I have to go here. It is less than 14, I have to go here. And it is again less than 13, so I have to go here and insert. So this is how 12 will be inserted in the tree, right? Now let us talk about searching. Okay, how do I search for a given node? Now for example, I want to search for, let's say, 7, right? Where is 7 present, or if it is present or not? So I just want to output yes or no whether this is present or not. So I start with 8. If 7 is present, it must be on the left, so I go here. At 3, if 7 is present, it must be on the right, so I go here. At 6, if 7 is present, it must be on the right, so I go here. Now I hit a node which is actually 7, right? So that means if I'm again performing an operation like search, I will do it in order of h time, where height in the worst case can be n also. For example, if you say, okay, I want to insert these nodes into the binary search tree, so it will form a skewed tree like this, 1 2 3 4, right? So a height can become n also, so that is why I'm not saying order of n, or I'm not saying order of log n, right? So the height in the worst case will be can become order of n, right? And in the best case, if your tree is a fully completely balanced tree like this, okay, in the best case, if a tree is like this, the minimum height it will have would be log of n, right? So height will be greater than log n, greater than equal to log n, and it will be less than equal to n. So height lies in this range, right? So accordingly, the creation and the searching time, okay, not about creation but inserting one node, okay, so inserting a single node will take order of h time, where h is the height of the tree. Searching for a given node will take order of h time, where h is again the height of the tree. I hope you understood the fundamental concept behind binary search tree, and now let us dive into the implementation of it. So let us start by building a binary search tree class. Okay, so in this class, what this class should know that what is the root of this tree. So I can say, okay, private node root. So I have a root node which is a private member, because I don't want a outside world to access this root directly, right? Now I want to initialize this root node by creating a tree, right? So I can say, okay, there is a binary search tree constructor, and in this case I can say this dot root, this is equal to some build tree method that I am going to create, right? Now let's see what is this build tree method going to be. So I can say, okay, public void or public node build tree. So build tree is going to read data from the user, and it's going to insert all the nodes into the tree one by one. Okay, so in the example that we took, we said, okay, we will take these nodes and we will insert them into the tree one by one. So if you take 8, you insert it into the tree, then you took 3, you inserted into the tree, then you took 10, you inserted into the tree, then you took 1, and so on, right? So what we have to do, we have to insert nodes into the tree one by one. So we will also build a insert method that will do the work for us, right? Now how do I read this data? So I will read it till I hit -1, right? So this is one way. Or you can ask how many nodes you want to insert, and then you can read n numbers. Both are fine, right? So I can do this as well, or I can say, okay, I will read n followed by n integers, right? So right now I'm doing it this way, that okay, I will read everything until I hit -1. So I can say, okay, fine, scanner equals new scanner, and now I'm going to read data, right? So I can say int data, this is equal to scanner dot next int. So while this data is not -1, what I will do, I'll insert nodes into the tree. So while data is not -1, I can say, okay, this dot root is given by the insert function, and what I need to insert, so I will say, okay, take root and take this data, insert it into the tree. Okay, so for example, if I want to insert 6, so I'll say, okay, fine, take this root node, take this number 6 and go and insert 6 into this tree. So maybe 6 will go here, right? Something like this I'm going to do. So I will give data as well, right? And finally I can say, okay, build tree is going to return root, right? That is fine. Or you can do it like this as well. Node root, which is initially null. You can say it like this as well. So I'm finally returning the root node, which will get updated here. And this root is the data member root that is here, right? Now let us write the insert method that is going to insert data into this tree. So this is just like a wrapper function, okay? So the actual insertion will be done by the insert method. So I want to say, okay, node insert. I'm going to get root node. Now this root node is in the beginning it is this root node, but it's going to be a recursive function. So this root node is going to change, right? And the key that I want to insert, right? Okay, so I'm already getting the key. Now can you think how this insertion will work? Okay, so let us take an example of beginning. What is going to happen in the starting? So in the starting you are going to insert 8. So root is null. So here the root is null and the data that you're getting is 8. So if the root is null, can I say inserting 8 is very easy? Just create a new node and return it. So your root will get updated. So you can say, okay, root is equal to insert. You give the current root node. Maybe you can give this root node, that is fine. And you can give the data, right? So what is going to happen? You're going to say, fine, I'm inserting something into a null tree. So you can say if root is null, that means you can insert it directly. You can create that node and you can return it. So you can say return new node and the data is equal to key. So this will also act as a base case, and it will also help us in the beginning to create the actual root node of the tree, right? But if this is not true, for example, I've inserted 8 now, so root is pointing here, right? And suppose I want to insert 3. Now this 3 is given input to this tree, right? So I will compare, is 3 less than 8? So I will compare if root dot data, sorry, if key is less than root dot data, then what should I do? I should go and insert in the left subtree, right? So I can say, okay, root dot left. Now this will point to a new subtree in which 3 has been inserted. So root dot left, this is equal to insert method again, where in the root of left, and the key will remain key, right? Now this is a very important step you have to see, right? So what I'm saying is that go and insert 3 in the left subtree of 8. So if you hit this, what will happen? So your root will come here. Again, you will observe that root is null. So you will return new node of that key. So you will say, okay, fine, I'm going to create a new node 3 and I'm going to return it. So where you're going to return it? You're going to return it from here. That means it will get updated in the left of 8. So this is how 3 will get connected in the left of 8. Okay, let me finish the code. I will do a complete dry run. Okay, and the complementary case, okay, we can make it less than equal to. So if duplicate elements are present, all of them, they will go into the left subtree. Else this is not the case. Else root dot right, this is equal to insert root dot right comma key. That means if it is greater, go and insert that node into the right subtree and update the root dot right. Okay, and once it is done, what I have to say? I have to say return root. Right now, this is important because every function is expecting that address of a tree or a subtree or a root node will be returned. So we are going to return the current root node. Now let us take an example of, let's say, 8, 3, 10, 1, 6. And let us try to insert some of these numbers into our tree. Okay, so I'll just take this example and I will dry run this function. So what is happening? Oh, okay, I think I missed out one thing here. I will have to read the data again also. So I have to say data equal to scanner.nextInt. So So I'm inserting a number, okay, and then I'm reading the next number, right? So first of all, I will read 8, fine. So if for 8 root is null, the root will point to 8. So I will say, okay, return new node of key. So insert call is over. Next time I'm reading this number 3 using this line, data is equal to scanner.nextInt, data is not -1, so I say, okay, root is equal to insert into this tree, right? So root is now 8 and I'm saying insert 3. So if you want to insert 3, what will happen? The base case is not true. You come here. If key is less than equal to root data, yes, root dot left, this is equal to insert root dot left comma key, right? So I will draw this call stack as well. So I have 8. So 8 makes a call on the left. So left is null. So you hit the base case. You say return new node of key, right? So it returns a new node 3. So this function returns a new node 3. Now where is this 3 getting updated? So 3 is getting updated in the root dot left. So it is getting connected in the left of 8. So this is how it is getting connected, right? So this is over. And now from this function call, you return root. So you basically return the address of 8 back into the build tree function, okay? Now you want to insert 10. Okay, you got 10. Again, you compare 10 with respect to 8, right? So what happens? You call the insert function, take this tree, insert 8. Now root 8 is not null, 10 is not less than root. So you come into the else block. You say root dot write, this is equal to insert root dot write comma key. Now root dot write, this is null. That means you again hit the base case. So this base case returns a new node that is 10. Now where is this node returned? It is returned to the previous function, which is this. And where it is getting updated? So 10 is getting updated in the right of 8. So you get 10 here. And this base case is over. So 8 is connected with 10 and you return root. So what is the root node? This 8 is the root node. So you return this address back into the main, right? Now comes the next node. You read 1 and you want to insert 1 into this particular tree. So now this is the tree 8, 3 and 10, right? Now you want to insert 1 here. So 1 is less than 8, fine. So 8 says go and insert 1 in my left subtree. 8 makes a call here, right? 8 makes a call here. Now when you reach 3, so your root is 3, right? And you again compare, is 1 less than equal to 3? The answer is yes. So you again make a call root dot left, this is equal to insert root dot left. So you make a call here. So you make a call in the left of 3. Now this value is null. So you return a new node that is 1. This 1 is updated in the left of 3. So you return 1. 1 gets attached in the left of 3 and then you say return root. Effectively now you're returning the address of 3 back to 8. Now 8's left is again, earlier it was referring to 3, now again it is referring to 3, but now with 3 1 is also attached. Okay, so that is what I was saying, that 1 gets inserted in the left subtree of 8, right? So this is again updated. So earlier 8 was storing the address of 3, now again it is storing the address of 3. And again you say, okay, from this function I'm going to return root. So you are going to return the address of 8 back into the build tree method. Okay, let us do one more insertion. Let's say I want to insert 6. So 6 is less than 8. So this is now the tree 8, 3, 1 and 10. Right? Now 6 is less than 8. I go here. 6 is greater than 3. I go here. So again what happens? This is null. So you return a new node. So you create 6. So that address is attached in the right of 3. And from 3 you say return root. So 3 gives its address back to 8 and 8 gives its address back to main, right? So by keep on doing this, you will be able to insert all the nodes until you hit -1 into this tree, right? So I hope you have understood the insert method. The insert method is going to take order of h time to insert one node into the tree, right? Now let us try run this code and see if it works. Okay, I want to execute this code. Dry run we have already done. So I have a binary search tree test class. I've created a main method. So I have to create a BST object here. So I have to say binary search tree BST. This is equal to new binary search tree. This will automatically trigger the build tree method, and it will start reading input from the user. Okay, but if I want to display this tree, maybe I have to do some kind of traversal as well. So I go into the binary search tree class, and here we can write a method for doing the in order print of this tree, right? So void in order, I can say node root, and here I can say, okay, if root is null, do nothing. Otherwise, do a in order print on the left subtree, print the root data, and do a in order print on the root dot right. So let's call this as in order print, in order print. Okay, let me create a display method from where I will call the in order print method. So I can say, okay, in order print, and here I give root, or you can say this dot root. Both are okay. This dot root means we are talking about the data member root. Okay, so display method is done. So I am going to create the BST, and I can say BST dot display. Let us execute this code. The build is complete. It is waiting for us to give input. So let us give the input, and here we got some output. So this is the output of in order traversal of this tree, and this output looks sorted. Let us see what output we should ideally get. So let us quickly create a tree with these numbers. So I have 8, I have 3, I have 10, I have 1, I have 6, I have 14, I have 4. So 4 will go here. Then I have 13. So 13 will go here. Then I have 7. So 7 will go here. That's it, right? Now in order traversal, that means before printing root node, you will print left and then you will print right. So now we know all the nodes in the left subtree are smaller, all the nodes here are greater, right? And if you do it for every node, you will observe your output will be sorted. So at 3, if I say okay, go left, that means I will print 1. Then you will print root, that is 3. Then you will print the right subtree. So for 6, you will print left, root, right. So you will print 4, 6, 7. And then you go back here. For 8, left subtree has been printed. So you print root and then you print right. So you come here. At 10, you say okay, left, which is null, then root, which is 10, then the right subtree. So again here, left, root, right. So again you will print 13 and 14. Right? So this is the expected output of in order traversal. Let us verify if it is correct. So we are getting 1, 3, 4, 6, 7, 8, 10, 13, 14, which is absolutely correct. So that means our build tree and the insert methods, they are working perfectly fine, right? So I hope you have understood the insertion in a binary search tree. So now let us talk about the search operation in a binary search tree. So given this BST, I want to search for a particular node. For example, let's say I'm given that I'm searching for a key that is 2. How do I search for 2, right? So I will start from the root node. I will compare 8 with 2. So I will say, okay, 2 is less than 8. So I will go here. I will go left. 2 is also less than 3. So I will go here. And here I compare if 2 with 1. So what happens? If 2 is present, it must be on the right of 1. So I go here. So I go in the right of 1. But as I reach here, I see that I am hitting a null value. That means 2 is not present, right? So one of our case would be that if I hit a node that is null, right? That means the given key is not present. So I can simply return false. That will be one kind of a base case, right? Now suppose I am not searching for 2, but I am searching for, let's say, 7, right? So 7 is present here. So let's see how we can do it. Now if I compare 7 with 8, I know it is less than 8, so I will go left. If I come to 3, 7 is greater than 3, so I will come towards right. And at 6, 7 is greater than 6, so I will again come towards right. So now I'm hitting a node where my root data matches with key. So what should I return? Of course, I should return true. So if root data matches with my key, I would be returning true from the method, right? Now let us talk about a recursive case. If we are searching recursively, so what exactly we are doing, right? So we are saying that fine, I'm going to compare root node with the given key. Let's say the key is 7. So I'm comparing 8 with 7, right? Now if the key is not matching, so what I'm saying that, okay, if the key is lesser, I will search in the left subtree. Whatever is the answer of left subtree, I will return that answer. Now suppose the left subtree says true, the key is found, I will return true. But if the left subtree says false, I will go and search. I will not go and search in the right subtree. Why? Because I am already checking whether I should go left or I should go right, right? Because if the key is less than or equal to, it will be present in the left subtree. If the key is greater than or equal to root node, it will be present in the right subtree. Let us take an example of 13, right? So now 13 is greater. So I will not make a call in the left subtree. I will make a call in the right subtree. So I say, okay, go and search in this tree. Now at 10, 13 is greater. What I do, I say, okay, go and search in the right subtree. At 14, 13 is less than 14. So what do? I say, go and search in the left subtree. Now as I reach this node, I say, okay, this matches my key. So what I will do, I will return true. This 14 will also return true. This 10 will also return true. And this 8 will also return true. So this is how true will be propagated back, right? So what I have to do, if root data is let's say root data is greater than equal to key, right? So that means key is less than equal to root data. That means I will return the answer of the search method by calling the left subtree. So I will say, okay, return whatever has been returned by the left subtree for that key. So root dot left comma key, right? Otherwise I'll say return whatever has been returned by the search method by calling it on the right tree. So root dot right comma key, right? So this will be my search method. Now let us quickly write this method in our code as well, and then we will see whether this works correctly or not. It should work, right? So this, I'm writing it recursively. You can also write it iteratively, right? So the only thing that you need to do is you need to travel at max from the root node to one of the leaf nodes. In the worst case, that means the complexity of this method will be order of h, where h can lie between n and log n, right? So in the best case scenario, when the tree is perfectly balanced, your height will be log n. In the worst case, if all the nodes are on one side, that is called as a skewed tree, your complexity for search operation will be order of n. Now it is much better than binary tree, because in binary tree you have to search for across all the nodes, but here we know that we have to move in one direction, either left or right, but not both. Okay, let us quickly code it up and see. So let us write a method called search. So it will have a boolean return type. So I can say boolean search. I'm going to get the root node, and I'm also going to get the key that I'm searching for. Okay, let's say this is some search function, right? So it's a recursive function, so I have to write a wrapper function as well. So I can say boolean search, where I'm just getting the key. So it will return whatever has been returned by the search function, and here I will pass the root node and the key. Now let us see how this can be done. So I discussed there will be two base case. So you can stop if your root is null, that means the key is not present. So I can say return false in that case. But if your root matches with the key, you can return true in that case. Okay, otherwise I have to compare. Okay, so I have to say if root dot data is greater than equal to key, or you can say key is less than equal to root data, then you have to call the search function on the left and you have to return whatever that function is returning. So you return the output of the left subtree. So search in the left subtree, that is root.left comma key, else you can return output of the right subtree. So root.right comma right. So this will be your search function. Recursive function is the search function. So this looks good. Now let us test our method. So here I can say, okay, sout t dot search. Let's say I'm going to search for 4. Sorry, this is not the correct file. I have to do it in binary search tree. So bst dot search, I can say let's just search for 4, and bst dot search for, let's say, 41, right? So I will s out the output, and same here. So this looks good to go, and let us run our code. Now let us give some elements, let's say 10, 20, 30, 41, 3, 5, 6, 8, 9, minus 1, right? So this creates a tree, and for the value 4, I'm getting an answer false, that 4 is not present, and for other values, I'm getting the tree is the 41 is present. The 41 is present here, right? And you can see in order display is looking sorted, and 4 is not present in this, and 41 is present. Okay, so this is how the search method is working. I hope you understood the search method really well. Next we will move on to deletion. Let us discuss deletion in a case of a binary search tree. So deletion means that, okay, I've given a particular node and I want to remove that node. Okay, for example, someone might say that, okay, let us delete 13, or let us delete 3, or let us delete 8, right? So if you observe closely, there are three kinds of nodes. Okay, so there are nodes which have no children, also called as leaf nodes. So there are nodes with 0 children. Deleting them is very easy. There are also nodes which have one child. Deleting them is slightly more difficult. And there are nodes which have two children. They are even more tricky to delete. Okay, for example, node like 8. If I want to delete this node, then how would my tree structure would look like? So we have to discuss all these scenarios now, right? So let us start with scenario 1, and let me create a copy of this tree as well so that I can use it, right? Now suppose I want to delete a node like 4, or I want to delete 7, or I want to delete 13. So deleting it is very easy. So suppose, let's say I want to delete 7, right? So that is my case 1, case number 1. So in that case, what I need to do? First, I need to search for 7. Where is this 7 located? Right. So I need to reach that node. Right? So I start from 8. I say, okay, 7 must be on the left. So I go to 3. So 3 says 7 must be on the right. So I go here. Now 6 says 7 must be on uh, right. So I go here. Right. Now if I reach this node, what should I do? I would say, okay, fine. This is the node that I want to delete. I will somehow delete this node, and I will return a value null to the parent. So basically what I will do in every call, I will try to change the tree. I will say, okay, in the right of 6, I will attach a null value, and this node is now referenced by no one. So that means this will be automatically garbage collected. Okay, so garbage collector will come and it will get garbage collected because no one is referring to this node. Okay, so garbage collection mechanism will clear out the memory occupied with by this node. Okay, so what I need to do is I need to reach this node, and if this matches with the data that I'm finding out, I have to return delete null. Okay, so when I return null value, that will get updated in the right of 6. Okay, so I will also update. So that means the return type of the function will be of the type node. It will not be a void function. There will be a function, and I say okay fine, root dot write, this is equal to some delete node, and delete node returns a null value which gets attached in the right of 6. Okay, so this function is delete node, something like this I will be doing. So just to give you an idea how it's going to work, so basically we are going to update the right reference in the parent. That is case number 1. This is how it will be deleted. Now let us write the code and see case number 1, and then we will discuss case number 2 and case number 3. So I am in the file called binary search tree.java, which we have written. Now we are going to define a method called as node remove, and here we are going to accept the current root node and the key that we want to delete, right? So of course there will be some base cases which we will see, okay, and there will be some recursive cases as well, right? So one thing that I told you, that first we have to search for the node. Okay, now 3 possibilities can happen. So if you are at 8 and that the node that you are deleting is also 8, then you can do work there. But if the data is lesser than 8, you have to go left. If the data is greater than 8, then you have to go right. So first let us do the searching part. So if the key that you want to remove is less than root.data, in that case you do not need to do anything at the current root node. What you need to do is make a recursive call in the left subtree. For example, this is 8 and I want to delete something which is 5. Now 5 is not present here. So what I will say, okay, I'll say okay, go and remove 5 from the left subtree. The remove function will go and remove 5 from the left subtree. So you say root.left and key. Go into this tree and remove it. Now it is possible 5 might be present here, or 5 might be present here, or 5 might be present here. We do not know, right? So whatever it is, after removing 5, whatever is the new root of the tree, that will be given back to me. So I will say okay, 8.left, this is equal to remove. So I can say root.left should be updated by the reference of the new left subtree that I am going to get. Now it is possible that here the node was 6 and nothing changed. Still I will get the address of 6 back here, right? So that is something we have to do. So root.left, this is equal to remove. So I make a call in the left subtree to remove it. So this is a recursive case, right? Else it is also possible that key is greater than root data. That means I have to do the same thing but in the right subtree. For example, I want to remove 10. I can say okay, go and remove 10 from the right subtree, and whatever is the new tree, give the reference back to me. I can say root.write, this is equal to remove root.write comma key, right? Else, that means this is the node where I have to do the actual deletion. That means it is the case of equality, right? So this is the node to be deleted. Now I said there can be 3 cases. Case number 1, that I have a node with no children. In that case it is pretty easy. That for example, if you are talking about a node like this, a node like 7, right? So if you have already traversed till this node and you want to delete this node, it matches 7. So what I can say, I can simply say return null, right? I can simply say return null. So I can say if root.data matches key, I can say return null. Now this null will be attached in the back in the parent, right? So if it was present in the left, so left value of the parent will become null. For example, 6 and 7, right? So 6 made a call on the right that okay, delete the 7 node from this subtree. Now 7 is equal to 7, so I'm saying return null, right? This null is returned, and root.write called the remove function which returned null. So this remove function returned null. So eventually what will happen, the right of 6 will start referring to null, and from 6 we will return the address of this subtree, which is nothing but this node itself, right? So finally what we have to return, we have to return root also, right? Like if we are not returning null, that means if we are returning from some other node, we have to return the same root that we were getting as input. So 6 will return its address. So 7 returns a null, okay, which gets attached here. 6 returns 6, 3 returns 3, 8 returns 8. Okay, this is how it's going to happen. So we have discussed the case with 0 children. Now let us discuss the case when we have one child, right? Now suppose I want to remove 10, right? Now look at this. I want to remove 10. So let me draw this diagram again, right? I want to remove 10, right? Now this is case number 2 where I have one child, right? Now if you look carefully, if I want to remove 10, what should I do, right? So that simply means that it is a node which has either a left child or it has a right child, right? If I want to remove 10, can I simply say that whatever is the left subtree or the right subtree of 10, this will get connected directly here and 10 will be removed. So if I simply say remove 10 and this child will be connected here, is it correct? Is it a BST? The answer is yes. For 8, 14 is greater and 13 is less than 14. So it is correctly placed. Okay. So what I'm trying to say is if you have 10 and if you want to remove 10, right? So you have to actually return the non-null child of 10 back to 8. What is the null child? So this is the right subtree, right? If you want to remove this node, you have to return the reference of this right subtree back to 8. So 8 will point to 14 and the remaining subtree will get attached as it is. So nothing changes in the subtree. Nothing changes in the subtree, right? Okay. This is the point that I'm trying to make, right? So how do you reach 10? By the search mechanism that we have already written, right? I want to delete 10, so 10 is greater, so I will come here. Now at this node 10 is equal to 10. What should I do? I will return the non-null child of 10 back to the parent. So this is what I have to do. Now let us see how we can write it in the form of code. All right. Okay. So I think I have made a small mistake. This is a node to delete. So of course the data will be equal because we are in the else case. But case 1 was no children. Okay. So I need to fix this case. So the condition would be both left and right of that node are null. Okay. So I'm fixing a small mistake here. Root dot left is null. And root dot right is also null. Null would be capital I. Small. So I can return null, right? So root dot left is null and root dot right is also null. That means if it is a leaf node. Okay. Now let's talk about case 2. That means exactly one of the child is not null. So else if root dot left is null, that means the left child is null and the right child is not null. In that case, can I say I will return root dot right back to the parent? Else if it is the other way around, if root dot right is null, that means the right subtree does not exist. So we are at a node where the right subtree is null, but the left subtree is existing and I want to delete this node. So what I need to do, I need to return the address of the left subtree back to the parent. So I can say return root dot left. Now what's going to happen? This will get attached here. But do you really think that this node will be deleted? Do you think this node will be deleted? The answer is yes. Why? Because who was storing the address of this node? The address was being stored here. If this is updated, if the right of this root node is updated, then no one is referring to this node. That means in a way, this object becomes eligible for garbage collection. So this will get deleted, right? So this is what we need to do. Now we have a third case, which is case 3. That means a node has 2 children. We need to delete a node with 2 children. So let us discuss how this case 3 will work. So let us discuss case number 3. This is the tree. And suppose I want to delete a node which has 2 children. So it can be any node which has 2 children. So let's say I want to delete 8, right? Now if I directly delete 8, this tree will be split into 2 parts, which I don't want. This tree should remain same, right? This tree should remain same. So what I can do is, I need a way so that I do not disturb the tree structure a lot, right? If I talk about in order traversal of this tree, I get 1, 3, 4, 6, 7, 8, 10, 13 and 14, right? So this is what I get, right? If I want to delete 8, the new root node should be either 7, okay, or it should be either 10. So one of them should become the replacement of this node, right? Now how I'm going to do it? So it can be the largest node in the left subtree, that is option number 1, right? Option 1 is make the largest in the left subtree as the root node, right? Option number 2 is make the smallest in the right subtree as the root node, in the right subtree as the root node. So you can use any of these options, okay? So if I show you, if I make smallest in the largest in the left subtree as the root node, in that case 7 will become the root node, okay? Now how it is done, let us see. Now suppose you have reached the node which you want to delete and it has 2 children, right? So you will say, okay, I'm going to find out the largest node in the left subtree. So how do you find the largest node in the left subtree? You start from this node and you try to keep on going right. You always go right, and eventually when you stop here, because the right of this node is null, so you have to stop at this node, and you will have to say, okay, this is the largest node, and I will put this node here, right? Now putting means I will copy the data, so you will copy the data 7 here. So this data is copied, right? I'm not changing the node structure, I'm just copying the data. So 7 is copied here, right? Now, if you copy 7 here, what you will observe? You will observe this 7 is duplicate, right? This is present 2 times. This is duplicate, right? Now, what I can do is, can I make a recursive call to remove 7 from this subtree? From this particular subtree. Can it be done? The answer is yes. If I remove 7 from this tree, then my work will be done, right? Now if you look carefully, now 7 will be a node which has either, okay, it will have either no children, for example in this case, or if it is the largest node, it will not have any right child, right? So 7 can have a left child, can have a left subtree, right? 7 can have a left subtree, right? So that means if I'm recursively removing 7 from this tree, two things can happen. 7 does not have any child, so it will fall back to case number 1, that a node with no children. So it can be easily removed. I can return a null here, right? Or 7 has a left subtree. In that case, that subtree can be returned here and it will be correct to attach it. Why? Because all these nodes, they are greater than 6, but they are less than 7. So they can be attached directly in the right of 6, right? So 7 still can be removed. So this, if this is the case, it will handled by case number 1. If this is the case, it will be handled by case number 2, that a node has one left child or right child, but it cannot have both, okay? So you can see largest node can never have a right child, okay? Similarly, the smallest node can never have a left child because it is a BST, right? If it is has a left child, then it is not the smallest, right? So we are going right until we don't find anything on the right. So 7 can be replaced, okay? So that means in this case 7 is not having any left child. I want to remove this node. I will make a recursive call on this left subtree to remove 7. So 7 will be removed, and this is how the tree structure would look like, right? So I hope you're able to understand. New tree would look like this. It will be 7, 3, 1, 6, 4, and here I have 10, 14 and 13. This is how the new tree would look like. If you talk about the in order traversal, it will be 1, 3, 4, 6, 7, 10, 13, 14. Is it correct? Of course it is correct. Is 8 removed? Yes, 8 is removed from this traversal, right? Now let us look at into the code how this can be actually done, right? So I have case 3 where the node has 2 children. So this can be handled by the else block. So what we need to do, we need to uh, so first we need to do is we need to find the max node in the left subtree. Okay, so I can say, okay, I will take a temp variable, node temp, this is equal to root dot left. So I can say while temp dot right is not equal to null, so I will move this temp towards right. So temp equal to temp dot right. So if you are confused what we are doing, now suppose this is the tree 8, let's say I have 5, 6, 7, and I have some nodes here as well, right? I'm saying, okay, I want to find the largest in the left subtree. So I start a temp here. So temp dot right is not null, so temp goes here. Again, temp dot right is not null, temp goes here. Now temp dot right is null, so what do I do? I stop. So even if it is a left subtree, temp will stop at 7, right? Okay, so we found out the node. Now what I need to do, I need to replace the data here. So I can say, okay, fine, root dot data will be replaced by temp dot data, the data of the temp. So I copy this 7 here, right? Now what I need to do, I need to recursively delete the node 7 from the left subtree. So can I call the remove function? Yes, because it will either lead to case 2 or case 1, which I have handled, right? So I can say, okay, fine. Now my function is to remove the node with temp dot data from the left subtree. So I can say remove root dot left. The node is called temp dot data. I don't want to remove 8 now. I want to remove 7 now. So that is why the value is not key, but it is temp dot data. But after removing this, something will be updated, right? So I'm standing here, I'm making a function call on this left subtree. So this left subtree will tell me the updated address of the left subtree or the updated reference. So I have to say that root dot left, this is equal to remove, right? So whatever is the tree after removing, please tell me, right? So root dot left, this is equal to remove, right? So once it is done, what should I do? I will simply return the address of the root. So this is something we will do, right? So I'll tell you quickly what is happening here, right? Okay, return root we have already done at the end, so no need to do it here. So we have three cases, right? When we are at the node which is matching the given key that we need to delete. Okay, we have two recursive cases which are basically helping us to reach a node. Okay, so there will be a base case also, right? So base case would be that if node is not present. So if node is not present, we might end up at a value that is null, right? So I will show you what will be the base case. Now suppose I want to delete uh, let's say I want to delete 41, right? Now I start with, let's say, 7. I say, okay, 41 is greater, I go to 10. It is greater, I go to 14. Now it says it must be on the right, so I go here. So basically the right of 14 is null. So if I reach a value that is null, that means the node is not present. So it is just like the search method where we were returning false. Here we will not do anything. So if root becomes null at a certain point, right? So I can say, okay, I'm also going to return null, right? So this, I think, makes the code complete. Now let us test our functionality by going to binary search tree test file. Okay, so okay, I was all doing searching earlier. Now I can say, okay, I will remove something and then I will display the tree. Okay, one more thing we have to do is we cannot call the remove function directly because we have to supply the value of root. So we'll create a wrapper function. Let's say node remove key. Let's say void remove key. This is the method, and here we will only accept the key, right? And from here we'll say, okay, let us call the remove function where we will give the actual root and the key here, right? So now from binary search tree test we can say, okay, bst dot remove key, and here I can give some key, let's say 41. Now if this is present, it will get removed, so I will give this value, and let's say I want to display this tree. So I have given this particular input. So this is the tree before printing, before removing. Then I removed 41, and this is the tree, right? So we can experiment with this tree as well that we had. For this tree, the input was 8, 3, 10, 1, 6, 14, 4, 13, and 7. Let us try to play with this tree as well. So I will quickly type the input. So this is the tree from the diagram, and now from this tree, let's say I want to go with case 1 where I want to remove, let's say, 7. So I will give input as, let's say, 7, or I can ask the user for the node to delete. Okay, that is also doable. I will just rerun this code, and I want to delete 7 from this tree. Let's rerun it. Okay, so let's say, sorry, this is the wrong input we have given. All right, so this is the input we have given, and now from this input I have removed 7. So you can see the 7 has been removed from this tree, right? So that means case 1 is working fine. Now let us rerun this once again, and let us discuss case 2 where I want to remove, let's say, 10. So the same input goes, but I have to remove 10, so I have to rerun this code once again. I will stop it and I will rerun it. Let's say I'm removing 10. Now from this code you can see 10 has been removed. That means it is working fine for case 2 as well. Case 3, let's say I want to remove 8. So I want to remove 8. I will rerun this code, and let's see. Now after removing 8, you can see this is the in order traversal of the tree, which looks correct. Okay, so in this code I have 2 4s, which is okay, but you can see 8 is removed, and 8 was the root node of the tree, right? That means it is working fine for all the 3 cases. That's about how you remove a node from a binary search tree. Okay, if you want a small dry run, we can do it once again. Let's say now you're removing it. So as I discussed, so what are you doing? You had 7 here, right? So you say, okay, I want to remove 8. So I will go in my right subtree, in the left subtree, and I will try to iteratively find the largest node. So it says okay, 3 says okay, temp is here, temp goes here, right is not null, temp goes here, right? Then I say root dot data. This is the current root where I want to delete. So I say root dot data, this is equal to temp dot data. So 7 is copied here. Then I make a recursive call on this. I say okay, root dot left, this is equal to remove. Okay, if I talk about in the code, I'm making this change here. If I show you, this is the remove function. So I'm saying root dot left, this is equal to remove root dot left and temp dot data. So I'm not saying remove 8, I'm saying remove 7 from this tree, right? Because 7 is now duplicate. So I can say root dot left should point to a new tree in which 7 is removed. So now I say 7, I want to remove 7 from here. So 7 is greater than 3, I go here. 7 is greater than 6, I go here. So I reach finally 7. If I reach 7, I say return null. Now 6 right is pointing to null, and I say return root. So 6 is being returned. So 3 refers to 6, this node is gone, and from 3 I say return root. So 7 now refers to this 3. So this is what is happening when I am doing a recursive call for deleting 7 from this tree. I hope all those who had a doubt, now it is clear, and this is how removal in BST works. Let us try to understand what is a hash table and how it works. Okay, so you might be already using hash table a lot of times, and it is known by different names in different languages. For example, in Java it is called as hash map. In Python it is called as dictionary. In C++ it is called as unordered map, right? So There are different names, but the internals of the data structure, they are same in different languages. Okay, so hash map in Java, dictionary in Python, and unordered map in C++, and in, of course, in other languages as well. You have this data structure that is available, right? So the reason why we are going to study this data structure is it is very, very powerful, right? And it is used a lot, right? It is used a lot, right? So when I'm saying it is used a lot, so not just business logic. So when you're dealing with your problem solving, when you're building real software, you would often require a hash map to store data in the form of key value pairs. Okay, so it stores information in the form of key and the value pairs. But not just that, we can also store key value pairs in the form of a list, right? Why it is powerful? Because it allows us to do operations like insertion. I want to insert a key value pair. I want to look up for a particular key, right? And maybe I want to delete a particular key, right? A key value pair. So I can just give, okay, this is the key, delete the corresponding value and the key. So delete the key value pair given the key. So lookup means the search, right? I want to search for a particular key, if it is present or not, and if it is present, what is the associated value with that particular key, right? So these are the three important operations associated with the hash table, right? And the good thing about these operations is why this is so popular, or why this is so powerful, because these operations are performed on an average in order one time. So order one on average, that means most of the times these operations will be performed in constant time. Okay, so we will discuss the scenario when they are not performed in constant time, but you can say, okay, most of the practical scenarios, these operations would be performed in order one time by the hash table, right? So now let us discuss where this can be used. Okay, so I discussed that it stores information in the form of key value pairs. Okay, suppose you are building a application for a restaurant, and user of wants to order particular item, right? So user says, okay, I want to check if dosa is available and what is the price of the dosa. The restaurant owner might instantly reply that, okay, the cost of the dosa is 100, right? So given this key, you are telling the value in order one time. Okay, maybe I want to order some coke, maybe this is priced at 50. Maybe I want to order some noodles, right? This is costing maybe 70, right? So what can happen with this menu? What are the operations we might be doing on a restaurant menu, right? So if we are building an online menu, we might be adding a key value pair. Okay, a new item has been added, maybe a pizza has been added. So you will supply, okay, pizza has been added and it is associated with some object, or in this case that object is nothing but an integer object only, right? So the cost of pizza is 250, right? So I can say I want to insert a new key value pair. That is doable. Second is I can look up. Now I can ask what is the price of the Coke. So the hash map will tell me in order one time, yes, the price of the Coke is 50 rupees. Then I can delete. I can say, okay, Coke is not in the stock, delete Coke. So it will be deleted from the table. So these are the three operations that our hash table is going to support, right? Now, of course, we saw that this can be used in business logic. When you're building an application, a hash map can be a useful data structure to use, right? Because it provides fast lookups, fast inserts, and fast delete operations as well, right? But one major application is also in the language runtime, right? So whenever you are working with a language like Java or C++, you know, you create certain variables, create certain classes. So you say, okay, I'm going to create a variable int x, and I'm going to say this is 10, right? Then you say, okay, int y, this is 20, right? So what happens is how these variables are stored. So these variables are actually stored in the memory, right? So X is a bucket that is storing 10, Y is a bucket that is storing 20, right? But when you want to make a change, you want to say, okay, X is equal to X plus 2, right? So your compiler needs to know where is this X located so that it can go to that location and change that bucket. Now, suppose this bucket is at some address ABC, right? Let's say ABC20, right? This is some address written in a hexadecimal format, right? So the compiler maintains a symbol table for all the variables and the classes that you're going to, all the objects that you're going to create. So there is a symbol table, right, maintained by the compiler, right? So this symbol table will tell that, okay, X is a bucket which is present at this location ABC20, right? Now when you do this operation, X is equal to X plus 2. So I'll just scroll up a little bit. When you're doing this operation, X is equal to X plus 2. So the compiler will look at the symbol table, where is X located, it will go to that location and it will make the change, right? Similarly, Y is located at some location, maybe 11462, right? And maybe, right? So 11462. This is some other location for Y. So Y will, it will again look up at the symbol table, where is Y located, it will go to this location and it will make the change in the Y, right? Similarly, if you create some objects, let's say dog D, this is equal to new dog. So this dog object is created at some location in the heap, right? So similarly, your D will be mapped with some address, right? Now, what is your symbol table? A symbol table is also of a form of a hash table, right? It is also a form of a hash table, right? That your compiler is maintaining, and it is called as symbol table, right? Similarly, when you have classes and objects, right? So you say, okay, I want to create a new class called dog. The dog has certain properties, right? Let's say it has a certain name, it has a certain breed, it has a certain method, right? So what is happening? So you're able to map dog with various attributes and various methods, right? So all these features, right, they are powered by the language runtime, and language runtime might be, is actually using hash table internally, so that you can do lookups very fast. Okay, if this functionality is slow, your language will become slow. So that is another application of hash table. It is used in the internals of the language. So I hope you got a good introduction about hash table. Now we will jump into the internals of the hash table. So let us talk about hash table internals, right? So what is exactly a hash table from inside? Basically, it is nothing but it's a container. Okay, it's like, in the simple form, it can be an array as well. Okay, of some size, right? So basically, whatever data we are given, we have to map this data with a certain index in this array, right? So suppose I'm getting dosa, right? So the first step of a hash table is that we have to hash the key value, right? We have to produce an integer location for a given key. Now, given key, in this case, I'm taking it of the string type, but it can be any object, right? It can be student, it can be book. So for that particular type of object, you need to tell the hash function how that integer value will be computed, right? So right now I'm assuming that there is a hash function which is going to accept some key, let's say dosa, and it is going to produce an integer location, right? So maybe that integer location is 0 1 2 3 4 5 6 and so on, right? Maybe dosa will get stored here, and the value will also get stored here, right? I got noodles, so noodles will go into this, and maybe I get a location 6, so maybe noodles get stored here and 150 gets stored here, right, in the same location, right? So what is this hash function doing? Hash function is taking input a key, and it is producing a integer location in the array, right? Now you might have some questions, right? How big this array should be, right? Now if I have 6 keys, and if I have six, let's say 6 size of the array, right, and I have 12 keys, then of course I cannot store 12 keys in this array, right? So it's going to cause problems. So we will look at how to handle this very soon, right? This is not the completely correct implementation. We are going to discuss it step by step, right? So the idea of hash function is that it is going to produce a unique integer location for every key, but it is also possible that for two different keys they get mapped with the same location. For example, if I get something like Coke, and this since this is a mathematical function, it might compute a similar location as well, right? So it might say, okay, Coke should also go here, right? So this is called as a collision. We will discuss how do we handle collision, right? So maybe 200 something, but the idea is how big this array should be, right? So one thing we need to note is that if it is producing an integer, then integer can take any value, right? So integer can be in the range maybe 0 to 10, it could be in the range 0 to 100, right? It could be even in the range of 0 to int max, right? So that means, like, if I talk about every possible integer that can be generated, this range can be int max as well, right? But do I really need to create this big array? Okay, int max is approximately 10 power 9 elements, right? If I talk about how much space this array will take in the physical memory, this will come out around 16 GB, right? So will you need 16 GB of an array, right? Or can you create this big array? The answer is definitely not. We cannot create this big array because this amount of continuous memory might not be available. And secondly, suppose you have created this big array and you have only 1000 keys in your key value pairs in your dataset, right? Then you are allocating space for 10 power 9 elements and you just need space for 10 power 3 elements. That means you are doing lot of space wastage, which is not a good option, right? Then how big this array should be? It should be roughly of the order of number of keys that you want to insert, right? So you, if you have an idea, okay, I want to insert somewhere around 1000 keys, then it is good enough. This array should have around 1000 buckets inside it, right? Or if you want to insert maybe around 500 keys, it should be of the order this much, right? So what I'm going to say that table size should be of the order number of key value pairs that you're going to expect, right? Now it might happen that you expected 500 keys, but in practice, since the data was dynamic, 700 keys came, right? So we will also look at techniques to grow this table dynamically during the insertion process, right? So that is something we are going to study, right? What happens if there is a collision? How do we grow the table? How do we initialize the table? So all these concepts we are going to see next. So let's begin. Starting with the hash function, we will talk about insertion, searching, and deletion in the hash table. So we are discussing hash function, right? So as I discussed, hash function can accept a key. Okay, input is a key. It can be of any it can be any type of object. For our case, I'm just assuming it to be a string, and I want an integer value in some range. Okay, in some range that is from 0 to n minus 1, where n is the size of the table, right? So n is the size of the table that I am implementing, right? So for example, just to keep things simple, I'm going to assume that I have a small table where the size of the table is just 7. So 0, 1, 2, 3, 4, 5, and 6. So indexing is from 0 to n minus 1. So I have this array, right? Or I call it as table as well. So this is having a table size of 7, right? Now I have a hash function which knows how do I convert a given string into a numeric value. So suppose I'm getting a key like dosa comma 100, right? The goal is to generate a integer, map it with an integer, right? And that value should not be random. It should be same always. So whenever you ask dosa, you have to tell me at what location this dosa is present, right? So goal is to convert this dosa into a number in the range 0 to 6, right? How do I do it? So one simple way could be that I iterate over the ASCII values of dosa, add them, and since this addition will produce a number much larger than 7, okay? For example, your capital A, right? I think it has a ASCII value of 65, B is 66, C is 67, so D will be 68, right? So similarly here you will have certain values 68 plus something plus 65. This is going to produce a large integer, right? Maybe of the order 200 to 300, right? But I want to map it in the range 0 to 6, right? So what I will do, how do I reduce a bigger range, which is some larger range, into a smaller range, right? So I can say, okay, fine, this can be easily achieved by using a mod operator, right? So I can say mod with n. So I can take a mod with n. So let us assume that this mod gives us an answer that is 4. So that will be called as a hash index. Okay. So basically the index on the table produced by hashing, the hash index is, let's say, 4. So that means dosa will go at this particular index and this value will be stored at this place, right? Now the question is, what should I do? Maybe I am getting another key, right, in which the result is also 4, right? The result is also 4. So can this happen? The answer is yes. So I can say, okay, I have maybe Coke and maybe 150, right? I do not know. I add the letters of Coke, right? And I take a mod with n, right? Now, mod with n can produce the same result for many numbers, right? So maybe this also leads to 4. What, what happened here, right? What happened here? So Coke is also fighting for the same position. That means I also want to store Coke here, right? Now this thing is called as a collision, right? We have space for only one key value pair, but we want to store maybe two or more key value pairs at that particular location, right? So this is something called as a collision, right? So what happens, right? So what is a collision? A collision is a scenario in which basically two key value pairs, two or more key value pairs, they get with the same bucket, mapped with the same bucket. So this, what does this mean, right? Can we avoid collisions? The answer is no. Can we reduce collisions? The answer is yes, right? So we will talk about both the things, right? So in order to reduce collisions, right, what we need is we need a good hash function. So we will work on both the fronts, right? So collisions should be, it they cannot be avoided, right? So how, irrespective of how good a hash function is, collisions cannot be avoided, but they need to be handled, right? So cannot avoid collisions, right? Okay, but I can reduce the chances of collisions, but chances of collisions can be reduced by using a good hash function, right? But chances of collisions can be reduced using a good hash function, right? Using a good hash function. Now, how do we design a good hash function? We will discuss by taking an example of string, right? And secondly, since you cannot avoid collisions, so even if the collision is happening, you need a way to handle that collision, right? So they still need to be handled. So we need something called as a collision handling scheme, right? Collision handling scheme. This is something we will discuss very shortly, right? Now there are two important things here. One is what is a good hash function. A good second is we need a good collision handling scheme. So first, good hash function will reduce the chances of collisions, but they still can happen. So if the collision is still happening, we need to handle it using collision handling scheme. So let us discuss how do we design a good hash function and how do we design a collision handling scheme next. So let us discuss the properties of a good hash function, right? So I am going to discuss the properties of a good hash function, right? So basically a good hash function should have two properties. First, it should ensure a more of a uniform distribution. Okay, it should ensure more uniform distribution, right? And secondly, it should be fast to compute, right? So that means we do not spend a lot of time in computing the hash index itself, right? For example, in our case, what we were taking, I will take examples of two hash functions. Okay, so let's say example number one, in which I'm simply adding the ASCII values and taking a mod with the table size. So I'm saying fine, I will add dosa d plus o plus s plus a, and I will take a mod with the table size, right? Now, is this function fast to compute? Yes, because I just need to iterate on the letters of the key, right? So when I'm talking about, I'm going to insert many key value pairs. So what is n? N is the number of key value pairs. Okay, so key 1 value 1, key 2 value 2, right? Key 3 value 3. So I want to insert many key value pairs. So my hash index does not depend upon the value n, but it depends upon how big my key is. So in general, the key would be small length. So we can assume that, okay, if it is a name of a person and the phone number as the value, the key would be maybe maximum 50 characters or 100 characters. So yes, in this case, this is a fast hash function, right? But is this hash function is going to minimize the chances of collisions? Maybe not, right? Why? Because if I talk about English language, right? In English, lot of words, they are anagrams. That means lot of words have same set of letters in them. For example, let's say the word is tab, right? So it is made up of T, A, and B, and if you add, you will get certain sum, right? But if I talk about the word bat, right, it is also made up of same letters. So in this case, we are sure that these two are going to collide because our hash function is doing a very simple sum, right? So in maybe, of course, there could be other words also. Maybe the word is mango, right? Now it is possible that even if you do a mod with table size, you might end up at the same index, right? So we do not know. So in this case, it is of course difficult to tell whether the collision will happen or not, but it may still happen, right? But here we are sure that a collision will happen, right? So many words in English, they will have such a scenario, right? What we can do is, instead of doing a simple addition, right, we can do a weighted addition, right? So this is like a simple addition of ASCII values we are doing, right? So a better way would be that you do not do a simple addition in your hash function, but you do a weighted addition, right? So example 2 of building a hash function would be that you do some weighted addition, right? So that means you are going to multiply each letter's ASCII value with some weight, right? So for example, I choose a weight, maybe generally it is a prime number, right? So maybe I choose a weight as, let's say, 31, right, or 29, right? So what I can say that fine, I will multiply dosa with powers of 2. So let's say the weight is 29. So 29 power 0, that is 1, into D, plus 29 power 1 into O, plus 21 square into S, plus 21 square into A. And then I take a mod with table size, right? What I'm trying to claim is, now if you do it for bat and tab, it is less likely that you will have a collision, right? So I'm saying you multiply 29 power 0, which is 1. This is 29 and this is 29 square, right? And then you, like, it's a weighted addition. Again, 1 plus 29 into A plus 29 square into B, and of course mod with the table size, right? Now earlier we were sure that these two values will surely collide. Now we can say, okay, the chances of the collisions are less, okay? So there is a less chance of collision, right? So these are the factors that you can keep in mind, that okay, if I'm building a hash function, can I modify it some way so that it reduces the chances of collision and it is fast to compute, right? So here also it is fast to compute, right? Maybe if you have a string in which the length is too big, maybe you can restrict that, okay, I will consider only the first 10 letters of the string for this weighted addition. That can also be done, right? So that will even make the function bit more faster, right? So if you are thinking that the keys are too long, you can restrict to maybe the first 10 letters or maybe something like that, right? So now we have a good hash function, which is the second one. The second one is obviously better. We are doing weighted addition, so it is going to reduce the chances of collision, right? But a collision can still happen, right? So how do we handle if still a collision happens? So here comes a collision handling scheme, right? So let us discuss about collision handling scheme now. So you have seen how do we design a hash function. Now we need to discuss how do we design a collision handling scheme, right? So collisions can still happen. We need to handle them, right? So let us talk about how do we design a collision handling scheme, right? Collision handling scheme, right? So there are actually multiple schemes, but I will particularly discuss one scheme, right? So in this case, what we can do something called as separate chaining. So we are going to discuss only one scheme. Uh, there are other probing techniques as well, right? So I will discuss separate chaining, right? So this is one of the most popularly and widely used schemes in implementing a hash table, right? Now I'll just copy the diagram that we have seen earlier. This is the diagram, right? So let me just copy it. Okay, so here we go. The idea is that if a collision happens, what should we do, right? That is what needs to be addressed, right? That we are going to address using a technique called as separate chaining. So suppose if we got dosa and it get mapped with index 4. So what we will do, we'll not store it directly inside this bucket, but instead every time we get a particular bucket mapped with dosa, we will start a chain from there, right? So what is a chain? A chain is like a linked list, so it's exactly a list, right? That means each bucket is actually going to hold the address of the first node of the list, right? So for example, I'm going to store dosa comma 100 here, right? Now suppose I got coke comma 150. So coke goes into the hash function, and maybe this time I get 2. So I will start a chain from 2, and coke will go here, coke comma 150, it will be stored here, right? Now suppose I got something like noodles, okay, and noodles is going to have a value, let's say 120. Now noodles, if it goes to the hash function, let us assume the hash function computes a index 4, right? Now at index 4 we already have dosa, so what we will do, we'll also try to store noodles at this index. How? So we can say, okay, we can add noodles to this linked list. Now suppose this is some address, let's say this is 150, this is 270, right? So this is storing 270, this is storing 150. So each array bucket is actually storing the head of the linked list, right? Now how we can insert noodles in this chain in order one time? It's pretty easy. So you can say, okay, I will create a bucket called noodles. Let's say this bucket is this node is created, so I'll create this node n with the given key value pair, right? So it's a new node with the given key value pair, right? Now in this new node, what should I do? Like how do I add this node in this linked list, right? So I can say, okay, this is some array, right? So, or this is some table. So I can say array of and let us also compute the index. So I can say index where I want to store this is given by the hash function of the given key, right? So I get to know the index also. So at this index I need to store noodles. So one thing I can do is either I can insert at head or I can do insert at tail. So since I'm not maintaining the tail of the linked list explicitly, but you can maintain if you want, I can also do a direct insertion at the head, right? So that means we can say, okay, this node 4 will refer to noodles and noodles will connect here. So right now this is connected here. So what I can do, I can ask noodles to connect with dosa, right? So I can say n dot next. So in every node I'm also going to have next field, right? So that I can actually form a chain just like a linked list. So every node is going to have a next field. So I can say, okay, you should connect here, right? So I can say n dot next should be equal to array of index. So array of index is storing 150. So that 150 will be copied here, right? And now I can update array of index to point to this node. So I can say array of index should point to n. So basically I'm changing this connection like this. So n is whatever it is. So this will be now referring to this node. Now if you look carefully, we have actually formed a chain, right? So this is, let's say this is some address, let's say 480. So this is now storing 480, right? So you can see we are actually forming a chain, right? We are actually forming a chain. So this is exactly how the insertion is going to work, and this is the code to insert, right? Do you think will it work in order one time? Absolutely yes. This insertion will be always order one, right? Because we are inserting something at the head of the linked list, irrespective of the chain length, the insertion will be always order one, right? So I hope you have understood insertion, but is it done? The answer is no. We are not yet complete, right? We have to still discuss one more concept, but that concept I will discuss after discussing searching. Okay, so this is still not complete. So this is insertion part 1, right? Okay, so there is something more to the insertion that is going to come up, right? Let us discuss searching, how we can actually search in such a scenario, right? So we are discussing searching now, right? So now what is the purpose of searching? The purpose of the searching is that given a key, I want to look up for the value of that particular key, right? If I ask, okay, I want to know what is the price of dosa, how I will find it? So first of all, dosa is a key. This is given as input. So dosa will go to the hash function. The hash function will generate an index where this dosa can be present. In this case, hash function gives me an index 4. That means now at index 4, I actually have a chain, right? If I write it little more clearly, so this chain looks like this. I have noodles and which is like 120, and I have dosa which is part of the chain, and this price is 100, right? And of course the next is null. Now I have to iterate on this chain to check if this chain can contain dosa or not. So if I iterate on this chain, I will find dosa at this particular position. And once I find dosa, I can return the value that is 100, right? That is how searching is going to be performed. So we first find the bucket where the hash function is telling me, okay, in this bucket you have to check. And in this chain, dosa can be present, dosa may not be present, right? Now you might ask, okay, if we have to iterate the chain, then what is the time complexity of this operation? So my answer is it will be order of chain length, right? Now how do we figure out chain length? Okay, can this chain length become very large? The answer is yes, it can become very large, right? So the key to successful search operation is that we have to ensure that this chain length is very small. Okay, so we have to ensure that chain length is very small, right? Maybe 2 to 3 nodes or maybe 3 to 4 nodes, right? And this is achieved using a concept called as rehashing and load factor. So we will discuss this concept. Ensure that the chain length is very small. So if the chain length is very small, we can say, okay, on an average, this operation will be order 1. Maybe I say, okay, the chain will have only 3 nodes, 2 nodes, right? But now let us discuss how this chain length will be decided, right? How this chain length will be actually decided, right? Now suppose I have a hash table where I have 7 nodes only, right? And I keep on inserting data, right? So if I say, okay, my table size is 7 and I insert 70 key value pairs inside it, right? So what will be the average chain length? If I talk about the average chain length in this case, so I can say, okay, I have done 70 insertions across 7 buckets. So it will be 70 upon 7, that is 10. So 10 is a big number. I do not want to keep this much chain length, right? So this quantity that I've just written here, it is actually called as load factor. So load factor is a technical term for the average chain length. Okay, so how do we compute load factor? So we say, okay, total number of key value pairs that have been inserted into the hash table. So total key value pairs I have inserted upon my table size, or in other words, you can say current size, the number of key value pairs that have been inserted upon table size. That could be another way of writing it, right? So I write, this one looks little more better to me. So in the current scenario, if you have 70 key value pairs inserted in 7 buckets, this is 10. It is actually huge, it's bad, right? So what do we need to ensure? We need to ensure that our load factor does not exceed a certain threshold, right? So in some languages it is 1, in some languages it is 0.7. So whatever is the case, we need to ensure that it does not exceeds the threshold value of, let's say, 0.75, right? Now what does it mean? So if I have, let's say, 10 buckets and I insert 7 key value pairs, so what will be the load factor? It will be 0.7. That means on an average every chain has less than 1 node, right? So that also means that my table size will be slightly bigger than the number of keys I want to put. So if I want to put, let's say, 100 keys, then my table size could be of the order 150, right? Something of that sort, right? So that is something we need to ensure, right? Now how do we ensure that our table grows dynamically as the data in the table is increasing, right? So one thing you can do is, if you have an idea that, okay, I'm going to insert somewhere around 70 keys, you can initialize your table size um, around 100. Okay, so generally it is a prime number, right? So if it could be like 103, something of that sort, right? Or 107, right? So you need to ensure that if it is a prime number, it ensures slightly better distribution, right, of the keys, right? So what I'm going to do, I'm going to do insertions, and I'm going to show you how the load factor is going to change and what happens if the load factor exceeds the certain threshold. So going back, I'm going to discuss the insertion logic once again, and now apart from doing the insertion in the chain, we will also discuss the concept of rehashing and how do we increase the table size dynamically. Let us talk about rehashing according to the load factor. Let us talk about rehashing, right? So rehashing is a mechanism that is going to help us expand the table size and bring down the load factor. Let us try to understand insertion and the rehashing procedure with the example. Okay, for example, now suppose I have a table which is of size 7, 0, 1, 2, 3, 4, 5, 6, right? Now I'm going to insert certain key value pairs inside it, and I will calculate the load factor during the insertion process. For example, I insert A, right? So the locations are decided by the hash index. So now the load factor will be 1 upon 7, which is 0.14, right? Which is well below the threshold. Okay, so our threshold is, let's say, 0.75. So it is below the threshold. I will not do anything. That means on an average, every bucket has 0.114 elements inside it, right? If I say okay, I will insert B, maybe it goes here. Now my load factor is 2 by 7, which is about 0.28, right? Then I insert C, maybe a collision happens and C goes here, but then on an average, each bucket has now 0.42 elements, so it is 3 by 7. That is my load factor, right? And maybe I insert D, so it's going to be 4 by 7, right? So it's going to be around 0.56, right? So it's around 0.57 on the calculator. And similarly, if I insert, let's say, E, maybe E goes here, right? So it is 5 by 7, it's going to be around 0.71. It is still below the threshold. Then if I insert the sixth element, maybe F, it goes here and it collides, right? So it's going to be 6 by 7, which is around 0.85. Now at this point, what do I see? I see that the load factor, right, has reached 0.85. That means it is close to 1. That means on an average, every bucket has around one element each, right? It is the time to grow the table, right? So what is a table? This is my table. I want to grow this table. I want to make it bigger, right? So what I will do, I will create a new table or a new array, right, which is approximately double of the given size, right? So maybe this table size was 7. So I generally look for a table size which is a prime number, right? So this new table size could be, let's say, 7 into 2 is 14. What is the nearest prime number close to 14? It could be 13 also, it could be 17 also. Let's say this is 17, right? So I'm taking the next biggest prime number, right? Now what I will do, this table is empty, right? This table is empty, and my goal is to remove all the entries from this hash table and put it into this hash table. Now you might ask, why can't we use this hash table, right? The reason being, your table size has changed and your hash index that we saw, right? So we saw it was a weighted sum. Okay, it was a weighted sum of the letters of the string taken mod with the table size. Now table size has changed, so my hashing will also change. That means if I now insert A, earlier it was going at position 1, now it might go at some other position. So A might go here, C might go here, B might go here, and D might go here. And since the number of buckets, they have also increased, that means my distribution will also change, and it is possible that the number of collisions that are happening, they might reduce, right? So what I have to do, I have to do rehashing. So this is what rehashing is. So we have created a table of size double the capacity, right? And we iterated over every chain in the original table. Every node we added again into the hash table. So once we are done, what we will do, we will delete this from the memory. This will be cleared off, and now my hash table is going to refer to this table, right? Now in this table, if I compute the load factor, okay, if I compute the load factor now, this will be much lower than 0.85. Why? Because it was now 6 by 7. Now this will be 6 by 17. So if I calculate this value, 6 upon 17, this value comes out to be 0.35. 0.35, right? So I can keep on adding more entries into this table, right? Again, if again it exceeds the threshold, what I will do, I will execute rehashing once again, right? Now what I'm trying to say is that this rehashing is a special mechanism that will be triggered from the insert method when my load factor exceeds the certain threshold, right? So it will be some condition like if my load factor exceeds the certain threshold, I will have to call the rehash method from the insert function, right? So this is something I will show you in the code as well, right? But I hope you're understanding the reason of rehashing, right? What is the importance of rehashing? So if we have done rehashing, right, can I say the average chain length will be always less than 1? That means on an average, no bucket has more than one node, right? So it might happen that some buckets may have 0 nodes, some buckets may have 2 or 3 nodes, but I'm going to say this average chain length will be a very small number, and it can be treated as constant. So that is why we say that our search is order 1 on average, right? Order 1 on average, right? That is what my search operation will be, right? Now another point, what is the complexity of rehashing, right? So of course we have to iterate on the entire table and put all the keys into the new table. So it is going to take order of n time, right? Then how my insertion can be order of 1? So if you look carefully, this rehashing is not happening again and again. So it is happening once in a while. So you inserted this element, we took order 1 time. This element, it took order 1 time, order 1 time, order 1 time, order 1 time, and at this point we saw that load factor is increasing and it is going to trigger the rehash function. So it is going to hit order of n time, right? So can I say that for 6 elements I spent it constant time, but for one element I spent order n time, right? So if I talk about on average how much time I spent on each element, so again if I take an average, it's like a worst case, right? Inserting 6 is like a worst case. Worst case, yes, it can go order of n, but on an average we are spending order of 1 time in doing an insertion, right? You might ask, how can I bring down the time of rehashing? So if you know that, okay, I am going to insert about 500 keys, so you make sure in the beginning that your table size is big enough so that rehashing is never triggered, okay? Or it is triggered very rare, right? So the correct way to do it is initialize a large enough table. Okay, it should not be too big that you're using too much of memory. So you have to make a balance between effective memory utilization. So you should know from the historic data, okay, how big table should be sufficient. So if you're storing phone contacts, you know, in general people might have 500 to 1000 contacts, so you can initialize a table of the size around 1000, right? So it is just large enough, so that rehashing is never triggered, right? Or it is triggered maybe just once, right? It is never triggered, right? So this is something we can do, right, to make sure that almost every insertion is order 1, right? So I hope you understood the concept of rehashing, and I'll show you in the code as well. Let us discuss the implementation of hash table. So I'm using C++, but you can also use Java or any other language to map the same functionality in your own language, right? So first of all, I discussed that hash table is a table, and in this table is going to contain the address of it is going to contain the head of the linked list. So linked list is made up of nodes. So a node will store key, a value, and the next field, right? So that is what I've defined in the node structure. So I'm using templated classes, so it's like generics in Java and templates in C++. These templates allow me to hold data of any t type in my node, right? For keeping things little simple, I'm assuming that my key is always a string, but it can be of other data types as well. For that also you need to use templated classes, and you need to provide a way to convert that data type into a hash index value, right? So for now I'm dealing with strings only, but I'm saying the value can be of any type. It could be int, it could be string, it could be float, because we are not computing any hash on the value. We are just going to store that value as it is. And third thing is the next property, that is of the node, right? Whenever I initialize the node, I set the value of key, I set the value which is the value, and by default I set the next as null, right? And this is my constructor. And if I want to delete a node, so this deletion will happen if I am deleting a certain value, or I'm doing rehashing and I want to delete some data, right? This is actually a destructor which says that if next is not null, delete next. So basically it is a recursive way of deleting the node, right? So that means if I make a call at this point, it says, okay, if I'm going to delete this node, and if the next is not null, first delete it. If the next is not null, first delete it. So it's a way in which I can delete the entire chain at once, right? So this is something which you can also, like, uh, it can be implemented in other way also, right? So you might not necessarily do the same thing, but in my case I'm doing it. I will tell you why, right? So that is about the node constructor. And now let us come to the hash table class, right? So what I have done, I am actually keeping a dynamic array called table. So table is referring to an array, right? So you might ask why star star, because see, each bucket in this array is going to hold an address of the node. So it is of the type node star, right? And what is table? Table is a pointer to an array of pointers, right? Because each bucket is going to point to the head of the linked list. So each bucket is of the type node star, hence the type of the table is node star star, right? It is going to be a dynamic array referring to an array of pointers. Okay, so I have a table which is not initialized at the moment. I have current size, I have table size. So current size will be 0 in the beginning. So I will show you the constructor for this. Yeah, this is the constructor. So whenever a new hash table is created, right? So current size is set to 0, table size is set to default size. I'm taking a parameter with the default value of 7. So if user gives me, let's say I want a table size of 107, it will be 107. But if nothing is given, by default I'm taking it very small and it is 7, right? Then I initialize my table array. So table is an array that points to an array of node star, and this is of size table size. So these many buckets I have initialized, and by default in every bucket I'm putting a value null, right? So this is null, this is null, this is null, right? So instead of having garbage, it is better to initialize everything with null. That is how that hash table has been initialized. I hope you don't have any doubts till now. Now comes the interesting method, that is insert, right? Now if I want to insert something, right? So my table is ready. So table is here. My hash function is also ready. Okay, I'll show you the hash function. Let's say I want to insert dosa, comma 100. What do? I will show you the hash function. Let us understand the insert. So my key, that is dosa, it goes through the hash function and I get an index. So maybe the index is 4, right? So at this index, what do? I will create a new node. So I say, okay, there is a new node called n, which is dosa, comma 100. In this line, I do this work and I say n dot next, this is equal to table of index. So table, and this is index. So n dot next will point to whatever this is pointing to. So it is currently pointing to null. So the next starts pointing to null, right? Then I say table of index is equal to n. So this index is going to hold the value n. So n is, let's say, 248. That is the address of this node. So it is going to store 248, right? So this is how this node gets attached to the beginning of the table. Current size plus plus. So current size becomes 1. Then I compute load factor, so which is 1 upon 7. Is it greater than 0.7? The answer is no, right? So if it becomes, then I will trigger rehash. I will show rehash method also, right? So this is about the insert functionality, right? So I hope you're getting it. Let's say I'm inserting one more node which at the index 4. So I just want to show you how the chaining is going to work. Let's say I inserted noodles And for noodles also, I got an index 4. So noodles comma 120, I created a new node called n, right? Then I said n dot next is equal to table of index. Table of index is storing this value. So noodles starts pointing to this value, right? And table of index is equal to n. So this connection is broken and this starts pointing to this node, right? So you can see in a way we are forming a chain in which noodles is getting inserted at the head of the linked list, right? So this is nothing but insertion at the head of the linked list. Current size plus plus, so current size is 2, load factor is 2 by 7, which is again less than 0.7. So hence I do not trigger rehash at this moment, right? So I hope you understood the insert method. Next I want to show you the hash function that I've used here. So hash function, I've made it as a private. So what I'm doing, I'm simply multiplying the numbers. Let's say the word is dosa. What I'm doing, I'm iterating over this and I'm multiplying it with powers of 29. So it is 1. So initially it is multiplied with 1. Then in the next iteration, power becomes into 29. So into 29. Next time it becomes, power becomes again power into 29. So it gets multiplied with 29 square. And again it becomes 29 cube, right? So in order to avoid overflow, I'm doing a percentage mod at each step, because if you take mod at the last, uh, or if you take mod at each step, we know this is the property of mod. So mod can be taken at each step as well. So this is a better thing to do because it helps us to avoid overflow, right? I'm taking a mod with power also, and I'm taking the mod in the answer also. So I get an index which is in the range 0 to table size -1, because I'm doing a mod with table size. So I hope you understand the hash function as well, right? Now what I need to do is I need to understand the rehash method, right? So if we understand the rehash method, our insertion will be complete. So I have written a rehash method as well, which is actually a private method as well. So what I'm doing in my rehash method, that suppose I have a old table, like the actual table. In this I have inserted some keys. Let's say A, B is there, C and D is there. What do? I say okay, old table is going to point to table. So this was my table. Now old table is pointing to this table. I create a new table, okay, which is almost double of the previous size plus 1. I'm just making it as an odd number instead of making it as a prime number. So I'm saying this is my table now, which is also the data member of the class, right? So what do? I initialize it with null. So all these values are set to null. And then what I do, I copy elements from the old table. So I iterate over the old table. And how do I do the work? Let me show you. So I do it like this. I take a temp variable, which is the ith row. So temp starts from here. Okay. Temp is referring to the head of the linked list. And while temp is not null. So I copy the key, I copy the value. So I say, okay, give me this key value pair, and I call the insert method. So insert method, we know by default it acts on the table, which is the data member of the class. So it is going to insert automatically in the new table, right? And temp goes as next. So temp comes to this node. Again, I copy B, I insert it in the new table, right? So once it is done, I make a destructor call. If old table of I is not null, delete old table of I. So in Java, there is a concept of garbage collection, but in C++, we have to use explicitly, we have to invoke the destruction of this entire linked list by saying delete old table of I. So I initiate a destructor call from here, which makes a call to A. A is being a recursive destructor, A makes a call to B. This way, this entire row is deleted, right? And then I go to the next row. So my I is increasing. So I go to this row, this row, this row, this row, this row. I do the same work, and all the nodes are inserted in the new table. And finally, I say, okay, I want to delete the array that is old table. So I also want to clear up this memory. So I say delete old table. This old table is gone. And since it is a local variable, this is also destroyed, right? So till now you have seen the insert functionality, and we discussed that the function rehash will be triggered from the insert whenever load factor exceeds the threshold. Okay, so we basically double the table size here, right? Now let us talk about searching a little bit. How do we actually do searching in a hash table? So searching is pretty easy. So if you have a hash table, right, and you want to search for a certain key, let's say dosa, so that key will go through the hash function. The hash function will tell you the bucket. So maybe this is the index of the bucket, and in this bucket there might be a chain in which dosa could be one of the item, right? So maybe this is some x item, some y item, some z item. So you need to iterate on this chain linearly, right? So I start temp from this node. While temp is not null, while I do not hit the end of the chain, I compare is the key of this node matches with the given key if I'm searching. So if that happens, I return the value. Otherwise, I go to the next node. If I hit end of the chain, that means I did not found the key, so I return null in that case, right? This is how searching is done, right? So on an average, what we are saying that this chain length is so small, right, because of the rehashing and the load factor that we are maintaining, right? So we can say, okay, iterating over a very small linked list will take order one time on average. Okay, so we are not talking about a worst case. A worst case scenario might be like this. A single bucket has all the n nodes inside it, right? So basically chain length is of the order n. But this is a very less likely scenario because this can be only possible if your hash function is too bad. It is producing the same bucket for many different types of keys. Okay, in general it's not going to happen. So that is why we say on average it's going to be order one most of the times, right? So I hope you have understood the search functionality as well, right? On a similar lines, you might have to do erase as well. You might want to delete a particular key as well, right? Now how you have to do it? Now this is pretty simple. If you know how to search, then you can also know how to delete, right? So suppose I want to delete a key that is y. What I will do, I will pass y to the hash function. It will give me the index. I'll find this linked list. Now the problem boils down to deleting this node from the linked list. Now you have to handle these cases. This node could be the last node in the linked list. It could be middle of the linked list. It could be beginning of the linked list, right? So if you know deletion in a linked list, you can easily handle the code to erase a particular key value pair from the hash map as well. So let us talk about graph. So graph is a network-like data structure consisting of nodes and edges. So it is a data structure, that means it is able to hold data, and the data is in the form of a network. Okay, and consisting of nodes and edges. So if I look at this figure, all these circles, they represent a node, and all these lines, they are representing a connection between these two nodes. For example, this edge is connecting node 4 and 25. So can we think of any real life example where the data might have connections in between certain objects? Of course, yes. If we talk about cities, then cities are connected with each other through connections which we call as roads. If we talk about a social media graph, for example, this is person A and he is connected with a person B, and A is also connected with a C. So we say B and C, they are friends of A, or A and B are connected, A and C are connected. If I talk about this person D, is it connected to A? We say no. The person A is not connected with D, or D is not connected with A, because there is no direct edge in between them. So if I add a edge, they also become direct connections. So there can be many applications in real life where graphs can play an important role. So let us try to understand the applications first, then we will dive deeper into the implementation and coding. So graphs, as I said, they are used in many real life applications, and they represent a network of nodes. Such a network of nodes can be a network of cities, a network of places, landmarks, anything. It can also be an electrical circuit. When you use your mobile phones, it has something called as a circuit. Okay, it has a motherboard on which you have certain elements, certain small embedded systems on it, and there is a wire connecting these elements. So it is possible that we want to find out the most optimal route for the wire so that we can reduce the cost. Okay, because it is a copper wiring, it can be expensive. It can be a graph algorithm can be used here to minimize the total length of the wire that can be used to connect all the components in this circuit. And of course, social media networks, we have just discussed that Facebook, Twitter, LinkedIn, all these networks, they can represent graphs. So let us go into the applications in little more detail. The first example is an example of shortest paths. We often use apps like Google Maps, Uber, Ola, and many other apps to compute to in our daily life. Okay, so these apps, they try to figure out what is the shortest path between the set of nodes that are there, and should I go from this route or should I go from this route. If you want to do such a calculation, okay, if you want to go from source to a destination, then what path would be best can be easily devised using a shortest path algorithm known as Dijkstra's shortest path algorithm. We will discuss that algorithm in this series. Then, of course, if you want to book flights, okay, you want to say, okay, I have to go to this region. Maybe there is a flight which costs 80 and there is a flight which costs 20. Should I take this flight or should I take these three flights? So maybe they are cheaper, but they are taking more time. So there might be trade-offs. Again, you have to look at what you want. What is your requirement? Do you want to optimize for time, or do you want to optimize for the total cost of travel? The social media networks I have discussed. So I will give you one more example. In some networks, when you connect with a person, for example, Facebook, so if A and B are friends, then this connection is bidirectional. That means A is connected with B, B is connected with A. But in some other networks, this connection is having a direction. For example, on Twitter, if A follows B, it does not mean B is also following A. So these edges, they can be bidirectional or they can be one directional. So we call such a graph as a directed graph or directed edges. Okay, so this graph has directed edges because A is following C and B, but B is not following this. So in such a case, this is called as a directed edge. And in example of Facebook, it is called as a undirected edge because there is no fixed direction. If A and B are friends, then B is a friend of A and A is also a friend of B, right? Now these kind of representations, the graph like representation is important to build algorithms. If you want to find mutual friends, if you want to generate news feed, so for A, it will see the post from B and C. If B is following someone, then this person's post will not be visible to A. So all these algorithms require graph like representation of the objects involved. Then there is also something called as shortest round trip. If you think of if you think of something called as a school van, okay, what is the purpose of school van? It will start from school and it will drop all the children on the way and it will come back to its location. So in this case, what is happening? We are doing a cyclic tour. We are coming to the source by covering all the points in the city where we need to drop the children. Now it is possible that multiple routes can be devised, but we want to devise a route which costs minimum. So such route design can be used in for Amazon delivery vans, for school vans, and this is a very famous problem in graphs called as traveling salesman problem. We will also discuss this problem in the coming series. Let us talk about one more application. So when you are installing software, you might have seen that the software is installing list of dependencies in a certain order. For example, you have to install a software X. For X, you need something called as, let's say, C. C is dependent upon something called as B. B is dependent upon A. And there is something called as D. X is dependent upon D and D is also dependent upon A and B, right? Now, in such a scenario, if I have to install the dependencies, what is the first thing I will install? Of course, I will install A. If I install A, then B and D, they do not have any dependency. So either I can go with B or I can go with D. So I can install B and D. If I have installed B and D, then X has only one dependency, that is C. So I can install C and then I can install X. So if I install the dependencies in this order, right, my software will be installed correctly. So this kind of a graph, it is called as dependency graph, and it is an example of a directed acyclic graph. That means there is no cycle, it is directed. And from this graph, we need to figure out what is the correct order of installation of software, right? So it is often used while installing software on systems, on servers, when you're installing libraries and modules. They follow this particular order, and this dependency graph can be easily created using a graph algorithm called as topological sorting. We will learn about this algorithm in the coming series of videos. Okay, so that is another application of graph. So let us talk about one more application, that is routing algorithms. So Bellman-Ford is a very popular graph algorithm that is also used in finding shortest paths. Now, this algorithm is also used in routing algorithms. So the world has lot of routers, right? And these routers are continuously exchanging data packets. So which data packet should go there, and what is the shortest time in which it can reach to the desired location? So all this routing is done using a distributed version of Bellman-Ford algorithm, which is again a very interesting algorithm in itself. So let us talk about one more application. So if some of you have done machine learning, then you know in deep learning, the deep learning models, they do gradient computation, which is an important step in training of the machine learning models. Okay, so these gradients are used in backpropagation to adjust the model parameters, and the way these libraries like TensorFlow, PyTorch, they build a computation graph of these gradients so that the computation can be optimized. So you do not need to worry about how to construct the graph. The libraries like TensorFlow, PyTorch, they automatically do it for you. Again, this is inspired from the idea of graphs itself. And in traditional computer vision, what happened? Image segmentation algorithms were used, which were based upon the concept of network flow, which is again a graph-based algorithm. So if you do not know what is image segmentation, so image segmentation is basically extracting out objects from an image. It's like drawing a boundary on an object that is like one entity. In case of this example, the car is one object, the building is another object, this footpath is another object, the road is another object. So these kind of algorithms are often used in self-driven cars, but in today's world we have deep learning techniques for image segmentation, but the traditional way of doing this segmentation was based upon a graph algorithm called network flow. Again, let's do one more application in web crawler. So basically, when you want to build a web crawler, for example, you want to crawl amazon.com and you want to scrap the entire website. So when you go to amazon.com, what happens? You load the code is loaded in the browser. So in the code, you will see there are a lot of products, and with each product, there is a hyperlink. So you want to go and scrap all those products. So what do? You build a web scraper that reads these links, adds them into queue. Maybe this is some TV button. Okay, so you go to that page, it opens up, and then again there are many links here. So you can also use these links to crawl further, right? So it's like a tree traversal. So web crawlers use breadth first search to crawl the web. So if you have built a web scraper, you would have know that you often do a BFS like thing, and you traverse the DOM tree, and a tree is also a graph. Okay, a tree does not contain a cycle, but it is also a graph example. So let us do one more application. So nowadays, we also have databases that are inspired from the idea of graphs. One such database is called Neo4j. So these kind of databases are used in recommendation engines, fraud detection, and many AI-based applications. Apart from it, there are a lot of other applications of graphs, such as in linguistics, social sciences, biology, neuroscience, atomic and molecular structure, computer processing, flood fill, and more. So what is this flood fill? This is an interesting application I often cover in my course. When you use the paint bucket tool like this and you drop it in an object, it automatically fills the color till it hits the boundary, like you can see here, right? So this again is an example of graph, and this matrix is an example of a 2D implicit. It's a 2D matrix which is representing a implicit graph. So we will discuss about what is an implicit graph and how do we build algorithms on implicit graph. That will be covered as well. So that's about the applications. Next, we will dive into the more technical concepts and understand how a graph can actually be created and stored inside the memory. Next thing I want to talk about in graphs is classification of graphs. Though we have talked briefly about weighted and unweighted graphs, let us try to understand with some more examples. Basically, there are two criteria for classifying graphs. One is weight of edges. There can be graphs in which there is no weight associated with the edge. That means each edge is treated equally. Each has a unit cost. Okay, you can say, okay, it is a unweighted graph. Such a graph is called as unweighted graph. But it can be scenario, for example, if you talk about roads. So each road might have a length, or it might have a time to travel from B to C, right? So some kind of weight or maybe some kind of fuel cost. So we can say that in such a scenario, each edge is having a different weight and we need to store that weight as well. Okay, so earlier if I'm representing a edge as a comma b in an unweighted graph, now I have to represent edge as a comma b comma 10. That means the time to travel from a to b or the edge weight from a to b. So this is a case of a weighted graph, right? That means in the implementation also we will have to store this weight associated with the each edge, and then there is direction of edges. Now there can be scenarios where the edges are not having any specific direction. For example, talk about Facebook friends. If A and B are connected, they are connected. That means A is a friend of B, B is a friend of A. But edges can have a certain direction. For example, a Twitter graph. So if A is following B, does not mean that B is also following A. So in this case, edge will have a certain direction. That means A is following B and A is following C and B is following C, something like this. This is an example of a directed graph, and wait, so this is an example of undirected graph. Let us look at some more examples. Okay, so we have discussed graphs whose edges or paths can have values associated with them. They will be called as weighted graphs. Edge value can represent either the weight or some kind of cost or length of that path. For example, in roads it might be the distance in kilometers. So directed undirected graph we have already discussed. Graph edges can have specific direction attached to them. They're called as directed graphs. Okay, now in such a scenario you might have two-way edges. For example, from 1 to 2 there is an edge, from 2 to 1 there can be edge as well, and it is possible a different weight is associated with each of it edge. For example, we are going from Delhi to Bangalore via flight. Now this flight might cost you 4k, but this flight might cost you 5k. So this is an example of a directed and a weighted graph. In an undirected graph, there is no direction of the edge. That means you can travel in both directions. You can go from A to B, you can go from B to A, for example, in roads. Okay, so I hope you are able to understand through these examples. So let us try to make a matrix and let's summarize, right? So I can say graph can have weights, weighted graphs, or unweighted graph. They can have direction or they can be undirected. Okay, so what would be an example of a directed and a weighted graph? For example, from A to B, okay, and there is a cost associated with it. This can be your graph of different flights across cities, because flights will have a cost and they will have a direction. So if there is a flight from A to B, it is possible that there is no flight from B to A, or B to A flight has a different cost. This will be a directed and a weighted graph. Let's look at an example of a directed and unweighted graph. I talked about topological sorting, in which we said that there are certain tasks and there are dependencies. For example, B is dependent upon A, C is also dependent upon A, and C is also dependent upon B. So this is an example of a directed acyclic graph. Okay, so this is an example of a dependency graph. In this graph, there is a direction, but there is no weight. So it is an example of directed and unweighted graph. So an example is dependency graph. Okay. Then there is an example of undirected but weighted graph. So I want a graph in which there is no direction but there is a weight. Maybe the road network, I can say, okay, the roads are generally two-way. So there is a cost, so there is a weight. but there is no direction. So 100, 200, 10, 20. This is an example of a undirected and a weighted graph. Then undirected and unweighted graph. So that means no direction and no weights as well. So it could be simple Facebook graph in which you are representing who is connected with whom. A and D, they are friends. So there is no weight. So maybe Facebook friends graph, okay, or Facebook network. So it is possible that it is unweighted, but depending upon how Facebook implements it, this graph can also become weighted. Facebook might represent a score, a friendship score on each edge, how strong these two people are, how strong their bond is. So it is possible that this graph can be made as weighted also. So I hope classification of graphs is clear through these examples. And next we will dive into the implementation, how to create a graph and store it on your RAM. Now the next question arises, how do we actually create this data structure and how do we work with it? So there are three common representations for graph. One is called as edge list, one is called as adjacency matrix, and one is called as adjacency list. We will go over all of them one by one. Each representation has its own set of advantages and disadvantages. But in general, this representation, which is called adjacency list, this is the most popular and most commonly used in many algorithms. But this does not mean that edge list is useful or adjacency matrix is useless. They are also useful. They have their specific applications in certain type of algorithms. So let us discuss edge list first. And what is a edge list? So in a edge list, we represent graph in terms of list of edges, right? So suppose we have vertices A, B, C, D. So we will make a list of vertices, and if we have edges, we will note down what edges we have. We have AB, so AB is an edge. We have AC, we store that. We have AD, we store that. We have BC, we store that. We have CD, we store that. So right now I'm assuming this is a undirected graph. So when AB is an edge, it also means BA edge is also there. That means if you can go from A to B, you can also go from B to A as well, right? Similarly, if you can go from A to C, you can go from C to A as well, right? So in my code, I will be storing two copies. AD is there, DA is there, BC is there, CB is there, DC is there, right? So I'll be storing it like this. That will be more helpful because if I'm at D and I want to look at what nodes I can visit, so I can clearly look at this. There is an edge from D to A and there is an edge from D to C, right? So I can look at this. Or you can say, okay, I'll iterate through the whole list. Of course, you will have to iterate through the whole list and you have to look at what pairs contain D, right? From that, you can get this information from D where you can go, right? But this kind of representation is pretty, I would say, inefficient if you have to find whether there is an edge between, let's say, B and D. I want to see whether there is an edge from B to D. The answer is it is inefficient because you have to do a linear search over the whole list. So that means you have to spend order of E time looking for whether such an edge exists or not, right? Similarly, if you have to do an operation like, okay, give me the neighbors, immediate neighbors of B, right? This is now a very common operation in graph algorithms such as BFS, DFS, Dijkstra's. We often need this operation, right? So neighbors of B. So what are the neighbors of B? So again, you cannot tell directly. You have to iterate over the whole edge list to find out what are the neighbors of B. Again, this operation is going to be inefficient. It is going to take order of E time, right? But one thing this edge list is good at, for example, suppose this this graph was a, let's say, a weighted graph, let's say 10, 5, 2, 1, 6, right? And I want to pick edges based upon their weight, right? So now in such a scenario, I will be storing three things in an edge. So I will be storing A, B followed by 2. I will be storing A, C followed by the weight, right? In case of a weighted graph, I need to store three things, right? And so on. Maybe I want to pick edges based upon their weight. So what I can do, if I've stored all edges in the form of list, I can easily do sorting on this list. Okay, I can do sorting on the list in like E log E time, right? E log E time. And I can pick edges maybe based upon their weight, right? So, or according to some criteria, right? So maybe I want to do sorting on the list based upon weight of edges. So this kind of algorithm is actually helpful when we deal with a topic that is called as minimum spanning tree, right? So when we are building a minimum spanning tree algorithm, we actually need to pick edges based upon weight. So in such an algorithm, we will go with the edge list kind of a representation, right? So that means this representation is also useful, but it depends upon the algorithm. What kind of operation do we want? Do we want to get neighbors of a node, or do we want to sort edges? So if we want to sort edges, then edge list is the representation that we will use. So I hope you are able to understand edge list. And now in the next video, and now we will discuss the code of edgelist. So I'm going to show you how we can create a graph using edgelist. So I am in my IntelliJ IDE and I'm going to create a class called as graph using edgelist. This class will be responsible for holding the data of the graph. So effectively what I'm going to do is I'm going to keep things little simple. I'm going to fix number of nodes. Let's say number of nodes is given as input by the user. Let's say user says 4 nodes. I'm not going to take input the names of nodes. I'm going to assume that the nodes are always numbered from 0 to n minus 1. So this is from 0 to 3, right? This is something which is very common in many coding problems, and we often use we make this assumption, okay? And you can also verify from the problem statement. If this is not the case, then we will discuss it separately, right? The number of nodes are 4, and let's say the graph looks like this: 0, 1, 2, 3, right? So what is expected in the input, that you will be given how many edges are there. So number of edges will be input, that is also 4, and then you will be given the names of edges. So 0 comma 1 is one edge, 0 comma 3 is another edge, 1 comma 2 is another edge, 2 comma 3 is another edge. So you will be given these numbers input. So what is our expectation, that this graph should be able to hold these pair of edges. So 0 comma 1 I want to hold, 0 comma 3 I want to hold, 1 comma 2 I want to hold, and 2 comma 3 I want to hold, right? Now if you look at this list, can you visualize this graph? Of course yes, right? That means this information is sufficient to store this graph, right? So what I'm going to do in this graph class is I'm going to make a list which is able to hold a following edge, right? Now it is possible that each edge might have a certain weight, let's say some weight w1, w2, w3, w4, right? So in such a scenario I can add w1, w2, w3. It will be list of edge where each edge object is a collection of 3 numbers in this case, right? So what we can do is we can define a class called as edge, right? We can define a class called as edge, right? And in this class I can have 3 things. One is maybe the source, so I call it as u. I have v and I have weight, right? So that means the triplet. So if there is an edge from u to v with a weight w, I'm going to store a triplet u v w, and I'm going to create an edge object out of it, right? Then I can make a list of edges. So I hope you understood the concept. Let us dive into coding. So I need a constructor for the edge class. So the constructor is going to expect u, v, and w, right, for one edge object. So I can say this dot u equals u, this dot v equals v, this dot weight equals weight, right? So later on I want to print the edges, so I might need a method to display an edge, right? So I can just use the toString method, which is going to show me, which is going to print, which is going to return a string representation for this edge. So this will be helpful when we are going to print the edge. So if I want to do s out an edge, I will see that the edge will be printed like this: u equal to something, v equal to something, and weight equal to something. This overrides the default toString method, right? And it is auto generated by the ID for me, right? So I have the toString method with me, right? This will be helpful if I'm going to display the graph. That means I'm going to display this edge list in the output. So I don't have to write for each edge. I don't have to do this work, because this method will be called when I'm going to print it. So I can simply say s out some edge, right? So something like this we can do. So now coming to this actual class, right? So let's make this class as public. In this class, what information it needs to hold? It needs to hold how many nodes we have, number of vertices. Number of edges is optional because it can be judged by the length of this list, right? So user is going to enter the edges and we are going to store them, right? So that is simple. And so let's have a constructor, right? So the construct, and apart from it, we need a list of edges, right? So list of the type edges L. Let's create the constructor graph using edge list. So in this constructor, I'm going to get number of vertices, which I can initialize. This will be list of edge. So I can say this dot v equal to v, and I also need to create this list. So L is a new list. So it can be a linked list or an array list, and I can say it is an empty list, right? So when a graph is created, it knows how many vertices it has, and it creates an empty linked list. Okay, now I want to add edges in this graph. So maybe I need to create some method, add edge u comma v and wait, right? I want to push an edge into this graph. So I can simply say uh, if there is an edge from u to v, so I can say um, L dot add. What I should add? I should add a new edge which goes from u to v and is having a following weight. So I'm doing it for a directed graph, right? I'm doing it for a directed graph. So I think this implementation looks complete to me. Now let us test our implementation by going to main, right? So here what I need to do, I need to create a graph object, right? Which I am doing, right? And then I'm saying that fine. Okay, so here I've passed one more parameter which is going to tell whether the graph is directed graph or undirected graph. So this is an optional thing. If you want to accept that, okay, this is a directed graph, then you can add just this edge. But if it is an undirected graph, you also need to do one more line of code where you are adding the edge from u to v, right? So you're saying that, okay, a and b are connected. That means a is a friend of b. There is an edge from a to b, but there is also an edge from b to a, right? So you can do this thing in case of a undirected graph. That can be handled by putting a if condition here. But for now, I'm keeping things simple and I will modify this code a little bit. Earlier, I did it for undirected graph, right? So it's just a signal to the graph whether you want to add this edge like one time or two times, right? And now I want to display the graph. I basically want to display the edge list, right? So I created a graph object using this class new graph. I initialize the number of vertices, which actually we are not using as of now, but this might be helpful in future, right? For some other use case. Now if I want to display this edge list, so I can say okay, void display. Okay, or let me see if I can do a toString thing here, right? So here I'm going to modify this, right? I'm going to, or this is fine actually, this is fine. So it is going to return a list. Let's see what does it return, right? So I'm going to say sout graph, show me the graph, right? So let's go and run this code. Okay, so this graph says that, okay, I know two things. I have vertices which are 4 and I have a list of edges which is this list. Okay, so there is an edge from 0 to 1 with weight 10. So 0 to 1 weight 10, 0 to 2 weight 20, 0 to 2 weight 20, 1 to 2 weight 30, right? So you can see this is completely fine and we are able to see uh, the edge list that we have implemented. So that is the idea behind edge list. Now you can use this edge list to do sorting. So right now I have hard coded values here, but what you can do, you can ask the number of edges, put a for loop, take input those edges, and inside the loop you can call this function g.addEdge, and this is going to add all the edges in your graph, right? So in generally, I've discussed how the input is given, number of nodes is given, number of edges is given, followed by list of edges is given, right? So pairs, like 0 comma 1 comma 10, followed by next pair 0 comma 2 comma 20, right? This will be input. You can scan it and call g.addEdge to add it in your graph, right? So I hope this representation is clear. Next, we will discuss another implementation. The next representation of a graph, it is called as adjacency matrix. So what is this? It is a 2D matrix which is of the size v cross v, where v is the number of vertices of the graph. The number of elements in the matrix indicate whether pairs of the elements of the matrix, actually not the number of elements. The element of the matrix indicates whether pairs of vertices are adjacent or not. Basically, if there is an edge from 1 comma 2, right? So what we will do, we will have a adjacency matrix. Okay, so in this case there are 5 nodes, so there is a 5 cross 5 matrix, right? And there is an edge from 1 comma 2. So what we are doing, we are saying that matrix of 1 comma 2 will be true. So if it is a unweighted graph, there is no weight, so I can simply set this edge as true. So 1 comma 2 is true, or it is 1, right? And similarly, if it is a undirected graph, there is no direction, so matrix of 2 comma 1 is also true, right? So this value is also true. So this value 1 comma 5, this is 0. So this basically indicates there is no edge from 1 to 5, right? So if there is an edge from x comma y, then in my matrix of x comma y will be set to 1, and matrix of y comma x will also be set to 1. That indicates that x and y, they are connected, right? So this is pretty simple. And the problem with this approach is that as your n grows, right? So if let's say you have 1000 nodes, right? Your matrix will be of the size n square, right? So that means it will have 10 power 6 elements. So if n is, let's say, 10 power 7, your matrix will be of the size 10 power 14. You won't be able to hold this big matrix in your memory, right? So it is not suitable for large number of nodes. Okay, it is suitable for small number of nodes, but again there are certain advantages and disadvantages for this, right? One disadvantage is that you are going to waste a lot of space. So in most of the graphs, if you have n nodes, you might not have n square edges. That means lot of zeros will be there in the matrix, which is leading to space wastage. Secondly, if you want to find neighbors of 1, what nodes are connected with 1? There is no way. You have to iterate over this whole list, which is going to take order of v time, right? Because there are v vertices here. You have to go to each vertex and check whether one is connected with it or not, right? That is again a problem. We do not want to go to 5 because 1 is not connected with 5, but we are still iterating, right? So this is a major disadvantage. That means you cannot get neighbors of a node. In order to get neighbors of node, you have to spend order of v time, which is not very efficient operation, right? But there is one advantage as well. So what is the advantage? If I have to check if there is an edge between 1 comma 3, right? So that check can be order 1. Why? Because you just need to go to 1 comma 3, this index, and check yes, this value is 1. So you can check yes, this value is 1. So that means I can figure out whether an edge is present between two nodes or not in just order 1 time, right? Now you might ask, what if the graph was a weighted graph? 1 comma 2 was having, let's say, w weight. So in such a scenario, instead of storing 0 or 1 here, you will store 0 followed by weight, right? 0 and weight. So 1 comma 2 has having w weight, so 2 comma 1 is also having w weight, right? So you can store integer values. 2 comma 5 has 8 weight, so 2 comma 5, you can put this value as 8, and 5 comma 2 as also 8, right? So depending upon the use case, this matrix can be an integer matrix or it can be a Boolean matrix, right? So I hope you understand the concept of adjacency matrix. Now let us look at the implementation of adjacency matrix. Let us implement graph using adjacency matrix. So again, I will have to keep number of vertices and I will have to keep a Boolean matrix. So I can say a Boolean some matrix, let's say called adjacency matrix, and we will initialize this matrix in the constructor, right? So I have graph using adjacency matrix. I'm getting the number of vertices. This dot v equals v, and adjacency matrix equals new Boolean of the size v cross v, right? So I hope this matrix, this initialization is clear. By default, I think all the values would be false. And now we can write the add edge function, right? So I'm not going to take the weighted graph because I've taken a Boolean matrix. So I will take only two parameters, the edge from U to V. And also I'm assuming the graph is a undirected graph, right? But if you have a directed graph, then it is even easier, right? So if there is an edge from U to V, what I need to do in the matrix for the uth row and the vth column, I need to mark this as true. So I can say adjacency matrix of u comma v will be marked as true. Rest everything is false, right? And adjacency matrix of v comma u, this is also true, right? So the other way around we also have to do, right? So that's it. Now what we need to do, we need to test our code, right? This adds an edge to our graph, and now we can have a display method, right? That is going to display the matrix. So I can add a toString method here, which is going to display the vertices and the adjacency matrix. Let's go to main here, and now I have to create a graph using adjacency matrix. So I've added a few edges, and now let us go and run this code, and let's see what output do we get. Now we are getting, okay, in this graph object we have 4 vertices, and now adjacency matrix is being displayed like this. So this is actually how a 2D array is stored in Java, right? So if I talk about a 2D array, a 2D array is a 1D array of rows, right? And each row is actually is storing the address of an array, right? This is how it is being done, right? This is how it is actually done. 2D array is an array of rows, and each row is, let's say this row is 30C, this is 97D, right? So what we are printing is, we are printing the address of each row of the array, right? So this is the address of a 1D array, 0th row, first row, second row, and third row. If I want to handle this in a correct manner, right, so I have to say that we do not want to convert this 2D matrix into string directly. We have to use a method called deep to string that will actually iterate deeply into each row, and then it will print convert the contents into the string, right? So I'll do it like this. This will actually give me the string like representation of the full 2D array, right? Let's go and run this code once again and see what do we get. Yeah, this time I'm getting the correct adjacency matrix. I will draw it for you. So what I did, I give 4 vertices, let's say 0, 1, 2 and 3. Then I said 1 and 2 are connected, fine. 0 and 3 they are connected, okay. 1 and 3 are connected, okay. And 2 and 3 they are connected, okay. So this is how the graph looks like. And then I have a 4 cross 4 matrix, 0, 1, 2, 3, 0, 1, 2, 3. So it is false, 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 true. So here I have a true here, false, false, true, true. So here I have true, true, false, true, false, true. So true, true. Then I have true, 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 false. T, T, T. If you look at this 0, so 0 is only connected with 3. So we have a true here. Then look at 1. 1 is connected with 2 and 3. So 1 is connected with 2 and 3, correct? Look at 2. 2 is connected with 1 and 3. 2 is connected with 1 and 3, correct? Look at 3. 3 is connected with 0, 1, 2. So 0, 1 and 2. Yes. This is a correct representation of the adjacency matrix for this graph. So I hope you understood this concept. Pretty easy, nothing fancy in it. And you can easily modify the code for a directed graph by making this as a integer matrix and putting the weight here, right? So that's all. Next we will discuss adjacency list. Now let us talk about one more implementation of graph that is called as adjacency list. So this is the most widely and most common used representation in many graph algorithms. What do we do in this representation? The adjacency list represents a graph as an array of linked lists. The index of the array represents a node. So we will try to understand. Now suppose I have 1 to 2, there is an edge, right? So what I really want to do is that with node 1, I actually want to store all the neighbors of 1. So 1 is connected with 2, 1 is connected with 3, 1 is connected with 4, right? So basically there is a key value mapping. So key is 1, value is the list of nodes with which it is connected. One way to store it is that we create an array. Now suppose there are 5 nodes. So here they have assumed a 1 based indexing, but in our code there will be a 0 based indexing, right? What it is saying that it is a linked list, right? So if you talk about 1, 1 is connected with 2, 3, 4. Similarly, if you talk about 2, 2 is connected with 1, 3, and 5. So I know 2 is connected with 1, 3, and 5. 3 is connected with 4 and 2, right? So and 1 also. So it is connected with 1, 2, and 4. 4 is connected with 1 and 3, and 5 is connected with 2, right? So each of this is like a linked list. We can definitely add more to this linked list. For example, if 5 and 6 are connected, so I can say, okay, in linked list of 5 you can add 6, and in 6, at the 6th position you can add 5. Okay, so why we are using this linked list? Because it is easy to add into this, so we can easily do a add operation, right? But how many linked lists do we need? Do we need one linked list? No, we need an array of linked lists. So this data structure is an array of linked list, right? So right now we are assuming a 1 based indexing, but it will be 0 based indexing. If I talk about array of 1, array of 1 is nothing but it is a list. What about array of 2? Array of 2 is nothing but it is a list. And what does array of 2 denote? Array of 2 denotes a list containing neighbors of 2, right? So if we implement this, right, so what we are going to store? We are going to store this, and we are going to form an array out of it, right? So this is what an array of lists look like. Some of you might ask, what happens if nodes are not numbered 1, 2, 3? Suppose they are numbered as Delhi, Mumbai, Jaipur. In that case, instead of using an array of lists, you can also create a hash map, right? Where the key is a string and the value is a list of string. That is also possible, right? That is also a way to implement a adjacency list. So in case of zero based numbering, it becomes easy because array indexes are numbers themselves. But if you have something complex like Delhi, Mumbai, Jaipur, Ahmedabad, you can also use a hash map in place of it, right? So I hope you are able to understand this concept. Now let us talk about advantages of this representation. So the first advantage is efficient storage. We are not wasting any space, unlike we did in adjacency matrix, right? So we are only storing the value of edges where the edges actually exist. So it is efficient in terms of storage, right? They are also useful for storing sparse graphs. That means um, which have much lesser edges compared to, like, what will be a dense graph. So if you have five vertices and you have, let's say, v square edges, in that case that means every node is connected with everyone. In that case adjacency matrix can be easily used, right? But if you have 5 vertices, 7 edges, it's kind of a sparse graph, right? Number of edges is much less than v square, right? And the biggest advantage is efficient retrieval of neighbors. As I told you that this is an important operation that we frequently do in algorithms like BFS and DFS. We can easily find neighbors of any node. If I ask you, okay, find neighbors of 3, what you need to do? You need to go to array of 3, which is an order 1 operation, and then you need to iterate on this list. So basically in order of neighbors time, if 3 has 3 neighbors out of 100 nodes, you can get those 3 neighbors in 3 units of time. You don't have to traverse the whole list of nodes, right? So this is a very efficient operation. Because of these two reasons, it is a very widely used. One is efficient storage, second is efficient retrieval of neighbors. This makes adjacency list a popular choice for graph representation and is used in many algorithms such as BFS, DFS, shortest path algorithms, and much more. Now let us discuss implementation of adjacency list. So let us start implementing graph using adjacency list. So we are discussing adjacency list implementation for the graph. One thing we need is the number of vertices. Next, what do we need? We need an array of linked list. So how do I create it? I can say list of what? List of integers. If I simply write adjacency list, this makes one list object, but I need an array, right? Now I need to initialize this array inside. Okay, this will be integer here, right? Because my collections does not accept primitive data types. I need to initialize this object in the constructor itself. What is the size of this list? That will be known when we are creating the graph object. So I can get the number of vertices, and I can say this dot v equals v, and I can say this dot adjacency list, this is equal to new linked list of integer. And how many objects do I need? I need v number of objects. Okay, so I have created an array in which this adjacency list, right? But right now this object is not created, right? Only an array is created. So what I need to create, I need to create a linked list at each index. So how do I do it? So I can say, okay, I will iterate over this I equal to 0, I less than v, I plus plus, right? So basically, when I say I'm creating this array, that means the array bucket can hold the address of a linked list. But right now that is null, right? So what do I want? I want this bucket to hold the address of a linked list object. So how do I create this linked list object? I have to use new, right? I have to say adjacency list of I, this is equal to new linked list. This actually creates an array in which each element is a linked list object, right? So this is the correct way of constructing a adjacency list. Now what do I need to do? I need to add elements into the linked list, right? So I will have a function called void add edge. So edges from u to v. What do I do now? I can say, okay, if there is an edge from u to v, what should I will do? And maybe I can accept, is it a undirected graph, right? If it is true, I will also add an edge from v to u, right? So I can say adjacency list of u dot add v, something like this. And if it is a undirected graph, I can say adjacency list of v. Oh, it will be boolean, right? Bool is in C++. Adjacency list of v dot add, something like this. Basically what I'm saying, that go and add an edge from 1 comma 2. So 0 1 2 3. So in first list it will add 2, and in second list it will add 1. Then I say, okay, go and add 1 comma 3. In first list it will add 3, and in third list it will add 1, something like this. Basically if 1 is connected with 2, 1 is connected with 3. If I read this, I see 1's neighbors are 2 and 3, right? So if I write it little more clearly, so 2 and 3, they have been added into the linked list which is at the first position, right? So this is how the add edge function looks like. Then I can display the graph. So I can write the toString method which is auto generated, and here, similar to the previous case, normal toString will not work. I want to iterate deeply into the data structure. I will use deep toString method, and this adjacency list will be converted into a string like representation that I can print. Now let us come to our main, which is here, and I have created a graph, right? I'm trying to add edges in it, and I'm trying to print it. So this I have already written before. So I'm just going to run this, and you can see the graph class we have just constructed now, right? Let us try to visualize this graph. So 1 is connected with 2, fine. Undirected graph. 0 is connected with 3. Okay, 1 is connected with 3 and 2 is connected with 3. So this is how the graph looks like. And now if you talk about the adjacency list, so 0 is connected with 3. Okay, 1 is connected with 2 and 3. 1 is connected with 2 and 3. That's correct. So list of 1, it is storing the neighbors of 1. List of 2, so 2 is connected with 1 and 3. Absolutely correct. What about 3? 3 is connected with 0, 1 and 2. So three adjacency list of 3 storing neighbors of 3. This is how this 2D array. Okay, it's not a 2D array, it's a array of linked lists, right? Each linked list is denoting the neighbors of the ith node, right? That is the adjacency list implementation. I hope you are able to understand this implementation. So pretty easy, nothing fancy, nothing difficult. And if you have more complex data, as I told you, instead of having this, you can also have a hash map where key is your this will become your key, and this will be added into the list corresponding to that key, right? That's all for this implementation. Okay, so we have discussed the most commonly used implementations of the graph: adjacency list, adjacency matrix, edge list. There is one more representation that is sometimes convenient for certain type of problems. Okay, so sometimes we are given a graph in which we are saying, okay, there is a 2D matrix and it is given that each cell is connected with, let's say, the 4 neighbors, something like this, or each connect cell is connected in the 4 neighbors which are of the similar color, right? And you have to do something, right? So in this case, what you have to do, you do not need to construct a graph, you can directly deal with the matrix, right? So if I say, okay, what are the neighbors of this one? Either it will be 4-way connectivity, it will be mentioned in the question, then you can go in these directions, or it can be 8-way connectivity. That means the diagonal directions are also included. This kind of representation is helpful in some algorithms like flood fill, right? So what is happening in flood fill? There is a 2D image which is made up of some pixel values, right? So you are filling the color until you hit the black boundary. And how are you finding the neighbors? You are going in this 4-way connectivity or doing the 8-way connectivity, right? So this is not possible for every type of graph, but certain problems where graph could represent an image, right? Or the neighbors have this kind of relationship where they can be represented using a 2D array, right? So we will deal with these kind of problems in the series, and I hope you learned a lot of concepts from today's video. So let us talk about graph traversal first. What is actually is a graph traversal? So graph traversal, also known as graph search, is a way or is a process of visiting each vertex in a graph. Such traversals, as I told you, are classified into two types. One is BFS, which stands for breadth first search, and it is a iterative way to traverse the graph. And second one is a recursive way called depth first search. In this tutorial, we'll focus on BFS and its applications. So BFS actually has many applications, and one of the most commonly used application is finding shortest paths in undirected graphs. We'll also look at such applications in this tutorial. So let us start talking about BFS. So it is a technique for traversing a finite graph. That means the number of nodes in the graph would be finite. And the way it works is it visits the sibling nodes before visiting the child vertices. So what does it mean? If you have something like a node A and it has children like B and C, and then you have some children like D and E, and so on. So the way it works is, if you look it in the form of a tree, suppose this graph is a tree. Now this is not a tree because I'm added one more edge here. So the way it works is it will visit this node, then it will come at B, but it will visit sibling of B, that is C next. So it will visit BC, then it will visit DEFG and so on. So in a way, if you look at in the form of a tree like traversal, it is like a level order traversal that we have done in a tree. But in a graph, it will be quite similar, but there is one catch. The catch is graph contains a cycle, right? We have to make sure that we are not visiting a node which is already visited. For example, from this node 1, if you visit 2 and 2 is connected with 3, 3 is connected with 1. So there is a cycle. So if you say, okay, I'll visit 1, I'll visit children of 1, that is 2, I'll visit 3. From 3 now you cannot go and visit 1 again, right? So this is something we have to make sure is handled properly by our algorithm. So before I dive deep into the algorithm or into the code, let us try to understand some applications of BFS. BFS can be used to find all the vertices within a connected component. So we want to see what parts of the graph are connected. It is also used to finding shortest path between two vertices in case of a undirected graph. That means all the edges, sorry, unweighted graph. That means all the edges, they have equal weight. There is no weight assigned to any edge. If it is a weighted graph, then we have to use a different algorithm. It can be used to check a graph for bipartness. It can be used for cycle detection in undirected graphs. It is also used in Ford-Fulkerson algorithm for maximum flow. It is also used in serialization, deserialization of binary tree. It is also used in maze generation algorithms, and it can also be used in algorithms like flood fill. So there are many applications, and that is why understanding this algorithm becomes very important. So let us now dive deep into the algorithm. Now suppose a graph like this is given. So what kind of graph it is? In my case, it is a unweighted graph, and it is also a undirected graph. That means edges don't have any specific direction. If 0 and 2 are connected, 2 and 0 are also connected. So we can go both sides, right? So now in this algorithm, what is the input? The input is a source vertex. That means you are given a starting point. From that point, you have to traverse the whole graph. The starting point could be 0, it could be 3, it could be 6, it could be any node. So just to keep things simple, I'm going to take 0 as my starting point, right? And let me also draw the adjacency list that could be possibly input for this algorithm. So that means 0 is connected with 2 and 1. 1 is connected with 0 and 4. So neighbors of 1 are 0 and 4. Neighbors of 2 are 0, 3 and 4. So 0, 3 and 4. Neighbors of 3, they are 2 and 6. Neighbors of 4, they are 1, 6, 5. So I'll write it as 1, 5, 6. Then I have neighbors of 5, which are only 4, and neighbors of 6, which are 3 and 4, right? One thing I told you, that if you start from this node, right? So what we need to do, we'll be using a queue in this algorithm. You will understand why this queue is going to be very helpful. Let me draw a data structure here, which is a queue. Apart from it, we will also need something to maintain whether a node has been visited or not, right? Because the graph contains a cycle, and it is possible that we are coming to the same node again and again, right? So this is a queue. It is a empty queue as of now, right? The queue, you know, it has a FIFO property, first in first out property, right? So it is a FIFO queue here, and apart from it, I'm making one more data structure, which is going to denote whether a node has been visited or not. So 0, 1, 2, 3, 4, 5, 6. I think this is sufficient. We don't need. So we will mark whether a node is visited or not. So right now it is nothing is marked, nothing is visited. We'll start from this node, that is the source node. Let's just assume the source node is 0. We'll mark it and we will put it into the queue. 0 has been visited, 0 goes into the queue, and I am going to mark it as visited. So here the circle denotes the queue has been visited. Now what you will do next? You will look at this adjacency list. You will find out the neighbors of 0. The neighbors of 0 are 2 and 1. So you will pop this node out. The node is 0. You will look at neighbors of 0, that is 2 and 1. You will mark them as visited and put them into the queue. So you from 0 you can easily visit 2, and you can easily visit 1. What I'm trying to do is I'm marking 1 and 2 as visited, and I'm putting 1 and 2 into the queue. So first I visited 2 and then I visited 1. Both of them, they are into the queue. That means I've marked 1 and 2 as visited. Now what you will do next? Nothing. You simply have to pop out a node from the queue every time and do the same process again. So now you will remove 2. Look at the neighbors of 2, which are 0, 3 and 4. Now 0 is already visited, so you do not do any work at 0. Then 3 and 4. 3 is not visited. You can visit 3. So mark 3 as visited, put it into the queue, and mark 4 as visited and put it into the queue. Okay, now 2 is gone, 2 has been removed. Next node you will get from the queue, it is going to be 1. So you will remove 1 from the queue and you will mark neighbors of 1 as visited. So neighbors of 1, 0 and 4. So look at 0. 0 is already visited. 4. 4 is also a neighbor. 4 is already visited. So you do not do any work. So you do not do any work, right? So in the meanwhile, you can print the nodes that you have seen so far. So you have seen 0, you have seen 2, you have seen 1. Next, you will pop out 3. So remove this node, print this node, look at the neighbors 2 and 6. So 2 is already visited, do nothing at 2. 6 is not visited. So mark 6 as visit, put it into the queue. So you have traversed 6 as well. So 6 is now also into the queue. Next, you will pop 4. So print 4, look at neighbors of 4. 4 neighbor is 1, which is already visited. Its neighbor is 5, which is not visited. So you will visit it, put it into the queue. 6 is already visited. Nothing to do here, right? Next, you will get 6 from the queue, remove it, print it, and now look at neighbors of 6. 6 neighbor is only 3 and 4, right? But both of them they're visited, so you will not do any work. So next you will remove 5. 5 neighbor is 4, so this is also removed. 4 is already visited, hence you do not do any work. And now what you can say is that your traversal is done, right? Your traversal is done. So what happened during this traversal? So we visited each node once, and in the worst case we are traveling through all edges once, right? So what we have done, like we have traveled through some edges, and we also checked that from 4 I can go to 1. So we did check this edge, right? We did check this edge. 1 was already visited, so we did not mark anything here, right? So we did not mark anything here. What I'm trying to say is, when you're running this algorithm, each vertex is going into the queue once, and it is coming out of the queue once. And when you're finding the neighbors of a node, you're traveling through all the edges, right? So all the edges are being covered at most twice. For example, neighbor of 4 is 6, neighbor of 6 is 4. So each edge is counted at most 2 times. So if I talk about the overall time complexity of this algorithm, it will be linear in terms of number of nodes and number of edges. This is what we are doing, right? So I hope you have understood the basic BFS idea. Next, we will look at the implementation and code this algorithm. So let us discuss the implementation of BFS. I already have the boilerplate code ready, which is basically adding edges into the graph. So the BFS function is something that I'm going to write now. So return type is void. We do not want to return anything. The method name is BFS, but what we may expect as input is one source node from which we should start doing the BFS for this graph. So this is the graph. So I told you we will be needing 2 data structures, one to maintain whether a node has been visited or not. So I can maintain a Boolean visited array, and this will be a array of size v, where v is the number of vertices in the graph. Next thing I will need would be a data structure q. So in Java we have q as an interface. So I'll create a linked list which provides me with the implementation of q as well. So linked list of integers, we will just call it as q, and I will say this is equal to new linked list. All right, so these are the data structures that we will be needing. Now let's start with the algorithm. So in the first step, what I will do, I will start with the source node, mark it as visited, push it into the queue. So I have to do 3 things. Mark it as visited, so visited of source is going to be true. So I will say okay, this is going to be true, and then I will traverse the neighbors of this node. So first thing I will do is I will push this into the queue. So I can say queue dot add last. The node is source. Okay. And second thing I will do is I will mark this as visited. The visited of source, this is going to be true. Now what can I do now? I can say while my queue is not empty. So I will stop once all the nodes have been popped out. So how do I add into the queue and remove from the queue? So if you have to add something into the queue, that addition will happen from the ending. So add last. And if you have to remove something from the beginning, so we can call remove first method. So I can say okay, the node at the front of the queue. So that is int node. This is going to be queue dot remove first. All right. Now what can I do? I can say, okay, for this node, so node that I've removed from the queue is 0, right? So I need to traverse what are the neighbors of 0. So 0's neighbors are there in adjacency list. So they are 1 and 2. So what I need to do, I need to traverse on these neighbors. If the neighbors are not visited, I will mark them as visited and I will push them into the queue. So this is what I do. So I can say, okay, for every neighbor. Okay, so to get the neighbors, what we can do, we can use iterator. I can create a iterator of the type integer and call it something like iterate it, and now I can say give me the neighbors of this particular node. So if you know this is the adjacency list I. So I want to iterate on this adjacency list of the node. So I can say, okay, while it dot has next. That means the next node is present. Basically, it is a way to iterate on the adjacency list. Sorry, you have to call a method called list iterator because we are iterating on the linked list. So zeros neighbors are 1 and 2, right? So these are stored in a list, which was a list object. So adjacency list of node is a list. We have to get the iterator using this method, list iterator. So it will iterate over these nodes until the list is not finished. It will go over these neighbors. Now I want to get the node, right? So how do I get the node? I can say, okay, the neighboring node is nothing but it dot next. That is the neighboring node. And now what I need to do, if it is not visited, if not visited neighbor, what do I need to do? I need to mark it as visited. I can say visited of neighbor. This is equal to true, and I need to add it into the queue. So I can say queue dot add last, and the item is neighbor. We are iterating over all the neighbors, and if the neighbor is not visited, we simply mark it as visited and we push it into the. So I hope this should suffice. And one more thing we can do in the while loop is we can print out the node. We can see what output do we really get. I can say sout node. Now let us test our algorithm on the graph I have already constructed. So let me show you. In graph main I will go, and this is the graph, same as this graph, and now we are going to run bfs function on it. I can say g dot bfs. Let's say the source node is 0. So let's go and run this code and see what output do we get. We should get all the nodes from 0 to 6 because we are doing a graph traversal. Let's see the output. Okay, we got an error, index 6 out of bounds for an array of length 4. Okay, so here we have to give, we have 7 nodes actually. Input needs to be fixed. Okay, so this is our adjacency list, and we are getting 0, 1, 4, 3, 6, 5. So we are getting all the nodes. That means the graph traversal is correct. Now the exact output will also depend upon the way you have stored these nodes. Okay, so you said, okay, 0's neighbors are 1 and 2. After 0 it will print 1 and then 2. But if you say in my adjacency list I will store 2 and 1 first, that means I will add this edge before this edge. Then the output will be 0, 2, 1 and so on. So right now our goal was to visit all the nodes which can be reached from node 0. So we are getting 0, 1, 2, 4, 3, 6 and 5. That means this output is correct. We are able to reach all the 7 nodes including 0. Now let us discuss one application of finding the shortest path from the source node to all other nodes. Okay, so what we are going to do, we're going to do shortest path from source to all other nodes in a undirected graph, in a unweighted graph. Unweighted graph. So this graph is an example of an unweighted graph. So graph can be directed or undirected, but it must be an unweighted graph for the BFS algorithm to work for finding the shortest path. Right? So we are going to talk about BFS shortest path algorithm. So the algorithm is very simple and it is very similar to just doing BFS. Let us try to visualize what we are doing in BFS. We are starting from node 0 and we can mark the distance of 0 as 0. And from 0 we are visiting the nodes 1 and 2. Since we are visiting a node for the first time, we will be updating their distance and we will be saying this distance is 1 and this distance is also 1 because we are coming from 0 and 0's distance is 0. Next, in the queue what you have done, you have said okay 0 is there, then you pushed 1 and you pushed 2 and so on, right? Now next item you will pick is 1 and you will update the neighbors of 1. Neighbors of 1 is, let's say, 4 and 0 is already visited, so you will not go there. So you will say okay, since I'm visiting 4 via 1, this distance must be 2. So distance of 4, I can say distance of the neighbor is 1 more than the distance of the parent. So parent is 1. Okay, so distance of parent node is 1, child node is 4, or the neighbor node is 4. 4's distance is 1 more than the parent. So I will visit 4 and I will push 4 into the queue. So next I will remove 2. So 2's neighbors are 0 already visited, 3 is not visited, so I can visit 3 and I can say okay, this distance is going to be 2. So I will push 3 into the queue and 2's neighbors is also 4, but 4 is already visited, so we will not update it. So it is not possible that you are reaching a node later which is already visited and the distance will get minimum. It's not possible in case of a unweighted graph. If it would have been weighted graph, this could have been possible, right? Now 4 is already visited and since you are reaching from 2 again, node is already visited, so this distance will be either greater or equal to 2. So we will not update it, so we will not do anything at 4. So 2 is done, 2 has done its work. Next we will pop out 4 and 4 can now update its children. So 4 children are 6, so this distance is 3, so you push 6 and 4 can also update 5, so this distance is also, you can push 5. Next you can pop out 3. Now 3 again, it will try to visit 6 but 6 is already visited, so hence you don't do any work. Then you try to pop out 6, so you can remove 6 easily, but there are no neighbors of 6 which are not visited. Then you pop out 5, there are no neighbors of 5 which are not visited. So if you look at these values, you will find that these are the shortest distances from 0 to all these nodes. These are the shortest distances from 0 to all these nodes. So that means distance of 0 is 0, distance of 1 is 1, distance of 2 is 1, distance of 3 is 2, distance of 4 is 2, distance of 5 it is 3, and distance of 6 it is 3. So one observation we can make out from here is that BFS visits nodes in increasing order of their distance from the source node. This distance was 0. These two distances were 1. These two distances were 2. And these two distances were 3. Right? So this is an observation, right? So when I said you can get any ordering, so that means between these distances the ordering can change. So BFS might produce an output like 0 to 1. It might produce 4 3, it might produce 3 4. 5 6 might get 5 6 or 6 5, right? So different orders, but the distances of these nodes will be in increasing order from the source node. So that is how we can find shortest path from source to all other nodes in a unweighted graph by simply using the BFS. In the next part, we'll show you the code changes that we need to do for this algorithm. So it is very simple. Take a moment, pause the video and think what changes you will make into the code. Alright, so let us discuss the code changes. Now, apart from the visited array, what you need to do, you need to maintain a distance array. The distance of each node from the source node. So you can say, okay, I need a distance array which is of size v, and in the beginning you can say distance of source You can update that distance of source as 0, and rest is very simple. As you are visiting more and more nodes, you need to update the distance. So you can say, okay, I'm going to visit the neighboring node. So when I'm visiting this neighboring node, I can say distance of this neighboring node is 1 more than the distance of the node that is parent of this node. So that node is nothing but this node. So this node is distance of node. So that's it. Now what we can do in the same function, maybe we can either return the distance array or we can just print the distance array. So here I can say, let's just iterate over the distance array for I equal to 0, I less than v, I plus plus. I can show the node, which is going to be I, followed by the distance, which is distance of I. So let's go and run this code and we should see. We're getting node 0 at distance 0, 1 at 1, 2 at 1, 3 at 2, 4 at 2, 5 and 6 they are at distance 3. This is how easy it is to make changes in the code. And now we have made shortest path algorithm using BFS. Now some of you might be wondering that, okay, we have figured out the shortest path, but we have only figured out the distance actually. What if I actually want to figure out the exact path from, let's say, 0 to some node 5, right? Maybe I want to find out what is the shortest path. Should I go like this, or should I go like this, or should I go like this? What will be the shortest path from source to destination in a unweighted graph? So again, this thing is very simple. So what we were doing BFS. 0 was visiting 1 and 2, 1 was visiting 4, 2 was visiting 3, and 3 was visiting 6. No, I think it was like this. 4 was visiting 5 and 6, and then 3, something like this we did, right? So now again, if you want to find out the shortest path to reach 5, you will know that, okay, 5 was visited from 4, 4 was visited from 1, and 1 was visited from 0, right? What you can get, you can actually store the parent. So you can store parent of 5 is 4, parent of 4 is 1, parent of 1 is 0, and parent of 0 is, let's say, 0 or minus 1, anything you can put. What you can do, you can store these parents for every node, and then you can do trace back. You can say, okay, I'll start from 5, and okay, from where I should go. So this is my destination node. Who is the parent of 5? How do we arrive at 5? We came from 4, so I can go to this node. Okay, how do I came at 4? I came from 1, so I can go to this node. How do I came at 0? I will go to 0. Okay, how do I came at 1? I came from 0, so I go to 0. Who is the parent of 0? Minus 1. That means we have finished the entire path. In this way, you will be able to store 5, 4, 1, 0 in an array or in an array list. So this way, you can also print the shortest path from the source node to the destination node. The only changes in the code you need to make is you need to create a parent array, and when you're visiting from a node to a neighboring node, so you can say, okay, parent of neighbor will be equal to node, something like this. And then you can simply put a while loop at the end. Once all the nodes have been updated, your BFS has been done, you can say, okay, while I don't get the source node, let me travel back from the destination node. So you will travel this way, and you will eventually reach the source node. So this is something you have to try, you have to figure out, you have to make the required code changes in the algorithm that we have discussed. Now we will discuss one application of BFS in solving a problem. So we are given a snakes and ladders board which looks like this, and what we need to do is we need to find out the minimum number of moves that are required to go from source, which is from cell 1, to destination, which is cell number 36. So first of all, we need to decide whether it is a graph problem. So if you look carefully, you can analyze that we can clearly see there are 36 vertices. There are 36 nodes where you can go. So clearly we see vertices. But how do we decide the edges, right? So basically the question says there is a regular dice. So on your dice, you can throw any number of your choice from 1, 2, 3, 4, 5, 6, right? So the rules of the board are very simple. Whenever there is a ladder, you can climb that ladder. but whenever there is a snake, you will be cut by the snake and you will reach the tail of the snake. So you can cut down from head of the snake and you can reach the tail, this position, right? So basically, like in any snakes and ladders game, you have snakes which can cut you down and bring you down, and there are ladders which you can climb and move to the top. The question is, how many minimum number of dice moves will be required to reach this destination? So you can assume there is only one player, it's not a two-player game. So the question is only about finding the minimum number of dice moves. We need to think carefully what kind of graph it is. If you analyze carefully, you will analyze that if we look at the dice moves, so at 1 you can throw a 1, that means you can reach 2, but at 2 there is a ladder. That means you will reach 15. So if I talk about this edge, there is an edge from 1 to 15 in this graph. Then if at 1, if you throw a dice 2, you can reach 3. There is an edge from 1 to 3 also. If you throw a 3 on dice, you can reach 4. That means there is a edge to 4 as well. And all of these edges are directed edges. And then if you throw a 4, you will reach 5, but on 5 there is a ladder. So that means the edge is from 1 to 7, right? And if you throw 5, you can reach 6. So that means there is an edge from 1 to 6 also, right? Now, if you throw 6, you can also reach 7. That means it is the same edge. We will not count that edge again. Again, starting from 2. So 2, there is a ladder, so we do not need to do anything. Then you go at 3. So from 3, again, there are edges. So there is an edge from 3 to 4. If you see carefully, from 3, you can go to 4 and so on. From 3, you can go to 7 also. From 3 to 7, there is an edge and so on. That means how many edges I have. So I have approximately 6 edges starting from each vertex, from approximately 6 edges from each vertex. Okay, so if the vertex is V, I can go to V plus 1, I can go to V plus 2, I can go to V plus 3, V plus 4, V plus 5. This would have been the case if there was no snake and no ladder. But now what is happening is, suppose I go to V plus 1. Here there is a starting point of the ladder. So that means I will reach at some other position. So that means there might be a factor which will add up or which will be subtracted, and that factor will come from if there is a ladder at that position or if there is a snake at that position, right? That is what I'm saying, that it is an example of a directed graph. It is an example. Is it a weighted graph? The answer is no. It is an example of unweighted graph. That means all edges are equal, because the cost to cover any edge is dice throw. So it does not really depend what number you throw on the die. Each move is counted as one throw, right? So if you analyze carefully, you will see it becomes an example of a directed unweighted graph. And if it is unweighted graph, we can use the BFS shortest path algorithm to find out how do I reach this node, right? So in this case, if I analyze little more carefully, I will see from 1 I can go to 15. From 15 I can throw 3 and I can reach 18. 18, there is a ladder, I can reach 29. In order to reach 29, I just need 2 moves. Then I can throw 1 to reach 30, and then I can throw 6 to reach 36. So I guess in 4 moves I can easily finish this game. So I hope the problem statement is clear. Now it's your turn to figure out how do we construct such a graph, take input such a graph. So regarding input, you will be given the number of vertices, the number of snakes, the number of ladders, as well as the position of the ladder. For example, 2 to 15 there is a ladder, 5 to 7 there is a ladder, right? Similarly, positions of snakes will be given as pairs. 17 to 4 there is a pair, right? So take a moment to think, how do you input such kind of a graph and how do you make your BFS algorithm run on it? Alright, so let us discuss how we are going to build the algorithm. So I have written some boilerplate code, it's not the complete code. So I'm going to read some inputs. I'm going to ask enter the number of vertices, source and the destination. So I'm going to read these 3 things. After that, I will create a graph. Since I know the number of vertices, right? I can create a graph object, or I can do it later on as well, that's fine. And I'm going to read the number of snakes and their positions. So in our scenario, we have 1, 2, 3 and 4 snakes. Number of snakes in my case are 4, and these are the positions of the snakes, 17 to 4. So I'm taking in this direction, head to tail. So that means 17 to 4. If there is a snake, you look carefully, 17 to 4. This is the snake. Similarly, I'm reading the letters in this direction. 5 to 7, there is a ladder. So 5 to 7, there is a ladder. Now the question is, how do we like handle this data? What should I do with this data? So first of all, I need to read this and I need to make sure that this data is used in my construction of the graph. Earlier we were creating a hard-coded graph, so we'll not do that thing here, right? So we'll create our own graph. So first thing is, here I'm just reading the number of snakes. I'm not reading what snakes I have. So I need to implement logic for that as well, right? This part I'm going to do it right now. So let's try to understand how we will actually create a graph. So we'll create a graph object C, and we will, of course, we'll try to add edges to it. Add edge. Now in edge, you need to know that from where the edge starts and where the edge ends, right? And it is a directed edge. So it's not a undirected graph. So I will set this third parameter as false. So now if I talk about vertex 1, so I told you from 1 I can go to, let's say vertex I can go to I plus 1, I can go to I plus 2, I plus 3, I plus 4, I plus 5, I plus 6, and plus something, right? This value could be 0, this value could be positive value, this could be negative value. What is this something going to be? It will depend upon whether there is a snake or a ladder starting from that position. For example, I plus 1. So at 2, I have a ladder which gives me, which actually takes me to 15, right? Which is actually taking me to 15. That means I'm getting a jump of 13, right? So for example, if I is 1, I take a move of 1, I reach 2, and 2, there is a ladder which is giving me a jump of 15 minus 2, right? So basically there is a ladder. So the delta that is given by the ladder, right? So if I go to, let's say, I plus 3, so there is no ladder here, so this delta will be 0, this delta will be 0. I plus 4, I reach 5. At 5 I actually reach 7, so this delta is 2. How do I compute this delta? This delta I have to compute and store it in an array. I have to compute and store it in an array. So that means in an edge, this becomes the starting point and this becomes the ending point of the edge. So this delta is very easy to compute. For example, you are given there is a ladder from 2 to 15. You can easily say, okay, I'm going to store it in some kind of array. Let's create a board array, right? So it's a 1D array of 36 positions, and in each position I'm going to store a delta. If someone says, okay, there is a ladder from 2 to 15, that means at the second position in this array, I can store 15 minus 2, that is 13. So at the second index in this array, I can store 13. So if there is a snake at, let's say 32, which takes me at 30, let us assume this index is 32. So at 32, I get a delta of minus 2. So if I reach 32, effectively I reach 30. So 32 minus 2. So this is how I'm going to do it. Once all the edges have been inserted into the graph, I can easily run BFS on it. So let us try to insert all these edges into our graph. So what I'm going to do, I'm going to run a loop. Let's say for I equal to 0, I less than snakes, I plus plus. I can say, okay, snake has a head and snake has a tail. So I'm going to read these values. So I can say head equal to scanner dot next int, tail equal to scanner dot next int, and I'm also going to create a board array. So the board array can be created here. So int board, and this is equal to new int. How many? So I'm going to do v plus 1 because it is a 1 based indexing here. So I've created a board array. Oh, I have to move this code here because v is not input yet. So this board array will come here, or you can do it like this. That's fine, that's fine. Board array is now created. So now when I'm reading the snakes, right, so I have to update the board array. So I can say, okay, board of head. So in case of snake, the snake is going to bite from the head, right? So board of head will store a value that is equal to, because now it is giving you a decrement. So from 17 you are going at 4, right? Let's look once again. From 17 you are going at 4. So board of 17 should say that my value is nothing but 4 minus 17. So this value should be minus 13. So this is how it should be. So it should be equal to tail minus head. So tail is a small value, head is a large value. So this value needs to be negative. This will update the board array for snakes. Similarly, we need to update the board array for ladders, and we will utilize this array while constructing the graph. I will show you how. Make a similar loop. I have the ladders. Instead of snakes here, I will have ladders. Now the ladders are given in this fashion, bottom to top. So ladder also has a head and it also has a tail. So tail is, this number is smaller, this number is bigger. Tail minus head would be a positive number here. That is fine. So I think board array looks fine. So I can just display you the board array as well. So I can say sout arrays dot toString, and I can give the board array. Now I have this board array, I have these delta increments. Again, I need to figure out how do I insert all the edges. Now that thing is fairly simple. You need to go to every vertex and create the next 6 edges that will start from that vertex. For example, if I start from 5 or if I start from I can go to I plus 1 plus board of this position that you have reached. If you do 5 plus, let's say, some number 5, or 5 plus 4, you reach 9. But 9 is not the end position. You actually reach 27, right? I plus 2 plus board of this position. I plus 3 up to I plus 6. Basically, from ith node where I can go. So here I'm going to use the board array to decide where I can actually go. So this will be board of I plus 1, board of I plus 2, and so on. So let's see here as well. So let's create the graph now. So I have graph G. How many vertices I have? I have V vertices. So I'll just keep V plus 1 because it is 1 based. So we are also adding 0 here. This is equal to new graph. New graph of V plus 1 vertices. Alright. I have to add edges, right? So I can say, okay, for int, let's say source, which starts from, or let's say I'm going to add edge from I to something. So I to some j. Okay. So if I goes from, I can start from source, which is 1, the smallest node. I can go till less than destination, that is my last node, I plus plus. So I'm going at every node, and I can throw a dice at every node. I can throw 1, 2, 3, 4, 5, 6. So I can throw a dice. Dice can take a value 1. The maximum value dice can take is 6, and I can say dice plus plus. So what is the node at where I'm reaching? The jth node is I plus dice, right? But this is not final. I also have to add delta. So I can say, okay, j equal to j plus board of j. So in this value, what I'm saying is, from I you throw a die, you reach I plus dice. Now at this position, it is possible that there is a ladder. The ladder gives you a jump of 13. So you have to add this factor also that is stored in board of j. But if there is a snake that takes you down, so you have to decrement this value also. That addition subtraction is already handled in the board array. Now if j is less than equal to destination, that means I do not want to add any edge that goes out of the board. So I can say g dot add edge. So u is my I, v is my j, and it is not an undirected graph, so this value is going to be set to be. This completes the graph creation process. Now what we need to do, we need to run BFS algorithm on it. So as you know, we have already implemented the BFS algorithm. I'll just copy this code and tweak it a little bit so that we can do it for this particular problem. So I can say BFS.s path. So in this case, I am getting source, I am also getting the destination. So if the user is interested in finding out minimum number of moves, so you do not need to print distance every node. You can simply return the distance of destination, and you can change the return type to integer. This can be done. Now, one thing might ask is user might ask you to give the path also. So as I discussed with you, along with the visited array, you can create a parent array as well. And you can say, okay, this is equal to new integer of v. And here you can say, okay, for first node, that is my source node, the parent is, let's say, -1. So parent of source, this is -1, or you can set this is the source itself, something like this, so that you can know, right? Right now I'm just saying this is going to be -1, and whenever you visit a node, you can set the parent of neighbor is going to be the node. Now, as I told you, you can backtrack and you can find out the complete path as well. Let us discuss that thing as well. If you want to do the path printing, that is fairly simple. You can start from the destination node, let's say 36. Now 36 nodes from where I was visited. So maybe the parent of 36 is 30, right? So I can start from this node, reach this node, again ask the parent, go back, and so on. I can trace the path until I hit 1 or -1, something like that. So I can say fine, I take a temporary value which is destination, and I can say while parent of destination or while parent of temp is not equal to -1, what do I do? I say, okay, fine, I will print out the destination. I will print out the temporary node. So basically what I'm saying is the temporary node is this. Temporary node is 36. I will print it out and I will go here. This will become the new temporary node. But how do I update this temporary node? So fairly simple. Temp equal to parent of temp. At every node, I take it back to the parent. So this is basically going back to the previous node in the path how it was discovered. Then I'm saying return the distance of the destination. Now let us go and run this code. I think it should be fine. Yeah, it seems fine. So let us try to execute the code. So I've given the input, I've just combined the input and I'm giving it, but now I'm getting a error. Actually, I will tell you what is the error. So it is saying exception in thread main, index 38 out of bounds. So in main, this is the array. So this is going out of bounds. Why this is happening? Because if you add something to, let's say, node 35, you say, okay, I will take a jump of 3. You will actually reach 38. So actually I'm checking it here. So instead this check should be done here, right? So when I'm doing this value, when I'm computing this j, so I should do this thing here. If j is less than equal to destination, then I should do j equal to board of j. And again I should check if j is, you can do it here. Yeah, that is fine. So if j is now less than equal to destination, then you can actually add that edge. I think this would be okay. Or you can do two conditions here, right? So you need to check that. See, what is happening is I added something here. I said, okay, 35 plus 2 or 35, or let's say 33 plus 2. Okay. And suppose there was a ladder here, right? It's not going to take you out. But what I'm checking is that when I'm adding this value board of j must be less than destination. And when I'm adding the edge, that edge must be less than destination. Let me run the code. Okay, so I think I commented out the shortest path. Let's rerun this code and it should be good to go now. So we do not need to print each and every node while traversal, right? One more attempt and then we should be good to go. We are doing BFS, we are printing the output of traversal, which we don't want. So let's paste the code. And here we are getting, yes, this is the correct output. So we are getting the path and we are getting the shortest length. That is going to be 4. If I show you, this is the path that we are getting. From 1 we went to 15, 29, 30 and 36. And it took 4 number of moves. 4 moves were required to cover this. You can verify also. 1, 15, 29, 30, 36. From 1 we went to 15. Then we went to 29. Then we went to 30 and then we went to 36. Yes, these are the 4 moves that were used. So I really hope you understood this algorithm really well and the application of BFS we have seen through this problem. Let's try to understand this algorithm called depth first search, or sometimes called as depth first traversal. So it's an algorithm for traversing the graph or searching the graph. It can be used on tree. So on tree, the pre-ordered traversal that you have done, it's actually a depth first search. The algorithm starts at root node. So in case of graph, there is no root node, so you can arbitrarily you can select any node as the root node, and or you can have some specific node, and you have to explore as far as possible along each branch before doing the backtracking. So we'll try to understand this through an example. And of course, this algorithm, since you are doing it recursively, uses extra memory, which is usually a stack. So if you're using a stack, in case of recursion, it will be created automatically. Even if you are doing this algorithm iteratively, you can maintain a stack like data structure and do the work which is needed to keep track of nodes discovered so far along a specific branch, which helps in the backtracking in the graph. We'll understand this concept when we are running through the algorithm. And this DFS has many applications. Some of the applications I have listed down here. It is used in finding out connected components. You can also use BFS here. Basically, you want to look at what components of the graph they are connected. So for example, if this is a graph, this whole thing is one graph, it has two connected components. So you can do a traversal from this node, which will actually visit this whole component, and you can do a traversal from maybe this node, which will visit this whole component. So we'll do a separate tutorial on connected components. Topological sorting, it can be used. It is also used in finding out bridges in a graph. Cycle detection, it can be used. We'll look at cycle detection in this tutorial. Strongly connected components is a different concept which is used in directed graphs. So DFS again is used there, and it can be used to solve puzzles with only one solution, such as mazes. Maybe you want to find out a path in a maze. Maybe there is only one solution, so you can easily use DFS along with backtracking to find out that particular path. It can be used in maze generation with the randomized DFS algorithm, and it can also be used in finding bi-connectivity in graphs. So let us try to understand the algorithm next. So DFS can also be used on a tree. So if you have this tree, so what this DFS will do, it will start from, let's say, root node. It will go in this direction, here, here, here. Then it will backtrack and it will enter into these branches. So it's just like a pre-order traversal that we have done on trees. But in case of graphs, the situation is little different. Why? Because graphs can contain a cycle. So we have to see what to do in case of a graph. Let us try to understand with the help of this graph how DFS will actually work. Let me draw the adjacency list as well. That will be input, and that is how the graph is actually stored. With 0 we have the neighbors which are 1 and 2. With 1 we have the neighbors 0 and 4. With 2 we have the neighbors 0, 3 and 4. With 3 we have the neighbors 2 and 6. With 4 we have the neighbors 1, 2 and 6. 5 we have only one neighbor, that is 4. With 6 we have two neighbors, that are 3 and 4. So this is how the adjacency list of the graph will look like. Now we need to understand how this DFS is actually going to work. So we are going to start from this node. It can be any node. So I'm going to take 0 as the starting node from the source node. And now since the graph can contain a cycle, I need to maintain a visited array. So I'm just drawing it here. So initially nothing is visited. So this is a visited array. 0, 1, 2, 3, 4, 5, 6. So I need this much array, right? I'll call it visited. This will help me to ensure that I do not visit the same node again. If it is already visited, we'll just backtrack, we'll go back. So I start with 0. I said fine. I will mark this as visited. And since it's going to be recursive algorithm, so this node is in the stack. Now 0 can say, okay, what are my neighbors? Neighbor of 0 is 1. So it will pick this node, the first node. I will try to iterate, but first I picked 1, and I will make a DFS recursive call on 1. So I will go to this node. So I'll mark 1 as visited. So 1 is in the stack also. And now from 1, I can go to some neighbors, right? So 1's neighbors are 0. So 0 is already visited, so I will not go here. If I go, I just come back, right? So I say, okay, this or I will not go. So this node is not visited. This 0 is already visited, so I will not make a call. But what about 4? 4 is visited, so I'm iterating on this list. So 4 is visited, right? So I make 4 is not visited, I make a call on 4. So I go and visit this node 4. So 4 is marked as visited and 4 goes into the stack. So I think on the diagram you should also see a 0 here, right? Before 1 you have a 0, right? So this portion got little cropped out from the screen. So 0 1 4. This is how the stack looks like at the moment. At 4 I again do the same work. I look at what are the neighbors of 4. The neighbor of 4 is 1, which is visited, so don't do any work. The neighbor is 2, which is not yet visited. Now what 4 will do? 4 will visit 2. I'll go and visit this node. So 2 is visited and 2 is now part of the stack. Now at 2 I look at what are the neighbors. The neighbor is 0, which is visited. The neighbor is 3, which is not yet visited. So I go to 3, this node. So I mark this 3 as visited and I come to 3. So what are neighbors of 3? So it is 2 and 6. 2 is visited, I don't do any work. 6 is not visited. So I go and visit 6. I go here. So 6 is marked as visited. So 3 is in the stack, 6 is in the stack. Right? Now at 6, I look at the neighbors. The neighbors is 3, which is visited, don't do any work. Another neighbor is 4, which is also visited. So don't do any work. Now what I can do? So 6 is already visited and 6 does not have a neighbor which is not yet visited. Right? So what you will do? You will go back. This is important. So this is backtracking. So you come back at 3. So from 6, you are now coming back at 3. So 6 is popped from the stack. Now at 3, you look at, I was running a loop. I was trying to traverse the neighbors and I already went and explored 6. So this is over. So from 3, I cannot go anywhere else. This list is over. So I will just go back. I will backtrack. I will come back at 2. So at 2, I see, okay, I went to 3. 3 is visited. Can I go to 4? 4 is also visited. So I cannot go to 4. So 2's neighbor have been visited. So I can say, okay, let's just go back from 2. I go back to the previous node. So before 2, I came from 4. So I come back at 4. So this is backtracking. Now at 4, I can say, okay, I went to 2, so 2 is visited. What about 6? Oh, sorry, what about 5? So this neighbor is 5 actually. 4 has a neighbor that is 5. 4 has neighbors 1, 2, 6 and 5. 5 and 6 actually. 4 neighbors it has. 1, 2, 3, 4. Yeah, 4 has 4 neighbors. So it will look at 5. Can I visit 5? The answer is yes, I can visit 5. So 4 will make a call at 5. And 5 will say, okay, I am visited now. So if I talk about the order, right? So it was like 0, 1, 2, 3, 6, and then 0, 1, 0, 1, 4, 2, 3. 0, 1, 4, 2, 3, 6. And now you are actually visiting 5, right? You are now visiting 5. From 6, you come back 3, you come back to 2, come back to 4. And now 4 will say, okay, 4 has a neighbor that is 5. It is not yet visited. It will go and visit it. And 5 will say, okay, I can only go to 4, but 4 is visited. Hence, I will go back. So it will simply return. I go back to 4. Now 4 says, okay, 5 is visited. What about 6? 6 is also visited. 6 is not visited by 4, but it is visited by 3. So it will not go to 6 also. Now 4 says, okay, all my neighbors have been done. I will go back. It will come back at now 1, right? So here after 4, you went to 5. 5 is over. 4 is over. Now you come back at 1. 1 says, okay, all my neighbors have been visited now. I will just pop. I will come back at 0. Now in the stack, you are in this function 0. 0 says fine, all my neighbors. 1 is visited. Now 0 looks at 2. 2 is also marked visited in this array. So it says, okay, my list is also finished. So I'll just go back. So this is also popped off from the call stack. This is how the DFS algorithm works. And given this adjacency list, this will be the output that we will get. So the idea was to traverse all the nodes, and this is what we will get by traversing all the nodes. Okay, so I hope you understood the algorithm. Fairly simple. If the graph has multiple different components, then we will see that you need to initiate DFS from one node in each component. Okay, so this is something easy that can be done later on. But first of all, we'll focus on this simple DFS algorithm where we are assuming there is only one component. Okay, so we are assuming one component in the graph as of now. So let us code this algorithm next. Let us look at the implementation of DFS in Java. So I already have the graph class which is implemented in the previous tutorials. So in this, I'm going to add a DFS method, and this is going to accept the source node from where I'm going to start the DFS. So I'm assuming there is a single component in the graph. So what I need to do, so firstly I need to build a visited array. That is the data structure we will be needed. So we can keep things simple. We can create a Boolean visited array, and this is going to be of size v. That is the number of vertices in the graph. So initially everything will be set to false, and in Java by default a Boolean array is false. Now I actually want to do this traversal recursively. So I cannot make this as a recursive function because I cannot create this array again and again in the recursive function. So what I want this array to be shared across all the function calls that I'm making. So for that is why I need to create another function which is going to help this DFS. I can call that as DFS helper, and here I'm going to get the source node or the node, the current node where I am, and the Boolean visited array. So this array will be passed and it will be shared across all the function calls, right? So I can simply make call to DFS helper, and I can give source node and the visited array as input to this function, right? Now here what I need to do, as soon as I come to a node, the first thing I will do is I will mark that node as visited. So I can say, okay, I can print out that node, that is fine, and I can say visited of that node, this is equal to true, that yes, I have visited this node. Let us take a small example. Let's say I have 1 2 3 and 4 and 5. Let's say this is the graph. So if I start from this node, so I will mark this as visited, and now I will look at neighbors of 1. So 1's neighbors will be, let's say, 2 and 4. So I'll iterate on this list and I will go to the neighbor which is not yet visited. So right now 2 is not visited, so I'll make a call to 2. Okay, so how do I do it? To iterate on this list, we need to create a list iterator. I think this part was not visible, so I'll just hide myself. What I'm saying is that 1 has neighbors 2 and 4, so I'll make a call at 2 first. So how do I get that? For that I need to create a list iterator first. So I can say fine, let us create a iterator of the type integer. Let's call it it, which is the iterator to iterate on this list. So I can say, okay, adjacency list of this node, which is, let's say, 0 source in my case, dot list iterator. So using this iterator we can easily iterate. So while I have items in this list, while it dot as next, what to do? I can say, okay, give me the neighboring node. So the neighboring node, this is given by it dot next. So I will now check, is 2 not visited? Yes, 2 is not visited. So how do I check? I check from the array. So 2 is not visited neighbor. Then what to do? I have to make a recursive call. So I can make a call to DFS helper, give it the node is neighbor, and give it the visited array. Right? So I'll show you what's going to happen in this scenario. So I have this, let's say 1 2 3 4 5. So generally in the code the indexing is assumed to be 0 based, but in the example I took it 1 based, but hopefully you will understand that part. So I check 1 is connected with 2 and 4. So 2 is not yet visited. So 1 is visited. So as soon as I come to 1, I mark 1 as visited. Then I iterate over the neighbors of 1. I check 2 is not visited. So I make a function call on 2. So 2 is now visited. Now I look at neighbors of 2. So 2 has neighbors which is 1 and 3. So out of this 1 is already visited, so I don't do any work. So I'll make a call at 3. So as soon as I come to 3, 3 is visited, and 3 has neighbors again 2 and 4. So 3 looks at, okay, 2 is visited, so I'll make a call at 4. At 4, I have again neighbors which are 1 and 5. So 4 says, okay, 1 is visited, don't do any work, make a call at 5. So 4 visits 5. So 5 is now visited. Now 5 has only one neighbor, 4, which is visited. So this loop will not run for 5 because it will iterate on 4 and 4 is already visited. So this if will not execute and while will not do any work. So you will simply return, right? So from here we will come back. So you come back here, right? Now at 4 you see 5 is done. So list of 4 is also finished. So this loop is over. So 4 goes back to 3. So 3 says, okay, I can go to 4. This is also done. So 3's loop is also over. You go back at 2. So at 2, you have gone to 3. That's also done. Now suppose there was a node 6 here, right? So what will happen now? 2 will say, okay, yes, I can go to 6. So 2 will go to 6 and 6 will get visited and you will come back, right? And of course, these nodes are also marked visited. This loop is also now over. Now at 2, you will say, okay, my list is done. I will go back. So it will go back here. Now 1 will look at, okay, can I go to 4? But 4 is already visited. Hence you do not go. You do not make a call at 4. So this edge is not considered. And at 1, you can say, okay, this list is done because 4 is also visited. And hence I go back. This is how it will go back into the main. So in this case, the output would look like 1, 2, 3, 4, 5. And then you have gone to 6 as well, right? This is how the DFS is going to get performed using this code. Now let us test our code. Does it work fine or does it work as expected? So you have understood DFS on graphs. Next thing we will learn is how do we do cycle detection on graphs. Basically, we will do this algorithm of cycle detection on two types of graphs. One is on undirected graph, which is given here, and secondly we will do it on directed graphs in which the algorithm will change a little bit. This graph is an example of a undirected graph. So now how do I detect a cycle in this? So I can use BFS or DFS, right? So if you remember, the fundamental difference between a tree and a graph is that a tree is always not containing a cycle. Tree does not contain a cycle, but every tree is also a graph. Basically, if you have a cycle in a tree, it becomes a graph, right? And every tree is also a graph. So if I give you an example, let's say this is node A, it is connected with B, and it is also connected with C. So right now it is a tree, right? And it is also a graph. But if I add this edge, it definitely becomes a graph, right? It is not a tree now because it contains a cycle, right? So now what is the significance of cycle, or how do we detect a cycle? So it is pretty easy. Let's say I start traversing this using any algorithm, let's say BFS or DFS. Let's say I start with A and I make a DFS call on its child, that is B. At B, I make a DFS call on its child C, and C will now look at its neighbors. So it will see, okay, I discovered a neighbor, right? Now C has two neighbors. So one of the neighbor is, let's say, B, right? So if C looks at B, right? B is already visited, but is it really a cycle? The answer is no. I cannot say that this edge is going to create a cycle. The answer is no, right? Let's say there is one more edge from C to D. C makes a call at D and it visits D. Is this edge causing a cycle? Basically, the answer is again no, right? So what is the difference between this edge, right? So basically, before visiting D, D was undiscovered. D was not visited, but B was discovered. B was discovered. Now suppose I create one more edge, which is this edge, right? So if I now C makes a DFS call on, let's say, A, right? But as soon as I make this call, I see, okay, I'm landing at a node which is visited, and I can say it is a cycle, right? It is a cycle, right? Basically, what I'm trying to say is that B was also visited, D was not visited. So here we are sure there is no cycle. But here the answer is no, because B was discovered, but it was parent of C. It was parent of C, right? It was parent of C. Whereas from C, when you go to A was already visited and A was not the parent of C. A was not the parent of C in the DFS call. So this is the condition that if we encounter a node which is already visited and it is not the parent of the current node, then we can definitely say yes, there is a cycle that is present, right? So let me dry run this algorithm on this graph. So let us create a adjacency list. So 0 is connected with, let's say, 1 and 2. 1 is connected with 0 and 4. 2 is connected with 0, 3 and 4. Then 3 is connected with 2 and 6. Then 4 is connected with 1, 2 and 6. Then 5 is connected with just 4 and 6 is connected with 3 and 5, right? Now suppose I start doing a DFS from node 0 and I want to check if there is a cycle or not. So I start from this node 0. I said okay, go and make a call at its neighbor. So 1 is the neighbor, it is not visited. So right now my goal is to iterate on this, but I make a refs call on the first node that is not visited. So 1 is not visited, I go here. Now at 1, I look at the neighbors. The neighbor is 0. But if you look at 0, 0 is already visited. 0 is visited. But 0 is also the parent of 1. So hence we have to skip this node. We will not do anything at 0. What about 4? 4 is not yet visited. So I go and make a DFS call at 4. Right. Now we come at 4. 4 is now marked as visited. 1 is visited. 0 is visited. 4's neighbor is 1. So I will not do any work. Like C's neighbor is B. B is visited. 1 is visited, but 1 is parent. So we will skip it. What about 2? 2 is not yet visited. So I can go at this node and I can mark it as visited. Right. Now look at 2. Now 2 has a neighbor that is 0. Now this is an interesting case. Okay. So 2 has a neighbor that is 0. So I will draw this edge separately. I'm going to mark this edge in red. So 2 says, can I go to 0? Now what is the condition at 0? 0 is already visited, right? And 0 is not the parent of 2, right? So basically you are hitting this edge. We will call this edge as a kind of a back edge, right? So it is taking us back in the same path from where we started or to one of the ancestor nodes, okay? So it is an edge from the current node to some ancestor node. Why ancestor? Because if you look at the path that we have traced is 0, 1, 4, 2, and then from 2 we are going back. We are going at 0. This is like a back edge, right? Now, as soon as I get this edge, it will be the terminating case, right? So at this point I can directly say without looking at the rest of the graph, yes, there is a cycle. So this is going to return true. Okay, so I'm going to say okay, I'm going to return a true from this node 2. So this true will be told back to 4. Okay, so 2 will say okay that yes, I found a cycle. Okay, so what 4 would have said that okay, I do not see a cycle I am not seeing the cycle as of now, but let me call a neighbor and check if it can discover a cycle. So 2 discovered a cycle, so that true is returned to 4. 4 will also return true, 1 will also return true, and 0 will also return true, right? Because it's going to be a stack based algorithm, so this true will be propagated back to the main in this manner, right? So there will be a base case, there will be a recursive case. So let us try to write the code and understand this algorithm in little more detail. So let us write the code for cycle detection. So I'm going to make a boolean method which is, let's say, detect cycle, and here I need to give some source node from where I want to start, right? Or you can take 0 as well, right? So we are assuming that the nodes are numbered from 0, and we can ignore this source, we can directly give 0 as well, right? So now since it's going to be a recursive function like DFS, right? So one thing we did in DFS was we maintained a visited array. So we also need to maintain a visited array that will tell whether a node has been visited or not. So boolean visited, this is equal to new boolean, and the size is, let's say, v, right? So by default this visited array is set to false in Java, so I'm not explicitly setting it. And here I can say, okay, I'm going to create a helper method, detect cycle helper, and I'm going to give it a node, let's say 0, and I'm going to give it the visited array, right? So this method is just like a wrapper function, because we need to create the visited array, and this needs to be shared across all function calls. So we are going to make a helper method, boolean detect cycle helper. It's going to accept the node, and second thing it's going to accept is the boolean visited array. So now here we will return some true or false, right? So let's see how this is going to be. So first of all, when you're encountering a node for the first time, so definitely you should mark that node as visited. So visited of node, this is equal to true. Next thing you will do is you will iterate over the adjacency list of that node, and you will make recursive DFS calls, right? So let's see how we can do it. So just like before we have done here, right? So I'll show you. So you will create a iterator to iterate on that node, right? Or like in DFS, right? Something similar we will do, right? So I'll just copy this node code, and I'll show you what modifications you need to make in the DFS code, right? So here we go. So we have created an iterator to iterate over the adjacency list of the given node. And then what I'm saying, I'm finding out the neighbor, right? So if the neighbor is not visited, now here the call will be different. Okay. So if the neighbor is not visited, I will go and visit that neighbor, and I will also store the result, what that neighbor is saying. For example, let's say 1 is connected with 2, 2 is connected with 3, 3 is connected with 4, and 4 is again, let's say, connected with 1, right? So I will make a call at 2, that is the neighbor. Now this 2 is supposed to return some result back to 1, right? So that result can be true or it can be false. So 2 might have called 3, 3 might have called 4, 4 might have called 1. Oh, and here it saw, yes, there is a cycle. So true, 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 that will get propagated back, right? So if the neighbor is not visited, definitely we have to go and check that, okay, yes, is there a cycle at that node or not? I can say, okay, boolean, I can say cycle found, right? Something like this. So they did find a cycle in that part of the graph, right? So here I can make a call to detect cycle helper, and here I can give the node, which is going to be the neighbor, and I'm going to give the visited array, right? Now this is like a recursive case. You called some node, that node said, yes, I found the cycle. If the answer is true, if cycle found is true, you can directly return true from this point without iterating on the remaining adjacency list of the current node, right? And there is one more scenario that can happen outside this if, right? Outside this if, so it's like a recursive case I've written here. So this is like a recursive case. There can also be a base case, right? So base case would be that you are hitting a node which is already visited, right? So I can say else if visited of neighbor, this is true, right? This is true, right? And there is one more condition, right? So I'm basically saying something like this. 1 is connected with 2, 2 is connected with 3, 3 is connected with 4. And now you said, okay, I came to this node, I came to this node, I came to this node. From 4 to 1, there is an edge. So as soon as you discover this edge, that fine, I am going to a neighbor which is already visited, and this 1 is not the parent of 4. Okay, so 4's neighbor is also 3, but 3 is the parent of 4. So you cannot say about cycle at this node, okay, but you can say about cycle because of this edge. The 4 is taking me to the 1 which is not the parent, right? So you can say the neighbor that we have discovered is not equal to parent of 4. But how do we get parent of 4? That is a question. Okay, so this is the neighbor, right? So that means, and this is the parent. So we want that this neighbor that we are discovering should not be same as parent, because 4's neighbor is also 3, right? If it is 3, then we cannot say anything, right? We have to skip this. But this neighbor, if it is not same as parent, then yes, definitely there is a cycle. But how do I find the parent of current node, right? So that is a question. This parent we will have to maintain in the function call by passing one more parameter, right? So parent, and here we have to, so when you discovered this neighbor, right? The parent of this neighbor is going to be the current node, right? So this will be node. So I'm setting the parent here. If neighbor is not equal to parent, then I can say return true, right? Since I'm using a else if condition here, right? So this else if will be only executed if the node is already visited, right? So if it is not visited, it will go here, but if it is visited, it will come here. So that means writing this part is optional. So I can just remove this, and I can just simplify the condition to be only this: neighbor is not equal to parent. I'm going to return true. But if I come outside the while loop, that means I could not detect any back edge, right? So this is actually the point where we are detecting the back edge, and this is actually the recursive case. This if condition is a recursive call, that's it, right? So this is kind of a base case that we found a back edge, right? Otherwise, if we could not find any back edge, we are going to return false from that node. So I think this function looks good to me. Now we have to give a parent here as well. So parent of the source node, we can just set it to -1, no parent, right? And let us dry run this code, and let us also test the functionality first. So here in the main, I have this file. So I have created a graph. I have done the DFS, simple DFS works, but now I want to S out about the cycle detection. So if g dot detect cycle, you can just see out, S out, yes, there is a cycle. Else you can say S out, there is no cycle. Let's go and run this code. So let's see what output do we get. So it says yes, there is a cycle. So I'll show you, this is the same graph that we have in the figure. So yes, it contains a cycle. So let me dry run this code for you once again. I'll do it on a smaller graph. Let's say the graph looks like this: 0, 1, 2, 3, 4, and let's say this is the edge, right? So you start from 0, so parent is -1. So you look at neighbors of 0, right? So you said, okay, visited of node, this is true. So this is marked as visited. Then you iterate over the neighbors. So neighbors of 0 are 1, 2, 1 and 3. First we will go to 1. 1 is not visited. So we make a recursive call and ask, did you find a cycle? So 1 is now marked as visited. And when I marked 1, so I said the parent of 1 as the node. So this was the node, this was the neighbor. So neighbor's parent is going to be the node. So parent is 0. So 1's parent is marked as 0. And again, same story repeats. At 1, what do? I make a recursive call. So I ask neighbor of 1, right? Now 1 has two neighbors. One of the neighbor is 0. 0 is visited. But what happens here? Is this condition true? What is the neighbor? Neighbor of 1 is 0. What is parent of 1? That is also 0. So we do not execute this else if block. So we basically ignore this case. Okay, we do not do any work here. Then we look at the second neighbor. So 1 has neighbors that are 0 and 2, right? So nothing happens here. What about 2? So 2 is not visited. So we make a recursive call, right? So we go to this node, we make a recursive call. Now 2 is marked as visited. Parent of 2 is 1. Now 2 also has two neighbors. 2 has a neighbor that is 1 and it has a neighbor 3. So I do not, if I look at 1, 1 is already visited, right? So I come into this else if. Okay, if it is not visited, I go here, but if it is visited, I come here. So what is the neighbor of 2? That is 1. What is parent of 2? That is also 1. So this condition is also not true. So I do not do anything here. So nothing happens here. We talk about this edge 2 to 3. So I go to 3. Now at 3, what happens? 3 has two neighbors, 0 and 4. So I go to 0. Is 0 visited? Yes, 0 is visited. So I do not go into this if block, I come into this else block. What is the neighbor, right? So what is now the neighbor of 3? So the neighbor of 3 that I'm considering here is, because of this edge, that is 0. What is the parent of 3? The parent of 3 is actually 2, right? So they are not equal. Yes, 0 and 2, they are not equal. That means yes, return true. So without looking at this part of the graph, 3 returns are true, right? Now 2 got to know, yes, there is a cycle found. So 2 also returns are true. It goes back. 1 also gets to know, yes, there is a cycle found. So as soon as it gets a true, it returns a true. 0 gets to know, yes, there is a cycle, it returns a true back to the main. So this is how this algorithm is working, and I hope you understood it. Now we will talk about cycle detection in case of directed graph. So in case of directed graphs, not just the structure of the graph, but the direction of edges also decide whether there is a cycle or not. If you look at this example, the edges are like this, and if you start from A, you can go to B, you can go to C, but from C you are not able to go to A, right? And of course there is no loop present here, right? So hence there is no cycle. But if I change the direction of this, just this edge, I reverse it, right? I can go from A to B, B to C, and from C I can again go back to a node. I can go in a cycle. So hence, yes, there is a cycle, right? So now I will tell you, if you use the same algorithm which you used on undirected graphs, what is the problem you're going to face, right? It's not going to work in the same manner. So let me take up one more example. Let's say the graph is like this. Let's say A. From here we have B. Let's say C, D, E, F, and let's say this is connected like this. And let's say I have G, and it is connected with, let's say, C, right? Now suppose you start doing DFS from A, and you say, if I hit a node which is already visited, I will say there is a cycle. This is the logic we did in the undirected graph. So let's say you started doing DFS, you started from A, you went to C, okay, from C you went to D, from D you went to E, from E you went to F, and from F you cannot go anywhere else. So you come back and you say, okay, no, there is no cycle. So you come back, you return false, right? And from E again you come back, D, you again come back at C, and again you come back at A, and from A you come back at B. Now you go to V, B is not visited, right? From B you go to G, and from G you go to C, and now you see that I am going to a node that is already visited, this edge, right? And it is C. C is not the parent of G. That means I'm going back in the path. But is it really a cycle? My question to you is it really a cycle? The answer is no. If you start traveling from A, you can come to C, and you cannot get stuck into cycle. From C you can go to E, right? So this is not a cycle. Or you can go to D, right? You can go this way. So this is again a case of non-cyclic graph, right? But if you run the previous algorithm that we executed on a directed graph, it is going to say yes, there is a cycle, because from G you discovered a node which is already visited, right? Hence we need to fix this algorithm, right? So we need to fix the algorithm for directed graph, for directed. Now the question is, how do we fix it, right? So thing is, we need to again detect back edges correctly, right? So from G to C, this is not a back edge, right? I will tell you what is a back edge in case of a directed graph. So back edge is an edge that takes you back to, from one of the node to some ancestor node in the same path, right? From the current node to some ancestor, right? Ancestor. So let us take another example inspired from this graph only. Let's say I have A, I have C, I have F, I have D, and I have E, and I have F, then I have, let's say, B, then I have, let's say, G, and then I'm pointing to, let's say, C, and let me add one more edge in this graph. So this graph, this edge maybe looks like this. Let's say the edge is like this. Do you see a cycle here? The answer is yes, there is a cycle, right? Or let me add two more nodes, right? Let me add a node, let's say H, and let me add a node. That's it. Let's say one more node I have added. Now in this part of the graph, there is no cycle. But yes, in this part of the graph, there is a cycle because you can revolve in this path again and again, right? So let us try to see what is a back edge in this scenario, right? So let's say we started doing DFS from A, I went to C, from C I went to D, I went to E, from E I went to F, from F I cannot go anywhere, so I will just come back, right? So what is the state of the call stack? The call stack has A, it has C, it has D, it has E, it has F. Now if F says I cannot go anywhere, so I'm just going to return false. So false is propagated back. Then E says, okay, I cannot go anywhere else, I will come back. D says I cannot go anywhere else, I'll come back. C says I cannot go anywhere else, I come back to A. Now A says, okay, let us go to B. So B goes into the stack. B says, let's go to G. G goes into the stack. Now from G I can go to C. C is already visited. But is it a back edge? The answer is still no, right? Because in the current path, right? So if G is giving me an edge that is pointing back to one of the ancestor in this call stack, only then it will form a cycle, right? So the answer still here is no. So I will not take this edge. So can I go anywhere else? Okay. So basically, what is the condition I'm going to check here? So when I'm checking G to C, C is visited. C is visited, but C is not in the stack. C is not in the stack. That means I came to G via path which does not include C. Okay, it is not in the stack. That is the important condition, right? Now G can say, okay, let me go to H. H is not visited, fine. H goes into the stack. Now H says I can go to A. So what happens here? We are going to a node that is visited, and that is also in the current path, right? That means from H I can go to A. From A, if you A again, you can go to H, A, B, G, H. So that means these nodes will form a cycle, A, B, G, H, right? What is the condition to detect a back edge? So I will say, okay, in this DFS traversal, this edge from H to A, this is forming a back edge, right? Because I'm going back to one of the ancestor nodes, right? So the condition is from the current node to some ancestor which is in the stack. We have to check two things. We have to check that this node A is visited and A is also present in the stack. A is in the stack, right? So if both of the conditions are met, we can say yes, there is a cycle, and recursively H will propagate back. So H knows yes, there is a cycle. G knows yes, there is a cycle. B says yes, there is a cycle, and A also tells back yes, there is a cycle. So this is propagated back. There is a cycle. So again, this can be implemented recursively, but how do you check whether A is in the stack, right? So we cannot directly look at the recursive stack. So what you have to do is you have to maintain another data structure. Either you can maintain a hash map or you can simply maintain a array, right? So whenever you are hitting a node, you mark it as visited. Okay, so when I hit A, so these nodes will remain visited, right? But when you're going back, okay, when the nodes are getting popped from the stack, you can remove that node from the stack array also, right? So I can simply create an array called in stack. So if you're visiting a node, next you can mark that yes, it is visited. But when you're going back, you're backtracking. For example, when you went back from C, you can say yes, this node is not in the stack, right? So you have to maintain two Boolean arrays, one for visited, one for stack. While backtracking, you will unmark from the stack array, right? So I'll write the code first, then we will do the dry run. But I hope you understood the concept that here just being visited is not sufficient. We also have to check whether the node is in the stack or not, right? So this is the main tweak that we will use in this algorithm.